And thanks for coming. Do we have the video and the sound? Is that all set up? Yes? All right, wonderful. All right, I'm really excited to be here today and have the first lecture on CS224D. We'll start with a couple of simple logistics and then really give you one of the most important ideas and high-level thoughts of deep learning for natural language processing through a series of natural language processing examples. And you see actually the output of a neural network and how it essentially classifies the sentiment. So for instance, the first 15 minutes were dry is negative. That's a negative phrase. And you see basically dry being negative and so on. But by the end, I really enjoyed the lecture. So hopefully this will be true for you as well, just like it was for this neural net. So maybe some of the most basic course logistics. Also, if you have any questions for any of the lectures, this one or any of the future ones, feel free to just raise your hand and ask the question. So my name is Richard. I actually got a Stanford PhD 2 years ago and then founded a small AI startup called MetaMind. And then we have a couple of great TAs. So far we have 4, but given that we currently have 200 students enrolled, hopefully we'll get some more. One is working on the camera, Samip. Maybe you can raise your hand. And can the other ones who are here also raise their hands? Oh, there's James. And I guess David I haven't met yet. He just signed up. And then Bharath is also one of our TAs. He's a PhD student. So you already got the first part right, which is we'll be here from 3 to 4:20 in Gates B1. Generally, there will be 3 major problem sets, and there will be a lot of programming. So hopefully, and we'll get into that a little bit more, that is something that you're comfortable with already. We'll have a bunch of office hours. If we schedule them well, probably one every day. They'll start next week. All the ones from the TA start next week, but I actually will have an office hour right after this lecture in case you have any questions sort of around general organization already. The slides will usually be uploaded before the lecture. I'll try my best. Then the video of the lecture and the lecture notes will come right after. All right, prerequisites. We will require you to program a lot in Python. So hopefully you're proficient in Python. If you know C++, Java, and Lua really well, then that's fine too, and you can probably pick up Python, but ideally you know Python already. Otherwise you're going to want to start right now taking a bunch of Python tutorials. We'll do a lot of matrix calculus, taking matrix derivatives. That's not trivial for some people, especially if your linear algebra and college calculus has been either a long time ago or still in its infancy. So that is definitely a prerequisite. Basic probability and statistics. Hopefully you know a lot of the basics of those. And then the most ideal prerequisite is really CS229, having taken the machine learning class where you have basic understanding or got a basic understanding for cost functions, taking derivatives of simple functions, and then performing optimization with gradient descent. If those words are already somewhat familiar, then I think you will have a fun time in this class. Are there any questions about prerequisites? All right. Grading. Very fun for everybody involved. So the 3 problem sets will each count for 15% of your final grade. We'll have a midterm exam, which also only counts for 15%, and the final course project. And the final course project will, I think, be the most exciting part for you personally. Several students last year were able to publish papers, got into Hacker News and various other fun places with their projects. It's a very exciting time right now for deep learning, and if you do a really good job on those, on your final projects, I think that's sort of something that that will last you for a long time in your career. We'll have a milestone where you basically have to at least have a project description. We'll actually give you a 2% bonus, 2% of the entire class grade if you have your data already and ran an experiment. And we do that because we really want to encourage you to start early on your class projects. Usually we will run experiments. Those experiments will take inevitably days or at least several hours to run, and if you start the night before, it's just impossible to get a good grade. So you want to start early. You also don't want to spend too much time, and we'll have a special session on just the class project in a couple of lectures, but you also don't want to spend too much time collecting the data and so on. You want to find quickly what is the problem domain that you have, and what excites you that you want to like to, you know, in natural language, or at least some of these related techniques, try to predict and automate. So I've last year found that several students who had a really great time came to a lot of the office hours, and then some students who didn't have a great time never came to the office hours. So this year we're going to try to make it a prerequisite or part of your grade to at least show up to one project advice office hour throughout the quarter. So it'll be a very simple thing like check mark once you came, we talked about your project, and then you're all set for that. There will be a final write-up project, and then we'll have a big poster presentation probably in the Gates lawn. And yeah, you'll get bonus points if you have exceptional fun poster presentations. We had last year, we had folks who had like live demos set up where they showed you something and then it described what it saw directly in language. Those are the kinds of things that if you're really getting into this, you could build, and those will get some bonus points. All right, late policy, we try to be very lenient. Basically, you'll have 7 free late days that you can use whenever you want. After that, we'll take 25% off per late day. You can use at most 3 late days per problem set, because we want to post potential solutions and discuss solutions openly in the office hours. And yeah, that does not apply to the final course project. You do have to submit that on time so that we have time to grade it. Collaboration policy, I guess, yeah, again, read your student handbook and codebook, and remember the honor code. And then, yeah, it's very important to understand what collaboration means, especially as we analyze your code. You don't want to have your code be looking too similar to other people's code. Any questions on grading?
If you use your late days, can you still get the 2% bonus on the milestone?
Yes. Cool. All right, so I want to give you a very high-level plan and overview of the problem sets, because they're going to be a major piece of the class. So I think if I sort of look at the class material the way we have it in from last year, the first half of the class will be quite hard, because you have to learn everything from scratch, and we'll actually make the first problem set also in pure or raw Python, just to make sure you really understand all the basics and mechanics. And then this year, we'll update problem set 2 and 3 to actually use a library called TensorFlow that was just introduced last year. It's a pretty brand new library that still has some problems, but I think the future for deep learning and practice will always involve some kind of automation, and libraries like TensorFlow or Torch. No worries if you don't know those yet. But these are basically becoming standard tools, and I felt it would be weird to make you do all 3 problem sets all from scratch in raw Python. So once you really got up to speed with problem set 2, which will be a pretty major neural network architecture, a very important one, so-called recurrent neural networks. Once you're up to speed in TensorFlow for recurrent neural networks, you're basically the world of NLP will be your oyster. Like, you can then all of a sudden do a lot of really amazing things. You will likely use that as part of your project to that kind of code, and it'll be exciting and really a very useful tool in your jobs, in your research, in all kinds of ways. But it's also non-trivial to get there. So if you have sort of high-level things you can plan throughout your quarter, make sure you're really up to speed through the second half, because then we'll also make problem set 3 a lot shorter, and because you then have the tool of TensorFlow in your tool belt, you'll be able to solve it, I think, relatively easily. So yeah, we'll again make problem set 3 a lot shorter so that you can have more time for your final projects. All right, so those were all the organizational things. Are there any questions around organization? All right, so then we can get started on deep learning for natural language processing. So very, very high level, what is natural language processing in the first place? So it's basically a field that is really at the intersection of computer science, artificial intelligence, and linguistics. And for us, the goal of this field will be for computers to process, or scare quotes, understand natural language in order to perform tasks that are useful. So for instance, question answering is a task that is incredibly useful. If you have a question about your iPhone, it broke somehow, and you want to know the answer, and we could have computers give those answers, that would be very useful and save companies a lot of money. Now, I use the scare quotes of understand because really fully understanding and representing the whole meaning and all its glory of language, or even defining it, is quite an elusive goal. There's a lot of philosophy of language, Wittgenstein, Frege. We won't go into any of those details, but we want to be realistic in our expectations. In the end, we will usually have a very concrete task that we think is useful to solve. And when we say meaning and understanding and reasoning and all these kinds of things, really we mean we have very complex functions that we learn to predict and solve some kind of useful task. So I will stop using the scare quotes throughout the lecture, but it's something to keep in mind. Really, perfect language understanding is kind of AI complete in the sense that it's inextricably linked to thought, and we don't really have a great way to represent all kinds of thoughts in a computer in all their fuzziness and concreteness and logical ways and so on. So what we'll look at very concretely are different levels that exist in natural language processing. It starts usually with speech, and then we use phonetics and phonological analysis to understand speech better. From there, we may go and look at morphemes, short stems, for instance, and prefixes and suffixes of words. Then we'll go to syntactic analysis, actually trying to understand how words are put together to form the meaning of whole sentences. Syntactic analysis is really more like the grammar, the structure and syntax of language. Once we have that, at least traditionally, we will then go to understand what the sentence actually means, and eventually we might want to use the sentence meaning to have a full discourse. Now in this class, we will not do much of OCR and simple things like tokenization. We will not focus on that. We usually will assume we have some speech, but really the major focus will be on syntactic and semantic interpretation. And in some ways, what you will notice is might actually sometimes go directly from here's a word or a list of words to what does that list of words actually mean. We may skip some of these levels that have been traditionally thought to be required for understanding language and go directly to semantic interpretation, because that's really where the meaning is, and in the end, when we communicate, it's all about the meaning. It's less about the structure that we use. All right, so let's look at a really, really tiny subsample of NLP applications, several of which we will implement in this class and cover. So it starts with really, really simple things: spell checking, keyword search, finding synonyms in a dictionary, for instance, or a taxonomy. Then there's some intermediate tasks that are a little harder, extracting specific types of information from websites, for instance, finding product prices or dates or locations or people names. And I'll give you an example in a live demo at the end of this lecture. Or extracting company names that can be useful if you work in finance and you want to find which companies are mentioned in similar articles and hence might be related, to understand sort of company networks or people networks. Then still somewhat simple kinds of tasks are classifying longer documents for instance, the reading level. Should this be a text that is suitable for fourth graders to use? Or understanding the sentiment of longer documents in case you want to predict movie revenue, for instance, after you see a bunch of movie reviews when the movie comes out. So those are still relatively easy and intermediate tasks. And then the really hard ones, which we'll also cover in this class, are machine translation, which really captures a lot of the complexity of language. Being able to translate from English to German or Chinese or any other language is really hard, and it's really also one of the tasks that we haven't solved in any kind of sufficient ways such that we can say we're better than humans. And some people think that that might be one of the most elusive kinds of tasks, being able to better translate, because you may need to know so much about life, love, and God and everything, the whole world, to really be able to translate subtle nuances in novels and things like that. But there is interesting research actually from Stanford and the NLP group here that shows that having at least an automated raw translation from a computer will speed up the work of human translators significantly. And so it is definitely something that is getting more and more useful and more used in daily life. We'll touch a little bit, but not too much, on spoken dialogue systems. It's something that's very hip right now in industry. A lot of people think that that might be one way you might interact with a lot of different companies in the future. Instead of having to email somebody or call somebody, you can just type in a chat window and or speak directly and have an algorithm or a deep learning model essentially communicate with you. And that kind of leads us also to some complex question answering problems where you might require logical reasoning to answer a question. You may have to read a bunch of materials in order to be able to really give an accurate answer to a question. So I guess I mentioned a couple of these already, but here are some more real applications that you see in industry, and a lot of them actually in this area. Of course, we all know search, and both written and spoken search nowadays. Online advertisement uses a lot of natural language processing to understand language. Automated or system translation I already mentioned, doesn't always work that well. Sentiment analysis is a very interesting task because it's one of those general classifiers. If you once train a really good, accurate sentiment classifier, you can use it across a whole host of different tasks. You might want to understand movie reviews, but you might also want to understand customer sentiment, like this customer is really angry when they're complaining about something. That too actually has some interesting pitfalls. So here's an example where Anne Hathaway starred in a movie that had really positive reviews, and then right after the positive reviews came out, the stocks for Berkshire Hathaway, the company, surged a lot. And so we know already that people are using automated sentiment analysis to financially trade, basically, do automated stock trading. And in this case, they didn't do what we call entity disambiguation properly. They didn't realize Hathaway was the person here and not the company. So there's still room for improvement, and it's clear that there's a lot of interest for these kinds of techniques in industry. So why is natural language processing so hard? Why do we need a whole lecture? Why can't we just take some standard machine learning techniques and apply them to text? Well, I guess I touched upon this a little bit, but there's a lot of complexity in representing learning and using linguistic, situational, world, and visual knowledge. So when we try to understand language, it touches also on the visual world, some meaning that we have, for instance, grounded. So we ground the meaning in the visual world. So what's the meaning of green, if not something that we as humans can see as green, right? That's a simple example. Now, there's also a huge amount of ambiguity and world knowledge that you need to, for instance, just understand this very simple sentence. Jane hit June, and then she fell. Now, if it's fell, who do you think she refers to? That's right. But if she ran, then she probably ran after she hit her, and then it's Jane. So the verb that comes after this word basically helps us to do so-called anaphora resolution, basically understanding what this pronoun here refers to. And basically it could be either Jane or June, depending on the meaning of the verb that follows it. And traditionally, when people started doing natural language processing way back in the 50s and 60s, they said, well, I can just define the list of all these words and then I will know. And I will be able to make computers understand language. And that just failed miserably because there's so many exceptions, there's so many different words you could try that, and there's no way you will ever be able to write down by hand all the rules of language and how you would understand it. Here's another really interesting example of ambiguity. I made her duck. So let's see if we can come up with a couple of different interpretations of that sentence. So the simplest one, well, I don't know. It's actually, it highly depends. It's even a little culturally dependent. So does anybody have a first interpretation of I made her duck and describe it in like a different sentence? Yeah.
I cooked someone a dish that is consisting of duck.
That's right. So that's the first one. I cooked her a duck.
I made her physically duck, yeah.
That's right. You like, you know, swing a bat or something accidentally and she had to duck. What else? Yeah.
You transform her like use some magic.
Interesting. I would say I made her a duck, but yeah, I could see that. Yeah.
You created her pet bird, her duck.
That's right. You carved maybe like a duck out of wood, and you made her a wooden duck by carving. And maybe there's one more. Yeah.
You turned her duck into a made man.
Whoa. Maybe. So I guess the last one might be you actually made her duck, like the one that she bought, right? And so all these are subtly, like some are obviously different, completely different, and you may want to see a picture, for instance, to understand which one you meant. The beautiful thing about some of the techniques that we'll cover in this class is that they actually transfer very quickly between language and vision, and so you can actually use and combine these techniques, especially if you've taken, who here has taken 231N last quarter? Awesome, so roughly half of all the people. Okay, so you will be able to see that a lot of the techniques will transfer. Hopefully some of this will be boring and you'll be able to do it very quickly, but there'll still be a lot of things that weren't in that class. All right, so what is deep learning? It's essentially a subfield of machine learning and basically tackles the following problem. That most machine learning methods work really well because it turned out that there's human learning or graduate student assent to try to find really good features to give to the algorithm. So for instance, if we're trying to find named entities like locations or organization names, one of these state-of-the-art methods in not too long ago, 2010, basically had to give all these kinds of features to a machine learning algorithm like logistic regression or conditional random fields to make a very accurate prediction. So it had to look at word shape, for instance. So it had features of like, is the first letter capitalized? Is every letter capitalized? Is there no letter capitalized? And it had one discrete feature for each of these kinds of problems. Or it looked at the current part of speech tag, in short POS. Is this a noun, a verb, an adjective, and so on? Or is the word in front of it an adjective, a noun, a preposition, and so on. Basically, a lot of different kinds of features were given to the algorithm, and only then was it able to find, oh, this is a location, this is actually a city name or something like that. Now, that's not very attractive if you try to build an algorithm and you had to actually manually sit down and look at all the data and all the examples and say, well, it's still making this mistake. Maybe I should add this kind of feature to solve that specific problem. Because that way, it will be very dependent on the kind of text that you're looking at as a human. And in many cases, it will actually be too specific to that data set that you're looking at. And then if you have another language or another kind of data set where now all of a sudden the people are from a different country, and you have to look again and manually look at over all these features. And the beauty of deep learning will be that we'll actually try to automate that process. So when you look at machine learning in practice, it used to always be that you spend the majority of your time describing your data, looking at how to basically make sense of it to a computer such that it can just kind of optimize a very simple function. And at the very end, you'd have the learning algorithm. And this is even a sort of optimistic way. Some people might say it's really 90% to 95% of you sitting down, becoming an expert in your domain, and then classifying or making certain kinds of predictions. And really, the learning algorithm is just very simple optimizing of weights, or basically saying this feature matters this much for this example. And it used to be that really to do the overall process very well, you kind of had to have a lot of experience, maybe even a PhD in that specific domain to do well overall. Now, in deep learning, we'll basically try to learn these representations. And you can see deep learning as a type of representation learning, which essentially attempts to automatically learn these features or representations by giving it the raw data. Raw data in the case of images was just the raw pixels. In our case, it will be just the raw words, or even lower level, just the raw characters. And then you give it the raw characters, you say this sentence is positive, this sentence is negative, you give it thousands of examples of positive or negative sentences, and then you ask the model to figure out which words seem relevant, which order of the words seems to matter. This was, not a good movie, but, well, yeah, so is not before the adjective and then becomes negative or things like that. You don't want to manually define any of that stuff. You just want to give it a lot of examples and have it figure out how to describe it and then make a final prediction. And what we'll see a lot, and no worries if you don't understand this figure yet, is that these deep learning algorithms will essentially attempt to learn automatically these multiple levels of representations. Now, sometimes we will be a little fuzzy with the term deep. Turns out, for instance, next lecture we will go deeply, no pun intended, into word vectors. But word vectors are not going to be actually deep models. They're actually going to be very shallow models. But there are ways for us to start seeing everything in the right kind of light and with the right kind of mindset. All right, any questions so far about deep learning, what we'll cover, applications that you're excited about and wondering if we'll cover it or not? All right, so a little bit on the history and the term of deep learning. Deep learning actually also includes a lot of so-called graphical models and probabilistic generative models. We will not focus on those. We will focus the entirety of the class on the neural network family, which is really now the dominant model family inside the field of deep learning in research as well as in industry. You might be a little snarky and say, well, this whole deep learning thing and neural networks, isn't it just kind of clever terminology for combining a bunch of logistic regression units? And if you've taken, who here has taken CS229? All right, excellent. All right, we'll have a great quarter. So you've all familiar with logistic regression, and one thing you will notice is that you will notice throughout the class is really we'll have a lot of logistic regressions kind of put together in all kinds of different ways. And that is really it. And so there's some truth to this. At the same time, there are a lot of interesting modeling principles, such as end-to-end learning. I give you the raw input, I give you the final output. You learn from the final output all the way to the raw input and everything in between. Really putting the artificial back into artificial intelligence, if you will. It was really a lot of human intelligence that went into a lot of these different applications. And in some cases, there are actual real connections to neuroscience, though I have to say that we will not go there. This is not going to be a neuroscience class. I'm not a neuroscientist. I published once or twice with some, and I know some things, but I really, the neural inspirations of these models are very high level and fuzzy. Especially for natural language processing, where I think we have even less of a good understanding of how the human brain really represents and processes language. At least compared to the visual cortex, where there are a lot more clear sort of this neuron actually does exactly that kind of thing that exists rarely or ever in natural language understanding. We'll also not be taking a historical approach. So there will be some folks online who say, oh, but hasn't this been discovered already like 30 years ago? by this person, and in many cases that will be true, and I'll try to give you the links, but I'll not ask you to read sort of historical papers. In many cases they're superseded, and while a lot of the very core ideas of deep learning have been around for several decades, there's still a lot of new techniques, and I think you can get a lot out of this class without necessarily knowing the full history of it. But if that is something that you're interested in, there's a great sort of long journal version of deep learning in neural networks, an overview by Jürgen Schmidhuber, who's done a really great job discovering all the intellectual history of the field. All right, so now why does it really make sense for you to take this class, and why am I so excited to teach it? I mentioned a couple of these before, but basically the field of AI had really been a lot about understanding your domain incredibly well and then designing features that often turn out to be overly specific to the problem that you were looking at, or incomplete because you can look at as much data as computers could, and it took a very long time to design and validate those kinds of features. On the other hand, with deep learning, we will learn these features, and that will make them easier to adapt, much faster to learn, and literally you will be able to solve problems in this class in your project that used to take 2 or 3 years for teams of 10, 20, up to 100 people, depending on how good you are in your project. And do this fully automatically. It's quite magical if you know sort of 10 years ago how long those kinds of things would have taken. Deep learning provides a very flexible and almost universal learnable framework for representing not just linguistic knowledge, but also world knowledge and visual kinds of information. And deep learning will also, and we'll see that starting next class, be able to learn in an unsupervised way. We'll just give it a bunch of text, and it will figure out interesting relationships and the actual meaning of words, just from looking at a lot of raw data. But then also, and that's where usually a lot of the power is, it's very, very good on supervised problems. So trying to very accurately predict a certain outcome. Are there any questions about these things so far? Yeah?
So is it like we need to prepare many features and deep learning is going to figure out which features are important, or like it's going to also like find combined features that are affecting the output rather than the individual features? How does it?
It's a good question. So the question is, will we give a lot of features to the algorithm that will learn how to combine them? And the answer is, we'll actually just give it the raw words. In our case, for this class, it could also be the raw speech signals, or raw pixels, or a combination of all these things. And then it will learn how to combine them and how to combine the features of those features in various different deep levels. So it will be completely, in the end, automated. You just give it raw text, a model specification, what output you'd like to predict from that text, and it will learn all the features and combinations of them automatically. Yeah.
How well can we describe the meaning of these learned features?
So we'll actually get to that in a couple of slides to give you some idea. And many times we can actually project them down into a 2-dimensional or 3-dimensional space that we can visualize, and then we'll actually see very interesting patterns that emerged from these models in often unsupervised ways. So there will be some ways we can visualize it, but it's also almost part of the art. Sometimes you get to know a model really well, and you get to like sort of tune it to work really well. And then others will actually come later and say, well, this model works so well, but we don't really know why. So they then analyze it and visualize it, and it becomes sort of almost a research problem in and of itself. And people have been able to come up with very interesting visualizations and interpretations of these models. Yeah?
Probably related to that, but when you talk about representation of information of various types, are you talking about representation at the output level, or are you talking about representation in the middle layers?
So the question is, when we say representing and middle layers, I guess we haven't really defined a lot of those terms, so you're probably a little ahead of the class, but we will do both. The final output is often very simple. Is this a negative sentence, this movie sucked? Is this a neutral sentence? I had watched this movie. Or is this a positive sentence? I love this movie. It's the best family movie ever. Those kinds of final representations are very easy. They're just like a binary output, or a small vector of saying, these are the probabilities for these three classes. So that kind of representation is the easiest one to interpret and to learn. But we'll actually also look at intermediate layers. And for instance, the very first layer, which will be word vectors. All right, now you might think, well, if some of these techniques have been around for so long, why is this so relevant now? Why is this only the second time this class was offered for deep learning for NLP and not, the 50th or 10th time? It basically started roughly in around 2006 that deep learning techniques actually outperformed these traditional machine learning techniques. So up until then, it was really all the hand-designed features that did so well for all the different tasks that you were using. And even 2006, you were probably already using a lot of machine learning when you used a search engine or something like that. So why now? Basically, deep learning techniques benefit a lot more from the data, because we will ask the models to learn the features by itself. It also requires a lot of data, right? If you only have 10 examples, and this is already kind of relevant for thinking about your class project and how to get started on that. If you only have 10 examples for something, and you ask the model, you know nothing about language, right? The model starts being a completely random gibberish kind of algorithm that doesn't make any accurate predictions, and you only give it 10 or 15 examples, it won't be able to understand all the complexity of whatever domain it is that you're trying to describe. However, when you give it millions of examples, then it can start to figure out all these patterns by itself without you hand-holding and describing these various features. And so deep learning techniques in somewhat benefit, but also require a lot more training data. Then we'll have a lot of faster machines, and especially multi-core kinds of architectures. We'll notice down the class that a lot of the things will boil down to making very large matrix multiplications, just W times X. And it turns out that those are very easily parallelizable, and so if you have multiple cores, you'll be able to make use of those. And now some of the GPUs have 4,000 cores, and it turns out with deep learning techniques, you can very efficiently use those 4,000 cores and parallelize very nicely. And then, and this is sometimes overlooked, but I think it's quite relevant, especially for natural language processing. In the last couple of years, there have also been a lot of new models and algorithms and optimization techniques and ideas that helped us make use of these very powerful techniques. And that overall resulted in just much, much better performance and accuracy, especially for tasks, such that they now become really viable to be used in practice. And it started with speech and computer vision, but now has definitely arrived in natural language processing as well. So let me give you at least a very sort of one slide per breakthrough kind of overview of how we got to where we are. Basically, it started out with deep learning for speech, where we had all of a sudden very large data sets, and basically we're able to take in not quite just a raw frequency, but some very raw features of the sound, and then basically predict phonemes and words. And here we see a word error rate, and the word error rate really dropped significantly. So when you actually now speak into your phone, your Android or your iPhone, you will very likely use a neural network in the back end that actually understands what you're saying. And if you tried speech recognition like a decade ago, it was for the most part a joke. And it's really now that it's become so accurate that you actually, it makes sense to talk into your phone, even sometimes with noisy backgrounds. The other breakthrough, and this was what all of 231N was about, is basically, or had been in computer vision. And really, computer vision was also what most deep learning groups had focused on up until maybe 2 years ago or so, their majority of their efforts. And so we understand neural network models a lot better for images. So we know, for instance, when you take in the raw pixels, the first layer of a neural network basically finds little edges. And then once in the second layer, we will combine some of these edges into more complex textures and shapes. And then in the layer 3, you'll have more complex, even more complex kinds of combinations, and maybe you have neurons that fire when they see a tire and things like that. In natural language processing, we won't have beautiful visualizations like that, unfortunately, and there won't be as kind of obvious connections of, oh, we put these two characters together and then they form kind of this positive meaning or something like that. But we will have some visualizations also that help us understand, and we'll see that in images, it is, in text, it will be very hard to understand exactly what one word would be represented as. So for instance, the example of duck. Let's say we try to represent duck. Should it now be close in our representation to a lot of verbs, like hiding and things like that, or should it be closer to other bird names, right? It's unclear. And so you already kind of see that the language understanding and representation part is often much more complex than the visual one. So basically, when we say deep natural language processing or deep NLP, we want to try to combine these two ideas and goals. Basically taking the goals of natural language processing and then try to use representation learning and deep learning methods to really solve them end to end. And so in the last half hour or so, I will go through a couple of these representations that we have for the different levels that we mentioned in the beginning: speech, morphology, syntax, and semantics, and give you a very high-level overview of what we mean with these different levels. And then we'll also cover a couple of applications that have already been transformed by deep learning. Are there any questions so far on the related kind of subfields of deep learning?
Is there a way to augment data for NLP problems?
So it's a pretty sophisticated question already. So in computer vision, what we often do is, instead of giving it just the raw pixels, we may change the input a little bit and we rotate the image, because we know, well, if this is, for instance, a quail, well, if I rotate that image a little bit, it's still a quail. So we can have these input transformations. Don't worry if you don't follow this yet. We'll get to that in a little bit, or well, in several weeks. But basically, it's much less obvious how to do that in NLP. I've actually tried it a little bit in research, and I haven't gotten any big gains like the ones you see in computer vision. That's the short answer of it.
I guess to follow up on that question, we could substitute with like synonyms and things like that, right?
That's right. But what we'll see is that that is already captured pretty well by the deep learning models themselves. So. All right, so let's go through these different layers of representation, and let's start with phonology. So originally, if you try to understand words from spoken language and transcribe it into written language, and you study linguistics, you would basically take a whole quarter on phonology, where you basically have here the International Phonetic Alphabet, and you try to find all the different, define all the different plosives. For instance, so p is a plosive, and you have fricatives, that's exactly the kind of sound that you'd see in those, or dental, where you actually use your teeth, like so. This is the little theta, and so on. So you basically would spend a lot of time trying to describe all the subtleties of how human sound can be transcribed, and then basically try to automatically predict one of these discrete categories. Now, in deep learning, what we'll do instead is just describe it as a vector, a list of numbers. And we won't try to make any of these fine distinctions between the different ways to pronounce a word. Now, moving on from just knowing what the sounds are, the next level might be understanding morphemes, which is basically the science or field of morphology, where we might want to understand a word like uninterested might be chopped up into a prefix un, and you see that prefix modifying lots of different words and changing potentially the meaning later on. You have the stem interest, and you have a suffix. The suffix in different languages can change time, for instance, so interesting versus interested, and things like that. Now, again, in deep learning, every morpheme will just be a vector, a list of numbers, and we will train a neural network that just combine two vectors into one vector, and then we hope that the resulting vector captures whatever we need to capture for our task. So this is modeled by Tang Luang, one of the PhD students in the Stanford NLP group, and he had used a so-called recursive neural network. It's also a family of networks we'll cover in this class, that basically combines just a list of numbers that represent un and one that represents unfortunate, and we'll combine those two to unfortunate. And we won't make any kind of explicit assumptions about what unfortunate should look like. We'll just let the model figure that out. So now word vectors, you won't see them very well, but I'll zoom in a second. The next level after we understand sort of the parts that words are combined from, we want to understand the words themselves. And I'll zoom in a second, but basically with unsupervised deep learning techniques, we'll understand that certain words are similar to one another and they're in certain relationships. And so we will go and we will learn just by giving it all of the text of Wikipedia, for instance, we'll find neural network or even more shallow, very simple techniques to learn to map words also into a vector space. So this is really going to be one of the fundamental ideas and the first main idea of this class, and one that we'll see throughout this whole lecture. As long as we can map any kind of input into a list of numbers, we're going to be in the world of deep learning, and we can use all these different techniques. And so words will also just be lists of numbers. And usually will represent a word in something like 50 or 500 dimensions. Of course, we can't visualize those, and if we want to understand what's actually going on inside the model, what we often do is project them down to 2 dimensions. And then we actually see interesting patterns, for instance, that countries all map into somewhere similar sub-area of this high-dimensional vector space. And for instance, companies like France and Germany that are actually close to one another in some fuzzy way, you know, geographically, also culturally, maybe a little bit. Interestingly enough, their vectors are also closer to one another than, you know, other countries that are further away. And those might be also more similar again to one another. And these are things that will be learned automatically from just giving it a bunch of raw text. And again, you'll see that it doesn't always make sense. There will be problems when you represent everything as just a single list of numbers, a single vector, but it will be very useful to solve a lot of different tasks nonetheless. Here are a couple of verbs. And you know, say, think, and expect are closer to one another, for instance, that coming, come and go, and take and get, and so on. Here we have a bunch of auxiliary verbs, are, is, were, was, and those are close to one another too. Now, once we understand how to represent words, words in isolation are not that useful. Usually when we communicate, we combine words into longer sentences. And so traditionally, people would describe sentences with very discrete structures and with discrete tree structures like this one here. So the house at the end of the street is red. We might say the is a determiner, and don't worry if you don't understand all that linguistic terminology. We'll go through it as we go through the class. But basically, the is a determiner, street is a noun, and that together combines into this discrete noun phrase. Now, unfortunately, just saying this is a noun phrase, it's not that useful, right? You still don't really know what does it actually mean, the street. How does the street relate to the road, or the side alley, or the alleyway in which I was born, or things like that. Like, it's very hard to capture all of that in one discrete category, but that has been sort of traditionally the way to describe syntactic categories, just the structure and the grammar of language. And so in the end, you might say, all right, that whole thing is a sentence, and the sentence is just the category, the discrete category S. Now in deep learning, and you'll start to see the pattern here, since we're already describing all the words as vectors, we'll also describe all the phrases as vectors. And then we can actually compare the cat, for instance, the phrase the cat with the phrase our dog, right? Now they're not just a noun phrase, but we'll actually have a vector, and we hope that the vectors for phrases that are similar are also similar to one another in some way. And again, because every word and phrase will be a vector, we can use standard neural networks, standard functions that map vectors to other vectors to learn to make certain kinds of predictions. Now, let's go to the next level above, which is semantics. Traditionally, and this is again, we're going through sort of a long history here of the whole field of linguistics, and again, morphology, phonology, syntax, semantics. You can literally have 1 to 4 quarters of classes about each of those separately. So we're sort of not doing them complete justice, and they're actually very interesting in and of themselves. But if you're trying to make predictions, trying to have a computer automatically understand and make predictions based on the inputs, it turns out we can, in some sense, get away with not having to understand all these subtle details. We can just make the computer do accurate predictions without us understanding all the subtle notions of these different layers of representation. So let's look at semantics. If we, for instance, try to understand the sentence Mary likes Sue, then if you took a semantics class and maybe then another advanced semantics class, you would go to eventually what we call lambda calculus, where you say likes is this complex function that takes as input some other variable y, and then takes as input another variable x, and then can basically combine these different representations. And don't worry if you don't fully follow this, but if you know a little bit of functional programming, there's actually a lot of connections to those. So here you might say Sue, for instance, is just represented as some discrete symbol s. And when we combine Sue with the verb likes, then what we'll get is basically a reduction here of lambda, and now we'll get this thing, which will, this expression is lambda calculus expression, where we replaced one of the variables, the free variables, with this concrete term s. And then if we combine Mary here on the left side, we'll replace that variable x with Mary. And in the end, we have this discrete representation likes m comma s. Now, of course, again, if we try to ask, well, how similar is now that sentence Mary likes Sue in that representation to the sentence Mary and Sue enjoy hanging out together, right? Like that sentence already will be quite tough in lambda calculus to represent, to be represented. And they're very discrete. They're not sort of fuzzy, long lists of numbers, and we're not in a vector space, but we have very discrete representations. And so there's no notion of similarity or the fuzziness of language when we use these kinds of representations. And now in deep learning, again, every word and phrase and even every logical expression will just be a vector. And because of that, we can combine different vectors, again, using neural networks into other vectors. And then we can still, it turns out, make it a classification problem. For instance, we could say all reptiles walk versus some turtles move. And then we can ask, well, does one actually logically entail the other? Well, if all reptiles walk, and we know that turtles are reptiles and some of them move, then this clearly has to be true if this is also true. This is the entailment problem. This was studied by Sam Bowman, who happens to also be a Stanford PhD student in linguistics. And basically, instead of us having now to define, oh, well, turtles are subsets of reptiles, and moving is a general expression, and walking is a special subtype of moving, and any of these things, he basically just says, everything is a vector. Let me just train a model with the final output that I care about, with a simple logistic regression at the top, and just say, yes, no. These two sentences are in this relationship, or they're not, and I learn everything in between. And eventually, amazingly, the model, without us having to manually define that, reptiles is a supergroup of turtles, And moving is basically more general than walking. Without us having to define any of these things by hand, the model figured it out to make the final correct prediction that one entails the other. Yeah.
How many examples did you need to train that?
You do need a lot of examples, right?
Like
You basically, like in the thousands. Generally, if you, for any of your projects and any kind of deep learning models, if you have 1,000 examples for each of the types of things you try to identify, then you start having a chance of having a deep learning model learn it. If those 1,000 examples are good representative examples of your overall problem. Yeah.
Will you lose some kind of like alignment information? Because traditionally in the semantic lambda calculus, the difference is going to be all and some are going to be very two different lambda expressions. And actually matching them one-on-one is one of the ways that humans do compare them, do entanglement relationships. So do you think this kind of like tree composition structure might not be the best structure?
It's a great question. So here we actually said we first combine all in reptiles and then say all reptiles now is combined with walk. And here we say some turtles. And first you try to represent the meaning of some turtles, and then you combine it with move. Now it turns out that you don't even need to have the tree structure. Eventually we'll just read words from left to right, and we'll do almost as well, in some cases better, in some cases only slightly worse, to having this complex grammatical structure where you understand that so why do we have the tree structure in the first place? And again, we'll have a whole lecture on just understanding tree structures better. But generally, you wouldn't say reptiles walk and then say all of that, right? It is much more intuitive to say this sentence first basically describes an agent or basically a noun phrase, and then you say now all of these reptiles, all reptiles, and then you combine that with walk instead of saying reptiles walk and then adding all after that. And so this is kind of the very, very high level idea of syntax and grammatical structure. And we won't need to go into too many details of that, but yes, sometimes the trees help, but not always. Yeah?
Is the claim that a properly trained model has different layers that actually does these things, or is it that with proper training you can mimic each of these levels with like an appropriate net?
So it's a little advanced of a question to really answer it. I think we'll need more time and sort of a lot more of the knowledge that we'll cover in this class. In the end, the hope is that if you don't have the tree structure, but you think it is required for the problem, that you will actually learn it sort of not subconsciously, that would be a lot of scare quotes, but implicitly. That if you just go from words from left to right, that the neural network keeps some kind of simple stack, for instance, and some neurons will capture, oh, now something happened, and now keep these things into, put them into this subspace and things like that. So we'll get into that a little bit more, sort of half of the lecture, half of the quarter. And but yeah, that's a short version of that answer. It's not very satisfying yet, but I guess that's why we'll have the class. All right, so we basically were able to see that for all these different levels of linguistic representation, starting from speech to phonemes and morphemes, words, phrases, grammatical structure, and the meaning, everything will essentially be mapped to a vector. Now let's look at a couple of applications. So here's one for sentiment analysis. And just again to help you understand how amazing it is that we'll be able to do in this class, and we'll be able to build some sentiment analysis models that are very, very accurate. I'll tell you a little bit about traditionally what it meant to do very well in sentiment analysis. Basically, you had to have a curated sentiment dictionary, and you said, well, if we try to do this really accurately, let's all sit down and think about all the positive words that we have. Wonderful, awesome, amazing, great, sweet, and so on. And then you look at your errors, you say, all right, now let's just basically sum up positive words and sum up negative words. And for each new sentence, we say if there are more positive words than negative words, we say this is a positive sentence. And that's our algorithm. Very simple algorithm. We look up something in some dictionary and do that. And then in that kind of project, what you would notice once you look at the errors that your algorithm makes, you see, oh, well, there's also negation. Right? And so I say, well, if I see any of these positive words and then I see not in front of it, I'll just say it's negative. So not good, not wonderful, and I'll say it's negative. And then you look at that and you say, well, not awesome, but still okay. Might actually be not negative, but it might be neutral or just slightly less positive, right? And you keep doing that until you realize you're never going to actually be able to write down all the rules by hand. Now what we're able to do is we basically give it a lot of examples of phrases and sentences, and we can train a single model that takes in these raw labeled phrases and makes a final prediction, and then was able to outperform all this human engineering of this domain of sentiment. And here's again an example. Unfortunately, we're missing all the trees, all the lines for the trees. But basically here we have humor is very positive, somewhat sadly intelligent humor is not as positive as just humor. But basically this whole phrase intelligent humor is identified as positive by this model. Now any other kind of intelligent humor is still positive. Cleverness and wit or other kinds of intelligent humor is positive. To care about all these positive things is still positive, but then, or neutral here, so this is a misclassification. But then once the movie doesn't care about them, the algorithm learned that now it's actually negative. So not caring about a bunch of positive things turns out to be negative. And again, we didn't have to give the algorithm this kind of rule, like not caring about positive things and so on. It just learned it automatically. Yeah.
Are you always initializing with like some sort of word pre-trained word to that here? Or
yeah. I see you'll have a huge discrepancy of people who are super advanced already and know word2vec, which is what we'll discover or describe in the next lecture. And then we'll probably have some people who don't know this yet. The short answer is almost always yes, unless you have a lot of data, and then you don't need to do it. And don't worry if you don't understand the question or the answer yet.
What's a lot of data?
Tens of thousands of examples at least per class. Yeah.
What if you have mostly positive training data? Like in this, like if you had mostly positive sentences, could you kind of still infer the negative sentence?
So it's a good question. So in general, you might remember some lessons learned from your machine learning class, and one of the problems in standard machine learning is this one called skewed class distribution or unbalanced data set. And deep learning is not immune to that problem. If you have 95% of your data is in one class, like 95% of all your sentences are super positive, and you have only 5% of your data set of sentences that are negative, your algorithm, even if it's deep learning, will still have a hard time learning that well, and we'll have some techniques that we'll cover sort of much later in the class on how to deal with skewed distributions like that. But yeah, neural nets are not immune to that problem. All right, so now let's go over another example, and then I think we'll only have 2 or 3 more, and then we'll end with a live demo of a very powerful neural network model. So question answering is one of these really tough problems in natural language processing, where generally you'd need a lot of feature engineering in past methods, and even in methods that are as little as 2 years old, where you may have to have regular expressions, for instance, and finding specific features is like a main verb. Does it trigger something very specific because you have a WH question for a subject or an object and things like that, or you define who's the agent of that sentence and things like that. So pretty complex kinds of features that you have to engineer to do well. And basically, in deep learning, there's some folks who use the exact same model architecture, the same kind of neural network architecture that we use in morphology, in syntax, in logical, semantics, and sentiment. In this case, it was a recursive neural network. The same kind of recursive neural network that we use for all these different levels turned out to also be able to answer questions for more complex kinds of things. And in the end, it stored a lot of the facts that were asked about during training in vectors. And so when you zoom into, again, these visualizations, the model had automatically learned that Ronald Reagan, Jimmy Carter, and Woodrow Wilson, for instance, are all somewhat similar. Now, how exactly they're similar? Well, we know, but that again requires world knowledge. But somehow the model was able to say, in this area of my vector space, I represented in some combination of numbers that these were former US presidents of maybe a certain time frame, right? And we didn't have to go in and teach it about, what presidents are and what time frames and different times are and so on. And it put, for instance, George Washington, Thomas Jefferson, and John Adams in yet another part of the space, and those are closer to one another and they're closer to other presidents. But if you go over here, you'll have, for instance, policies or explorers and emperors or wars, rebellions, and battles. So these are all kinds of questions that were asked during training, and those are in a completely different part of the space. And again, the model learned that automatically just by having asked and seen a lot of answers for different kinds of questions. Yeah?
Did the computer generate those labels?
No, this is basically the authors, Mohit Ear and folks, basically trying to understand what the actual algorithm learned when it mapped these different entities into a vector space. And it basically nicely showed that they cluster very well together. Yeah.
Are these clusterings dependent on how you project down the dimensions?
Yes. So depending on how you project down your high-dimensional vectors into 2 dimensions, things look slightly differently. But usually you see the same kinds of groups, no matter whether you use TSNE or PCA. Don't worry again if you don't know this methods yet. We'll cover a lot of that. Yeah.
You need to know that William Mackin is a single instance, or can the algorithm learn that this is a single name?
Can the algorithm learn what?
That these two words belong together and should be in the
Those things can also be learned. In this case, they actually just learned that there are certain entities, and each entity just had one vector. But you could learn the combination. All right, now machine translation. I mentioned that was one of the toughest tasks in NLP. And again, just to give you a very high-level overview of the history, there are a lot of different techniques that people have tried to translate from one language into another. Some people said, well, first we need to, maybe we can just directly translate from one sentence to the other. But then people said, no, we first need to understand the grammatical structure. And then from one grammatical structure, we can translate to another grammatical structure. And others said, no, what we really need is to understand the meaning first, and then we can translate easily from one meaning into another language, that same sentence. So they're traditionally extremely complex kinds of models that require hundreds of gigabytes of RAM if you want to keep them in RAM, for instance, because they have to store all possible phrase pairs and things like that. It's very complex models. And they're, it's a huge area of research. We obviously, a lot of us use machine translation. It's one of the most useful tasks in natural language processing. And it used to literally require many years and many, many different people to build systems that were at all decent. And none of them are still great. Nobody in machine translation comes even close to human translation. But even for like reasonably, decent systems, it was huge efforts for many years. And now I might ask you, what do you think is the interlingua, the sort of main way to represent language if you want to do translation? Vectors, that's right. So everything will be mapped into a vector, and we will go over this model in a couple of weeks where you basically take any kind of input language, you map it with a neural network into a single vector, and then you translate, and from that vector you generate the translation sentence. So if that doesn't convince you that vectors are useful, then nothing will. So yes, there will be always fuzziness, right? Duck, should the vector be here, close to hiding? Should the vector be here, close to bird? But in the end, when we look at these kinds of impressive applications, we will see that no matter how we represent it internally, it's just incredibly useful. And so to give you one idea of this, I actually have a little demo of a model that can basically be asked any kind of question, and it's the same kind of architecture that underlies all these different applications. So I can ask, for instance, what is the sentiment of this kind of this sentence? The best way to hope for any chance of enjoying this film is by lowering your expectations. So this is one of those really hard sentiment examples that we literally only in the last half year are able to consistently correctly predict. And the algorithm correctly says that this is negative, despite having lots of great positive words like best and hope and enjoying. But in the end, to do all these things, you have to lower your expectations, so it's negative. We can also, here's another sentiment example. The film starts out as competent but unremarkable and gradually grows into something of considerable power. So even subtle notions like that can now be learned, and this is all learned with a single architecture, which we'll come to only at the very end of this class. It's called a dynamic memory network. Combines recurrent neural networks, which we'll learn about in this class, but then it also needs attention mechanisms to focus on specific words while we're making predictions. It's a pretty complex model. We'll cover it towards the end of the class. And the same kind of architecture, we're also able to ask what are the named entities. And here we see it basically will tell us what locations are, what are organizations, and also people. Then we can also ask it what are the part-of-speech tags, and it will basically give us an output at every word, finding all the different nouns and verbs and determiners and so on. We can also ask it very logical questions, and again, it's the same kind of architecture, and it's an architecture that if you start early, you could probably implement in this class, especially if you come to office hours. Here's a story, a bunch of inputs, and we'll represent all of these inputs with just a simple vector representation. And we might ask, where was Mary before the bedroom? After we give it all these different facts. And amazingly, the model is able to reason over these different facts and basically come up with, well, first I pay attention to where she was this morning, and then I find things like yesterday. And because yesterday happens before this morning, I now give you the answer that it's cinema. And we didn't require any logical expressions of like, here are temporal words, and I combine these temporal words this way. We just gave it a lot of training examples. Here's a story, here's a question, here's an output answer. You figure out what you need to focus on, what temporality means, or any of these things. And then it represented it all in a vector representation, just a list of numbers, to give the final answer. Now, we can also ask, we give you this story, and I'll give you a second to see if you know the answer. Does anybody know what the answer would be? I think I heard it. That's right, yellow. And so if we ask this question, what color is Bernard, we really have to look at the input multiple times. In the first iteration of asking the question, what color is Bernard, we might just find Bernard is a frog, and that's what the model pays attention to. But it doesn't yet know the answer. It's still, from just knowing that he's a frog, you might not know the answer. But then it goes and finds other sentences about frog, and going over the inputs again, realizes Lily is a frog, still knows it's not enough, but now goes and finds Lily is yellow, and then actually transitively reasoned over these different facts to give us the final answer. And that kind of thing, that used to require humans sitting down and defining what's transitive logic. How do you go from A to B to C and then know that it goes to A to C too? And now all you need to give it is a bunch of vectors and represent that, a bunch of these kinds of input stories, in this case question, answer, input triplets, and the model figures it out. Maybe to show you how general this is, again, you don't need to have any knowledge about the language. In some kind of almost sad way, it's just a bunch of IDs and we learn vectors for each character or for each word. And we can make very accurate predictions at the end. So I'm not going to make a fool of myself trying to read that out loud, but I think it's kind of a fun sentence. And again, question answer input triplets represent everything as a vector, make very accurate predictions. Same thing, translate. Question is, translate to German, give a bunch of question input triplets, and you can build a translation model. And last but not least, if you've taken 231N, you're going to be able to combine these techniques and even ask questions about images and also get answers for that. And it turned out all these examples can be solved with the same kind of deep learning architecture, which is one that we'll cover towards the end of the class. All right, with that, I'll wrap up. Basically, in the next lecture, we will learn the first step that we'll always need for all these different models, which is to learn how to represent words as vectors. All right, thanks. Welcome to lecture 2 of CS224D. Today we'll talk about word vectors, which is really exciting because they're the fundamental Lego block that you'll need in all the other classes in the future. Also, it's exciting because you'll see a little bit of the kind of math that we're going to do. Inevitably, I will probably bore 1/3 of you to death today. I'll probably be too fast for 1/3 of you, and I'll hopefully be just at the right speed for the last third. So I will err on the side of boring more people, but making sure we're all on the same page, because right now we all think we may know the chain rule already, but once you have the chain rule in some complex beast in recursive functions with a bunch of matrices or tensors and very complex chains, you want to make sure you really have the basics right. So sorry for those of you who I'll bore, but also for those who I won't bore and for whom this might be a little too fast. Definitely it's important for the first week or two to come to the office hours, start with the problem set early, and really make sure you have the basics all figured out that we'll cover today. I had some questions already on how much natural language processing do I really need to be able to successfully complete this class. I think we will cover almost all the natural language processing sort of knowledge that you need to be successful in this class. So you don't need to already know what Chomsky tree structures are, or named entity recognition and the BIO scheme, or any of these kinds of things. We'll cover that when it comes up in the class. Are there any other questions organizationally? So the first problem set will come out next week. The office hours of all the TAs will start next week. We actually have 2 exciting new additions to our TA team. I saw David back there, was waving. And then I think we had Samip also back there on the camera. Barath, is he here today? Yeah, there he is, and James is right there. And then I think we have one new person. Is he here too? All right. Hopefully he'll be here soon. All right. So, are there any questions? Cool. All right, let's get started. Word vectors. This is a little bit of the background of why do we represent words, and what do we mean when we say we represent the meaning of a word. And meaning, again, is one of those elusive things that we're trying to capture when we try to have computers understand language. And here's just one dictionary from Webster that gives you a little bit of a flavor of what could be behind the word meaning. It could be the idea that is represented by a word or phrase. That is what we're trying to do, but it's really a bit of a cop-out because now we need to define idea, right? And then you get to thought, and before you know it, you have an hour-long discussion about the philosophy of language and thought. The idea that a person wants to express by using words, so not necessarily what's inherently in the word, but something that you're trying to express. Maybe that's a little bit easier for us also to deal with. Or third, the idea that it is expressed in a work of writing and art. note how that is, now you have to understand what's the difference between being expressed and being represented and so on. So it gets very tricky very quickly, but fortunately for us, it will be much more concrete. So let's take just a few minutes on the history of how people try to represent words in the past and actually still do in the present. And then we'll sort of see how we get to word vectors eventually. So a common answer to how we represent words so that computers can understand them is by using a taxonomy, such as WordNet, a great project at Princeton University for many years. It's also the start of ImageNet, which all of you are familiar with who've taken 231N last quarter. Basically, it's a very large graph that defines a lot of different relationships between words. Not just is-a, but also hypernym or hyponym relationships. So, for instance, we can look here at all the hypernyms of a specific word. So in the end, everything in WordNet ends with being an entity. Every noun is at some point an entity. And then there are different tree structures. It's almost a tree. It's actually a DAG-directed acyclic graph, but for most people, they just see it as a tree. So every entity is either a physical entity or an abstract kind of entity. And then this is basically going down a very long, deep down into a tree structure. You have carnivores, and then you have basically all the way at the bottom a panda. So now one way to represent the word panda is by saying, well, a panda is a special type of carnivore, placental, mammal, vertebrate, and so on. Maybe some you're more familiar with, some you're less familiar with, like it's an animal, an organism, and so on. So that's one way we could try to have a computer understand or represent the meaning of a word, by basically connecting it to all the other words that we have in this big graph. That works not just for nouns, but also for adjectives. So here, for instance, we can look at synonym sets, or so-called syn sets. They're basically just a list of words that, according to the people who create this taxonomy, have roughly the same meaning. But you will see here that really when you say somebody's good or honorable or respectable, these are really quite different definitions and different syn sets of the word good. So good can have different meanings, and each of the different meanings can have its own synonyms. And a good can, of course, also be a noun. So it can be an adjective, an adverb, or a noun. So you'll quickly see, just with the example of good, that there are a lot of issues with that. So for instance, the synonyms of good might also be adept, expert, good, practice, proficient, and skillful. But of course, each of these words, while in some abstract way they roughly mean the same thing, you wouldn't use them in the same context, right? You wouldn't say somebody is an expert versus he's just good versus he's very proficient. You use those kinds of words in different contexts, right? Proficient you would use more likely for describing the language skills, for instance. Also, you'll have a lot of missing words, because language is this evolving, beautiful beast. Beast when you try to tame it, beautiful if you just play around with it. And it's impossible to essentially keep this kind of list up to date, right? And here are just a couple of examples that basically come up. And probably this year we had invented 2 new synonyms for the word good, right? In Ninja, you might see in lots of terrible job advertisements, and maybe that's only specific to this area and certain startups and so on. So there's so much subtlety that is lost when we just say all these words have exactly the same meaning, that it's going to be tough for a computer to be able to capture that if we just say they're exactly the same. So basically these lists and this taxonomy is inevitably quite subjective, and it also actually requires a lot of human labor to create and adapt. And there's really this great taxonomy of WordNet really only exists for English. There are a couple of other languages, but none of them is as vast and well well maintained and updated as the English WordNet. And then the worst part is that it's going to be hard for computers to accurately capture similarity. So we just have basically, if we have these synonym sets, we say it's a synonym or it's not. That's just one dimension and it's binary. It's not very ideal. So generally, that is a problem that has plagued a lot of different natural language processing models that started and start with discrete representations. And that is really the vast majority still of rule-based systems and a lot of statistical natural language processing work. So, for instance, when we say hotel, and we try to now, in the end, of course, that's still a string, but you want to give it a number. You want to assign some kind of vector so that a computer that deals with numbers can accurately represent that. And so, basically, what you'll see here is that this is a so-called one-hot or one-on vector that basically describes words in the simplest way. It's still very, very common in a lot of NLP systems and a lot of just generally methods that are being used in industry and in research. Basically, what it just is a lot of zeros and a 1 of the index for that word. So if you have 20,000 words, you have basically for each word is represented by a 20,000 dimensional vector that has a single 1 in it. And you can give that to a logistic regression classifier, for instance, to classify a document by combining a bunch of single 1s for all the words that appear in that document. This is a so-called bag of words representation. Of course, you'll notice quickly that if you have a very large vocabulary, those kinds of vectors will be gigantic, right? And then you'll probably try to have some sparse representation that really only captures that index. So the one-hot representation, the main problem with it is, again, this notion of similarity. If you train a model and you say, well, I try to classify positive and negative sentences, for instance, and I see the word awesome. Now, the word awesome basically has no connection to wonderful or great. It's just a single one-hot vector. And if I try to see, well, which words are similar, none of the words are similar to one another in this kind of vector representation, right? Hotel and motel, for instance, if you just have a simple AND operator between all these indices, the similarity is 0. So that's not great. Now, the main idea of today's class and a lot of the other work is to essentially, instead of representing a word by just its own index, you're going to represent a word by means of its neighbors. And this is a very old idea from Firth from 57, who basically said you shall know a word by the company it keeps. And that very simple idea underlies a lot of old and traditional representations for words, but also the newest ones like Word2Vec, which we'll cover later in this class. They turn out to all boil down to this idea. So if we want to represent banking, we'll actually represent it by the words to the left and to the right of this word. So we might see already that banking and bank might both have, debt problems or something in their contexts, right? So if you now represent that one word instead of with a single index, with a bunch of indices at the very least of the words around it, you already gain something. So the question is now, how do we make these neighbors represent words properly? And the simple answer is by basically collecting with a large text corpus a co-occurrence matrix. We'll call this X. And there are basically two options of how we can compute X. The first one is we can use full documents, basically just this word, we don't care about only the next 5 words to the left and 5 words to the right, but we'll just say any word in that document will describe the current word. So these are Word document co-occurrence matrices, and what we'll gain, and we'll get into that a little bit, is essentially just general topics. If you just ignore all the word order and all the local contexts of a word, all that a Word document co-occurrence matrix will give you is general topics. So swimming, wet, boat, and ship, they'll all be kind of similar to one another because they all appear in some kind of boating topic. So we will basically lose any notion of syntax, any notion of parts of speech when we just look at the entire document as a context. But this kind of representation, which we won't go into details that much, it's called often latent semantic analysis or latent Dirichlet allocation, or different models that capture essentially a document context. They're great at capturing topics. This is about sports, this is about politics, real estate, science, things like that. Instead, what we're going to do for the most part in this class is to actually just look at a window around each word. N words to the left, N words to the right. And so let's look at a very, very simple example and actually see what traditionally one would have done with this kind of co-occurrence matrix and get some intuition of what's going on there. Here, we'll create a very, very simple word co-occurrence matrix with a very, very simple corpus. This is our corpus. I like deep learning, I like NLP, and I enjoy flying. Those are 3 sentences, and we're going to essentially build this co-occurrence matrix X now, and we will use a symmetric window. What does that mean? Sometimes people look at just the left word, the 5 words to the left, or the N words to the left. Sometimes some people only look at the N words to the right, but we'll have a symmetric corpus where we basically look at the N words to the left and N words to the right. Usually N is around 5 to 10. Because these are very short sentences, we'll keep it simple, and we'll describe each word through context windows of 1 word to the left and 1 word to the right. Yeah.
How well does that context window hold up if you're inserting start and stop words? Like if you just have a repetition of 5 start words, and then I guess like what is the similarity then if you look at the 4th word in the sentence, so you only have 1 start word?
So by start word, you mean often in these kinds of contexts, if we have a symmetric window and we want to describe the first word, then we might say, well, there's 1 word to the left. So I will basically have a special token S and end S for the beginning of a sentence and the end of a sentence. Here it wouldn't make that much of a difference because I is the first word in all of them. In general, that is something that you would do for most methods. Though if you use all of Wikipedia and you just have the entire document instead of sentences only, which is the most common way to do this, the start token doesn't make that big of a difference.
I guess I was wondering, like, in terms of, because you can chain adjectives before an object, and so like depending on your vocabulary, you can end up in a weird situation where you might have multiple start words for one object, but almost none for another object that is synonymous, just because that other object in your training vocabulary was preceded by a bunch of adjectives.
That's right. So in general, what we'll observe is that training word vectors will hugely depend on the corpus that we'll train it on. So, and if your corpus is not representative of language overall, you won't get good word vectors out of it. So here, this one will have, for instance, no connection to we or they, right, or other pronouns. It only knows I. And so that's step 1 for a good corpus. It should have the words that you like to describe in it. But then even once you have them only once or twice, that's also going to be tough statistically. So we will run into that problem. The sort of default solution is to just use Wikipedia. As long as you use Wikipedia, it's actually a really great corpus to start learning these word vectors. And that way you have fewer of these problems, but in general, the more the better. So the largest word vectors that we've trained in the NLP group, I think it's still correct, as a project with Jeffrey Pennington, Chris and me, we used Common Crawl. It's basically a way to download almost all the websites that allow you to be downloaded, and just you have a gigantic 840 billion token corpus. So tokens is basically word instances, and that has a very large vocabulary, and that works even better than just having in comparison, small Wikipedia. All right, so let's build our matrix. So the example corpus is above here, and now all we do is very simple. We look at each word, and we basically look at how often each of the other words appears to the left and to the right of the current word. So I basically has like twice in its window, and enjoy once in its window, and that's it. And like appears in its window has twice I, and once deep, and once NLP. Yeah?
I was wondering for larger windows, so do they usually use just like this 0, 1 kind of thing, or is there like a kind of decay function based on how far?
That's a great question. So you might say, instead of giving 1 to every word in my window, I actually give 1 to the first words to the left and right, and then half to the second words to the left and right, and so on. And that is actually a technique that can help some of the word vector representations. We'll mention it briefly in a couple of slides, but yeah, it's a great idea. Especially if you have 10 words or so, the 10th word to the left might not be as relevant. Yeah.
Is there a token for like starting a sentence? In this case, like all the I's have some token for start of sentence, start of text.
That's a great question. And yes, sometimes you do use it and it can help, but the larger your corpus is and the longer your documents are, the less it matters. So here, we could have done it, just kind of made the table even larger, but yeah. Definitely like start and end token of sentences are commonly used for smaller corpora. Great questions. All right, so this is basically one way to represent words as vectors, right? This is already it, right? It is a list of numbers, and now we at least would have certain things such as like and enjoy at least have some overlap. If we just kind of did a simple inner product or a simple logical AND, then like and enjoy would be more similar to one another than enjoy would be, for instance, to deep. Right? So we captured that liking and enjoying might be actually more similar. So that's something. It's an improvement over just a single one-hot representation. But of course, the problem with this is that now our vectors increase in size with the vocabulary, which isn't ideal. Right? We have a new word in our corpus, and now we have a new column in this matrix and a new row, and we have to update the whole matrix. So that's not ideal. Also, we'll have a lot of words, so that matrix will get really, really large. Think of Common Crawl, 840 billion tokens, millions and millions of different words. You wouldn't want to have to install that on every time you install your app that uses some deep learning or some other algorithm on your phone, like have to carry that gigantic matrix around. And basically, that kind of matrix is still very sparse, right? So every classification algorithm that we'll use on top of it that may eventually have to learn a weight, an importance weight for each of these different dimensions will have a tough time. So the models that you'll train will not be very robust. So the solution will be to use low-dimensional vectors instead. So the idea is that we're storing only the most important, and again, this is a little bit with scare quotes, the important information in a fixed small number of dimensions. And that will essentially give us a dense vector. And I won't go into, we'll go into some details for the dimensions, but in most cases, the dimensionality will be between somewhere between 25 and 1,000, which is a pretty large range. In most of your applications and your projects, you're unlikely going to need 1,000-dimensional word vectors because you won't have enough training data to train these kinds of models. You need huge machines and so on to do that. So if you just train a simple, small data set with a couple of thousand of examples, you usually can get away with 25 or at most 100-dimensional word vectors. So the big question now is, how do we reduce the dimensionality of this matrix X? And the first method, which is quite common, is to use singular value decomposition, or SVD. Can you raise your hand if you're familiar with SVD? All right, excellent. All right, great. So basically, we just have here our orthonormal columns. We have our singular values here, and they're sorted by the first ones in the top left. And basically, we know that each of these columns basically describes sort of or reflects the principal components here, the axis of the greatest variance of your data sets. And now what we can do is, instead of representing X with all of the orthonormal columns and rows, we can just take the top K. And that will essentially allow us to reduce a lot of the noise in this representation. And also now we can fix K and say, no matter how many more numbers you get in here, we will only take the top K eigenvectors. Principal orthonormal columns. So let's actually look at what this would mean if we implement it. It's very simple to implement this kind of model. Again, same corpus. I just basically created a simple array in Python, and we just run svd on x. And we basically get here our orthonormal columns, our singular values, and v. And now we can represent and project this by taking only the top two biggest singular values and corresponding orthonormal columns of u here, and basically plot the text and plot the words in these two dimensions. So again, we have a simple, very simple co-occurrence matrix. We just apply svd and take the first two orthonormal columns here, or the left singular vectors. And already, we just created a word vector that captures in some low-dimensional space some of the relationships. So for instance, like and enjoy or close by, I being the only noun or the only subject of these sentences is by itself. NLP and deep and flying are closer to one another, flying and learning are close to one another, and so on. So already, with this very simple corpus, some very straightforward relationships are captured in our word vector space now. And now n here is 2 dimensions, and these 2 dimensions capture some of the information we would want. Any questions about using straight up SVD and co-occurrence matrices? Yeah.
What are the axes?
Sorry?
What are the axes?
Oh, these are basically just when you look at your orthonormal columns U, there's no specific meaning to these axes. That's just where the numbers come out to be. Yeah.
So like and enjoy should be relatively similar, but it seems like is kind of way out there because it's in every single.
Right. So we can look at essentially like has, and this is actually a good observation, it actually appears quite a lot, and it has the most words in its window. And you'll notice that that's probably not ideal, right? We'll actually have some hacks to deal with exactly that problem in a couple of slides. So it's a very, very good observation.
Yeah, in examples with more data and more dimensions, do we have any intuition on what these dimensions correspond to in terms of word meaning?
So very rarely can you find that a single dimension by itself will have a great meaning of like, oh, these are only things that have a very high value are objects and not verbs or something like that. In most cases, the meaning will come through multiple dimensions only, and through the relationships and bases vectors of that entire space. So yeah, so we already observed that just because like had a lot more values in its row, it kind of made it more special than it should be. So the frequency of the words mattered a little bit. But basically, we got somewhere, right? We now have one way, it's a very simple way, to get dense vector representations for every word. And this is going to be for all the subsequent models we'll use, all the deep learning models. That's how we're going to represent words. We're going to find better ways to compute this vector, but that's essentially what all these different methods will capture. Co-occurrence counts, words to the left, words to the right, projected into some lower dimensional space.
What is this 2 dimensions?
So 2 dimensions is a good question too, only for visualizing the vectors. In almost all cases, they will be higher than 2-dimensional. It will be 25 at the very least, up to 1,000.
You determine the dimension based on, like, for example, how the singular values decay? Or?
Yeah, exactly. So these are the top 2 dimensions corresponding to the top 2 largest singular values. Yeah.
No, I mean, like, for example, if there's an energy criterion, for example, in trying to
to cut off the singular values, it's rarely ever used. It really. We're getting a little ahead, but it's a good question. So how would you make this decision now, how many dimensions you should use? This will come up over and over again in your class projects. You're going to get extra points if you do this properly, and you're going to lose some points if I see certain graphs where you have a hyperparameter, for instance, one that you will very often optimize over, which is number of word vector dimensions. And if your graph goes up like this, and then you end, I say, in my feedback, well, why didn't you run it with even larger, right? Maybe it would go up even further in your accuracy or something like that. And so the best answer to how many dimensions should you use is determined by your overall task. And we don't know yet any overall tasks we could do, such as named entity recognition or sentiment analysis. Those will come later in the lecture. So right now, we'll find simple intrinsic evaluation metrics, which we'll cover in a couple of slides. Yeah.
By representing words as vectors, don't we impose, I guess, some kind of transitivity? So like if A is close to B and B is close to C, then A is also somewhat close to C.
Yeah, so if you have a proper space, then that will be the case. And we will see lots of interesting relationships that will come out of exactly those kinds of similarities.
Okay, so it's not like a bad thing. Because I mean, it's not always the case that if like, you know, like is similar to some other word, like you don't always have that with words.
That's right. So, but you're also fortunately not going just in a single directions when you compute these similarities, right? You can have various distances and things like that. And the distances, you can also, when you try to understand the geometry of the space, you can make them directed. So it's not just like a similarity, which is undirected kind of distance. So, but in general, you're right. There are a lot of problems with capturing or with representing words as a single vector, right? We have words that are polysemous, that have multiple meanings, right? Good can be the goods that you buy in the store. It could be an adjective. It could be an adverb. Can have different meanings. Bank could be the sandbank, could be the money bank, so it could be the bank you're sitting on. So there are issues with word vectors, and there are also people who try to deal with those issues, such as learning multiple vectors for each word. And you have bank _1, bank _2, bank _3. So we had a paper of Eric Huang, Chris and me, about just that, like learning multiple word vectors. And so there are lots of issues, there are lots of fixes, but in the grand scheme of things, just having a single vector for each word will get you very, very far. And it's what you almost always have to do for your projects. Or it's enough to just do that. There are also other problems, such as sometimes you might say, so if you ask, for instance, some people in one country how similar they think their country is to that other country, they might say, well, we're similar to them, but then other people might say, but they're not similar to you, right? So you can already make this fail, the kinds of geometric representations for single words, with just two words by themselves, not even relationships. So lots of issues. But in practice, and that's kind of why we defined that in the beginning, we're going to try to make computers understand language to solve a real task. And for those kinds of real tasks, this is a great representation. All right, so from now on, every word will be a dense vector for us. So we already had this very cute observation that like, which had a higher frequency, turned out to be somewhat special and by itself in this space. And this is actually a problem that people observe a lot and have essentially fixed by saying you have a maximum value for the counts. So there are certain function words or so-called stop words that are very frequent, but rarely ever add that much to the meaning. So the, he, or has are very frequent in a corpus and basically just capture syntactic information, grammatical information. And so there are two fixes. One is to just ignore them all. You just delete all the words from the corpus. That's one way. I think a slightly better way is to basically say you take the minimum of the actual value that you have in each cell, in each element of your matrix, and some maximum value like t equals 100 or so. And with that, these stop words or function words will not be that special. And then another great idea that already came from you guys too is to have a ramped window where closer words have a larger count. And you basically give fractional counts to your word matrices. to the co-occurring words. Instead of just taking the counts, you can also actually compute correlations between words and then set negative values to 0. There's a lot of work. Once a paper from Google came out a couple of years ago by Tomasz Mikolov, a lot of people got really excited about word vectors and started doing all kinds of really great analyses. And next week we'll capture just a couple of the details of word vectors, but we're still just doing an overview. So let's look at what you can capture when you just use a simple kind of SVD on some somewhat massaged count matrix. The first one is that we get very interesting semantic patterns in terms of very simple inner product distance. So you basically just look at how close are two words in this resulting vector space. And then you can group them, very simple binary tree, and amazingly it does find that wrist and ankle are the vectors closest to one another. And shoulder and it comes next, and then arm is the next closest, and so on. So you can basically build these similarity trees, and they already capture an amazing amount of what we would think is kind of world knowledge, right? But again, there's no magic here. Wrists and ankles are probably appearing in similar contexts. You can sprain them, you can break them, they're close to your body, they might be mentioned in connection or in co-occurrence windows with athletes and things like that. So no magic, but still kind of amazing that we're capturing all these semantic similarities. Here's another interesting observation where we again project down these word vectors. Sometimes you can use PCA for that. Sometimes you can just look at the first two orthonormal columns of straight up SVD. But basically you can see also that different temporal expressions for different verbs are actually close to one another. So show, showing, showed, and shown are close to one another in the vector space, and grew, grow, and grown are also close. So it captures also some temporal aspects of language. Here's another interesting semantic pattern, such that a verb and a noun of an agent that is most likely going to partake in that kind of activity is essentially in an interesting linear relationship even. So drive minus driver has a similar sort of direction as swim and swimmer, or learn and student, and teach and teacher, treat and doctor, marry and priest, or pray and priest, and marry and bride. Right? And this is from over 11 years ago. Yeah.
What is the input of this vector?
What is the input of the vector? So it's the co-occurrence matrix that we started out with. We take a very large corpus, and then we compute the co-occurrence matrices, run SVD, and then visualize it in 2 dimensions.
So you should eliminate all other words just to use those words, right?
We eliminate what?
Other words.
Oh, yes, that's right. So for a lot of these visualizations, if you mapped all the words of your vocabulary into the space, it would be very hard to visualize. All the words would kind of be overlapping. It's just very hard to visualize. But you also won't see as many beautiful kind of relationships. It's a good question, yeah. Yeah, so for these kinds of visualizations, you often only project a subset of the words into your lower dimensional space. There are some visualizations also that try to do that with many different words, but then it's harder to see interesting linear relationships.
Do you manually choose a subset of words or do you visualize?
Yeah, so here they did choose that subset. Though there are also some visualizations where you take 100 or 2,000 words, and then you can zoom into the space. You just create a very, very large image, and you zoom into the space, and you still see some relationships. So they're not like totally cherry-picked, but not always do these kinds of relationships work. Like again, if you have something where you have a very polysemous word, then it will only have basically the majority meaning, the meaning in that corpus that you trained it on, where that meaning appeared most frequently. That's the kind of meaning that will have the nice sort of linear relationships as you project it down. Yeah.
Just out of curiosity, did anyone do an analysis of whether this is statistically significant?
there will be a lot of statistical analysis that we'll get to, where somebody created a data set, also Tomasz Mikolov from Google and co-authors, where they essentially took thousands of examples, currencies of countries, country names, and then tried to, basically find linear relationships, like, and again, this is temporally different, like Germany minus Deutschmark plus US dollar goes to United States, things like that. So there are different ways. Now, it's not quite statistical significance, but they basically created a data set that had tens of thousands, because you can kind of artificially create all the currencies, all the temporal expressions like show, shown, shown, and so on. And then you can compare a lot of the different relationships in at least significant kind of way, where you evaluate and you say, oh, my method got 80% of all of these relationships correct.
So how do you update the word vectors if you have to? So for co-occurrence matrices, it can be very large, right?
Right.
So as language changes, do you want to update your word vectors?
That's right. So that is exactly what we'll describe in the next slide here, which is there are some problems with this. So what happens when you add new words or new documents, and now you have to rerun your entire SVD. Now, I think there are online versions of SVD, so that's one way to solve that. But in general, for running proper SVD, you're going to have a huge amount of cost for very large matrices. So if you have millions of words, millions of documents, SVD is not going to scale very well. It will require a huge amount of RAM. And yeah, it's very hard to incorporate new words. You just got a couple of new Wikipedia articles, a couple new words, but you really want those words to be in the space of all the other words. Now you may have to rerun that full SVD. And also, the SVD optimization is going to be a very different learning regime than all the other methods that we'll see in our deep learning models. And so we'll actually not use SVD for most of our techniques, and you also won't have to implement it in your problem set. And instead, what we'll do is we'll try to directly learn low-dimensional word vectors based on just single windows. And then we might go back to SVD and see if we can learn from both of these kinds of models and combine them. So basically, it's quite an old idea, but there are a couple of papers that are quite relevant for this lecture. So the most relevant one, which I'll also encourage all of you to read, is NLP Almost from Scratch by Colbert and Weston in 2008, and in 2011 they had a journal version. I think it's listed in the syllabus as well. And then the most recent, even simpler and faster model is the well-known Word2Vec by Tomasz Mikolov and other folks, and that's the one we'll describe right now in all its gory details, because it's really nice, very simple. We can get our hands dirty with a little bit of math on the whiteboard and start thinking about how to take derivatives, how to update them with SGD and things like that. All right, so the main idea of Word2Vec is, instead of capturing all these co-occurrence counts directly, we're just going to predict surrounding words of every word. So instead of collecting a large co-occurrence matrix, we're just looking at each example one at a time. We're going to say, in the current window, based on my current center word, can I predict the n words to the left and the n words to the right? I guess it's hard to draw something. Yeah, that's basically the main idea. It turns out that idea of predicting the words to the left and predicting the words to the right will eventually also capture just co-occurrence statistics, just like the previous method. But it does it in a very online way. I can easily add a new word, run it over that word, and update the model. And yeah, it's very easy to add also new words, new sentences, and so on. So let's look at the objective function of Word2Vec. And we're going to drill into this quite a lot in the next half hour. We'll define again our co-occurrence window. We'll say here the window has length m. So for each word, I will try to predict the m words to the left and the m words to the right. And we're not going to use any of the hacks of weighting them differently for now. And what we're going to try to do is to essentially maximize here the log probability of any context word given a current center word. So we have a very large corpus of t tokens. Could be 840 billion. It's going to be tough, but it'll take a very long time. And we go each word one at a time, and for each word that we have, we're going to go m words to the left of that word and m words to the right. And for each of those context words, we're going to try to maximize some kind of log probability here of that word. And theta will be all our word vectors that we're going to try to jointly optimize. So let's look into how we could represent in the simplest, cleanest way the probability of a context word given the word in the center. So I will describe here O as the outside or output word ID. So again, that's just the context word, the outside word, but context is not a great word because C is going to stand for center. So the outside word ID, we're going to try to maximize that probability, conditioned on the current center word. And the way we will do this is with this relatively simple expression where we just have an inner product here and the exponent of that. So just get positive number here. And we'll have a vector u for the outside word and a vector v for the center word. And I will use u for always the outside words. And so this is already an interesting observation here, which is every word will have two vectors. One vector when we represent it as an outside word, and one vector as we're trying to predict the outside words. So I think it'll be good to show you. How can we get the screen up? Oh, magic. All right, thank you. So just to walk you through the process, we're going to have a bunch of different words in a corpus, like I like this class and so on. Each line here will represent one word, a one-word vector. And let's say for simplicity for now, we'll have a window of two words to the left, two words to the right. And so we're going to start at this word and basically try to predict this word and that word and then this word and then that word. And once we optimize for this window, we will move one to the left. And now this is our center word. And now that center word will try to predict this one, and that one, and this one, and that one. And so we're basically going to move this window one word at a time and try to maximize this probability. All right, now we have to go back down. Sorry, we're going to have to do that twice. Yes?
You mentioned having two vectors per word because you want to distinguish between the input versus the predicted. Why not represent the input as a vector? Because that's really what it is, right?
The input is also a vector. Sorry, the input is a word vector and the output is also a word vector.
No, I mean like it's going to be a vector of two words, right? Because you have n words to the left, right?
Mm-hmm.
You can change that formula so that C is actually going to be, or I guess it's going to be a vector.
Yes, you could try to represent all of the vectors you're saying at once in each window. You could do that.
And then you don't need two separate vectors per word anymore.
To be honest, you don't need two separate word vectors in general, right? We could just have all the vectors be v, and then you just have here a quadratic expression inside. It turns out that having these two vectors is just basically going to make your optimization easier. And this is not very beautiful, but in the end, in order to capture as much as you can of all the statistics, you're just going to average or concatenate these two vectors to represent each word. So at the very end of this optimization, after we basically learn two vectors for each word, we're just going to average the two. Not very beautiful, but works incredibly well. All right, so this is going to be our objective function for each single window. And we'll derive basically the derivatives and all these in 2 slides. But before that, just on a very high level, once we have computed here our entire objective function, we want to optimize this, and the way we're going to do this is with very simple gradient descent. And who here is familiar with gradient descent? Excellent. Most of us have all the prerequisites. But just a very simple refresher, you're going to have some function that won't ever look as beautiful as this one in deep learning. You have a derivative, and you will just basically start at some random value. So we will initialize all our word vectors at just small random numbers for a very large matrix. Usually we call this d-dimensional, and you have n many different word vectors. So you start out with a very large matrix with a bunch of small random numbers. And then we're just basically computing a derivative and then updating with some step function based on that derivative all our word vectors. So here this is just obviously not the kind of function we're using, just to basically show you gradient descent, which is what we'll do. Technically we'll do stochastic gradient descent, but we'll get to all of those details later. All right, now let's do a quick refresher on gradients, and then we'll actually derive on the whiteboard in 2 slides the gradients for the objective function I just projected on the board. So the first and most basic of the Lego pieces are the derivatives for just a single vector. Hopefully these are familiar, but might write it out. So if generally you're in doubt, it's always good to write out the indices. So maybe, sorry, if you can just put up the board like a little bit, not all the way, thanks. So generally, if you try to get the derivative of, that's perfect. Can you stop? No? All right. So x transpose A, derivative of x. If you're not certain, and for this it's very straightforward, you can just write out A. But eventually we're going to have lots of matrices, and it's much more complex. And so sometimes it's helpful to actually write out what the inner product really means. So here we just have xi, ai, and I equals 1 to the dimensionality d of those 2 vectors. And this is the part where I'm going to bore 1/3 and sorry, bear with us for this lecture. Basically now we can look at the derivative for each of the elements of the vector. And then we basically see, okay, xj only appears in one of these elements, so we just have the derivative with respect to just one element of the x vector xj is just aj, and then we can compute basically here our vector for each of these. So the first element will have this as its value, the second one will have this as its value, and this seems very trivial if it's just 2 vectors, but once you have gigantic matrices or tensors, it can help sometimes to write this out. And so on, all the way to an, and that's how you'll then see that this is the right derivative. And sometimes when we basically take these shortcuts by just knowing what the derivatives are in matrix notation, but you feel like, oh, it wasn't quite intuitive, it can be helpful to write it all out with the indices for each of the elements of the matrix, and at some point you gain like an intuition of like, oh, this makes sense overall. So maybe instead of going up and down again, I'll just write out some of this stuff. So let's make sure we get the same notation. So let's write, for instance, a function that is a little more complex, and do a little refresher on the chain rule. So y, the f of u, and this is the same notation, u equals g of x. And we may have some complex function that basically combines these and says y is a function, or y is defined as f of g of x. And now we want to take the derivative. I sometimes use d, so dy dx. I also often write delta partial of y, partial of x. And that will just be what? Quick refresher on the chain rule. We have a function here we define as y, and we have want to get derivative with respect to x. Say again?
Partial y, partial u.
That's right. Times? I think that's what you said. That's exactly right. All right, so that's the chain rule in its abstract form. Now let's make this very concrete and start out with a simple example, and then we can do it with a much more complex example. So let's just define our function y here as y equals f of u equals 5u to the power 4, and our function u equals g of x equals x cubed plus 7. So for a simple function that basically we're trying to compute now y dx of putting those two together, 5 times x cubed plus 7 to the power 4. Right? And now that looks much more familiar. And now we will basically define here our different elements. So we can define this here as our u. Right? And now we can just write out dy du. So what would that be? Can you raise your hand? U what? Cubed. That's right. All right. So straight up derivative, assuming this is just the function. So here, this is our simple function. Now let's do the derivative of u with respect to x. So that's just this function.
3x squared.
That's right. 3x squared. And now we basically can combine both of these, and we'll just basically multiply both. And so we have dy dx, or partial y with respect to x, equals 20 times u. We can put in u again, plus 7 to the power of 3 times 3x to the power of 2. We can simplify that, but we don't need to. All right, so that's just straight up chain rule with a very simple function. Any questions on that? Great. All right, so now let's do the actual function of word2vec, or the simplest version of word2vec. Nope. No, we'll stay on the whiteboard. Sorry. All right, we have here our log probability of P of O given the center word, and these are just word IDs. And our formulation for this function was to have the exponent of a vector u of the outside word transposed times VC. And then we normalize this with by going over all the word IDs of small w to capitalized W of the exponent of u W transposed VC. And if you're familiar with logistic regression, you can kind of see this as a dynamic logistic regression, right? These are our weights, and we have a probability for each of the potential classes W, right? And one of those is O. All right, now generally what we'll do is we'll actually take the log probability, log monotonously increasing function, so the argmax of whatever we have in here when we optimize this is the same as when we optimize the log of that function. So now let's basically take the derivatives of this with respect to VC. All right, now we're going to make this a little interactive so that we don't fall asleep. So what would be the first thing we might want to do to simplify this function, given that we now have the nice logarithm of this fraction? Yep.
Split into a difference.
That's right. So we can now, right, we're not taking any derivatives yet. We just basically split this into difference of log of exponent of UO transposed VC minus the sum over W equals 1 to W of exponent UW transposed VC. Oh, wait. What did I miss? That's right. All right. Now we can see this part already simplifies, and we basically just get this portion here. Now the derivative of a sum is the derivative of the summand, so we can just basically take both of these and separate them out. So we can write derivative of VC of just UO transpose VC minus derivative of the log of the sum All right, now this one we already know, so that's just UO. So basically, we have UO. We'll remember that. And now let's look at this beast here. And let's not remember the minus in front of it. So what could we do next to take the derivative of VC? Well, we see here something that looks like a great application of the chain rule, right? Because we have a function f, so we can define the log as our function f, and we can define this whole sum here as z, which is a function g of VC. And now this is where it is really great to know the chain rule in all its gory details. So now what we're going to want to do is take derivative with respect to VC of f of g of VC, right? And g again was our z. So what's that in abstract? Well, let's just write it out abstractly. So we have what? Just chain rule like definition almost. That's right. Times derivative, and we just call this f of z, times the derivative of g of VC times the derivative of VC. That's right. All right, now we already heard the first one, which is derivative of f of z with respect to z, where we can basically, we know f of z is log, and so we also know that derivative of log of c with respect to z is what?
1.
That's right. So what we can write here for the first part is simply, since this is just simple function f, it's just 1 over whatever z was. Now z we nicely defined as just this whole sum. So let's just write out what this sum is. So again, w equals 1 to capitalize W of exponent of UW transpose times VC. All right, now times the derivative of g of VC with respect to VC. Now g of VC is this sum, so let's write it out. VC of this sum, W1. Now, first, really easy to mess up point here. We don't want to use the same index twice, So let's have a different index here. Let's call it x equals 1 to capitalize W of exponent of UW transpose VC.
UX, right? Because you changed the index.
Oh, yes. Perfect. Thank you. All right. Does that still all make sense? All right. Then.
Does the index matter? You're still doing the same sum.
So it will matter. It will matter quite a bit. All right, so now we're just going to take the derivative of this sum. So let's maybe write that out. So let's look at this, number 1 here. And so what can we do to simplify the derivative of the whole sum? That's right. So we'll take it inside. So we're going to have the sum. So this equals the sum of all the derivatives with respect to VC of x equals 1 to W times the exponent of UX transposed VC. All right, now we'll apply the chain rule again here. What's the derivative of the exponent of something? That's right. So we can rewrite this as x equals 1 to W of the exponent of UX VC transpose times the derivative of the inside. So this is derivative of VC with respect to UX transpose times VC. And that's again something that we did already right here. So what's this? UX, that's right. All right, so now let's put it all back together in one equation, all the different pieces we just computed. So we basically have the whole derivative back to VC was UO, the very first part here, minus the sum of, and now this is where it's important that we have x and w. So this sum over w is outside of this sum, right? So we have here now the sum over x equals 1 to w times the exponent of ux transpose vc times ux, our final vector here, so this part of the sum. And then what we could do also, instead of multiplying, now technically what we would do, and I'll just write it out, is this times 1 over the sum that we have with w equals 1 to w of the exponent of uw dc. But we can now pull this sum in and multiply each of the elements of this sum with this one. That's why it's so important to keep the indices separate. So let's multiply, again this is just this part right here. We're going to multiply this with each of the elements of this final sum. So we have UO minus the sum over x equals 1 to w times the exponent of ux transpose vc divided by the sum of w equals 1 to w of the exponent of uw transpose vc.
Seems like moving it inside just makes the configure have to do more work.
it's a great question. So what do we observe from having done this now? When we looked at the very beginning definition of the conditional probability. That's right. It's still sort of a softmax, kind of a dynamic one with these vectors, but it's basically the probability. And we dropped something very important, which is the ux here. So basically, we can rewrite this as u of O minus the sum over all our word vectors, or word IDs, of the conditional probability of this x given this c times this ux. Right? And in general, and this is something we'll get to now in the problem set a lot, this is a very, very expensive function to calculate, right? Because this capital W could be hundreds of thousands or even millions large. But these are basically all the mathematical tools you'll need to do problem set 1 of the math. And then we'll actually come up with much more efficient ways to avoid having to have this entire normalization. And what we might do is just have a very simple binary problem of saying improve the probability of these two being on. Yeah?
But wouldn't we have already had to compute all the terms inside that sum when we did the forward pass to output the probabilities?
That's right, but even that forward pass is too expensive. We're going to try to avoid at all costs summing over the entire vocabulary at each window. Imagine you have millions of windows, and now you multiply that with millions of, like a sum over millions of elements at each of the millions of windows. It just doesn't work. So this is the simplest way. Now, nobody would actually implement it exactly with these equations. But intuitively, we just went over this to understand sort of what the equations look like. So can we pull the projector back down, please? So really, this sum will be too expensive to compute, and hence this whole objective function is not scalable. And we already observed that very well. So what we will do is to either approximate this normalization constant or define negative predictions where you only basically sample a few of the words that do not appear in the context. It's very hacky, but in deep learning land, nothing has to actually sum to 1, right? All we care about are these word vectors in the end. Whether you actually get a really nice probability that sums to 1 is kind of irrelevant. You're just trying to capture the co-occurrence statistics. And it turns out that if you have millions of words, most of the words don't appear in any given other words context, right? If you look at zebra, the fact that zebra doesn't co-occur with toaster, TV, you know, laptop, like it doesn't, none of these words give you that much additional information. So what we will do, and what you will do in the problem set 1, is essentially focus on mostly the positive correlations and just randomly subsample a couple of the words that don't appear. And so I think we have 7 more minutes. So let's go a little bit into what kinds of amazing things will fall out once you are able to optimize this function very efficiently. These are basically the well-known analogies that happen to fall out of these low-dimensional vectors. So for instance, there are syntactic grammatical relationships of singular and plural. So the vector difference between going from the vector, now again 100 to 500 or higher dimensional, of apple minus the vector representation that we learned for apples is similar to the vector direction that we get of car minus cars or family minus families. So what's being captured in these co-occurrence statistics, and again, it's not very intuitive why predicting the words to the left and to the right captures the statistics of these words to the left and to the right, but there's some interesting work that we may touch upon a little bit next week of why this actually happens. But again, there's no magic here. The main idea is that it turns out when you subtract some of these statistics from that happen in plural words, they happen to be similar. There are more other, you know, like the word multiple, for instance, or several, or a couple, right? These are all words that might appear in the context of plural words. And now you projected it all down, and it's now in the lower dimensional space, not really in the whole high dimensional space, but you still capture that you're taking out all these other co-occurrences when you do compute these subtractions. You also get interesting similarities and geometric relationships for verb and adjectives, such as, shirt minus clothing is similar to chair minus furniture. So what we described in the taxonomy originally, where you had to very rigidly define this is a subtype of this thing, it turns out it's kind of in the vector space that we learn just by basically projecting co-occurrence statistics into a lower dimensional space. And this is very surprising to a lot of people, and they think, oh, the model knows and learns and understands, but it doesn't. It doesn't do any of these things. It's just basically co-occurrence statistics if you train it with the right corpus. And this one is one of the most popular ones, and also the prettiest ones of the data set from Google, where if you take the vector of king, you subtract the vector of man, you get something similar to the subtraction of queen and woman. Again, just from having low-dimensional co-occurrence statistics. Yeah.
It seems like when you run a forward pass through word to vec with a word that it hasn't seen during training, it should project it in a similar point cloud cluster.
So as you run a forward pass with a word that you haven't seen during training, so the default thing just in practice will be that you just have an UNC token and nothing happens at training.
Wouldn't it?
Sorry, you mean at test time or at
No, like
training?
I guess I'm trying to draw an analogy to like how would this perform without the absence of with the absence of smoothing, right? If you've been doing kind of smoothing during your training, it should still recognize the surrounding words around that unknown word, and it should still project it into a similar area as it's like syntax.
That's right. So as soon as you train and you project and you say, now in order for me to be better able to project these context words, you immediately will update with stochastic gradient descent the word vector for that center word in order to make it be more likely to predict the outside words, hence more likely to capture the right kind of statistics if you do it a lot of times.
But have people evaluated how this performs with respect to like traditional ML, NLP algorithms?
Yes.
Smoothing to predict unknown words?
So I don't know about the unknown words. Usually all these methods work better the more words you have, as long as your corpus can allow it. I can't think of any specific unknown word evaluation, because basically you just say the words that I rarely ever see are just getting the UNC token, and that's one vector for all the unknown words. That's usually how most people deal with it in practice. But what people have done is actually now went back after seeing these beautiful results of king minus man plus woman goes to queen, and understand how do actually these new methods relate to the traditional PCA or SVD kinds of methods. And both of them have actually some advantages. So when you look at SVD or various other methods like it, they actually train quite quickly. They require a huge amount of RAM, but they are quite fast. And they make very efficient use of the statistics. Instead of collecting statistics and optimizing a function one element at a time, you just can collect it once, and then you can run immediately on the statistics, which is an advantage. However, they primarily used to capture just word similarities, and they didn't have any of these beautiful linear relationships of king minus man plus woman going to queen. And they used to give disproportional importance to these large counts. Of course, that though is a way, there's a way you can fix that by just having a cap on those counts. Whereas the skipgram or word-to-vec kinds of models, so word-to-vec is kind of a summary term for multiple different methods, skipgram and continuous bag of words. You actually can implement both in problem set 1. Continuous bag of words is very similar. The main differences are sometimes you can compute or predict from the center word the surrounding words, but you can also go the other way and say from the surrounding words I want to predict the center word. So it's not that big of a difference. But basically, those scale with the corpus size, which is not great, right? If you add a larger corpus, you now need to go over many more windows. And they make very inefficient usage of the statistics. You just kind of hope that after running it long enough, you capture overall the statistics of the data set. But as we've seen, they have these great performance improvements on a couple of different tasks and capture these complex patterns that go beyond just these two things are similar. And I guess we're running out of time, so maybe in the next lecture we'll look into a method that will actually combine the best of both worlds. It'll run something like what we've seen here, but there are no more exponents needed. It's a very simple function, and it will actually run that function over the co-occurrence matrix elements instead of over each window at a time. And then we'll have the best of both worlds. All right, see you next week. Welcome to lecture 3 of CS224D. Today we will talk a lot more about word vectors. I understand that last time we went over things fairly quickly. Today we're going to go over all the gory details, lots of analysis, and a little bit more understanding. So let's refresh where we ended off last week. We basically had our main cost function j for theta, which had all the different word vectors in it, and we'll go over all these details a lot more today. I think there's one typo also. So u are the outside vectors, u of o is the index of that word vector, and v are the inside vectors. And let's go over this model in detail again. What do we do at each window? Could you roll up the projector, please? So at each window, let's say we have a corpus here, and let's say today I am giving a lecture. Not a very creative sentence, but true. And so let's say for now we don't have a start word, so we will just start at this word right here, I. And let's say our window size m is just 1, so we just look one word to the left, one word to the right. Now, if we start here, then this will be the vector v for the word I, and then we have the vector u for the outside word for today, and the vector u for am. And now we will try to predict from v which word index we have here on the left and on the right. All right, so just this pair is the first pair that we looked at in our exponent. So here we had the exponent of VC transpose UO. Of course, UO transpose VC is the same thing. And now, in the first step of this window, we're going to look at basically this word pair. So in this case here, for the first window, and our context, our window size of only 1, we will basically have in the exponent here v I transpose u today. And then in the second, so this will be the first element for that window, and the second element we would have the exponent of vi transpose um. Does that make sense? And then, okay, could you raise your hand if this makes sense? For those who haven't raised their hands, do you have any questions? So each of these is going to be one, we'll often call them d-dimensional vector, right? So this is just VC, and UO will always be in RD. And you'll go over that in a lot of details in the problem set, in problem set 1. And given that there might not be as many questions for your projects yet, I'll have 2 hours of office hour today after lecture. So if you have any questions about this model, it's still a good time to ask. All right, so then in the class we derived, and of course, this is just the numerator we had here, the sum over all these words in both cases. All right, we'll use the whiteboard again, please. Sorry, the projector. So on the whiteboard last time we derived the gradient for VC. And I encourage all of you to derive the gradient for the outside vectors U also by yourself and make sure you can follow that. Okay, so generally when we write that in each window we'll compute the updates for all the parameters that are being used in that window, it'll mostly be all the outside vectors and the one inside vector. And then you move one over. Now what used to be an outside vector will be an inside vector, and some of the outside vectors, depending on your window size, might still be shared in each window. All right, so if we had, for instance, a simple sentence here, and we looked at like, and we had our external vectors UI and learning, and we move over one, now learning will be the inside vector, so we'll compute V learning and U like, right? So they switch. Any questions about so generally looking at one window? Yeah?
Do we consider the period as its own token?
Good question. We usually do, yes. In fact, tokenization is sometimes considered a problem in and of itself. In English, we often have quite short words, so it's not that relevant. What we'll notice if we look at other languages, such as German, where you can have single nouns that could have as many characters as some short English sentences, then you might want to split words into their morphemes, for instance, and learn those morphemes. We'll eventually have trouble also when we have numbers, where we have the period or the dot inside, and then there are lots of different numbers. And the question is, do we want to compute a different vector for each different number, or do we want to tokenize that differently and say all digits just get replaced by some digit token like D? So lots of subtlety that we're glancing over, but you'll get exposed to that in your problem set. Great. All right. So now as we compute the derivatives for all the different parameters, we basically would always look at our theta when we start. So theta will essentially have all the different word vectors, and again we have 2 for each word, with the inside vectors and the outside vectors. So this will be a very high dimensional vector theta. 2D times V. D again usually between 25 to 500 or so. V on the other hand could be hundreds of thousands. Right? So this is a very high dimensional vector theta. So the simplest thing we could do now to really optimize this is to directly optimize or minimize, in many cases, our objective function J over the full batch, as in the entire training data. But that would indeed require us to compute the gradients for all the different windows. So not only do we have millions of potential words, but we also have many, many millions of windows as we convolve or go over each separate window one at a time, over, for instance, all of Wikipedia, right? And so if we wanted to compute the next update for theta, so theta new during our gradient descent method, this would be our standard equation for gradient descent. And usually we'll use matrix notation for all our parameters, and basically these are all interchangeable. And I want to expose you sometimes to different notation, because on the one hand it'll be nicer if we use the exact same notation throughout the entire class, but then you might get confused reading the papers that are in the reading materials, and in the papers you'll be exposed to all kinds of different notations. So I want to make sure you understand, kind of see beyond the syntax and see that just the semantics are the same here. All right, so vanilla gradient descent is essentially very simple, both in math and in code. We could just say, while true, we continuously update this whole function. So we have our corpus here, and inside evaluating our gradient, we'll essentially give it our current function j, the entire corpus, and our current set of vectors, or word vectors, theta. And we just update that. And if this was a simple function, then our updates would just look like this. Of course, in deep learning, we'll never have such a nice, beautiful convex function. So here you see the level sets, and you would see an update that gradient descent does at each time step, trying to get to a minimum. Now, again, our corpus may have 40 billion tokens, and hence over 40 billion windows. And if we had to evaluate all of them to make a single update, we would wait a very long time before the model does anything. And we wouldn't know how well it does until we actually make the update. And it turns out that this is, in almost all cases, a very bad idea for neural networks. In none of our assignments and in none of our implementations will we ever use full batch gradient descent, where we go over the entire training set and then make one update step. What we'll almost always do is to update our parameters after we see each window. And then we'll immediately see whether we're improving things. We can immediately evaluate and visualize what's going on. And in almost all cases, instead of summing over all the windows at time steps t, we'll just basically make one small update at each window. So also very simple code. Instead of just looking over the entire corpus, we will sample a window. The simplest thing is to just go one word at a time to the right. And then we will evaluate the gradient only with respect to the word vectors that are in that window, and then make an update step. Are there any questions about stochastic gradient descent? Yeah.
Maybe I missed that part. How do you initialize the center and the vectors?
That's a great question. So how do we initialize the center or the word vectors in general? Basically, they'll all be very small random numbers. So usually we'll initialize all the u vectors in something like a uniform distribution between minus 0.001 and 0.001.
So for the same word, the center and the outer vectors are eventually going to be different.
That's correct. Yes, the u's and v vectors will be different. They will capture slightly differently the statistics of co-occurrences. Yeah.
Do we know if the likelihood function for optimizing over is convex?
We know that it's not. And that will be an unfortunate truth for almost all the models we will look at. None of them will be convex, and all the beautiful convex optimization will usually go out the window. Hence, there are lots of interesting optimization questions in deep learning, tackling saddle points, and so on. A few of them we will actually go into in this class, but if you are so inclined, you can evaluate those for your class projects, but it's hard to make a really impactful class project based on the optimization. You have to be pretty good at optimization. A lot of the ideas from convex still kind of hold. You will try to approximate things, for instance, with stochastic gradient descent. Sometimes you can look at second order derivatives to try to get to your local optimum more quickly and so on. Of course, the entire shape of our objective function also changes with each window, and it changes to different non-convex sort of manifold you're trying to go over. Any more questions? Yeah.
I'm assuming there's a problem with just initializing to 0?
That's right. You do want to initialize to small random numbers. If everything is 0, then in the beginning, you're not going to go anywhere. In some cases, it'll be hard to.
So will the gradient become 0 or something?
Let's go over that. So here, what would the gradient be if this was 0? What would the exponent be?
1.
That's right. So it won't be 1, but it will be in a very bad, usually when you optimize, it'll start in a very bad place. And also there will be symmetry issues and so on, so you do want to use small random numbers. All right, great. So really our update at each window, t, let's say we have this simple first window of I like deep learning or I like learning, we will only really have 3 of the vectors actually be populated in this very high dimensional update vector, the gradient with respect to theta. Right? We'll have only derivatives for the inside vector of like and the 2 outside vectors of I and learning. And so instead of actually creating that, and this will be very important for all your implementations, because if you implement everything naively with single for loops and indices and then gigantic vectors where you're going to go over every single one and you have here a million numbers that are all 0, it's not going to be very efficient code. And so there are a lot of things that we can do that are much smarter than that. Essentially, we're going to want to only update the word vectors that we actually see at each window and not keep around all the zeros for all the word vectors. And so we can keep around basically a hash, a mapping for all the word vectors, and only update certain columns of this full embedding. So one is either you have a large hash that has for each ID you get the word vector, and then you look at the ID of that word vector and you get the word vector, or you have one very large matrix that you can efficiently index, and then you just basically take out specific columns of that matrix, and you update only those columns. Yes?
So are you saying that we're storing theta in this kind of different form?
That's right. So you can essentially decide how you want to store your theta. It could either be the word matrix. Usually, sometimes you call this L for the embedding matrix. In our case here, we'll call it capital U, which has all the U vectors, and then capital V for all the V vectors.
So there's going to be 2 of these.
That's correct.
One's D by V, and one's D by cardinality of U.
Yes. So here, when I write this notation, I usually just mean the size of the vocabulary. So that will be the same for both U and V, because all the words will appear in both.
Which method do you recommend?
I usually have a big matrix that I efficiently can index. But I encourage you to play around with both, and you can even mention those. All right, now in problem set 1, as I alluded to in the last lecture, you will realize that this normalization factor here is much too computationally extensive to actually compute for every word pair of inside and outside vectors. And so instead, we will actually implement the skipgram model, which is the most popular model in sort of the word-to-vec family. And the main idea will be that instead of having one softmax where we try to penalize and basically lower all the probabilities for all the words that don't happen to appear, we'll actually only look at the true pair of a center word and its context word, and then we'll look at a couple of random other words, a small set, maybe 10 or 20, and we just push those down. We don't push down all the words that don't happen to appear in this current window. And intuitively, again, what we're basically doing here is if you try to learn the vector for zebra, it doesn't help you that much to tell the model that zebra doesn't co-occur with these million other words. It's mostly helpful to say it does co-occur with, I don't know, Serengeti or lion, and then it doesn't co-occur with a couple of other random words. It's not that helpful to say it doesn't co-occur with all these other words. So let's go over the objective function that you will implement, and this is from the paper Distributed Representations of Words and Phrases and Their Compositionality by Tomasz Mikolov. And the main objective function will again be our capital J over theta, now being all the word vectors. And we'll again look over each single window, and I'll just basically write this here. T is basically it goes through all the tokens, all the potential windows that we have, and JT of theta will be the objective function at that window. And because we use stochastic gradient descent, we'll basically only ever evaluate one JT at that window. And then what we'll do is we'll actually maximize here this inner product. And if you're familiar with logistic regression, you'll see logistic regression again here. It's basically just a binary problem. And we want to maximize here the probability of these two words co-occurring. And then we will go over a couple of k random word IDs. So I equals 1 to k. And for each I, we'll basically randomly sample a word index from our whole vocabulary. So out of the millions of words that we may have, we may only sample 20. And then we will try to minimize the probability of them co-occurring. And if you don't find it intuitive that we're minimizing this, one thing you might want to look at and prove to yourself is that the sigmoid of 1 minus x is the same as 1 minus the sigmoid of x. I wish I could just write something on the board. So sigmoid of minus x equals 1 minus sigmoid of x for the people on the left side of the. Yeah. Yes?
Is there a rule of thumb for a number of negative samples to use?
There is, and I will show you in a couple of slides at what point it becomes not as useful anymore to go above. But usually 20 or so is a good number.
Do we fix the random like negative samples on every iteration or throughout the whole batch of the update?
Do we, sorry, say that again?
Do we fix the number of, the specific words that are not co-occurring on every iteration of SGD or for the whole epoch, for the whole batch?
We'll usually have a completely random sample for each window.
Is PFW a uniform or?
I'll actually show you in the next slide. All right, so just a refresher here, the sigmoid function, it's a very popular function. We'll use it a lot, and you're going to want to really understand all the derivatives you could possibly take with respect to anything inside a sigmoid or using the chain rule with sigmoids. It'll be very important for the midterm and all the problem sets. Basically, it'll just take any random number and map it to be between 0 and 1. And then in deep learning, we'll just say, well, if it's between 0 and 1, we'll call it a probability. It's not a really great way to deal with probabilities, and if you actually took the graphical models class like 228, you kind of cringe a little bit, but that's how we often roll. All right, so we'll use the sigmoid function a lot. It is not the most popular function in internal layers of deep learning, but it is very popular, especially if you have just a very simple binary problem at the end. All right, any questions about that objective function? All right, we released the problem set this morning, so I encourage you all to get started hacking on it. So here it's just a slightly cleaner notation. Instead of summing over this index and you sum over k and then you sample j, sometimes we just write we sample a couple of j indices from our word distribution, and somebody already asked, is it a uniform distribution? One thing that actually often makes sense is to sample more frequent words also more frequently in this, and so the answer is that empirically something that worked was to take basically this function where you have here the unigram distribution, so just how often does each word appear in general in their corpus, raised to 3/4 power. And we'll provide this function in the starter code, so don't worry. Basically, yeah, the power here makes less frequent words be sampled slightly more often, but not as often as if it was completely uniform. Yes?
Isn't the point that we want to sample words that are often co-occurring?
That's correct. So we still, if it was completely uniform, we would sample very rare words like aardvark as often as very frequent words like hello. And so here we will sample those more frequently, but not crazily so. Basically, if we, because you usually have a very much a power law kind of distribution, so the most frequent words appear so much more than very rare words, we want to basically attenuate that a little bit. Still encourage slightly more frequent sampling of frequent words, but not as frequently as they actually appear in a corpus. All right, great. So mostly we focused on the skipgram model, where we take the inside vector and we try to predict the outsides. The main idea for another very popular model, the continuous bag of words model, is actually quite similar, and you'll look at both in problem set 1. But we can, instead of predicting the center from the center word the outside words, we can also average all the surrounding words and try to predict the center word. Very similar idea, but slightly different, results in slightly different results. And in the end, again, somewhat hackily, we might also combine the two and average both. Turns out to also work well. But basically, the idea is very simple. Instead of taking the center word, trying to predict the surrounding words, you can take the surrounding words and try to predict the center word. You won't actually have to implement the continuous bag of words, because I think once you implement the skipgram model, you'll kind of get the idea. I think it'll be a bonus point question. And if you implement your code well, then it'll be very easy to just switch that in and get those bonus points. All right, so that was the main model of word2vec, the skipgram model. Are there any more questions around that?
How do you pick the dimension field?
How do we pick that? I'll actually go over that a little bit. We'll get to that in a second. It's a great question, and it's very important, hence we have lots of slides for it. So then at the very end, we mentioned a couple of advantages and disadvantages of these different models that we looked at in the beginning, models that are based on SVD or PCA versus the one window at a time approach of the skipgram model. And we ended on this equation where we didn't have much time to go over it. So here, the idea is, instead of going over one window at a time, maybe what we should do is we collect the whole corpus and we basically collect all the co-occurrence statistics. So for each row, it's what we started out with, right, when we just used the SVD approach. But instead of now running all of SVD, we're going to sample and actually go over each of the indices of that gigantic matrix X. And we're just going to optimize this function for all the word pairs, ij, in the corpus. So here, we basically will also want to minimize this squared loss, where log p is basically just the log of the probability, or of the counts in many cases, of how often words I and j co-occur, and want to be able to make their inner product predict how often they would co-occur. And that is essentially capturing the similar idea of word2vec, but instead of doing it one window at a time, you once collect all your co-occurrence statistics, and then you can run the optimization over that. And that Pij matrix, or we often call it X also in the first lecture, or the second, is also going to be very sparse. So we're not going to have to go over all possible pairs. And then because we have some of our word pairs, like the and cat, for instance, or he and has, those word pairs appear so often, they would have a very, very large impact on this objective function. And so what we found empirically is to actually just cut off in this f function here and have a maximum that I think is usually, yeah, we basically don't want to force the very large counts to dominate the entire objective function. And so we'll cut that off and have a linear scaling until then. Does that make sense? Basically, otherwise the model would spend a lot of its parameters making sure to capture the and cat and he and has appear very, very often together. And it will kind of dominate the rest of the model and the rest of the optimization. Yes?
I'm sorry, what was the Pij again? Like what's
So these are basically the co-occurrence counts that we started out with when we looked at the SVD-based method. And you can, in various ways, pre-process those co-occurrence counts. You can look at correlations instead of just the raw counts. There are lots of tricks, but the main idea is you just take some transformation of those co-occurrence counts. Cool. So this will be scalable to gigantic corpora, right? Because we only once have to compute the counts, and then we can store that matrix and then do all our math afterwards on that matrix, which is a lot smaller than the original corpus too. And because this makes very efficient use of the statistics, it'll also work quite well on smaller corpora. So let's look at a couple of the results. This model is the GLOVE model, global vector model. And if we now look at simple inner product similarities and distances, we can basically find that, for instance, for frog, the next nearest neighbors in our now usually 100-dimensional or so vector space are all different kinds of frogs. So even for very rare words, this model does phenomenally well, because these crazy words here are also just different kinds of frogs, but they're just not as frequently in the corpus as simple things like toad and frogs. So it captures similarities very well between both very frequent and infrequent words. Now in this model too, what you notice is you have here u and v vectors, which again is not very intuitive, because here I just showed you similarities of just a single word. And so the question is, which of those words do you actually use, or which of these vectors? And it turns out after we train the word vectors, in almost all cases what we'll do is we'll simply sum them up or average them, or in some cases concatenate them too. And that is, depending on how you evaluate, and we'll get to that in the next slide, another hyperparameter that you can compare. Should you actually concatenate the two or just sum them up? The most common thing is to sum them up. I think we had a question.
Yeah, I just wondered why it's much more efficient to train this model. Because it doesn't seem like a priori you still have to train to optimize each of these vectors. You still have to compute the gradient for each of these vectors, isn't it?
Yes, but you basically only have to compute the gradient for each of the co-occurrences once. So imagine the word, I and like appear in the same corpus 50,000 times. Like in actually 50,000 separate windows, you now want to say these two things co-occur, improve the probability of those co-occurring. In this model, you have to do that only once, because you already collected all the counts, and you're just going to say minimize basically the distance between the inner product and some transformation of those co-occurrence counts, right? So it's a lot more efficient in that respect. You immediately go after the statistics instead of going after each sample once and hoping that eventually the statistics will fall out of the model. It's a great question. Yeah.
So it looks like in like the straight word to vec, like the co-occurrence matrix never really makes an appearance.
That's correct.
I mean, completely incidental that they might be related, whereas GLOVE is precisely trying to optimize against the co-occurrence matrix.
That's correct.
More like happenstance, and just sort of.
Yeah.
It's just purely an alternative to SVD as a way to approximate.
That's right. That's right. Cool. All right. So now, how should we evaluate these word vectors? Before we go there, are there any last questions about the word vectors? Okay. Well, if there are still some, I'm sure you'll get to them very soon, because the problem set will force you to. All right. So basically, in general, in natural language processing, and in most applied machine learning fields, you will have, in many cases for your projects, two options for evaluating how well you're doing. And in some level, the two options are extrinsic and intrinsic. Intrinsic, usually you evaluate on some specific or intermediate subtask. So for instance, how often do words appear in specific relationships, like king minus man plus woman goes to queen? Or, dollar minus America plus Mexico goes to pesos or something. So you can basically evaluate that, but in the end, you don't usually care about your intrinsic tasks. But they do help you to basically very quickly evaluate how well you do. In many cases, word vectors are really step one to a more complex natural language processing model that actually does something useful, like machine translation or sentiment analysis or question answering or things like that. But every time you tune your model and your word vectors, you don't want to have to then plug those into some other model that also takes potentially days to train before you get some response of knowing how good your word vectors were or not. And so usually it just helps you to just understand that specific model, in our case the word vector model, and iterate very quickly on that subproblem. However, whenever you do this, you do from time to time want to make sure that there is actually some correlation between your intrinsic task, and we'll look at the word vector similarity and analogy task, and make sure that actually improvements on that intrinsic task have at least some correlation, some positive correlation with the accuracy of the task you eventually care about. And because there are some people who literally spend their entire careers optimizing these intermediate metrics, literally years of their lives in their PhD, evaluate these intrinsic metrics, and then some other PhD a couple years later finds that there's actually not a great correlation between that intrinsic metric and some other metrics that most other people would care about. And that would be quite the pity. So that leads us to extrinsic tasks. Basically, it's a real task, like I said, semantic question answering, sentiment analysis, things like that. In general, it's preferable. However, in most cases, especially in deep learning, it will take a very long time to actually compute an accuracy for a very complex model, especially, for instance, machine translation. It can take weeks to train a machine translation model to high accuracies. And once you evaluate on the whole model, it's also sometimes unclear if you improve that whole model because your subsystem improved or because you improved other pieces of the system. So whenever you want to write a real academic paper and you say, well, I have better word vectors, and I'm going to show them on some other model, you want to very carefully tease apart all the potential changes that you made and then be able to drill down and say it's because of my novelty in my word vectors that the overall sentiment analysis model actually improved. And so in general, you want to have both. That's the best you can do. But you'll observe it'll be hard to have both in most cases. So yeah, this is an important statement if you want to write papers that actually get accepted in real academic conferences. So replacing one subsystem with another improves your accuracy, and everything else is fixed. Everything else is the same. Then you know that your subsystem actually made a real improvement. So let's look at both intrinsic and extrinsic evaluations for word vectors now. Intrinsic word vector evaluation, one of the most popular one that sparked a lot of interest are these word vector analogies. Basically, if we say that man is to woman as is king to something else, then we would ideally hope that somehow in the geometry of our space, this is captured. So if we take, for instance here, the vector difference of man minus woman, and we get this vector here, and we did the same thing for king, then ideally up here, our word vectors would have placed queen. And so we can essentially just use here this cosine distance after all these additions, and we find the argmax, the vector that maximizes essentially this cosine distance. It's normalized inner product. And we should note here that in all these evaluations, the other input words, as in man, woman, and king, are usually discarded, because otherwise they would often come up as the best answer. And I want you to think critically about this. This is one way. It's very popular. Hundreds of papers have come out about these kinds of analogies since, but we can still be skeptical, largely because your word vectors may include all these analogies, but it might not be in a simple linear kind of way, right? Maybe it's a more complex nonlinear function that has to be learned to capture these. The amazing thing here, though, is that there's no extra function needed that needs to be trained. It just happens to fall out of the co-occurrence statistics that we're able to capture with GloVe or word2vec kinds of models. And when we run PCA on a bunch of different pairs of words, here are some of the examples that fall out. And we basically see that the vector differences look very similar, and that will allow us to then also say, well, basically, if whenever you take this one minus that one plus this one, it will go to whatever is at the end of that vector difference. So brother is to sister as nephew is to niece. Or sir is to madam as heir is to heiress. And for some, they're even nicer and they go exactly in the same direction and have similar lengths, and in others they're not quite, but still go roughly in a similar direction and have roughly similar lengths. Of course, the length shouldn't matter because we'll use the cosine distance here. But for this, this visualization, you still see that there's a difference, which we'll get rid of in our evaluation. It even works for some more modern things, such as companies and their CEOs. And again, you might think this is kind of magical, but really it's just straight up co-occurrence statistics that are being captured, right? All these people usually appear in similar kinds of contexts to their companies, like is leading or made an announcement about, and so on. So you would assume that whenever you try to take these very large vectors or co-occurrence statistics and you collect the right kinds of statistics with the right window sizes and so on, that you eventually capture these kinds of similarities. It's still pretty cool, don't get me wrong. We're all, the whole field was very excited to see that these relationships, when you project them down, look that linear and are that consistent. It also works for other sort of more grammatical things like superlatives. Here you have slow, slower, and slowest, for instance, or short, shorter, and shortest. They're all also in very similar kinds of geometric relationships. And this, of course, is great because once you have an unsupervised system like that, it may allow you to say, well, I don't need to know that much about the domain, but just from looking at these linear relationships, I may be able to look up facts, quite logical or discrete facts, despite everything being just in these fuzzy co-occurrence statistics. All right, so let's look at a couple of examples and think critically also about what they're being captured, what is actually being captured. So here we look at the word vector analogies. Now they don't actually have the CEO in this actual data set, because in the end, if you're optimizing something, you want to see is your new model idea actually improving the state of the art. You want to have some real number, not just a bunch of cute examples. And so to get the real numbers, these are some of the subsets of actual triplets where you usually take out one of the words and you see if you can recover it. So Chicago minus Illinois plus Texas or something should go to Houston. And so here we have city is in state relationships. And of course the problem is that different cities may have the same name, right? And one city might be, so there's for instance, there's a Paris and a London somewhere in the United States, right? So what we'll notice eventually in many cases here is that the city name that is the most frequently used is the one that you would get right. But of course, there's some problem with this. Does this make sense of how we compute? Basically, you basically do this evaluation, this argmax, and you try to find if the argmax d here is actually the right last word in these two relationships. So city and state is one. The capital is another one. Of course, here the problem is that those might change also over time. then we have a lot of superlatives. So bad to worst should be, have bad minus worst should be similar in vector direction as big minus biggest, for instance. With past tense, dancing to danced should be similar to decreasing and decreased. And of course, there are lots of examples that we can collect. So in the end, we'll have tens of thousands of these kinds of analogy pairs, and we can really see if our model captures all of them consistently. Yes?
Would these analogies still hold up if the training data had been stemmed prior to training the model?
No. So stemming refers to basically taking away, for instance, the ing or the ed, and you just say decreasing and decreased all get changed to just decrease without the e at the end, and then you would lose all of those.
But conceivably, you still have similar context around something like dance versus something like throw. So you would still have that relationship of.
I mean, you'd have some, right? I'm not saying they would all be gone. You would still get the cities because those usually don't get stemmed very much. But for instance, the past tense you would lose if you stem. Yeah.
I had a question. Would you retrain your model for different corpora, or for the English language, could you have just a set of these vectors?
It's a great question. So would we retrain for different corpora? In many cases, it's just best to train on the largest possible corpus you can find. So if you have multiple corpora, you just put them all together and you train on the final biggest possible thing. So let's look at what that actually means. So here's a very careful analysis of the skipgram model, the continuous bag of words model, which we now know very well. We haven't really looked at these two, so let's ignore those for now. They're also rarely ever the top vectors. And we have the glove model here that we've also looked at in more details. And then we have actually the very simple SVD baseline, and then there's several ways, which we won't go into details of either, of tuning SVD to actually improve it a lot too. But sort of the straight up SVD baseline that we looked at in the very beginning is mentioned here as well. And so now here we basically try to disentangle what matters more. The dimensionality, for instance, of the word vectors versus the size of the training corpus. And so, for instance, if you take the glove vectors, they're 300 dimensional, and you train it on 6 billion tokens, then you would get an accuracy of 71 in terms of these word analogies. So we had tens of thousands of examples, such as these pairs, and we basically look is the ID with the argmax of the cosine distance that we defined a couple of slides before, actually the ID of flu, for instance. And then we look at how often is that actually the case, and here it's 71 and 71% of the time, the cases, it is actually the case. But if we train on 6 billion, on 42 billion, it improves significantly by over 3%. So just the same model, same vector dimensionality, but a larger corpus in almost all cases basically gets us the best performance. And it didn't even make that much sense here. We basically also can compare, and this is very important again, and something that it has to really get into your mindset to do well in your final project. You want to only ever change one thing at a time in order to really understand these machine learning models very well. So here we also looked at having the exact same corpus, same size, at 1.6 billion, but changing only the vector dimensionality from 100 to 300. And we again see here that 300 is much more accurate, over exactly 10% in total, than just having 100. So basically projecting down our very high dimensional co-occurrence matrix to just 100 dimensions just loses too much information. But at 300, we start to see really good performance. And then we can again here compare and go even further and have 1,000 dimensions, for instance, but 1,000 dimensions then actually keeps around maybe too much noise and actually works slightly worse, having the same corpus size, for instance, for the skipgram model. So skipgram here and skipgram here, 1,000 dimensions, 300 dimensions actually decreases. And so really what we want to see, and what I encourage you all to do in every machine learning project ever, but especially in your class projects, is to compute and visualize the performance in as many plots that are sensible as you can. So let's look at the word vector dimension, for instance. Here we basically see, and we can mostly care about the overall, that basically combines semantic things like gender or cities and their states and their capitals and things like that, and syntactic things such as bigger and biggest, superlatives, or different tense of verbs. We combine these in the overall. And we basically see that in terms of word vector dimensions, as we have higher and higher dimensions, at some point it levels off and it doesn't really improve. So between 300 to 600, there's almost no gain anymore. And hence, it doesn't make sense to go much beyond 600. Also, of course, the lower dimensional, the word vectors, the more efficient your whole system is, right? It's much faster to train, smaller inner products, it's much more efficient. So in terms of efficiency, you want to ideally find the smallest vector dimensions that still give you the highest performance. Then window size was also a common question. How many words to the left and to the right should we actually predict? And here we also see actually something that's quite interesting and actually very intuitive. Syntactic performance actually decreases if you have windows that are too large. Because at some point, if you just look at 20 or 30 words to the left and 30 words to the right, all of which have no order, right? We just essentially had said that we just try to predict center word times u, the outside word. We don't care how far away the outside word is. It could be 1, 2, 3, or 4 to the left or to the right. And so if you make this larger and larger, at some point you will lose syntactic structure. Syntax captures grammar, grammatical structure, and if you have very large bag of words or no word order kinds of models, it will hurt the grammatical understanding that the model could capture. But semantics actually keeps going up. It turns out if you talk about a king, a lot of the words around that word are still roughly in the same kind of semantic space. So if we care about the overall, we basically see that around window size of 8, and again here, the smaller the window size, the faster and more efficient your model is too. So in terms of efficiency, you would like to keep the window size very small. And then here we actually look at the asymmetric context. So we look at only the words to the left, for instance, and we see that in general it performs reasonably well and has a similar kind of trade-off curve where you don't want to go too far and have a window size that is too large. Yes?
When we smush together all these documents together, and we have this window, can the window span 2 different documents?
Yeah, usually you don't care about that. You just let it go over it. It makes not that big of a difference. All right, so these kinds of plots you will want to produce in all your projects too. And sometimes it's actually hard if you want to compare two different models that are very, very different. It's hard to compare them properly. So this was an attempt at doing this where we say, well, maybe all that matters was training time. So you also want to make sure that if you compare vector dimensions 300 or 100 versus 300, maybe the 300 will eventually be better, and we know they are, but maybe they also take more time. Right? You can't just train both models for 1 hour, because maybe the 300-dimensional vectors will be worse after 1 hour, but then much better after 5. Right? So it's very, you have to be very careful and question all your assumptions and all your hyperparameters. These hyperparameters are, how long does your model train, what's the vector dimension, what's the window size. We call all of these kinds of higher level parameters of your model the hyperparameters. You want to be very careful at analyzing these. And so here, what we tried to do is basically compare both the time, but then as iterations as well. So how often do we go over the entire co-occurrence matrix? It turns out it's much better to go over it multiple times. So kind of countering the question of, you still don't go over each window as often as the words co-occur, but you do go over it 20, 40 times or so over that entire co-occurrence matrix. But it turns out that glove, for instance, is still more accurate in terms of these analogies on roughly similar times trained. And one way to account for that for the skipgram model is to actually look at the negative samples. So those were the number k that we had, where we summed over a couple of other random words. And here we basically can see that it makes not that big of a difference, but around 15 or 20 is usually a good number to just push those probabilities down for other words. Any questions about the evaluation? Yes?
About the intrinsic evaluation, and I might be wrong, but can you also evaluate over like phrases, like you normalize a phrase and then you want to see the correlation, like, maybe like King is a, or like Paris is a city of light as New York is to not just across words, but if you actually aggregate.
Yeah, so it's a really interesting question. How would you deal with phrases and trying to have analogies for phrases? It's actually much harder to come up with a nice list of 10,000 examples to have an efficient way to evaluate, Paris is the city of love, and I don't know, New York is the city of lights. It's like, it's a little unclear. And it's actually generally a tough question. What should vectors that capture longer phrases, what should they actually capture? It's much less obvious than it is for words, because some vectors you might want to capture that they're resulting in an action, like answer this email or go get the groceries here or something like that. Other sentences or other sentence vectors might just capture an emotion, like a sentiment, is this positive or negative? There's so many things sentences can capture that there's no obvious way to deal with analogies like that. All right, now, usually I said more data helps, but if you had to choose what kind of data you train these word vectors on, then it actually also helps to use Wikipedia. For instance, if you said I only have this limited computational budget, so I can only run it on one specific corpus of 1 billion tokens, and now you had the choice of a news corpus or Wikipedia, in many cases Wikipedia is better. So looking at, for instance, the overall accuracy here, if you use GigaWord, which is mostly news text from different newspapers, it's actually larger, several x larger than the Wikipedia from 2014, but it still results in an overall worse accuracy on this intrinsic task. Yeah?
Do we know why syntactic tasks are harder to see than semantic?
Why syntactic are harder? We have no nice proof for it, but basically you might not see all these different adjectives, for instance, together or in general as frequently. So we talk a lot more about facts, especially in Wikipedia and the news. We have a lot more sentences about different cities and different currencies and so on in semantics than we have, that we talk about the darkest place or something, or the greatest something. So these generally are not as frequent, and that's an unfortunate truth for a lot of this. The models are only as good as the training data that they have. Yeah.
What happens if you mix like a random mix of multiple training sources into your training model?
I mean, that's essentially what Common Crawl is. So Common Crawl includes Wikipedia, includes all the different newspapers that allow themselves to be crawled in their websites and so on. So Common Crawl is really just 42 billion tokens of internet text. And so it's a very broad range. It includes Wikipedia, and it's usually the best you could use. But it's also a huge pain. I wish you could all do that and use Common Crawl in your projects, but it's unlikely you'll be able to just deal with the gigantic size and the machines that we have. A couple of days at least if you have a very, very efficient C++ implementation. And as soon as you go to Python or something, you'll be talking about weeks. So yeah. you're already too late. Don't do it. All right, now another intrinsic word vector evaluation that is very common and has been used a lot more in the past is actually just look at similarities. So you look at inner products and you say, well, if we asked a bunch of humans on a scale from 1 to 10, how similar do you think tigers and cats are? Tiger and cat, these two words, then they might say, well, if 1 is they have nothing to do with each other, and 10 is they're basically synonymous, they're exactly the same, then tiger and cat is 7.3. Very subjective, of course, might be culturally dependent, and so on. Usually, you just ask a bunch of college students who were around when the researchers did their research. So they're again, potential problems, but in general, it's helpful, right? Because if you think that your vector similarities or inner products capture these kinds of human similarity judgments, then maybe eventually, if a model is trained, and now you see paper and book, for instance, and you're trying to classify, is this something about reading or is this something about watching movies or something? And your vectors captured at book and paper are actually kind of similar. Then maybe a subsequent model that you train on for classification might make use of that and get better performance. So you want basically these word vectors to capture these relationships. And computer and internet, of course, they're very different. Sometimes they're subsets. Sometimes they're just different kinds of words for the same thing. Sometimes they're hypernyms or hypernyms and so on. Just in general, you'll kind of get the idea though here. Here's basically a random sample. So professor and doctor is 6 out of 10 on similarity according to a couple of human judges, but a stock and a CD is only 1.3. And now you can also look at basically just correlations between these different vector distances and the human judgments. And you want to basically have high correlation. And again, the glove model that is trained on a very large corpus does very well on a lot of these different kinds of similarities, and has basically its inner product distances have high correlation to the human judgments. And there are a couple of different corpora that are available. This one here is very popular, though it is very small. It just has 353 word pairs. And in the end, as you dig into this space more and more, you realize there's been so much excitement. People have done so much work on that also since GLav in 2014. Hundreds of more papers came out, and you can now combine the different ideas. So for instance, originally skipgram just looked at the concatenation and maybe just the v vectors and not the u vectors, and then GLav realized, well, if we train v and u, but then in the end we sum them up, we actually get better performance. And then you go back and say, well, maybe if you did that for skipgram, that could improve the skipgram models too on all these evaluation metrics, and you can basically combine all the various ideas of the different models in various ways. All right, so now one question that came up already is what happens if we have ambiguous words. So for instance, you might say run could be like I had a good run, and it's a noun, or it could also be a verb. We all run every day. And then you're basically now, when you're training the model, you pull the vector for run into different directions. If it happens in a noun context, you pull it into the noun direction and you pull it closer as you visualize this. And this is actually kind of cool. I don't think anybody has done a really good job at it, but I've sort of internally, when I played around with word vectors, tried to do this during my project. And kind of as we train the model, you can kind of see how the words start to move around. And so intuitively, when I say it's getting pulled in different directions, you can kind of see as it's optimizing in this 100-dimensional space, you project it down to 2 dimensions, and then you look at what happens after you train for a while, you see that different words get pulled in different directions. And so as you train for each new window, for instance, in the skipgram model, and it's a noun window where run, for instance, the word happens to appear as a noun, it basically gets pulled closer to other nouns, and then gets pulled away again and goes closer to walking or something if it's in a verb context. And so one way we thought about dealing with this is to essentially cluster the word windows that we have. So imagine you have your v vectors and your u vector, and you just concatenate all of these vectors. Let's say you have each vector is d-dimensional. You basically have a window size of 1, so you have 3D dimensional vector, as in 3 times d. And now you basically just cluster all of these with some simple method like k-means. And then you assign IDs to each of the words based on those clusters, and then you can train basically with each word having multiple indices and multiple meanings and multiple vectors. So you will eventually have bank 1, bank 2, bank 3, and so on. And when we visualize those, we actually see that the model can capture some pretty cool kind of ambiguous words. So for instance, this is hard to read, but this is bank 2. And bank 2 is close to banking and finance and transaction, or laundering for money laundering. Whereas bank 1 here is close to plateau and boundary and canal. It's basically the sand bank, whereas this is sort of the money bank. And we have here star, and there's one star that's close to galaxy, and here we have another star that's close to movies. And you basically, it learned that there are different kinds of stars, like movie stars and galaxy types of stars. And there are lots of other examples. Jaguar, it's actually, I think, an instrument, a bass guitar manufacturer, but it could also be a software, and could also be the Jaguar, actually the animal, and that would then be close to hunter. So while that is very nice and has better performance, of course, on certain similarity metrics, where if you actually create similarity metrics where you have to be able to tell the difference and have to be able to say, well, this word has different meanings in different contexts, it works better on intrinsic tasks. But to be honest, for extrinsic tasks, it doesn't often make a difference. The models that you put on top of that, which we'll cover in the next couple of lectures, will do just as well if you do this as a pre-processing step or you don't. So in many cases, if you just have very high dimensional vector, it turns out that some of the dimensions implicitly seem to capture that words can have different meanings. So as cute as this idea was when we published the paper in 2012, I don't think it's very necessary for most of your projects. Now, these were all intrinsic evaluations, and basically what I would encourage you to do is actually is to look at extrinsic word vector evaluations too, if you work with word vectors in general. And one such example would be to do named entity recognition. And in the next lecture, we'll actually cover a model to do named entity recognition and with deep learning. And once we understand that, we'll understand really how we got to these numbers. But basically, this also shows that sometimes the differences aren't actually as big. So remember how SVD was really, really bad for the intrinsic task? Well, it turns out it's only around 3% worse on a real task of named entity recognition, for instance. So we did all this work, but in the end, it doesn't make a huge difference. Though, of course, like 5%, that is very statistically significant, and it's definitely worth a paper, and you're pushing the state of the art, and so on. So these are all great numbers to improve, but the differences might not be as large as the intrinsic evaluation suggested. So all that you need to understand, for instance, for named entity recognition, is that it's a person, organization, or location. It doesn't really matter that this person, like the CEO, is in exactly that relationship with that company. You just need to know it's a person, right? And that might be already captured in much simpler word vectors that you got with simpler methods. All right, now, on the one hand, it might not make a big difference if you use SVD or skipgram kinds of models. On the other hand, training single word vectors actually has several benefits. And using deep learning methods will have even more benefits, because eventually we can train the entire system end to end. We'll have a very complex model, a recurrent or recursive or convolutional neural network, that takes as input these word vectors, but we can actually train the word vectors as part of the overall model. And that's when we'll have very powerful, we'll get, I think, the highest accuracies in almost all cases if you have a large data set. So generally, the benefit that we get from these methods is that similar words will cluster together, and then that will help us for downstream classification tasks. So for instance, when we want to do named entity recognition, we want to classify locations. Well, if all the location names cluster together, then it makes it much easier for the classifier to find locations, right, and build sort of a decision boundary around all the word vectors that have locations. It's also amazing that we actually showed in many different papers that word vectors can really capture facts, like discrete kinds of facts, and you can later query also these facts from the word vectors. So when we actually want to classify, in the end, we will not just train the word vectors for their own sake, but we'll actually use so-called softmax if we want to have any kind of multi-class classification on top. So this will be a little boring again for those of you familiar with logistic regression and very familiar with it, but it's still good to look over the notation and basically introduce this. So now that we have word vectors, we usually don't end there, right? We want to train some system that predicts some output, some class, based on our inputs. The simplest thing we could do for now is just train word vectors after we train them in an unsupervised way, and then we classify the different word vectors into different categories out of context. It's not a task that we'll actually really have to do very much, but just for illustration, and we can go to more complex things next week in the next lecture. So let's define the softmax, because that's one of the most basic building blocks for our neural networks. Again here, we'll start, for instance, with a simple word vector x. That is, in many cases, the average of our u and v vectors. And this is the notation that we'll usually use for the probability for a class y given some word vector or eventually some other random vector x. And we have our exponent here, and this notation wy dot will basically mean that we take the yth row of our matrix W. So if we have C classes, we'll have C rows and D columns. And because W, the row, is already a row vector, we're not going to write the transpose here. And then we normalize this over all our classes so that overall our probabilities for all the classes y will sum to 1. All right. We'll essentially interchangeably use logistic regression and softmax classification, yeah, we'll use those interchangeably. And we already had the sigmoid. Sigmoid is perfectly fine if you just have two classes, right? Then 1 minus the output of the sigmoid is the probability for the other class. But the softmax will allow us to have lots of different classes. All right. Let's look at some more terminology. As we train our softmax, I'll sometimes use the word loss function or cost function or objective function. It's somewhat interchangeably. Usually when we say cost or loss, we want to minimize it for sure. Whereas objective function, sometimes we minimize it, sometimes we maximize it. And you have to be paying attention to which one we use. Generally, as we compute the probability for a certain class y, like I said, we take the yth row of W. And this is some of the notation that we may use. So if we have this inner product here, it's basically just taking the yth row and the ith column and then multiplying it by the ith element of the vector x. And that will, sometimes we'll use the feature vector f for the class y. And we'll compute fc for all the classes, c of 1 to capital C, for the number of total classes that we have. So if we have 5 classes, we can compute f1, f2, f3, f4, and f5. All right, now a little bit more of notation. Basically here, in our case, the loss that we optimize for will maximize the probabilities of the correct class Y. And so intuitively, we often minimize the negative log probability of that class. All right, some background. I don't think this will be very relevant for most of the class, but if you're familiar with information theory, it's definitely interesting to think of and keep these in mind sometimes. Basically, assuming that our ground truth, our goal or target probability distribution is usually 0, 1 vector or one hot vector, where all the probabilities for the classes that are not true are 0, and then we have probability of 1 for the class that we actually want to predict. If we assume that, and then we compute with the softmax our basically probability from the model that our softmax gives us, give an input vector, apply the softmax, get a probability out. So usually we call that Q. Now, basically, the cross entropy here for P and Q is defined with this, the negative of the sum of the probability of each class times the log of the probability that we predict for that class. And now, since we define P to be this one hot vector, we basically see that this is either 0 or it's 1. And so basically, we can only care about the log of the probability that we actually try to predict here. And we can also rewrite the cross entropy in terms of the entropy and the KL or Kullback-Leibler divergence. And again, it's not relevant if this is a little too fast, don't worry. Just want to make sure those of you familiar with information theory understand the difference. And it is actually, it's nice to know this here. It's very intuitive. Basically, the KL divergence is just this non-symmetric measure of the difference between these two probability distributions, P and Q. And because we can rewrite the cross entropy, this cross entropy error is actually the one we always optimize for when we train our softmax classifiers. So it's pretty important. When we rewrite it like this, you can see here that it basically is the sum, and we can look into that a little bit more also. Essentially, the entropy here of P is again 0 in our case, because again it's either 0 and 1, and it's also just the negative sum over the probability of each class times the log of that probability, and so that will be either you have the probability, which is 0, or the log that is 0. So h of P goes away. Also, P is, of course, the ground truth. So as we optimize anything, there's nothing to optimize there. So really, when we say we minimize, and this is the main takeaway message here, if we minimize the cross entropy between our target distribution and the distribution that our model gives, it's essentially minimizing the KL divergence between these two distributions. And again, sometimes people mistakenly say that KL divergence is a distance. It's not a true distance because it's actually a non-symmetric measure. All right. Again, it's just background. Don't worry if that was a little too fast. All right, in problem set 1, you'll derive the gradients of the cross entropy error with respect to all these different input word vectors that we have and the matrix W of the softmax. And that will familiarize yourself with the concepts to exactly the kind of degree that you need for the class. All right, and now it's 4:20. I think that's a good place to stop. Thank you. Hello, everybody. Welcome to lecture 4 of CS224D. Today I think is very exciting because we're going to start introducing the last very basic Lego block, and then starting next week we'll actually get to really interesting juicy bits of deep learning that will then kind of fulfill the most basic Lego blocks, and from there on we can play with much more higher level kinds of models and ideas, and it'll be very exciting. So today we'll basically finish up some general classification background, just to refresh some of the ideas from 229 that you may have already seen. Then look very carefully at updating word vectors, what happens to them sort of on an abstract level. And then we'll get to the first model that will actually be useful for downstream tasks, which is a window classification model. Very simple. We're going to classify single words, but in their context. And then we'll probably just get to defining the first and major Lego block, which is a single layer neural network. And then next week, we'll get to how to actually train that. And then after that, it'll be sort of much faster in pace because we have all the basic tools to really start building interesting models and putting all these tools together in new ways. Are there any organizational questions so far? You should have seen problem set 1, had a first look. Yeah?
Up to what lecture would we be given with all the material to do the problem set?
You should be able to do the problem set already, most of it. Yeah. So you can get started on it right away. We try to time the lectures usually in a way such that once the problem set comes out, you should be able to get started on it.
But the problem set has many like neural network related questions, and we are only doing neural network now, right? So.
That's true, but you can already get started because some parts of it only require word vector learning. And those you can already get started with. And then the second part of the problem set is something you'll learn about today and next week. Yeah.
Do we know when the midterms are going to be?
That's a great question. I think we have a date. There's only 1 week in which it can be, and then we only have these 2 Tuesday, Thursday classes. I want to say, David, do you know if it's on the website? All right. Maybe we'll follow up at the end of the class. Good question. Cool. All right. Let's get started. Classification, some setup and notation before we can get into what it's really about. So basically, in general, for classification, we usually assume we have some kind of training data set where we have some inputs xi and some class yi. And we usually have 1 to n many samples. Now, xi for our purposes will usually be either the words, could also be the entire context window of multiple words, could be whole sentences or even entire documents. And we'll usually try to define that properly when we actually look at each problem separately. Yi, in most of our cases, will be just simple labels, but it could also be entire other words. Words and labels will be in many ways treated very similarly, but of course, labels you usually have only a handful or a dozen, whereas if you try to predict a bunch of potential words as output, where each class, so to say, is predicting whether that word is the next word that should come in a translated sentence, for instance, the output space is much, much larger. And then we want to be very careful about how we treat the softmax classification, for instance. We'll get to that in a bit in this lecture. The class could just be sentiment, so for most purposes, you can simply think of yi as one of the potential classes, like very negative, negative, neutral, positive, or very positive, 1 of 5 classes. Named entities are other ones that we'll see a lot in this class, but it could be very high-level things too, such as buy-sell decision based on reading some article or something like that. So pretty high level. And we'll later in this class get to multi-word sequences where the output space is actually not just a single label, but a sequence of output labels, such as a sequence of words that we want to translate a sentence into. So let's look at a little bit of the intuition for the classification. Let's say here we'll have a very simple 2D problem. Let's assume, for instance, these 2D points are all word vectors. Word vectors that are simply two-dimensional. Again, rarely ever will we have a real example where it's in 2D. This is just for illustration. This is actually a great visualization from Jacob Hathi that I encourage you all to play around with. This is not a confident, this is just a simple logistic regression model, hence with no extra features added, you would just have a linear decision boundary to try to separate out these 2 points. But it gives you great intuition if you play around with this demo. So the link is in the slides, and I encourage you all to play around a little bit with it and see how eventually we're going to add different layers, and you add new points to your training data, and it changes the decision boundary. It's very intuitive. So let's say we have this simple classification problem here. We have green points, we have red points, and we have a linear decision boundary. And let's assume for now that x is fixed. So the word vectors may be fixed. They may have come from glove or word2vec initialization, but now we just try to classify each word separately and independently. So in this case, we would only train our logistic regression weights W here to modify where exactly that boundary should be. And this is again our definition of softmax, or the softmax classifier, or the logistic regression classifier. We're basically just for each probability to compute each probability of a class Y, we'll basically have the exponent and the inner product here of the ith row of W times the vector X. And we normalize this by summing over all the inner products with the other classes, with all the classes. All right, now we introduced in the last class the cross-entropy loss function over a specific data set. So let's use our notation here. Let's assume xi is our data input x, and we have the class yi that we'd like to predict. So then we're going to basically sum over this expression here the negative log of basically here our exponents, where fyi is just that inner product that we defined in a slide before. All right, now usually what we'll do, and this is going to be an important, one of the most important takeaway messages for this class, is how to write these kinds of operations in matrix notation, because matrix notation will enable you to implement this much more efficiently in code, and we'll look at some code examples and timings specifically in this lecture. So instead of saying we compute this actually by taking out a specific row in our W matrix and then multiplying this with X, of course what we'll instead do is we'll compute the entire vector of features F of the softmax with one large matrix multiplication, right? And each row is essentially independent, and hence we can parallelize this computation very well. Any questions so far around the notation? Yeah.
I was just curious, why do we use cross-entropy loss as opposed to some other loss function like mean squared?
It's a great question. So why do we use cross-entropy loss versus mean squared error or max margin loss and so on? We will actually use the max margin loss function a lot in the future. This is kind of the most basic one. It's very well understood, very common. It is still used very frequently. As soon as you have a lot of classes, or you want to speed up your training, or you don't care exactly about getting probabilities, you will end up using the max margin loss or objective functions much more frequently. It turns out squared error does not work very well with neural networks, and it's still not very clear why. There's no nice theory of why it doesn't work, but in most cases squared error loss will not give you great results. So this is a little bit outside the scope of this lecture, so don't worry if you don't understand it. But generally, well, this specific lecture maybe eventually for your projects, you might want to keep this in mind. But when you try to even predict a real number, you would usually want to use a kind of linear regression output and a squared error loss. But even then, it's better to make it into a classification error and then have a weighted sum of your different buckets of numbers to predict the final output. It just happens to work much better in practice. It seems like neural networks have and that's just my intuition, I don't really have a great backup for this, but they have very sort of high volatility dynamics. And so they can be very clear about it's this class, but if you kind of overfit to specific numbers, they're just not very stable. But yeah, great question. We'll look at other objective functions, and I think even the next week. All right, now whenever I say we use the cross-entropy error, I'm kind of lying, and really what we always use is a regularized version of any error. So throughout the lecture, when I focus on different kinds of loss functions, you can almost always assume that we also have our regularization term here, where we essentially assume we have a Gaussian prior on all our weights, all our parameters of our model, and we'll try to keep those to be close to 0 if we can. And we're going to penalize in a square term here any deviation from 0 for all our parameters. Otherwise, we'll always overfit these very powerful models. Yeah.
Yeah, I just wanted to ask on the previous slide, so we're talking about x as d-dimensional, so that would correspond to like one word, I guess. Wouldn't the number of features be out of hand once you have?
That's a very good question. We'll, in fact, talk about this right here. You're right. X will be our d-dimensional word vectors, for instance, often, and we have a lot of word vectors. That's a lot of parameters, and so you'll very likely overfit. And if you want to train your word vectors, you better have a very large supervised training data set. Otherwise, it will overfit very quickly. And we'll cover throughout this class a lot of techniques on preventing overfitting. In fact, some could say that a lot of the techniques in deep learning have been around for 20, 30 years, but it's really now that we understand, one, that if you have enough data, the data by itself almost regularizes your model. And we have various techniques, which we'll cover in this class, such as dropout, or now even stochastic depth networks, where you have variable numbers of layers and so on. There are lots of different techniques, sparsity constraints and so on, that we'll cover in this class in the upcoming weeks to try to regularize these models better and better. And in fact, sometimes you might not want to update the word vectors at all. We'll get to that in a bit in this class. In today's lecture. So basically, this regularization term will help us prevent overfitting, and this is one of the most important graphs that you may see in any machine learning class. In fact, when I took my very first machine learning class, the professor said this is the most important graph in machine learning. Basically, the x-axis, and it's by design here that I didn't write a specific one, it's essentially the model power, or the number of parameters, or the amount of training time that you have, and things like that. So basically, things that make your model more powerful and more accurate. And then on the y-axis here, you basically have your error. And in blue, you have your training error. And as you add more and more parameters, for instance, your word vectors, that's the one thing we now know already. If you make your word vectors 500 dimensional, and now you train them, your training error will go further and further down. But at some point, your test error will actually start increasing again. And so in all the cases, what you will want to do is first have a proper train and test split of your data set. In fact, what you really want to have, and we'll get to that in future lectures again also, is a train, development, and test split. And you're going to want to compute this graph on your development split. Basically, you just take your inputs here, and you take, for instance, 80% of your data points for training, 10% to develop and test and basically visualize a graph like this, and then the final 10% you only run once a week or once a month in a real project to understand how well your data would actually work on held out data sets, or on held out data in real life. All right, so this term is the simplest way we can prevent overfitting, but it certainly is not the only way we'll prevent overfitting. All right, so now for general machine learning, our theta will in most cases just be basically the columns or rows of W. And here I will introduce the opposite of the rows. Whenever we see dot and then the index, then that means we'll take this column of the data set. So here, just to get one long column vector, we take all the columns of W, and we define this W here as basically our entire theta. That's the standard for machine learning, where we used to always have specific hand-designed features, and we just want to weight those features to make a final prediction of a class. So in this case here, we would have C, the number of classes, times D, the input dimensionality, many parameters in the model. And that's the only thing we would update when we update our model. And we compute the gradients, and we plug that into stochastic gradient descent method to update our theta. And in this case here, all we would do is basically update this decision boundary. Now, in deep learning, we want to try to do end-to-end learning. So anything that can be learned, we try to learn. In the case of NLP, we at least have a word index, but then the word vectors are ideally part of the training model and part of what we already update. And so what we'll more commonly see is that we have both W, the softmax or the logistic regression weights, as well as the word vectors. And that now, of course, increases, and you already pointed this out, the number of parameters by a lot. Because V, again, is the size of our vocabulary, and D is the dimensionality of our word vectors. So we have here 500 times 100,000. So all of a sudden, you have way, way more parameters than you previously did. And so, like you said, overfitting is very likely. All right, now overfitting is one of the many problems with this, and here I'll show you an example of the very simple word vector example of what this could look like. Let's assume we're trying to train a simple logistic regression classifier on movie review sentiment. And in the training data, we have the words TV and telly. Let's say it's a British data set. And in the testing data that we don't see during training, we have the word television. Originally, we would hope from training our great word vectors that TV, telly, and television are all close by in the vector space. And again, usually those will be 200 dimensional. Nothing will ever in real life be 2-dimensional. But let's see what this would mean, what this means when we say we update the word vectors and we basically include them in our updatable theta vector. So what happens now when we train the word vectors? What do you think would happen intuitively when you start propagating TV and telly, and you might say they are negative, for instance? Well, they will start moving around. And the words that we also had pre-trained word vectors for, but that did not appear in our new supervised training corpus, they will stay where they are. So TV and telly might all of a sudden move over here because we keep projecting into them, you're negative. We're going to try to make it easier for the model to predict that you're negative, and maybe it'll be easier for the model to push them all into one specific area of the high-dimensional vector space to create a very simple decision boundary. So here we had in the training data TV and telly. Now those two might move over here, and in the testing data, television will stay where it is, right? And in general, because we only saw the word television in the test data set. Now, of course, when we try to classify the words, we will misclassify television if we see it at test time only, right? And that's not ideal. So we lose a lot of the power of the unsupervised word vectors if we update them on a very, very small data set. In fact, I have a fun visualization I might try to pull up. Where did it go? So this is a fun visualization of word vectors after you train them with sentiment. So here we again projected down high-dimensional word vectors into 2 dimensions, and after you train them on just sentiment analysis, so very simple sort of positive, negative task, what we color them here in is basically the probability of being positive. So the more blue the vectors are, the more negative they are, and the more red they are, the more positive these vectors would be by themselves if you were to classify this model. And if you go in this part of the space, and again, these are just the two first principal components of the space, you see that stupid, bland, thin, waste, awful are all pretty negative words, and they cluster together. So whatever we initialize them with doesn't matter anymore. They lost all this beautiful, king minus man plus woman stuff, and now all their vectors are capturing is whether they're positive or negative. And so we see here in this space mildly, mediocre, generic, all negative words, all coming together, but it doesn't really matter whether they're nouns, like it's an episode, or awful, which is an adjective, right? They're all just semantically and mostly sentimentally close together. And then as we move through the space, we get to sort of the middle part of the vector space, where you just have a bunch of very sort of neutral words, personal, classic, debut, effects, visual, and so on. And then as we go further and higher up in the space, we see more positive words. So for instance, cool and warm are close together, right? Which is, again, semantically maybe not ideal for some other modalities or some other kinds of tasks, but for sentiment, these are both positive. So this is basically the intuition of this very simple example, but in real life. On a larger data set, of course, we train them again in 50 dimensions, and just for visualization, we projected them down. All right, so the main take-home message here is that if you have a very small training data set, you never want to update your word vectors, because you will just overfit to that data set. However, if you have a very large data set, it often works better to also train a word vectors for the specific task that you have. So for instance, if you train a machine translation model and you have many gigabytes of training data, it's fine. In fact, at some point, if your data set is large enough, you don't even need to do any of the interesting word vector initialization stuff that we talked about in the previous lectures, word2vec and glove and so on. You can just train on the tasks that you have, and that's it. So, but that you need very large data sets for that. Generally, if you have medium-sized data sets, and again, this also depends, like what is medium, small, and large? It kind of depends on your task. If you have just a binary classification problem, you might get away with a couple of thousand examples. If you have something like machine translation, where your output space is a sequence of words, of thousands of different words in another language, you may need a lot more training data.
1,000 of examples per word?
So in thousands of examples for a simple classification problem, where you have 2 or 3 classes, you have a couple of thousand examples per class. For machine translation, you want to have many hundreds of megabytes, ideally gigabytes of training data. Nobody really has like a how often does each word appear a kind of statistic, because you know that you have a very sort of power law distribution of words, and some words will never just, even in a corpus of billions of words, some words will only appear a couple dozen times or less. All right, are there any questions on training word vectors? Cool. All right. So I think in a week or two, you'll all have trained your own word vectors, and this will become second nature. All right. Now, a quick side note on word vector notation, because throughout this class, and as you start reading actual papers in research, you'll see lots of different notations and nomenclature for word vectors. We sometimes use the word vectors, but others use word embeddings. Sometimes we use word representations or word vector representations. They're all basically the same thing. And sometimes we call the final matrix L for a lookup table. Sometimes we call it X. In many cases, you'll see very quickly, what dimensionality it is, and then you'll understand what is meant. Now, when I read my very first deep learning papers, they said, and then we take derivatives, and they just had a lookup table and a hash. And I'm like, how do you take derivative of a hash? This doesn't make any sense. And so intuitively, mathematically, the way you can think of taking out a specific vector from this matrix in order to then initialize some kind of follow-up model with it is that you can essentially left multiply a very large one-hot vector E with this L matrix. So imagine you want to get the X vector, the word vector, out at the location, let's say 2, then you basically take this very large L matrix and you have a very high dimensional one-hot vector E that is basically 0, 1, and then hundreds of thousands of zeros, and you multiply these two together, you have a D by V large lookup table or embedding matrix times this V by 1 vector, and you get back a D by 1 vector, and that's exactly the word vector at the second location of that index. And of course, you're never actually going to want to multiply this very, very sparse matrix with this very large, the very sparse vector with this very large, dense matrix. But intuitively, if you try to think of the derivatives and you work through the problem set, you can think of it that way. Yeah?
Quick real-world question. Has someone released like pre-trained word vectors? Are those available?
Yes, that's a great question. So the question is, and so I'm going to repeat them for the videos, have people released these? And the absolute answer is yes. A lot of them have been released. So for instance, if you go to Glove project from Stanford CS, you can download the vectors that have been trained on different data sets. Also, again, understanding that word vectors are very different depending on what they've been trained on. So here you have some Common Crawl trained word vectors with 840 billion tokens, which is not something you're ever going to want to do by yourself. So it's a phenomenal resource. It's also, just to download them, I think in a zipped up format, it's 2 gigabytes. So it's rarely that you ever want to use the entirety of those word vectors. Yeah.
Which one of these should we use?
The best one is the Common Crawl one. We saw in last lecture, in the terms of performance of various intrinsic and extrinsic measures, the larger the better. But when you download this file and you look at it, you'll observe that the last couple of 100,000, so in total this is 2.2 million different word vectors, and each one is 300 dimensional. And this again comes, like these choices came from very carefully looking at the graphs and observing performance for these different hyperparameters. What you'll observe is that the last couple of 100,000 are basically different numbers, like 0.001, 0.35, 0.67. Like they all have their own word vector, which is really kind of silly. You don't need all those word vectors. It still helped, because sometimes you may have 0.1 dash debit or credit or something, and then if you see that one again, it might help you a little bit. But you basically have very much diminishing returns from taking the entirety of that word vector. Now, sometimes what you can also do is you can actually run your own PCA. If you say 300 dimensional is great, I want to use the Common Crawl ones, you just take the first 200,000 most frequent ones, and then you say, well, 300 dimensional is still too much. What you can then do is run PCA and only take the first 100 or so.
So they're in order in a file?
They're just ordered by frequency, I think. So but that's a very useful order. Yeah.
So it says 2.2 million vocabulary, so
that's right.
The number of words.
Mm-hmm.
And what's then 840 billion token? Is that what's token?
So the question was, the 2.2 million is the number of words, the size of your vocabulary. The 840 billion tokens, a token is basically just an instance of a word. And 840 billion tokens is basically the size of your training data set. So yeah, the corpus on which you train the word vectors.
Does it make sense to update your vectors if your data set isn't as big as these?
Yes. So rarely ever will you have a data set ever that is that big. Usually you're lucky if you have millions of tokens in your data set. And once you have a couple million, you definitely want to update your word vectors. Yeah. Though, whenever you're not certain, the best answer, if you think, oh man, I wish I had a professor who gives me advice on my project, and I have the following type of question. I wonder if I should do X or Y, because I don't know which one is better. The default answer that is always correct is to do both, and let the data decide. Look at your test data and let the test data decide which is the better one. Because even the person with the most intuition, they have seen 50 different projects and almost never did it work, but maybe you're the one exception. So you can never go wrong by running the experiment, making the choice that you had in your head by yourself, and evaluating, again, on a development test split. Don't ever run it on the final test data, because then you just start overfitting to that. But that will always be a good answer. All right, those were great questions. Yes?
When you said pre-trained over there, do you mean that you have a sentiment analysis that start pre-trained it, or you have what is the why basically?
Oh, great question. So the question is, what do I mean by pre-training? Usually when I say pre-training, I will mean that we use word2vec or glove to initialize these word vectors. Later on, you can start towards the end of the class, we'll get to transfer learning, where pre-training might be you train on sentiment and then you try to predict different emotional classes that aren't just positive, negative, but might be happy, sad, ecstatic, and things like that. And then you might pre-train on an actual supervised task. But in most cases, pre-train just means unsupervised word2vec glove style training. Cool. All right, so now word vectors, great, useful first step, but rarely ever do we use word vectors just by themselves. They're the first step towards training some real system. So let's get to window classification, which is the simplest of the useful deep learning models. Basically, we're trying to classify rarely ever a single word by itself in complete, independent of the context. Most words appear not in isolation, but in some linguistic context. That context could be images, but in most cases for this class, it'll just be the other words around it. And it's incredibly useful to actually consider that kind of example. So for instance, here are a couple of fun examples where really you have to have the context to understand and even classify something as simple as a single word. So for instance, there are auto-antonyms, words that mean their opposite as well as their default meaning. So to sanction, for instance, can mean to permit or to punish, right? Or to seed can mean to place seeds or to remove seeds. And you have lots of those examples in English. And of course, there are other simple words, so even ambiguous named entities. So Paris could be the Paris Hilton or the Paris of France. Right? Or Hathaway could be Berkshire Hathaway or Anne Hathaway. So it might be an organization, it might be a person. All of these are very, ambiguous, and we only know what they really are in context. So let's look at a word in context by essentially just considering it together with its neighboring words. And this model will be one that you'll implement, and it's actually the first reasonable one. Even for your projects, this might be the first that actually is a reasonable baseline to implement. For instance, if you wanted to implement your own named entity recognition algorithm, this is one of the most basic, simple Lego blocks that you can use. So there are lots of different possibilities for classifying a word in its context. One would be you average all the words in a window, but that loses the position, and you might want to know whether the or driving to appears before or after a specific word, because if you're driving to X and you can see all the movement to X kinds of windows will probably make X a location. Right? So you want to have a model that captures that. And so the simplest one that we'll look at today is to just train a simple softmax classifier by assigning a label to the center word, which is again not required. You could have the word that you want to predict as the last word, but for most of this lecture, next lecture, we'll just assume we try to classify the center word of a window. And what we'll do to define our features is simply concatenating the word vectors of all the words that are around the word we're trying to classify. So let's say here, for instance, we're trying to classify Paris in the context of this sentence. So maybe I visited all the museums in Paris, or I think all the museums in Paris are amazing. And now we're trying to classify this word, and what we'll do is basically just take the vector of museums, the vector of in Paris are an amazing, and we concatenate them into one long column vector. And here this looks like a row vector, so I'll make it very explicit. The default for all our vectors will be that they're column vectors, which will be important for all our dimensionality checking and the equations that are coming up. Okay, so depending on our window size, we have a differently sized feature vector x. And those will be exactly the x's that we defined in the very beginning for classification. And y here could be, is this a location or not? Could also be y1 equals its location, y2 is it's a person, y3 it's an organization, and y4 is it's none of the above. That's a very common set of tags or classes for named entity recognition. Okay, so if all of our word vectors are d-dimensional, then, and we have, let's say, a window size of 2 to the left, 2 to the right, we'll have a 5D dimensional column vector. And now we can basically go through our standard logistic regression. X here, each x is the x of our window. We concatenate the word vectors, and we can use the exact same definition of a softmax classifier or logistic regression or cross entropy. Those three are also all synonymous. I usually stick to the softmax classifier in this lecture, but we basically can take the standard softmax classifier and we basically predict here some model output probability with this equation. And we'll update this by taking derivatives of the cross entropy error, and we've basically done most of those in the previous lecture, and in the problem set you'll extend this here to the softmax. But it's going to be very intuitively here, right? You just take the derivative of the log, you apply the chain rule, take the derivative of the inside, and so on. So now the question is, how do you update the word vectors, right? The default here would be we just update W. And the short answer is, well, we just take derivatives as before, but we apply the chain rule again. We don't just go to the W when we take derivatives, but we go one step further. And that's one of the things you'll have to do in problem set 1. And so I want to basically give you now a couple of tools to make this easier for you as you have a complex, well, it's not quite complex, but it's the first sort of most important Lego piece, how to take derivatives of word vectors as there are layers in front of it. So some people might say this simple model where we have a softmax layer on top of word vectors is already a 2-layer neural network. It's not really. You could also say it's not really a single neural network layer, but softmax is considered 1 layer, and the word vectors could be considered another layer too. So let's go over a couple of tools, and those won't be just useful for deriving word vectors, but for all the derivations that you have to do in the midterm, in the problem sets 1, 2, 3, and so on. So step 1, very carefully define all your variables. So let's do this for this exact problem. We just have a softmax here, and we basically want to derive derivatives for the W matrix and all the word vectors X that we see in a specific window. Is the goal clear? Right. Mostly nodding. Cool. All right, so let's define our variables. Y hat is the softmax probability output vector. Just this one right here. If we do a subindex of that, then we mean we have the yth class. So just one element of that vector. T will be the target probability distribution. Again, this will be all zeros except for the ground truth class y, where it's 1. And then f, or f of x, is basically just defined as a simple matrix vector product, where we have here a number of rows equals c, number of columns. Actually, let me ask you this question. What do you think is the number of columns for W if we have d-dimensional word vectors and we have a total window size of 10? That's right, 10D. Great. All right, whenever we subindex f here, then again we'll take that subindex element of this vector f. All right. This can be a little hard if you haven't taken derivatives for a long time, so we'll go through a couple of tips now. All right, so let's say in our case here we had dimensionality of, or window size of 5. So we have towards the left, towards the right, trying to classify the center word x. And each of them is represented as a d-dimensional vector. And the first thing is not just define your variables, but also carefully keep track of their dimensionality. Because whenever you have any multiplication in your derivations, and you already know just from understanding what matrices you can multiply with other matrices or vectors, and they don't actually are proper multiplications. Let's say you try to multiply x times w, and x is a 5D vector, and w here is a c by 5D. So you have x on the left side, you already know that this is not a proper multiplication, and you already know you made a mistake. And once you implement this in code, it will also nicely throw an error. All right, now step 2, know that chain rule. Don't forget which variables depend on what. So if we have x here, for instance, and you want to basically take the softmax of fy of x here, the yth element of this, make sure you sum over all the classes, and make sure you know that your x is actually in fc of x. So sometimes we'll just write this whole vector as its own variable, but make sure you understand that the variable, this vector actually dependent on a specific other variable. So you can write it as a function also. Now for the softmax part of the derivative, you want to first take the derivative with respect to fc, which is the class that you might want to actually predict, the correct class. And then you can take the derivatives with respect to fc when c is not equal to y, all the other incorrect classes. And some of this might not be as intuitive until you actually go through the steps, and you can refer then to the lecture slides when you go through it. All right, tip number 4. When you take derivatives with respect to one element of your vector f, for instance, try to see if you can create the gradient, the final result in the end, by looking at all the partial derivatives. So for instance, you will notice if you just take all the classes that aren't true, so let's say y here is the true class, and 1 to c with y not equals this exact y, all the wrong classes, then you may basically put this together, and then you see a larger structure, and then you can write this overall as a vector. And this is something that's very important to later not go insane as you're as you're trying to implement this. You basically want to define, every time you have something where you have all the partial derivatives and you can concatenate them in a vector, you want to put that into some vector notation. So maybe you can see this being your derivative, and now this doesn't maybe intuitively look like a vector, but then you can see, well, if I just subtract always something on this side, which is 0, then I can write this whole thing in terms of a vector subtraction. So here, for instance, y hat will be our predicted probabilities, and t will be our target. And we'll subtract t. This is basically our target probability distribution, which happens to be exactly one of the things that we defined in our notation in the beginning. And we'll define this as delta, and we'll become good friends with delta in the next couple of slides or in lectures. All right, now we're almost at the end. So tip number 6, when you start with the chain rule, first you can write out explicit sums and then look at all the partial derivatives to get a good sense of what's going on. So for instance, as you write down this chain rule, you will at some point hit this kind of sum, and that's very intuitive. You'll have some delta, and don't worry if you don't understand how we got there, but you'll have some delta times the transpose of your softmax matrix. And it's very intuitive what's happening here for each of the classes. But in the end, and this is kind of a skill that you'll develop in this class, you can see, well, if I multiply each of these and I keep summing them up, then maybe what I can do is I can actually combine all of this in one large matrix notation. And again, here it's very important to know that you have the right dimensionality, so you always have to keep track of your dimensionality. It's very quick to subtract points if we see any multiplication ever that isn't even a proper matrix multiplication because the dimensionalities don't add up and don't make sense. So here, you can basically, will eventually see that the derivative with respect to x will be w transpose times delta. And again, if some things are not clear, write it all out in the full sum and then try to backtrack to see if you get to the matrix notation that way. So now, to wake you back up, what's the dimensionality of the window vector gradient? So if we have here x having been the vector of all the word vectors that were concatenated, and we're trying to classify the center word. So intuitively, when we have our gradient of the objective function with respect to this vector, we want to update that vector. So what does that mean for the gradient? Yeah?
If it was, well, if you have 5 words, it would be 5.
That's correct. That's exactly right. So if x is the entire window and we have 5 d-dimensional word vectors, then the derivative with respect to x has to have the same dimensionality, right? We're always going to update theta new equals theta old minus the step size times the gradient of that theta. So if the theta is the current word vectors, then that's the exact update. So that is another sanity check. In the end, after all your matrix multiplications, if the final result doesn't have the same dimensionality as what you're trying to update, you've made a mistake as well. All right. So the gradient that arrives at and updates the word vectors can, in the end, be simply split up for each of the word vectors. So this is not really that intuitive, but, well, it's very intuitive, but you might not sort of derive at it by yourself. So I want to make this very, very explicit. So generally, we'll get some update delta for the entire window. And as we just said, this derivative will be 5-dimensional, but we have actually 5 separate vectors in here. And intuitively, you basically have an error message that arrives from your gradients at each of these vectors. And what we can do to update the whole one is basically just split them all up at exactly the dimensionality. So this will be essentially 5 separate d-dimensional vector updates. And then intuitively, as you update this, you will find what is the actual ID of the museum's vector in your final lookup table or embedding matrix. You find that ID, let's say museums is the 80,000th word, then you look at the 80,000 column and you update that column with this derivative. Yeah?
So what happens if you have multiple of the same word in the same window? So like museums in Paris and France?
That's a great question. What happens if you have the same vector, the same word in the same window multiple times? Well, it's just the same thing. You have here delta of your window, and museums happens here and here. And in the end, you look up the ID and you add both of those derivatives to that ID in your lookup table.
So we just apply the class here.
Yeah. So these are all the very basic applications, and again, usually I know that I will bore 1/3, I'm a little too fast for 1/3, and for 1/3 of the class it's just the right speed. Depending on which one you're at, feel free to come to office hours that we started this week. All right, so now this will again push the word vectors into areas in a way that it will be helpful to determine what are the named entities for the center word. And what intuitively this model can already capture is that when you see the word in, for instance, as the word just before the center word, you already know that this is indicative to be a location, for instance. So these are the simple things that this can now figure out. And if you have word vectors that are similar to in that you haven't seen during training, then if you had a good initialization of your word vectors, it will generalize better to this than if you just had a word index, right? And that's really the power of these word vectors. The similarity of words will enable us to do downstream tasks better and generalize better to unseen test data. All right, now what's missing for training the full window model, of course, we don't want to just train the word vectors. We also want to train the softmax weights. So the gradient, the final gradient of J with respect to the softmax weights, and then with respect to the entire parameters that we may want to update, theta here will essentially be this. And it will again just concatenate a bunch of column vectors together to get the full update of theta. All right, any questions on the math so far? All right, great. So now a note a little bit on matrix implementations, because we'll tell you roughly how long training should take for your problem set 1 as you implement your first algorithm, but it will widely vary depending on whether you use this trick or not. So for instance, for the softmax function, there are two things that are very expensive in terms of the operations. The first and major one is that we have a large matrix multiplication. And that is basically the major bottleneck of all of deep learning, is you have lots of matrix multiplications. And these W's and X's can get very, very large. So at some point, you may have a 5,000 dimensional vector X and a 5,000 by 5,000 dimensional matrix W here, and that's basically a layer that goes from 5,000 to 5,000. It's going to be very large. And then you also have the exponents, and exponents in the computer are also not that cheap to compute. And so the most important thing for implementations in any higher level language, such as Python, MATLAB, Java, or any of them, is that you want to always avoid, as much as you can, any for loops. So let me walk you through an example, a very, very simple one that's similar to this simple example that we just walked through. So let's say we have here all our word vectors, and instead of concatenating them all into one large matrix and then multiplying them, we did just a for loop. So here are the two implementations. Let's say our W we just initialized randomly, and again we have C number of classes, and let's say we have D is 300 dimensional windows. So let's say we have gotten this from maybe from some other things, it's just for illustration. And let's say we have 500 windows in total that we want to classify. And generally, and the graders would all appreciate if you also properly define all your terms and your variables this way. Now would end up with some kind of matrix W here for our softmax, a C by D matrix, and we have basically our word vectors, which will just be a bunch of random d-dimensional vectors, and that will basically here be our word vectors as the entire matrix. So let's say we had, for instance, n many different windows, and each of the windows was d-dimensional. Now, if we did a for loop over all the windows that we have, versus we have one very large matrix multiplication where we multiply all the windows in one go, the difference is huge. So here, when you have basically this implemented as a for loop, it'll take 600 microseconds, and if you had it in one large matrix multiplication, it would only be 50 microseconds. Right? So, and right now these are all small numbers, but even in your projects, you'll have tens of thousands of windows, and you want to go over this matrix many, many times, and this could be the difference between 12 days or 1 day, right? And that will be the difference between you submitting the project on time versus you having no results to show, right? So very, very important. Yeah.
On the topic of runtime performance, I noticed that NumPy doesn't by default do parallel matrix multiply. Is there a way, like clean and cheap way to get it to do that, or no?
So it's still more efficient even if it just uses one CPU, but you're right, it's non-trivial to make Python do proper multi-CPU even implementations. It's super hacky and hard to make it work, and that's one of the main reasons we went through all the work, or are going to go through the work of updating the problem set 2 and 3 to use nicer frameworks that will do that for you. In fact, they will not just do it for CPUs, but also potentially for GPUs, and that will help you immensely if you have a GPU.
So we can't like give it an argument and say, please use all my CPUs?
Unfortunately not. There's no simple way to make Python nicely use with NumPy all the cores that you have. But this was also not done, like this was just done with simple NumPy things, and it still has that speed advantage. So just from the overhead and the efficient matrix multiplication, it already helps a lot. Are there any questions about this code? Cool. All right. So matrices are awesome. You should always do this. Also, the time it quick hack if you are in an IPython notebook is super helpful. Sometimes you think you have two vectorized implementations and you're not quite sure which one is more efficient. Again, there's always a simple way. You just try both and you time it, literally, and then you can know which one was faster. So the speed testing of your code is going to be very useful. Otherwise, you're just going to sit in front of the computer for a long time and keep checking your results. All right, now I mentioned softmax, and softmax is the first simple thing. But if we have the word vectors and we fix the word vectors, it's not very powerful because it's only going to ever give us a linear decision boundary. And sometimes a linear decision boundary is actually not so bad. If you have very high dimensional input data and you don't have that much training data, then forcing your function to only be linear might be actually some way of regularizing your model, like keep the model very simple. But as you have more data, and that's exactly the regime where deep learning will be so useful, it is very limiting. So let's say, for instance, here, you started with simple softmax, or again, logistic regression, just a synonym, and you have training data in green in one class and red in another class. And this is kind of lame, right? We basically, with a linear decision boundary, we could never get to classify these points correctly. And again, if you have very little data, you might not want to because they might just be outliers and you would overfit. But if you have lots of data and it's clear that the data and the ground truth or the real manifold that your data lies in is just not linear like that, then it would be nicer if we could actually have a decision boundary that looks like this. And that's when we'll use neural networks. Because neural networks will enable us to give us arbitrarily complex decision boundaries of that nature. They're so powerful that they will very quickly overfit. So here in this case, for instance, we have so few training examples that this is clearly an overfit example. But as you have more and more, it'll be actually very powerful to have that. So now, since we've defined and very carefully analyzed and you'll derive all the logistic regression derivatives and so on, we can use that notation to define neural networks, and we'll really start building. You can really see this as a Lego block. And yes, the first couple of Lego blocks are not that exciting for the class, but you can start very quickly build very cool things once you know them very well. So let's demystify neural networks a little bit and just define the terminology for neural nets. So basically, there's lots of terminological baggage, but it's kind of true for every machine learning model. So once you understood the softmax, it'll be very easy to understand what a single neuron does, and then we just kind of put them all together with very deep neural networks. So single neuron will often say it has some inputs, and sometimes we also define it to have a bias unit that basically also is sometimes referred to as the intercept term. Then we will have an activation function and an output. So let's look at one very simple definition of how we can define a single neural network unit or single neuron. And again, neurons sort of in scare quotes. Real neurons in the brain are very, very different, much more complex. There's a very simplified model. And in some ways, really, we could also just call it a binary logistic regression unit. This doesn't sound quite as cool as a neuron, but they're also synonymous. So here is one way of defining this. We basically have our h here, which is the full output. H of x is the output of one neuron when it gets as input a vector x. And we have here a simple inner product with with a vector, in this case for now, a vector w. And because the default for our vectors are always that they're column vectors, we'll say here we transpose this, so it's a row vector, so we have a row vector times a column vector. And then b here is our always on feature. And again, other terminology for that is the class prior or the bias term. And I'll personally use bias term most of the time. So b here in our case would just be a single number for a single neuron. Now f, I mentioned before, we could have here our sigmoid function. That's the simplest one. It's not one that we're going to use a whole lot, but it is going to be used even in very fancy models later on. So basically, f of z just basically maps any real number to be between 0 and 1. As a squashing function is also what we sometimes call it. All right, that's it. That's a neuron. That's the simplest small Lego piece. And now we can basically say, well, we have some input. These could be our word vectors that we already know. And we plug them into a bunch of these logistic regression functions or neurons. And maybe we'll do that a couple of times. And we have different neurons all on the same input. And all of them have their own bias term here. And maybe we can do that again and again. So here it's not really clear what we're trying to predict yet. So maybe what we would do is instead of giving those directly as like a single output, so here the model we've walked over before was where we tried to classify this unit, for instance, is this a part of a named entity location or not, right? And we could have had this neuron here also define, is this a person or not? And we have different binary classifiers on the same window input that we defined before. But the main idea of deep learning will be that we won't define explicitly what these intermediate logistic regression units will do, but we'll actually have another logistic regression unit that sits on top of the output of those. And now it's basically the loss function that we have on this layer that will determine what these so-called hidden or intermediate layers and variables should capture, in order to make the final prediction at this layer to be very accurate. And that's basically it. That is we took this simple Lego block of a logistic regression unit, we can put it together in sequences, and then we can follow them up with multiple other logistic regression units. We plug them all together, and that's the definition of a deep neural network. And that is going to be the major focus for the next couple of lectures, really understanding all the notation and all the computation and learning of these kinds of architectures. Yeah?
Is a multi-layer neural network the same as multi-layer logistic regression then?
Yeah, you could say that. So multi-layer logistic regression, it kind of depends on how you define it, but I would say in the end, up here, you have a logistic regression layer or softmax layer. And if you say it has multiple layers before it, then that would define a deep neural network. Or a multi-layer perceptron is another word that you sometimes see in the literature. Yeah.
What is the question neuron?
Sorry, say again?
Plus one neuron, the additional neuron, the added layer.
This one here? So this is the bias term. So in order to have, we'll get to that in a little bit, in order to have a bias for each of the neurons that we have in intermediate layers, sometimes people write this as a +1 here. It kind of is just notation for visualization. It basically will give us a bias term that is independent of the input. And sometimes you might want to say, this neuron, maybe it's just never that useful, so the bias term is very largely negative in magnitude, which will then push, because of our activation function here, if b is very large and negative, it will go down here, and then no matter what the input is, that neuron will never be on. and maybe some neurons for later layers. It'll be helpful that they're always on, and then if your B term is very large, then no matter what the input is, you'll always be somewhere over there. Yeah.
In general, how do you decide how many layers you have?
Ooh, that's a tough question. How do we usually decide how many layers we'll have? There's some intuition, there's some basically experience for different kinds of problems, how many layers are useful. The best answer is the one of try them all and look at your dev test performance. Try 1, 2, 3, 4, 5, and usually if after 3 to 4 you don't see any there's improvements, it stops making sense to add another one. But we'll get to sort of when does it make sense to have how many layers. In many cases 1 or 2 is actually the right answer and it's already enough. Yeah.
So to follow up on his question, it seems like word to vec has 2 layers because you have the logistic hidden layer and then the softmax output. Is there a reason why that was like decided upon? Like everybody uses that?
So it was decided. So one, it's technically only at most a single layer, because you have the word vectors, which are linear, and you have one sigmoid on these word vectors, right? The inner product. So remember in the objective function, you had sigmoid of your center word times the outside word. And that was all. And then you had another part where you had center word and a bunch of random other words.
So you still had softmax loss, right?
No, that was the final loss function. You'll see it once you implement it, but that was, you just take the derivative of the sigmoid. There's no other thing on top of that. And so it is really the least deep model that has ever been called deep in deep learning.
So then it's basically just a linear model, which is why it's only one layer.
That's right.
I wanted to have non-linearities.
That's right. It basically only has one output with one sigmoid. And usually what we define as one proper layer is exactly this, which is a linear layer plus some non-linearity applied to all the elements. So let's define this very carefully. So one neuron, A1 here, its output will be computed by basically this simple sum, where we just wrote essentially out what the inner product here is between the first row of the matrix W, which defines that entire layer, and the first row times the input is basically plus the bias term is the output of the first neuron. And the second row is just the second row of W plus the bias term. And that's how we can essentially, we can put this all together in matrix notation and then just write Z equals WX plus B. And so the number of rows of W is the number of layers that we happen to have here. Sorry, the number of neurons that we have in this layer is the number of rows in W. And the number of columns is basically just the number of the dimensionality of the input here, X. And whenever we write F here, now very important, in a couple of slides before, we called F a vector. From now on, F will be a function. It will be our non-linearity, like the sigmoid. And the sigmoid function is, of course, only defined for a single number. And so whenever we write F of a vector, what we mean is we apply this element-wise. So F of Z1, Z2, Z3, the vector, will just be F of Z1, comma, F of Z2, and so on. Yeah?
So here X1, X2, X3, they are basically the different dimensions of the input. So it's a given window, and we're taking the first and third dimension.
That's correct. So the question is, what is our X here? You could, for instance, see X as the window that we have, and each word, let's say the window is only size of 3, so there are 3 word vectors, and each word vector is only 1 dimension. Simplest kind of word vector you can have, just a single number. Now that would then give us exactly this kind of input. So each X here is just a single number. So this is abstractly defined, right? It could also be a single vector that has 3 dimensions, and you just classify one word vector here in isolation.
So it basically is a real number. It's not capped between 0 and 1, right?
That's correct. Yeah, that's a good question. Is X a real number? X could be anything. X, in many cases, is a real number. But, and we'll get to that very soon when we look at tips and tricks on how to not mess up training these models, you do want to make sure that X isn't gigantically variant. So because if, for instance, X here sometimes is 1,000,000, then whatever comes out here and you multiply and one of your elements of x here is 1,000,000, then all of a sudden this w, no matter what it is, small random number, large random number, will dominate everything. And then very likely if you multiply this x element with 1,000,000 and w here is positive, then this A1 unit will just be always on, right? Because you will then be very quickly right here, somewhere way out here, for your sigmoid activation.
So this only affects the first layer, not the ones after that?
That's correct. It will only affect the first layer. So this is just the definition of a single layer, and so all of what I've just described will only be true for that first layer. Yeah?
But even if that one neuron has really high activation from the input, does it learn a bias to sort of counteract that?
It could, but we'll get to that very soon. But what happens if you try to optimize the function and you're stuck right here? What's the gradient going to look like if you're up here? That's right. It's basically flat. And so it's 0. So you're already stuck in a local optimum. And that's why making sure your inputs are in a specific window and your weights are such that you start somewhere here and not somewhere way out here or way back here of the sigmoid is going to be important. We'll get to all of that as we learn to implement these from scratch. All right, so now nonlinearities, F, why are they needed? So you might say, well, why don't we get rid of the nonlinearities and we just have multiple W matrices? Well, that's going to be completely useless because the nonlinearities are really what enables deep neural networks to learn much more complex decision boundaries that look like this instead of just linear decision boundaries like this. If we had no nonlinearity and we just had added a bunch of separate W matrices, well, you could just basically multiply these together first and you would end up again with just a single linear layer. So it's really these nonlinearities that make neural networks so powerful. So to give you an intuition, let's say we had, and we'll get to this model in very soon, but let's say you had a very simple one-dimensional input here. And you had different numbers of hidden layers, a single layer only, and you tried to have a simple linear regression output here. Now, if you had one hidden neuron, this would be how you could fit these points. If you had 3 hidden units, you could fit this function, and if you have 10 hidden units, you can basically completely overfit this function, and your regression algorithm will be very, very overfit to this specific data set. So this is kind of a regression example, and this is a classification example where we have decision boundaries and decision regions. And we'll usually want to have a couple of layers that are variable sized in their depth. And another way of thinking about this is that deep neural nets are really just general function approximators. You have any kind of function you try to approximate, it will be defined over some kind of n-dimensional input. In this case, for instance, just a simple 2-dimensional input, and you want to learn a function that basically maps any point in that input to a specific output class. And that's the magic of deep learning. They're general function approximators. They just happen to be very, very powerful as we add more and more of these layers to them. All right, now let's actually look at a more powerful window classifier that we'll be using in practice, and that actually started in 2008. One of the most exciting papers that have come out in deep learning in a very long time until then by Colbert and Weston. So let's say we revisit again our window classifier, but now instead of taking the input vectors x and directly giving them to a softmax, we will first give them as input to a hidden layer, a hidden neural network layer, and then to a softmax. So let's define what this will look like. So we have here x, which is again just a concatenated, it's not so gross. We had a single layer neural net here that we'll define in the standard notation where we have a linear layer followed by a nonlinearity. So we have here our concatenated word vectors in x. and we plug them through this matrix multiplication. Straightforward to now have an element-wise nonlinearity. And now the neural activations that we often call A basically can be used to compute some other function, right? And now this could be the softmax, which we used before, but it could also be just a very simple unnormalized score. And we're going to want to say that maybe the score for x should be very high if the center word in the window that is defined by x is a location, for instance. And we'll soon get to why we might want to use just a score instead of the softmax. But intuitively, we could also use the softmax. Now, in order to compute that window score with a, again, some people might call this a 3-layer neural network, others might just call it a 1 hidden layer neural network, will be as follows. So we take here our window, we concatenate the word vectors. Let's assume, for instance, each of the word vectors is 4-dimensional, and we have 5 of them that we concatenate. Now, the first layer will be, again, a linear matrix vector product plus the bias term, matrix addition, simply element-wise nonlinearity, and then we'll compute a score. And that score is just U transposed times A, which is just a simple inner product. So we could now define the entire computation as basically this way. It's U transpose times F of WX plus B. And that's the definition of our first useful 3-layer neural network or 1-layer hidden neural network. And again, this one is the hidden layer. Nobody quite knows what these should be learning. But you can also say, well, our word vectors are a layer, this is a hidden layer, and this is the output layer. So you might call it a 3-layer neural network. And this might compute a score here for museums and pairs are amazing, and we might want to say this score here should be very large if the center word is a location. And these should be very intuitive in terms of dimensions. So our x vector here, we had 4-dimensional word vectors, and we have 5 of them concatenated, so we have a column vector of 20 by 1. That means that W, if we want to have, for instance, 8 hidden neurons in our first hidden layer, should be an 8 times 20-dimensional matrix, and then U again is an 8 by 1 output layer. And in the next lecture, we'll actually learn how to train this kind of simple window-based neural network, and then we'll take deeper derivatives, which will eventually lead us to the powerful algorithm of backpropagation. Backpropagation will eventually just be applying the chain rule and being smart about it. But because it's non-trivial to actually derive it in its full glory, eventually people gave it a name. And really after that, we have all the basic tools. We'll stop going through nitty-gritty derivatives with lots of sub-indices. We can say, all right, we understand now what a layer is. Now we can put them together and we'll learn very powerful, cool functions. Thanks.
When in diagram of the neural nets that you drew with the x's, xi's up to some xn being fed.
Welcome to lecture 5. Today is the last lecture that will be sort of introducing the most basic pieces, the most basic Lego blocks of deep learning. After that, we can basically put them together in all kinds of new ways, but you'll basically have covered all the important stuff. It will be kind of the hardest lecture of the quarter, and I encourage you to read the lecture notes that we'll upload by the end of this week and really go through it, come to office hours. Today is sort of the heavy stuff, and then after that it will get a lot easier. We'll start introducing the real models you may actually use in practice. We'll introduce tools to you like TensorFlow that will allow you to make use of these basic blocks very easily, and we're good. The mic's not on? Okay, all right. For the people online, today will be hard. So first we'll go over a little bit of organizational stuff. Then I'll give you some project tips, because now is also a good time to start thinking at least about the problems that you want to work on. And then we'll introduce the multi-layer neural network and how to train it and all the nitty-gritty details of the derivatives. And then we'll be good to go for the rest of this quarter. All right, so some organizational announcements. We'll actually introduce a 1% extra credit for Piazza participation. So if you see a question from somebody else and you know how to answer it, and you do that a couple of times, we'll give you some extra credit. Also, there was a little bit of confusion in problem set 1 around the dimensionality of some of the vectors. And so generally, the best way to go about doing this is first you figure out the math, you understand exactly what the dimensionality should be, and then after that you can basically check them with either breakpoints if you use something like PyDef and Eclipse, or with simple print statements. And so, for instance, if you have here the softmax cost and gradient function, you want to test something, you can always just say print v hat of the predicted dot shape, for instance, or the output vectors dot shape, and then you can check and make sure they make sense given the equations that you have. And then last night we also introduced a student survey, so I would love to get your feedback so we can improve the class. It will sort of moving forward change for sure, because we can go higher and higher level, start to put these basic Lego blocks together. So we'll stop after, I think this class, basically we'll stop going through all the indices of various derivatives, but it'll still be great to have your feedback and know if we're going too slow or too fast and or just the right speed. All right, are there any questions? The organization, the problem set? All right. So the class project, it's really one of the most important and lasting results of the class. It's 40% of your whole grade. In order to facilitate making it easier for you to create a cool class project, we'll actually make problem set 3 a little easier, so you have more time on the class project. We'll also introduce in problem set 2 new this year TensorFlow. It comes with a bit of baggage, and you need to there's a bit of a steep learning curve in the beginning, but once you mastered it, you can put these models that we're talking about in the class together with a few lines of Python code, and then everything else will be automated. So this lecture will go through what's actually happening in the back end of a library like TensorFlow, but then you don't actually have to do it anymore because it can be fully automated. So it's a really powerful tool. Problem set 2 is really the corner piece of the class, and for you the first step towards your class project. It's likely that a lot of you may reuse parts of problem set 2 also for your final class project. So start early on both problem set 2 when it comes out, I think next week, but also on the project. So if you're done with problem set 1 already, you may start thinking about the kinds of tasks that you want to tackle. So in terms of project types, there are roughly 4 that we often see. The first one is just applying an existing neural network architecture or model to some kind of new task that is relevant to maybe your research or just generally something that you find interesting. The second type, and we'll go over a little bit more in detail what this entails. The second one is to just implement a complex neural architecture that goes far beyond the kinds of things we covered in the class. So for instance, there will be attention or memory mechanisms, neural Turing machines, dynamic memory networks, more complex architectures, and that is definitely more advanced than the first type of project. The third one is even more advanced, which is to come up with your own new neural network architecture. I think you will soon have all the basic Lego blocks to start putting them together in new and creative ways, but it's also much harder because it kind of entails number 1 and 2. So in some sense, you put work on top of number 1 and number 2, so you can really only tackle that if you start early and you really want to get into the zone and work in this field a lot more. And then number 4 is quite different, but I know there are a couple of double E and stats majors and PhDs, and so that is definitely an option also, which is basically the theory of deep learning, looking at optimization, looking at saddle point problems, looking at better optimization techniques, or things like batch normalization and other kinds of complex and novel ideas on how to better optimize these non-convex functions that come out in deep learning. Yeah.
So for 3 and 4, you obviously have the very big problem of they're unlikely to work on a first pass. What happens in that case?
That's correct.
The deadline comes, and do you just report why it didn't work and what you would try next time?
Yeah, so I discourage most of you from 3 and 4 for exactly this reason. This is really, if you're a PhD student and you really want to get into this field, then you might want to do this, but they're very high risk, especially if you come up with a new neural network architecture and you don't do it well, as in you don't start with project number 1, project number 2, and you implement something to show that you did some work, and you just try to start playing around with models and none of them work, and you don't come to office hour and I can't give you any feedback. And in the end, it basically is unclear whether your code was entirely buggy, whether you ran anything, because none of your numbers actually work and none of your code produces any reasonable results. So that will not go very well. Likewise, if you say, I tried to prove something really hard and I just happen to not get anywhere, it's tough to grade that and give a good grade. So this is, especially number 3 and 4, I would only encourage you if you're really in the zone, you're at least a master's who wants to go to a PhD or already a PhD, and you want to deep dive into this, no pun intended. Especially in those, I would encourage you to come to office hours very frequently, especially to my office hours. Yeah.
Will your project be related to natural language processing?
Yes, so most of these number 1, 2, and 3 ideally are. So, and I'll walk you through what doing just number 1 would entail right now. So basically, you start with defining a task that you want to solve. So let's take, for instance, summarization. It's a little more interesting, less common than classification, which we'll cover it a lot. We'll cover it a lot in class. So that's step 1. Think of something that you're actually excited about and that you would like to have a deep neural network do automatically for you. Then step 2 is define your data set. And we give you extra credit also if you're able to define your data set and run a first experiment before the milestone deadline, because we know it's often very time intensive. It's not very hard, and so it doesn't get you that much of the credit for the class because it's not really related to deep learning so far, right? Defining a task in a data set, you can do that and not implement anything that we learned in class. But if you understand everything you learn in class and then you get stuck on this, you also can get a great grade. So start early to define your task, come to office hours, and I'm happy to chat with most any kinds of tasks that you can think of. There's probably a data set that somebody has already tried to tackle this task with. So there are 2 options for defining your data set. The first one is you can just take an existing academic data set. So for instance, for summarization, there's a document understanding conference, and they already have nice baselines. There are papers published about those academic data sets, so when you implement your model, you immediately know whether you're onto something, you basically are pushing the state of the art, or whether you're far behind simple baselines and you may have a bug, or you may not understand the problem very well, and so on. So that is, I think, the best thing for most students. Now, the second option for defining a data set is much harder because if you define your own, you create your own, you write a crawler for Reddit. 1, it takes a lot of time. 2, also has nothing to do with deep learning, so it's hard to give a great grade for writing a crawler for Reddit data or Twitter data or any other kind of data that is online. So I would only encourage you to do this if you're a graduate student, you already have a data set maybe from your research, or you're working with a professor already and you have some interesting psychology data set or finance data set or natural language processing, ideally, kind of data set. And so in our case, for instance, if you wanted to build a summarization algorithm, you might say, well, I'll download Wikipedia and I'll try to summarize the Wikipedia page, the entire page, from just the intro paragraph, or the other way around. From the entire page, I basically produce the summarization that is just the introduction paragraph. And then I write a little crawler, Wikipedia has a nice data set in that you can just download it in its entirety, but it's also very big, so you need to have a big machine, and that's a problem that you'll run into a lot. As you define your own data set, you'll need more machine power. And then you might pre-process your data, and you've tried to, in the end, get a proper input, output data set. Your creativity is really, there's no bounds here. We have some people who asked already about music data sets, for instance, generating lyrics, or other kinds of things. Or you can really come up with any kind of sequence data set that you want. In fact, I'll also be very lenient when it comes to the definition of language. So if you have the language of music or the language of genes, as long as you use the kinds of models that we cover here in the class, I'll be okay with that. But if you don't have an obvious NLP task and data set, do check with me to make sure it makes sense in the office hour. It'll be again today for 2 hours, starting at 4:30. All right, now you have your data set, you have your task. The next step will be to define your metric. That is also an easy pitfall. If you have, for instance, a data set that's very skewed, let's say you have a simple binary classification problem, but in your whole data set, 95% of all your data points are in one class. And now your metric is accuracy, which is just total correct divided by total number of data points. Then you would get 95% accuracy by just giving the majority class every time. So that will also not be great, because that shows me that you weren't close to your data and you didn't carefully analyze the distributions of your labels and what your data set is like, and you chose the very wrong metric. And if you ever submit a paper like that and you're unlucky enough that the paper gets accepted, it would kind of ruin your reputation in the eyes of a lot of other researchers if you made that kind of mistake. So it's very important to choose the right metric for your task. So in this case, does anybody know what you would use as a metric if you had a very skewed data set distribution?
You would use your F1 score.
That's right. That's right. You would use F1 scores, which I think we'll define later on in this class too, instead of accuracy. So for summarization, what is very commonly used is Rouge or Rogue. It's a recall-oriented understudy for gisting evaluation. It's interesting abbreviation, and which basically defines n-gram overlap. So imagine your algorithm generates a summary of some larger text, and you have humans that generated summaries of larger text. Now you basically look at how many n-grams overlap between your automatically generated summary and the human summary, or multiple summaries. So that seems like a reasonable metric to capture how well your summarization algorithm works. Now, step 4 is to properly split your data set. It's also a very common mistake in any machine learning project, and it's very important to not make it, which is you want to take, let's say you have 10,000 training data, training examples, you want to split them into a train, development, and test split. And sometimes the def is also called def set or development split. And basically, a reasonable split would be 80% of your examples will be used for training, 10% will be used for development, testing, and then on the remaining 10%, you only evaluate ideally 1 week before the final project is due. Maybe you're okay with testing it once a week. And you really shouldn't test more and more often on your final held out test split. Now, even in splitting, there are some mistakes that you can make. So for instance, if you have a lot of things that are very similar, but then they change over time, and you want to understand the test set ideally gives you an idea of how accurate your algorithm would be in the real world, where you just took another couple of random Reddit messages or tweets, and you now evaluate your algorithm. So if your test data looks very similar or it has duplicates, for instance, in your training data, you overestimate how accurate you would be. So you want to make sure there are no duplicates in your development and test data to your training data. And if you had a time series, for instance, the best thing would be to actually take out the last month of your data and have that be the test data. So you train on 10 consecutive months, then you have the next month be your development, split, and then the next month after that your test split. That way the algorithm would give you your results will be very indicative of what the performance would be in real life. So there's some mistakes that you can make here, and what I encourage you in many cases is to be close to your data. Do look at what your data set looks like, look at some examples. If you have the report, show some examples. You know, you're doing sentiment analysis, show some of the interesting sentences that you have. You do summarization, show us in the project report, and look at yourself, like, is the algorithm, would this even be possible to predict this from your inputs? And show us as graders also how hard your task is by just looking at real examples. Are there any questions around splitting your data set and defining your metric? Yeah?
Around what size of a data set should we strive to look for?
That's a good question. What is size is good? It kind of highly depends, largely because your output space can be very different. So far we've only looked at classification. If you only have binary classification, then maybe having, starting at 1,000 examples per class starts to be reasonable if the task is not super hard. Not all training data is equal. Ideally, you'll have a distribution that is somewhat indicative of what your final testing distribution is like too. So if you have, for instance, you have 10,000 training examples, but again, 99% are in one class, and only the last percent is in the other class. That's not that helpful. In fact, then you could have another 1,000,000 examples of the majority class, and it's still not going to help you that much to find that really rare class. So, and then there are other tasks like summarization that are much harder, or machine translation, which is probably one of the hardest tasks in NLP and requires the largest amounts of training data too. And there you start to going into the gigabytes, basically, like a lot of training data, because machine translation is such a complex output space, right? It's the entirety of the target language that you're trying to translate into. So, but roughly once you have 10,000 examples of something and the distribution of your labels is not totally skewed, you're usually in good shape. Cool. All right. I think we have 4 more steps or so. So the step number 5 is to establish a baseline. And that's especially important if you have a new data set that nobody else has worked on yet. But it can also be helpful, even if it's a publicly available data set, to just make sure your training split is correct and you can replicate roughly baselines from the literature. So these can be very simple models. You can download open source packages like scikit-learn. We don't really care that much about how you get to those baselines. In many cases, like logistic regression for unigrams and bigrams, if you have a classification problem, for instance, are fine. But basically, establishing a baseline helps you to make sure you understand you have properly split your data set, you have properly defined your metric, you're using now properly your development test set and not your final test set. You don't just look at your training accuracy, which will often be very high, especially in deep learning, but also in standard methods. You can already know, you can analyze your errors, you can visualize what is the baseline actually getting wrong, so that it might give you some intuition of how you want to design your deep learning model to improve over the mistakes that the baseline makes. And then you may get into the somewhat lucky stage if you're just an industry and you're just trying to solve a problem to make some customers happy. But in our case, it wouldn't be that ideal. If you just implement your baseline, you collected your own amazing new training data set and some interesting task, and now you basically run the baseline and it just solves it. It just gets 100% or 99% test accuracy. At that point, you probably chose a task that was a little too easy. And if the task is really interesting, then let's chat during office hour, and maybe it's okay. But in most cases, you either made a mistake, you have a lot of duplicates in your test set that were already seen in training time, or the task is just way too easy. and probably a very simple method would suffice, and then it doesn't really make that much sense to implement a fancy deep learning model. That's likely going to take a lot more time because you can't really improve that much over your baseline. Then we finally get to the actual stuff of the class, and this is why you want to start early on these projects, because to do really well, you want to have enough time at the end to actually spend on steps 6, 7, and 8. So now that you have established your baseline, you have your task, you can basically implement some existing neural network model, likely one, for instance, that we used and introduced in the class in one of the problem sets. Then you can, again, compute your metric on your training and your development splits. You can analyze the outputs and the errors, and that's kind of the minimum that you should do for the project. It's really the bare minimum, though, because really what this means is you can just run problem set 2, the code of problem set 2 on some new data set, and just rerunning problem set 2 code on some existing data set. It's not that exciting, but that's sort of the minimum bar to pass if you take the class like pass-fail or something. Now, once you've run this, again, be very close to your training data. Oh, I have a question? No. You're always close to your data set. Visualize it. See, you can, for instance, visualize the label, the distribution of the labels that you have. You can visualize just some examples that you see. You can look at a confusion matrix, for instance. And especially, you want to look at the errors that your model is making, because that might give you some intuition of what the model might be missing, and then you can improve it in step 8. And very importantly, also, you want to analyze how the different hyperparameters affect your performance. So these are all sort of standard things that we will check off as we look through your final project report. So I encourage you to go through these steps in your project. So for instance, we already know a couple of hyperparameters like word vector size. The hyperparameter could also be size of your training data. And what you'll often observe is that as you increase your training data set size, the accuracy also will improve. And sometimes it will improve more than all the things that we could do on the model side. Any questions on how you can be close to your data or establishing your baseline? Cool. So now we come to the most exciting part of the project, which is to try out different model variants that you may have and that you may have thought of based on the errors that you've seen in your simpler neural network models. And you can already start, but really starting in the next, by the end of next week, you'll have a lot more options all of a sudden on what you can try and all the different, how to put together the different Lego blocks. So for instance, we've already seen the word vector averaging model, also sometimes called the neural bag of words model. And we've looked at the fixed window neural model. But then starting in the next lecture, we'll actually get to recurrent neural networks. And then in the weeks following, we'll have recursive and convolutional neural nets. And I think recurrent neural networks are really the best default model for a lot of NLP tasks. And so that's why we're focused on that a lot during in problem set 2. In TensorFlow, we'll have a special lecture on just recurrent neural nets, and then advanced recurrent neural nets, and one on TensorFlow for recurrent neural nets. So hopefully you'll be all very familiar in the end with those, but also understand the trade-offs between these different models. Cool. All right, now the advanced, just one slide on the advanced option of trying to create a new model. The tricky bit with that is that really the ideal way to do this is as essentially step 9, after you've done all the previous steps. Because it doesn't make sense to implement some new fancy model if you don't know that on that task, a simple baseline or a simple neural network would already solve the task. So you first really want to gain intuition of why all the existing models are flawed for the kind of data set that you have. And there is a bit of a shortcut here, or cheat in some ways, which is you look at the literature, and we'll show you a couple of papers here that essentially do this for you. So if you look at, for instance, sentiment classification, I have a bunch of papers. We post a couple of them on the syllabus too, and you'll see, oh, people have already tried all these different baseline models, so you don't have to really restart there from scratch. But we'll never penalize you if you do. So I still encourage you to look carefully at those baselines. If you want to do this, ideally you will talk to other researchers. Don't try to do it all in a vacuum by yourself. Definitely come to my office hours. I usually the last half hour, so it gets pretty empty. So there's plenty of time every week. You want to implement your new models and then very quickly try to iterate over ideas. So machine translation, for instance, as much as it's a really great task, it's probably not the right task for this class, because generally experiments in machine translation, even if you have a very sophisticated implementation on a GPU, it will take around a week to get one number and run one experiment. So if your data set is very large, the larger it is, the less quickly you can iterate on your model. So you want to set up some efficient experimental framework. We'll help you starting next week in setting up TensorFlow. We actually got the Myth cluster to have TensorFlow installed now, so we're happy about that. We're trying to get it on the Rai cluster too, which has GPUs. And we'll help you also set up AWS, so Amazon's Web Services. So you can, in theory, run on 100 GPUs, but each GPU machine costs, I think, 65 cents an hour. So don't go too crazy if you want to do that. Of course, if you work with a company or you're an SCBD student, you can do whatever you want, but we can't really reimburse all the AWS costs. So though I do think every Stanford student actually gets $75 for free of AWS credits. So if you haven't used that yet, you can definitely make use of that extra resource and essentially launch a couple of extra machines. And I think those are all, it's a little bit of extra work for the TAs, so thanks to the TAs for figuring that out. But I think it's a very useful task nowadays in the world to be able to understand how you set up essentially a new computing cluster for yourself, right? And if you don't go too crazy, you don't have very large machines, and you don't let them run for many weeks, it's a pretty cost-effective method to just get a couple of GPU machines, run some experiments in parallel. All right, so always start with the simpler models and then go up in the complexity of your model. So for instance, for summarization, we may start with a very simple average word vectors in a paragraph, and then just do a very greedy search of trying to find like what word to predict next, for instance, something very simple. Then we might implement a language model where we try to predict the next word, or an autoencoder, which both of these models will introduce later. But basically, you can start with something very simple in almost all the tasks, including sentiment analysis. Just average all the word vectors and try to predict something with a deep neural network. And then this one would, for instance, be a fun sort of stretch goal or extra bonus point question if you want to have one of the top sort of projects of the class, and you could try to actually generate the whole summary instead of just kind of greedily selecting words for the summary. And that would be very hard. So you need a lot of training data for it and so on, but people are able to generate sentences with deep learning models, and we'll cover how to do that starting in the next lecture. Cool. Are there any questions around general project steps?
For the baseline, you give the example of just regression. Should we tune? Like, should we optimize the hyperparameters, or is that no longer a baseline?
Baselines should always ideally be tuned, and they should be given the same TLC or attention as your own model. There's some people who often say that if you read papers in the literature, you should always implement the second best model, because that probably didn't get as much tuning, but it still works almost as well or close to the best model of the paper that the paper usually introduces. So it's definitely good to at least try like unigrams and bigrams and a little bit of the regularization, for instance, and a simple sort of bigram logistic regression model. Definitely that is very encouraged. Great question.
So we talked a lot about tasks such as named entity recognition, summarization, sentiment analysis. Are there any other interesting tasks that might not be as popular but might just as well be interesting?
Absolutely. So there are tons of interesting problems out there. I often talk about these just for sort of educational purposes. They're easy to understand, and then we can focus on the underlying models, because then the underlying models are general and you can apply it to any other task. So here are a couple of other, well, including those, but also some other tasks. So there's named entity recognition, which we just talked about, and summarization. There's simple question answering. This is actually a really fun data set, and it's now also a challenge that people are running, where you basically try to predict simple facts. So who was the president after George Washington or something like that, and just you basically try to predict that out of a large set of possible entities. It's a very fun task, and one that hasn't been worked on as much, but Mohit and his collaborators have developed lots of different baselines for it, and so you can really see if you can do something interesting there. Image to text mapping or generation is a really fun task. If you've taken 231N and you already know how to take a convolutional neural network and get a vector representation of features for an image, then you can also train a model to try to map images and sentences into the same vector space. Again, the simplest model, for instance, would be you just take your word vectors, you average them, and you use the max margin objective that we'll cover in today's class, and you try to have them be close to each other, or have a large inner product of the sentence that describes an image versus sentences that don't describe an image. That's a really fun task. I think one of the coolest projects last year was actually people who had a real life camera feed. You could point it at stuff and it would just output what it sees in natural text. That's a pretty cool project. But there's also they even got an exception to have 3 people on the project because it was a pretty ambitious project. And I think the 3 of them were all PhD students, so no worries if you don't have a live demo like that.
What do you mean by image to text mapping? So you take the image and it maps it into the same word embeddings that we saw a couple lectures
That's right. That's right. So you can co-train 2 models, 2 deep learning models, and don't worry yet, we'll cover all these kinds of models that you would use for this in the next couple of lectures. You can also just take the model and then train a recurrent model to predict the description. Entity level sentiment is a really fun twist on general sentiment. So the difference between general sentiment is you just say this sentence is overall positive or negative or neutral. But entity level is a little more interesting. You might have sentences, for instance, such as, I thought the iPhone was better than the Android. And now it doesn't really make sense to say that sentence was overall positive, because it was positive for one phone but negative for the other phone, right? Or you might say, the acting was a little silly, but I love the story so much that the movie was overall pretty good. So now acting is negative and movie is positive. So that's kind of entity level, the task of entity level sentiment. There are unfortunately not as many great data sets for that task, but it's a really interesting task that a lot of people in the industry care about a lot, like going through Yelp reviews and extracting different aspects of a restaurant and then basically enabling you to search for the best atmosphere, maybe not the food as much because you don't want to eat that much anyway or something like that. And then most tasks on Kaggle, I think that question already came up in one of my office hours. Can you use Kaggle datasets? Absolutely. It's great to use Kaggle datasets. Kaggle is a machine learning competition website where basically companies or sometimes universities upload datasets, and there's a nice leaderboard, and you can see exactly how well your model does compared to hundreds of other groups that all try to tackle that task. And I don't know if there are any competitions that are going on right now that actually have a deadline that fits with the class, but of course if you win a Kaggle competition, you have a almost guaranteed pretty good grade, because it's very hard. And usually they come with like a huge pile of cash too, so they're quite fun. And then I've been asked for sort of a default project, and one of those would be sentiment analysis. We've covered it a lot in class, and this is a data set that I had introduced during my PhD. Hundreds of researchers have since worked on it, and it's basically a very nice, clean data set. It has a train def test split already. It's harder to mess it up. So if you are kind of busy and you just want to get a passing grade, and you don't want to think too much about some creative task in the world, this is a reasonable data set that has clean labels. You know it's going to be big enough to train deep learning models, and it's just a very simple thing. It's hard to do something really impressive on that data set just because hundreds of people have already worked on it and pushed the accuracy pretty high, and it's very unlikely you'll be able to even get to that accuracy by re-implementing a lot of the state-of-the-art methods, because even just replicating some of these top models is a lot of work. So it's not like the most exciting project, but it's it's a reasonable baseline project. Cool. All right. So that was all about the projects. Any more questions about projects? If you can't make my Monday office hour, just shoot me an email. We can try to figure out some other way. I really encourage you to come to office hours. Cool. All right. Now let's get to the hardest and most exciting bit. I think after this, a lot of deep learning will kind of lose its mystique or magic, and you just realize, wow, I just need to keep track of indices and know the chain rule really well. And then I understand all these crazy deep learning papers, and I could implement them from scratch myself. But it's not going to be easy, so let's get to it. All right, so let's take the basic idea of the window model, where we wanted to basically classify the center word here. And let's, for now, assume we just have a very simple binary classification problem where we want to say, is the center word a location or not? Now, towards the end of the last lecture, I introduced the single layer neural network model that basically just had a single linear layer followed by a non-linearity. And remember again, f could be a sigmoid function or tanh, any kind of squashing function. The simplest one that we've looked at in the class so far was the sigmoid function. And we now basically call A here our neural activations. And we can use that feature vector now instead of the original window, which was the concatenated word vectors here in X. So again, X is the definition here. For a single window, we usually just use it X to define the concatenated word vectors of that window. Multiply it by a matrix W. The number of rows of W is the number of hidden units that we have, and basically defines the dimensionality of our neural activations A here. So those can now be seen as our features. And now what we can simply do, instead of computing a softmax probability, is we can just use compute an unnormalized score with another inner product here. So just basically summing up, having a weighted sum here of our features in A. So that's just a single number, and that's our score. And if that score is high or above 0, we'll say this is a location. If it's low, below 0, we say it's not a location. So that's our straightforward model. Now let's visualize what this model would look like. Here again, we concatenate all our words. Let's say, for instance, each word is 4 dimensions. Each bubble here basically represents a single number. Then we often write a layer like this. Sometimes you also see connections to all the different nodes, but that gets pretty tedious and messy looking once you have a realistic number. And even with such a small number, it gets very messy. So sometimes you just abbreviate all these connections with a single arrow. And then we have just a single score. And again, you might say this is a 3-layer neural network or a 1 hidden layer neural network. Now, one thing that will be very important is to always define what the dimensionalities are for all the different parameters that you have, your hidden layers that you have. And so we write this out very carefully here. For instance, X is a column vector, so 20 by 1 vector. If we have 8 hidden units, then W has to be an 8 by 20 matrix, and then U has to be an 8-dimensional vector again. sometimes I like to write out the score function also as like one entire function, which will help you sometimes to think about the chain rule a little better. But we can also define intermediate terms, because that will enable you also to know exactly which parts of the chain rule to define properly. Yeah.
So in the second row of the picture, we have 8 circles. Do those represent Z or F of Z?
That's a good question. Usually they represent f of z. It's the final thing. And then, but we'll also, I think in one figure, I'll split it up so you can kind of see how the errors change as you go through the network. Okay, so the main intuition, just on a very high level, of why we might want to add this layer and not directly train the classifier on the word vectors themselves, is that we might want to have nonlinear interactions between the word vectors. So for instance, museums, if museums is the first vector here in this window, should it matter that in is in the second position? That's the kind of feature that you can learn once you add an extra layer in between. If you don't have an extra layer in between and you just classify directly, then basically it just says, if I see this kind of word at this exact location, then it's either, you know, indicative of a location or not. But if you want to actually have combinations of words that are captured in the window in specific locations, then you need to have a second layer. Cool. All right, so let's summarize the feed-forward computation of this first neural network and with this example here. So let's say we have, for instance, a window. We go again through the windows, just like when we train word vectors. We go through the windows and we say we have a correct score whenever the center word of that window is indeed a location. And we were going to want to maximize this score here. And now that's basically just giving the algorithm positive indications of these things should be high. But if you now optimize only scores to be high when they have a center word, then you only basically, there's nothing that would prevent the model from just making all the weights very, very large and giving high scores for everything. So you want to always counterbalance and teach the algorithm with negative examples as well. Now the question here is, how do you create negative examples? Well, that it's usually very easy, which is you just take a bunch of windows that don't have the center word as a location, and you'd have those as negative examples. Another option could be you corrupt the existing window and you just say replacing the center word with a random word. So for instance, museums in playing are amazing. So just some random word like a verb, and then you'd say that would be my corrupted window, and I want to lower the scores of that. So now to put those ideas together, for each window, we will have this main objective function. Basically, the idea will be to make the score of the true window S to be large, and the one of the corrupted window lower. Hence, if we minimize this, then S will get larger, and SC, the corrupted score, will get smaller. And now this idea here is a really powerful one. We'll see this kind of objective function a lot during this class. It's essentially a so-called max margin objective, where intuitively here, after you train for a while, your model might realize, like, I have moved to something that's always a location. And you don't need to teach the model again in the new window that to increase the score of that window, because it already knows how to do it after having seen a couple of examples. Now what this model, this objective function will essentially help you do is that if the score of this correct window is indeed already one higher than the score of the corrupted one, then you will just switch to 0 here. So intuitively, for instance, let's say you ran through this computation, your final score for this museums in Paris are amazing is 5. And you take some random other window, such as not all museums in Paris. Now museums is not a named entity location, and that scores only 0.5. Now you take 1 minus 5 plus 0.5, and that overall is smaller than 0, but your objective function basically takes the maximum of these two numbers, and the maximum here would then be 0, and hence you can ignore that window. So that's one really powerful advantage of having the max margin objective versus the softmax. The softmax does the same computation and the same training every time, even for examples where it's essentially done. It's already doing the right classification during SGD, during training. But here, after a while, you can stop doing backpropagation on examples where the model is already very certain about getting the right answer. So since this is still a continuous objective function, we can perform stochastic gradient descent just like we do with the softmax. Okay, intuitively, you can also think of the max margin to essentially try to define a better decision boundary. So if you have, for instance, two word vectors, if you have two word vectors, and let's say you have a positive example here and a negative example here. Now, there are lots of ways you can try to compute a decision boundary to distinguish one from the other. You could, for instance, say, this is my simple linear decision boundary. Of course, that's not a very robust decision boundary, because if you now have just another example here that's also in that class, then that would already get misclassified. So intuitively, what you do when you have a max margin objective function and you have these kinds of examples is you try to maximize the distance between the two different points from your decision boundary. And you want to make sure that that is at least 1 until you stop caring about that example. Okay, now there's no magic here. We'll basically just take derivatives now of this kind of function in order to optimize this neural network with the max margin objective function. Are there any questions so far? Okay, so that is just the objective for a single window. Now you could sum over several corrupted or other windows that aren't in this true class. So you could sum here over a couple of different random windows that aren't right. And of course, in the end, you're going to sum over all the training windows to compute your complete objective function. But in SGD, we're going to subsample always a small batch. All right, any questions? Okay, so now let's go into backpropagation. So this is basically our main function, and we only have to really look at scores and derivatives when the cost function for that window pair is actually larger than 0, right? Again, if it's this part is smaller than 0, you just jump to 0, and there's nothing to take derivatives off. Derivative with respect to all our parameters of 0 is just 0. So now we'll compute the derivatives of the score S and the score of the corrupted S with respect to all the involved variables that we have, which will be U, the final scoring layer, W, the weight matrix of our first hidden layer, W, the bias B, the bias term, and X, our word vectors in that window. Now, because S and SC are basically the same, I'm just going to go over S, and you just basically have negation in front of these two to differentiate the two. So let's start with the first derivative of S with respect to U, our final scoring layer. Well, that was quite easy. It's just a simple inner product. In this case, A is just a fixed constant because there's no parameter inside that we're trying to compute the derivative for. So the derivative of S with respect to U is just A. That's the simple one. Now let's look at the weight matrix W, which starts to get a little trickier. So let's write out very carefully what the terms are. So this is something that I sometimes do just to show you sort of what the terms are and how we can play around with them, and to make it very clear that while we might write A here, really A is defined in terms of f of z, and really z is defined as wx plus b. So it's very important to keep track of when you define variables that actually have other variables inside, or parameters that you're taking derivatives with respect to. Now let's look at a single weight in that entire weight matrix W. Let's look at the single weight Wij. Now you remember, for instance, for W23, that's basically in the second row, the third column. That's the element of W23. And we also remember that at every neuron basically comes from one row of our W matrix. So the first row of W defines the weights for the first neuron, and the second row of W defines the weights for the second neuron. And here we'll have, just for illustration purposes, a very, very simple neural network where we have just 3 input numbers and our bias term B2, and we just have 2 hidden neurons and the final score function S. And so when I write U2, for instance, the sub-index here is just the second element of the vector U. And W23, for instance, is the weight that defines how important the third input is for the second neuron, and how much we weight that element, for instance, of a work vector. Any questions so far? Cool. All right, so let's take the derivative with respect to Wij. So let's write out very carefully what that final score actually is and how we computed it. So each step here is very simple, but in the end, when you look at it sort of from afar and you just spaced out for 2 minutes, you're going to be like, oh my god, what just happened? So we have to look very carefully at each step, because each step is indeed very simple. So remember here again, we just have our chain rule. So if you have, for instance, some function y that's defined in terms of u, you just basically compute this product. So now let's look at our chain, the application of the chain function to this. So Wij of u transpose A. Well, u transpose A, we really don't care about u1 and a1, because we know that W23 doesn't even appear in any of these parts, right? The parameter W23 only appears when we look at A2, if we look at W23, for instance. So in the general case of Wij, we really only need to look at the ith element of the hidden vector, A. So let's look at the derivative, the partial of ui times ai with respect to Wij. So, well, ui is just a constant in this case, so we can just pull that out. And then look at the derivative of ai with respect to Wij. Now, ai was just defined in terms of zi's, so we can apply the chain rule here and basically write out what this means, which is the derivative of ai with respect to zi times the derivative of zi with respect to Wij. And again, we know that zi was defined as just the ith row of w times x plus bi. We also know that ai was just basically equal to f of zi by definition, so we can plug that in here. And for now, since zi is just a single number, what we can simply do is just write f prime. Whatever f is, it will have some kind of derivative. The sigmoid has a derivative. I think you'll derive it in your problem set. It's very simple. And so we just write for now f prime and keep that general. And then we have the derivative of zi with respect to wij. And again, we just plug in the definition of zi, which is this simple inner product here with this row vector times this column vector with respect to wij. So let's copy that over. And now when we just write that out very carefully, this is basically just an inner product, so it's just a sum over the dimensionality of how many columns we have. So let's say we have k equals 1 to capital K columns. We just basically multiply these two numbers with one another. I have this weighted sum here. And now again, we know that from the first lecture when we looked at the word vectors, the derivative of the sum is just a sum of the derivatives. And really, wij only appears when k equals to j. All the other ones are constant as well when we look at the derivative of wij. I'll let that sink in for a second. Okay, so now that we basically, the derivative of the sum with respect to wij is just xj. Now here comes the first and important trick of backpropagation, which is we will define a delta, which sometimes is sort of called the local error signal, or just some people kind of confusingly call it error message, but really it's just the best terminology for this is the local error signal. And so we'll define delta I as just this simple product of ui times f prime of zi. And xj is just our element of the word vector here, and we'll call that our local input signal. And here's just one definition, for instance, for f prime if we use logistic function, often abbreviated with sigma. And we'll notice here that very conveniently, f prime is actually can be computed in terms of f of z. Why is that nice? Well, that means we don't have to compute a completely new function with the exponent during, when we take the derivatives. Because this kind of function is much easier and cheaper to evaluate than if we had to run another exponent to have another complex derivative. And in many cases, the kinds of nonlinearity functions f that we'll use will actually be computable. The derivatives of the functions f will be computable in terms of just f. Okay, so far I haven't really given you any reason of why we defined this term here with a new special variable called delta. But it'll become very apparent when we realize, well, instead of wanting to just compute a single weight, ideally we'll compute all the weights of all the different wij's. And so the question here is, what could we do if we wanted the combination of I equals 1 to 2, the two hidden neurons here, and j equals 1, 2, and 3 for our three inputs? What would be if, let's say, those two were, for instance, vectors, where we have delta I for I equals 1 and 2, and we have that as a single vector? How could we get the combination of all the partials? Outer product, that's exactly right. So the derivative of j with respect to w here, assuming j was larger than 0, will just be delta times x transpose. So if this is a column vector and this is a row vector that we transposed, then we'll basically get the nice outer product. So it's a 2 by 1 times 1 by 3 vector, and then we'll have exactly the right dimensionality of a 2 by 3 matrix. And so another terminology for delta is the responsibility, or again, error message, coming from each of the activations of these neurons. All right, so this was all the gory details of the first layer. We'll get into 2 more gory details, and after that we'll just kind of zoom out for the rest of the class. So now is your time to ask some questions. Did all the steps here make sense? Were there any questions around over these steps? Yeah.
Is there any intuition behind why it's called local error signal?
Yes. So basically, the delta will kind of tell you how important was xi for the overall error that you make in your total objective function. So in our case, the score and the max margin objective function. So as you go further down the network, which we'll do in a bit, you'll notice that the deltas will get smaller and smaller often, because the changes will make less of a difference to the final error that you have, or the final objective function that you have. Yeah.
It looks like here, like x and e are column vectors, but in the homework they're row vectors. Is there a reason to prefer one or the other, or like
it's kind of an implementation detail. So Python sometimes, like NumPy, has a certain default. So the important thing there is just to make sure you print out what they are, and you make sure that you do the right thing. So there's no reason. I think there are, well, I guess in programming languages there are certain ways that vectors are stored, and matrices are sometimes stored as like column first or row first, and so there can be slight inefficiencies if you have to transpose it manually every time. Or
Given that, can we change our implementation in homework to match the math here?
Yes.
Even if there are inefficiencies?
You can always, as long as your math is right, you can always change the implementation and the transposes and all those things. Yeah. Yeah.
How did we go from partial S over partial W to partial J over partial W?
Oh, great question. So here we wrote S, but then here in the final thing I wrote J, and I just kind of mentioned it briefly, but I probably glanced over it too quickly. So here we basically note that you're actually right, it should be minus, because we have here a minus in front of it. But basically, when you take the derivative and you assume J here for this window pair is larger than 0, then you kind of can ignore the max 0 part, and then you just look at 1 minus S plus SC, and then derivative of anything with respect, like of 1 with respect to any of the parameters, this just goes away, and then we can basically focus on just S. But you're right that derivative of J should actually be minus S. Great question. But it's because it's linear and it's right there at the top of the objective function. That's kind of how we jump from one to the other. Great. Okay, so now let's look at the bias terms. So here we just basically have similar steps. UI, AI again, just defined as f prime or as f of zi. We'll apply the chain rule. We end up in a similar spot to where we ended up for the derivative partial of wij. And so, but now we're with respect to bi, we notice here, okay, bi is just basically 1 for this derivative, so we end up with just the delta term that we had defined before. Yeah?
You see that j is max of 0, 1 minus s plus sc. Here, sc is also a function of your W matrix and the U, right?
Oh yes, of course, you're totally right. So this is doubly wrong, and you're absolutely right. We really, I should have just written S here. So the overall thing, and I think we'll get to that actually in another slide, because really this is minus delta of xt plus delta c times xc. You're totally right. I'll fix that.
Are double the number of parameters, or are they?
No, they're the same. They're the same W.
Okay.
Yeah, because you don't at test time you wouldn't know which one to apply, so you always have to apply the same one. Very good. All right. Several of you are totally on top of it. All right. So now that was almost backpropagation, but it's not quite. We're not quite there yet. But really, what we've just done is take a bunch of derivatives and applied the chain rule. Now the remaining trick is that we can reuse the derivatives that we computed for higher layers for lower layers as well. And so in the simple one hidden layer neural network here, that will come up when we try to actually backpropagate the error that we have into our word vectors x. So let's do that in a second. And again, this reusing of derivatives, the simplest form here we've already seen here. To compute the derivatives of b, we didn't have to actually do any more computation, right? Because we've already computed delta to compute the derivatives for w. And so to compute the derivatives of b, we basically reuse the same delta, right? So no extra computation had to be done. And now it gets even better because we can compute or reuse all those deltas as we compute derivatives with respect to a single element of that. So let's take, for instance, the example here of the derivative with respect of s with respect to one of the elements of x. Now the main thing that we'll notice is, unlike before, where W2, for instance W2, 3, only appeared in one of these neurons, x2 actually modifies both of these neurons, right? And so we'll have to sum the derivatives as we apply the chain rule. So let's look at the example of derivative of s with respect to xj. So basically here we sum over our two neurons and apply the chain rule to both. We'll define here our the full score with respect to ai, and ai with respect to xj. Now we'll again just define what this is. This is again the simple inner product, so we can write that out very quickly as ui. And then we apply what the definition of ai really is. That was just again f of wi dot times x plus b. Now we'll apply the chain rule, we'll get f prime, and lo and behold, that's the same ui times f prime of zi that we've had before when we computed the derivative with respect to w. But now we have this other term here, because we still have x, and derivative of this inner product with respect to just one element of that inner product, again, is just that element of this row vector. All right, so now we basically have this sum here that is just multiplying two numbers. Now, if you're familiar with linear algebra, how could we rewrite this sum in terms of a vector multiplication or a vector matrix multiplication? Or maybe just for the simplest one, it's just a straightforward vector multiplication with a column or a row vector of w. Yeah? That's right, just the dot product. So basically here, the important part of the dot product though is that we're summing over I. So we have to take the column, the jth column of w, transpose it, because now it's a column vector, we want to make sure it's a row vector, so we define properly our inner product and it doesn't become accidentally an outer product or something, times, again, this exact delta that we've had, which is just our two-dimensional vector. So now the amazing thing is we were able to compute the derivatives with respect to x using that same delta that we used in the computation before. All we had to do was multiply it by this w. Now, this was just for one of the elements of our window x. What should we do to get the whole gradient with respect to x1, x2, and x3? That's exactly right, the full W transpose. So basically, as we have multiple of these inner products for each separate element of xj, you can just combine all of those, and here I did it right thing, it's just for s, the derivative of s with respect to x, it's just W transpose times delta. So we had a linear layer, just the x's are basically right there, and all you had to do to get to them is multiply with W transpose times the error message that we had before, or the error signal. And now this is a very important observation, and it's a sanity check as you do these derivatives yourself. the error message delta that arrives at the hidden layer, in this case the word vectors, has the exact same dimensionality as that hidden layer. If it doesn't, you couldn't really update it, right? In the end, you want to have, you know, your x in stochastic gradient descent, your x new equals your x old minus alpha, your step function times this gradient, right? So they have to sum up. All right, now I do the almost right thing, except this s should be j. So this is the full final objective function when we put all of these together. So we had here the gradients for s and for sc. This is sort of the indicator function. So if this part is actually larger than 0, then this is our final gradient. So we always have to sum up for the full sum here in our max margin objective. The a's, for instance, plus ac. For the derivative of j, this should be j here, sorry, with respect to u. So that's how we put it all together. All right, now let's get to the two-layer neural network. So very important to keep track of all your indices very carefully here. So let's define x as the first input layer, and just for notational convenience later, we'll define this as A1, the first activations of the first layer. Now Z2 will always be computed with the parameters of W1 times A1 plus B1, and A2 just defined as, again, element-wise application of the linear layer output Z2. And then we can repeat the same exact thing, but with C3, A3, and we'll compute our final score S with A3 instead of just A2. All right, now when we take the derivatives of W2, which is the output here, it's really the exact same thing as we did before, but instead of having X underneath it, you have A underneath it. But that's completely independent as we compute the derivatives with respect to W2, so we can really go over those pretty quickly, and we'll basically have the exact same output here, which is delta 3, very carefully now defining the delta messages also in terms of a superscript, which is the layer that they're coming into. And then, but basically the computation derivation here is exactly the same thing that we had before, but with A2 now instead of X. Now, again, we defined delta here. Delta here we'll define properly and very carefully as this Hadamard product. The Hadamard product is basically just the element-wise product between these two vectors. So this vector, each element gets multiplied by the element, the corresponding element of this vector. So this is our definition of delta 3. So now the last missing piece for understanding general backpropagation will be to take the derivative of S with respect to W1. And now if we wrote that all out, it would get pretty messy. I encourage you to do it at home. But it basically takes all the exact same tools that we just used and apply them very carefully, keeping track of all the indices. And the main thing that you'll have to compute is basically the error message or the error signal delta 2. And it's a similar derivation to what we did in the single layer model. But the main difference here is that you'll have to basically apply the chain rule twice, and you'll notice that you have to basically compute all these or derive all these different terms. One way that might help you is to gain some intuition is just to assume all these numbers here or all these parameters are actually just single scalars. That might help understand sort of how to apply the chain rule, and then you just kind of have to make sure you understand how to do it when they're all matrices. And intuitively, whenever instead of having a single number, you have multiple nodes at each layer, you basically have to sum over all those nodes. And so when you put these various things together, you end up with a delta error signal that looks like this. It's very similar to the one we just computed, but you have to have also applied the chain rule to the next layer down. And so it's going to be W2 transposed times delta 3 and then Hadamard product of all these elements. So this is a vector, and just multiply these element-wise. And so the final derivative will be, again, delta 2 times x transpose, the same kind of outer product that we've had before. And so in general, and these are sort of the two main equations, if you go through that extra step, and I encourage you all to do it, it'll be very useful for the midterm and all other kinds of places, and after that it has sunk in. You fully understand backpropagation. These two equations are the main equations of neural networks. Basically, how to compute your delta error messages, which will always, in standard neural networks, will be of this form. And then you update and compute gradients for all your matrices W here. And that will always be the outer product of these delta error signals times the activations of that layer. And in many cases, we add regularization to it as well. And so I think personally, I think probably half of you find this sort of very careful derivation intuitive, but I know that for some people it makes sense to look at and visualize this intuition a little differently. So here's one last way, really quickly before we end, of also thinking of how backpropagation works. So let's say we have this simple function here, or this two-layer neural network, and we've already computed our gradient with respect to W2, which was just the first delta message that came in here, times the activations of A2. And here we separate out the linear, the linear layer and the element-wise non-linearities that we'll define here as sigma. So F, in this case, is defined as just a sigmoid function. Now, what we're going to do is we're going to reuse, as we propagate the error back through this network, we're going to reuse this delta 3 and pass it through W2 by essentially moving this error vector across the simple affine transformation, this linear layer, by just multiplying it with the transpose of that forward matrix W2. And notice how the derivatives, the dimensionalities here exactly line up, because this delta had to have the dimensionality of this layer, and so when you transpose W2, you get exactly that dimensionality. And now, as we propagate the error through the nonlinearity, which was element-wise, well, what happens and what we need to do is exactly do a pointwise or element-wise multiplication with this local gradient that we now have of this nonlinearity. So again, we move through the affine transformation, we just have W transposed. Now we move the error through the nonlinearity that is element-wise, so we have an element-wise product here with sigma prime, or in our case, in general, F prime. And that now defines delta 2 to go down to the next layer. And so then we can define, again, the gradient with respect to this matrix as, again, just the outer product of that error message times the activations that come from that layer. Cool. All right. You survived the hardest lecture of this class, and I think next time I'll just start the first 5 minutes with another intuition visualization of backprop, but it'll just be chain rules again. So we'll just have one more visualization. Thank you. Hello everybody, and welcome to today's lecture number 6. Today will be a little more practical to get to really be able to tune some neural networks, and then it'll become even more practical with the introduction of recurrent neural networks. Those are super exciting because it's likely the method of choice for a lot of different tasks, and it will set us up to get to the most exciting and interesting models that people in research are working on right now. So I'll start with just another explanation of backpropagation, just to I know that sometimes different explanations work better with different people, and so I think it's good to just look at it one more time in another visualization, another explanation, and then we'll mostly focus on practical tips and tricks to really train a neural network in a way that will get us great performance. Are there any organizational questions about the problem set? Anything else? I was very happy to have had a lot of folks in the office hour on Monday. Again, I encourage you all to stop by. We can start brainstorming your project ideas, your data sets that you could work on, and so on. Cool. All right. So, backpropagation, yet another explanation. So, in general, we'll always want to just compute the gradient of each example with respect to our parameters. So, again, major piece here is just using the chain rule and not replicating computation. And in general, one really good theoretical property of neural nets is that whenever computing your loss for a given example and a set of parameters of your neural network is an O of n, then the computing the gradient is also going to be an O of n. So unlike kernel methods, if you're familiar with those, they can sometimes be quadratic in the number of examples that you have for training, and that would never scale to the kinds of data sets that we have nowadays that get into the millions and hundreds of millions. You could never train something that has quadratic complexity in a number of input samples. And so really it's about the chain rule. We will always have a feed-forward or fprop computation where we start with some input x, we'll compute some intermediate representation y, and forward propagation to get to some z, and then in backpropagation we just go backwards through that computational graph. And so if we just had a single parameter y in between x and z, then this would be the chain rule. In many cases we'll have multiple paths, and so when that is the case and we want to get through these multiple paths to a single input, then we will just sum up the partials here with respect to each of the intermediate inputs. So again, it'll just be the computation fprop and backprop, or forward propagation and backpropagation. And in general, as we have multiple of these, we'll have a general sum over all the intermediate nodes at the previous layer. And we can describe this as a general sort of flow or computational graph, which will be any directed acyclic graph, where at every node we'll have some computational result, and every arc will be some kind of computational dependency. And that will be also the viewpoint that we'll take in next week's lecture when we introduce TensorFlow to you. In TensorFlow, what you'll be able to do is just define any such computational graph, and many of the ones that we'll look at will be standard neural network type architectures. But the amazing thing is that once you define this in this form, you'll also be able to automate backpropagation. Yeah.
Does TensorFlow do backpropagation in an efficient way? Like, so like, let's say a logistic unit, does it do the logistic times 1 minus logistic? Or does it actually have to go through the whole equation?
So if for many of the basic Lego blocks, it does something pretty smart. So softmax, for instance, logistic regression and cross-entropy error, those are basic building blocks that it has where it does the smart thing.
Can you define the fast derivative of anything that you come up with?
Yes, but I mean, in general, it's an open source framework, so you can modify it, but it's like the more complex and the more out there it is, the more complex it will be to do it. But for almost all the computation that we look at in this class, you will be able to use TensorFlow as is. So even the most complex model that we'll get to sort of in the last couple of weeks of the class, like dynamic memory networks or neural Turing machine type networks, those can be implemented in TensorFlow quite easily. And so this is yet another visualization where we have some input x and y, a label y, and you can also write the computational graph or the flow graph in this kind of way where you include, for instance, your negative log likelihood here for your cross entropy, error computation, and then you will basically go backwards. You don't usually update your label, of course, the label y that we want to predict, but you go backwards through the graph in your derivative computation. So yeah, this is basically all of the neural net models that we'll capture. Some forward propagation, going in some topological sorted order through this computational graph and backwards. So far we've had some very simple two-layer neural networks, but if you keep this in mind and you keep the derivations in mind, then you will see how basically error messages are just basically being propagated through the network as you try to train it. In the exact same order, or reversed to how we computed forward propagation. And like I just mentioned, the nice thing is once you define your forward propagation in your network, and it's just simple matrix multiplications and things like that, or convolutions and other kinds of operations, you can basically completely deterministically infer how to do backpropagation. And because of that, we can have symbolic expressions that we define in these flow graphs, and then we can automate the entire training procedure. So last year, TensorFlow wasn't out yet, and so in the class I really asked everybody to implement these models in all their gory details to really get it. I think now we did that in problem set 1 because I wanted you to understand really what it means when we call backprop. But moving on, starting in the next problem set, a lot of this will be automated for you. And so with that in mind, also last year it was much more impressive if somebody took a complex recurrent neural network like the ones we'll introduce in next week's lecture and implemented it from scratch with just basic Python. Doing that in TensorFlow will basically be a copy and paste from some code on the web and just taking the standard TensorFlow implementation. So in some ways it ups all of your games, but it will also make it less impressive to just take a standard model and apply it to a standard data set, which will probably result also in just you being able to do more cool new models and applying it to new interesting tasks. All right, now despite that, we still want to understand how to really tune the models, and not everything, of course, is going to be automated. And so I'm going to go through a couple of really neat tips and tricks. Some are sort of more high level, like doing multitask learning. Others are pretty low level, but also very important, and they're going to be design decisions that you still won't be make automatically. So let's start with a very powerful technique, which we already kind of talked about a little bit, but only in terms of word vectors. So oftentimes we took word vectors, we trained them unsupervised based on the co-occurrence statistics, or the just general context windows, and then we took those vectors and we actually started another model, the window model, for instance, for named entity recognition with those weights. Now it turns out you can do the same thing, but not just for the word vectors, but also for other higher layers that you might use. So here, for instance, we may have our standard window model where we might want to compute the, again, named entity tags or sentiment or whatever, any kind of label you can think of for a specific word. And then we have, for instance, the softmax classifier. And now what we can do is we can not just share the word vectors X, but we can also share the intermediate layers between different tasks, and then only basically change the top layer. And so as you would train this, you'd basically take the softmax here and you have a different weight for this softmax, but you share the weights of the intermediate layers. So only you have basically the overall cost function or objective function will be the sum of the cross-entry pair errors for this classification problem plus that classification problem. And there will be some, okay, it really wants me to get on the internet. I'll get on the internet. All right. Now, you can think of how to implement this in a very efficient way. One inefficient way would be we just take the cross-entry pairs here, propagate it, and that's it. But when you think about it a little bit, and let's say you try to do named entity recognition and part of speech tagging, so trying to find, again, locations, organizations, and people names, but also understand whether something is a determiner, an adjective, a noun, and so on. And so what you'll end up seeing if you try to write all this out in the math and you try to see where is computation again being repeated, then what you'll notice is you can actually take the delta error messages that you get from one softmax and from the other softmax, and you can sum those up and then backpropagate both of them. In the end, this will again just be a computational flow graph that has two different outputs, but they come to the same input. And so you can combine the error messages simply additively. And I encourage you all to think through what it would mean having these two different softmax units on top of the same neural network, and then see where in your equations you notice that the delta messages can just be added. It's going to be a very useful exercise. So for word vectors and also some of this pre-training of higher layers, we can see here that that makes a big difference. So the previous state-of-the-art methods that weren't using deep learning, for instance, and these are two tasks that are very, very optimized. So hundreds, or in some cases even thousands of researchers worked on part-of-speech tagging on this exact data set and manually tuned features. And so if you just took a standard supervised neural network and you trained it, it got close but didn't beat human performance and human engineered features from over 2 decades in the case of part-of-speech tagging. And I think about half a decade or 8 years or so in the case of NER. But if you took the word vectors and you pre-trained those, then you actually got fairly close to the human engineered features, especially for named entity recognition. There's a big jump between just training on the task by itself versus training on the task but having initialized the word vectors from the unsupervised task that we described. And those word vectors weren't also the most ideal word vectors. We now have even better ones like word to vec and glove, and so there the results are even better. Basically all of these models are now dominated in terms of performance by neural network models. But just when the first deep learning papers came out, they still had to have a couple of handcrafted features. They're simpler, so you basically had special embeddings for part-of-speech tags, and you had so-called gazetteer features. Now, gazetteer features really sound like a cheat, but basically if you do named entity recognition and you try to find all the locations and people names and company names, gazetteers are essentially lists of states, cities, and countries, of which there are only finitely many. And so if you have an extra list of all the things you're trying to find, then all the model has to do is, in some cases, disambiguate. Whether it's this Paris, the person, or this Paris, the city. But it knows that Paris is, for sure, either a celebrity or a location already. So gazetteers are basically just lists of locations and people names and so on. And yeah, we basically, once they tuned their neural networks a little bit better, then in the end, this first paper, or extension of the first paper from 2008, so Colbert and Weston started in 2008 to really work on deep learning for multitask learning, for solving different kinds of tasks like part-of-speech tagging, named entity recognition, and others. And after they tuned their system a little bit more, they did indeed outperform some of the best methods out there. All right, now let's move on to some general strategies for training, successfully training neural networks. These are, I think, some of the good high-level steps that you want to repeat in almost every neural network project, and several of them generalize to any machine learning project. So the first thing you want to do is you want to select the network structure that you have. And so far we've looked at single words, which rarely is the end task that you might care about in the real world. Then you have the option to look at fixed windows. You often, when you can determine what you want to classify for a single word based on just the local context, then a fixed window is enough. It turns out part-of-speech tagging, for instance, it gets you to almost state-of-the-art if you just look at the 3 words before and the 3 words after. All the other context around a word is not that useful for part-of-speech tagging. It's a relatively simple task. But if you want to do, for instance, named entity recognition or harder tasks like semantic role labeling, where you want to understand this is an agent and this is an instrument and things like that, then it makes much more sense to take into consideration a broader context. So then we might want to look at sentence-based models. You can also look at document-level models, where you try to, for instance, have a bag of words kind of representation where you just average all the word vectors from a longer document. And then there's some other models that we'll cover later in the class, like recursive or recurrent or convolutional neural nets. Once you define those, often one sub-decision is what kind of nonlinearity you use. Sometimes for some of these models, the choice will be very clear. In others, you might still want to basically see this as a hyperparameter and then choose the right one. So let's step into the options for some of the nonlinearities before we go to the other steps. So far we've only talked about the sigmoid. The sigmoid is in many cases not the optimal nonlinearity to use. Just in terms of the optimization, it's not as good. Another better one that you'll see in more papers is the hyperbolic tangent functions, or tanh function. Oh, it's a bummer, it's very hard to see. But basically, it looks somewhat similar to the sigmoid, but it's not, instead of mapping numbers to be between 0 and 1, it'll map them to be between -1 and 1. And just like the sigmoid, what you observe here is that the derivative of the tanh can also be written in terms of just the tanh. And that will make the computation a lot faster. Because in backprop, remember we had at some point, we always have to have the f prime of z, our activations here from the linear layer. And if you can compute that with this simple computation, instead of having to take another exponent or sine function or whatever, it speeds up the computation significantly. And so you might think, well, there's not that much difference here, because technically tanh is just a rescaled and shifted sigmoid. So if you can get to the tanh with just multiplying by 2 the output of a logistic whose input was also multiplied by 2, and you subtract 1. So in theory, they should be fairly similar, but in practice, the optimization for tanh behaves much better. Now, what you'll see a lot in the future will actually be the rectified linear unit. So the rectified linear unit is a very, very simple nonlinearity that is basically just max of your output from the linear layer and 0. So this is what it looks like. Very simple, just linear and 0. So basically sometimes that unit is just completely off, and if not, then it's just a linear output. So just having this max function instead of a completely linear thing makes all the difference. It turns out that when you stack a bunch of rectified linear units, you also get a general function approximator. You can approximate any kind of function. And the beauty of this is that once you're in this linear regime, you won't have the so-called vanishing gradient problem, which we'll cover in a future class too. But basically, on a high level, intuitively, once you're in some of the regiment here, as you train more and more, the derivatives for both the tanh and the sigmoid are often below or smaller than 1. And then you're going to multiply in your backprop computation numbers that are smaller than 1 each time you go through your network. And as you go deeper and deeper in your backpropagation derivatives, at some point after multiplying numbers that are smaller than 1 enough times, the derivative is close to 0. And so there's no error signal that arrives at the lower layers. And the beauty of the rectified linear unit is really that it doesn't have that problem. Now, I think I've mentioned this before, but gradient checks are the most wonderful thing if you actually implement a new neural network architecture completely from scratch. Basically, whenever you think you have your forward propagation at least correct, then gradient checks will basically be able to guarantee you that you did not have a bug in your backpropagation implementation, which is rare for a lot of other kinds of machine learning models, like graphical models or others. So basically, all you do is you implement the finite difference computation by going through all the parameters of your network, adding and subtracting a small epsilon, and using the straightforward definition of what a gradient is, and then you can compare this estimated derivative with your derived one, and as long as they're close enough to one another, you can basically know that your computation and your derivatives and your implementation are correct. Now there's one small caveat to that. If you implement your forward propagation incorrectly, and then you make just the right kind of error in your back propagation, then maybe the two will cancel out and you still think it's correct. But in most cases, this will catch bugs for very novel implementations. Cool. Okay, now if you actually have a complex neural network model and you really want to understand all its details and visualize everything very carefully, and you implement your model, and now your gradient check fails, and it's just everything is wrong. Usually what you'll observe is you'll have your long theta vector, and sometimes only some of the blocks are wrong that come from different W's, different parameters of various layers. But sometimes everything is wrong, and you just don't know how to start, right? Because if you have one error in the top of your derivatives, in the top layer, and it backpropagates all the wrong things into all the other layers, then everything will be kind of wrong. And so one really great way to help you debug your models, both very conceptually but also just in terms of the implementation, is to create a very small synthetic model and data set. So basically you will simplify your model to the extent possible. Like you may start with the simplest thing, like just having a softmax on a fixed vector. Right? That's basically just standard logistic regression. You make sure that that is correct. And then you might say, all right, now let's backpropagate into the word vectors. Maybe you had a bug in how you derive, pull out the word vector from your general word matrix, word vector matrix. And then you train both jointly and you see if there's some issue with joint training. Then you might add a single unit in one hidden layer. And then you might add multiple units, then you add the bias term, then you might add multiple layers after that, multiple units for those layers. And at the end, you have one softmax on top, and then maybe if you want to do multitask training, you might add another softmax to the top. And that's basically how you can start from the simplest building blocks and then go on top. And this might sound rather trivial, but I wish I had known this when I started my PhD, because I lost weeks of time by not following these steps. So it's really useful. All right, so let's say you chose the right model for your task, chose the right non-linearities for your model, you implemented gradients, and the gradients are correct. Now you need to initialize your parameters. And parameter initialization is super crucial for neural nets. Basically, we covered this just briefly before in the class, but let's assume you have a non-linearity, and let's say you have the 10H, and now let's say this is just one unit. This is f of z. And now z here was just w of the, let's say this zi. You compute your activation ai. And zi was just wi dot. So that was already a row vector, so we just have this inner product here plus the bias term for the ith unit. Now, what happens if, let's say, your x numbers are all in the reals, and let's say each xj is somewhere between minus 100 and 100.
Can you slide the paper up a bit?
Oh, thanks. So, and your w numbers, wjk, is somewhere between, let's say, minus 1 and 1. And let's say your bi is, let's say, also crazy high, so b, I guess j here, or it doesn't really matter. bi is somewhere also between minus 100 and 100. Something crazy large like that. Now, what happens when you multiply just at the beginning of training? You haven't really trained anything, but this is how you initialized your parameters. Because you're crazy and we haven't gotten to it yet. So where would AI, come out at? Statistically speaking, roughly. sometimes. Worst case scenario. Let's say we have a 10H unit here. So F, so this is 10H CI. Now, where in the worst case would, at initialization, the first time you do forward propagation, where could they come out? That's right. Close to -1, somewhere over here, or somewhere over here. And so what's the gradient in those locations? Sorry again?
Close to 0.
That's right, it's close to 0. And so when that happens, and we can often visualize some very high dimensional, very complex function, then you might want to optimize this. Well, maybe you just initialize it here, and now it's basically already stuck and won't ever get to better local optimum that may have been down here somewhere. And because the gradient is already 0, it's already stuck. You can't even get anywhere better, right? And so that's why it's very important to initialize. To basically, the first thing you want to do is you want to make sure that as you initialize your parameters, that your x inputs are somewhere in a small range, and you normalize it. And especially if you use 10H units. And then you want to initialize your matrix W and all the elements Wij such that in the first computation you end up somewhere roughly in this linear regime of your nonlinearity. And you can visualize this too, right? You can initialize your weights, you look at the activation of the first layer after the first forward propagation, nothing is trained yet, and you can check what the numbers are for your activations. And if they are roughly in this linear regime, then you know that you're in this complex optimization, you are more likely to have initialized it somewhere here, and you might get to a much better local optimum. So it's super, super crucial. We'll come to, we'll have a special slide just on like how to initialize specific type of networks like recurrent neural networks, and it can make all the difference between your model basically not training anything and being completely useless, and you thinking, oh, it's the wrong model, why isn't it working, and like you getting a really good performance. And so people have looked at this a lot, and for instance, for sigmoid units, people want to often make sure, one, they initialize the biases to be 0, and then also try to have a mean 0, so you can normalize your inputs to have a mean 0 and a small standard deviation. And we often initialize the weights to be uniform between two small numbers. And often what people use is, for instance, the square root of 6 over fan-in, which is the elements, the number of units that are coming into a layer, plus fan-out, which is the number of units that are coming out of that layer. And really all it does is for sigmoid units, or for 10H units here, that you end up in that linear regime of your nonlinearity. Sometimes the numbers here are 4 times bigger when you have sigmoid units, and again, you just want to end up in that linear regime of the sigmoid unit. So just somewhere close to this area when you start your optimization. Now, a beautiful thing about the rectified linear units is, because they're just linear, you just want to make sure that they don't all start in the 0 part, where they're basically dead. You want to make sure they start also in a linear regime, but it's much easier to do for rectified linear units because you don't have the problem on the large values of the inputs. All right, any questions around initialization? So how do you adjust the weights if they're not like that? Well, if you start, you define what they are. So you can look at the visualization, and maybe you have some new type of neural network activation function, maybe you have something really interesting that you just want to try and see how it works, what you can always do is you initialize them to small random numbers between minus r and r here, and then you look at what the activation is in the first layer, and if it's too large, you just make r small, and that way you make sure that they get to be in the right area. Oh, for ReLU? So for ReLU is one trick to make sure that you end up not having them all be small is you can actually have the bias to be initialized also a little bit in a positive number. That way you start out for sure in the positive part of the value. And otherwise you still use relatively small numbers just because you don't want them to blow up like crazy. Cool. All right, so stochastic gradient descent. How do we actually optimize this? And those will also be hyperparameters and options for you in TensorFlow. So TensorFlow isn't going to automate everything. So these are all still really important tricks. So basically, we talked about general gradient descent, where you take the entire gradients with respect to your entire training data set. So full batch training is never the right solution. What we then looked at was completely stochastic gradient descent, where you might look at only a single data point, a single window, for instance, one at a time. And that is definitely the better end of the extreme spectrum. Again, never use full batch methods with neural networks where you compute the entire derivatives over the entire training set. You could sometimes use second order methods, but they actually have been somewhat out of favor. And what is much better are other techniques like momentum, which we'll talk about in the next couple of slides. So in very few cases will it be necessary to basically use LBFGS or conjugate gradient methods, where you may need to approximate the second order derivatives with a lot of computation. Now, what is really useful is to actually do mini batch stochastic gradient descent. So instead of looking at a single window, which is on the one extreme, instead of looking at all of the windows, which is on the other extreme, or all the data examples that you have in training, you actually go somewhere in between and you look at 20 or 100 different training examples before you make one update step. And so the beautiful thing when you do that is, and often you can concatenate all your inputs in some principled way, and you can multiply your activations and your W parameters of each layer with all of them in one large matrix multiplication. So what do I mean by this? So in many cases, we'll have some computation W times X, right, to compute some kind of Z. Now, that is, at least you can parallelize it, because to compute each unit here, you multiply this by this, and this again by this, but they're all independent, right? So in theory, you could multiply this one in parallel with this one. Does that make sense, that visualization? Now, what's actually better is if you had a W here, because it takes time to set that up in general in the computation. Instead of having just one X here for your first training example, you can have multiple X's, and you have a very large matrix of X inputs. And now you can parallelize not just these computations across one X, but also across all the other X's. So instead of having computing X1, X2 and X3 one at a time, you can have one large matrix where you concatenate all these vectors into one larger matrix, and these are all the same, and basically parallelize like that. So now you only have to give one set of training data to your GPU or your parallel multi-core CPU, and it can parallelize across all these different computations. And if you have, for instance, a GPU which has 5,000 cores, and there's overhead of copying from your CPU RAM to your GPU memory, it'll be very, very efficient to have larger and larger matrix multiplications. So that's one of the advantages of using mini batches. It still has a lot of the stochasticity and the changing landscape of your objective function that prevents you from getting stuck in a local optimum, but you can use some of the parallelization from having the computation of multiple gradients for multiple different inputs. Does that make sense? Are there any questions around that? That is basically the default that you almost always want to use, is some kind of mini batched stochastic gradient descent. Cool. Now we can further optimize or improve over standard stochastic gradient descent by having momentum, and that plays nicely with whatever mini batch size you use. But basically the idea is to add some friction or fraction v of the previous update to your current one. So basically, when your gradient keeps pointing in the same directions from one mini batch to the next mini batch, or from one window to the next window, this will essentially increase the size that the steps are taken towards the minimum. And another way you can look at it is also that it will reduce, what you want to do when you do this, because you keep adding something to your updates, you also want to reduce your global learning rate that we have in general. So if we use this one here in general, we have alpha. If you now, instead of updating directly your parameters with alpha, you use this v term, you want to have a small alpha, because you keep adding to it. Often what we basically do here is we have this update rule v, and we have a hyperparameter mu. Sometimes you start with larger mu's, and then you with smaller mu's, and then you keep increasing it until you get close to 1. And then you update your parameters data with this. Now, this is not super intuitive when you just look at the equation, so let's look at a geometric interpretation. If your gradient would just point in this direction, but maybe in the previous time steps you had a v that points in this direction, then your actual step will be the sum here. And you can kind of think of this as a friction. So if you had optimized something and your gradient points into a valley, you might not want to overshoot out of that valley in your highly non-convex optimization landscape. And also the parameters will build up velocity in some interpretation in the direction of the consistent gradient. So here's a great visualization when you optimize with pure SGD versus with momentum SGD. So it's a very simple function, but it's in some cases tricky because it has this sort of valley, right? So these are the level sets. You can kind of think of this as a bowl that is very, very wide, but also very narrow. And so if you look at the gradient, let's say you try to minimize this here, the gradient here points into this direction, right? You have the bowl that is very, very narrow, and so as you go, you basically go and overshoot a little bit and you get stuck in the other side of the valley. Now with momentum, you'll kind of average the directions from the previous time steps, and so it'll basically point towards the minimum much more quickly, and you'll optimize that function and get out of that narrow valley much more quickly and go in the right direction. Now in this case, we assume that alpha is always fixed, but this momentum term, which in physics term is much more of a friction term than a momentum term, but this basically changes. Now what we can also do on top of that, which is very, very useful, is actually change the learning rate itself over time. So the default would just keep having the same alpha, the same learning rate or step size here, to be fixed across our optimization. One important term here that I may not write down here is an epoch or epoch. Some people pronounce it differently. It's spelled E-P-O-C-H. I say epoch. And an epoch is essentially one pass over your entire training corpus. So if you have 1,000 training examples, it's going once over all 1,000 training examples. Now, what we may often do instead is we actually change the learning rate and we decrease it. So you might, for instance, what's quite commonly done is reduce the learning rate alpha here, the step size again by 0.5 once the validation error stops improving. So what does that mean? We can visualize that, and I encourage you all to visualize furiously and very often what your model is training. So let's say this one here is your error, and you have a training error, and let's say your training error keeps going down, and this is the number of iterations. And now we basically observe, okay, in the beginning our training error goes down, and oftentimes we'll have some validation error as well. So maybe we'll use this here. And our validation error goes down too, but now maybe they both kind of flatten out. And you observe this, so this is training error. And this is our validation error. And now we observe that it flattens out. And we're great, and this is usually, if you have many batches, it'll be much noisier. So let's say it's sort of the average. Now, once we see this, and now because training, let's say you're training on a very large corpus and you don't want to wait because the deadline will come soon, right? And you can't wait for another 2 or 3 days to see what happens. As soon as you see that your validation error kind of flattens out in your visualization, it's usually a good time to reduce your learning rate. And so if you now change and your alpha mu is just, let's say, 0.5 of your previous alpha and the learning rate after you had maybe run 3 epochs or just half an epoch, depending on how large your data set is, what you'll often observe is something amazing, which is the next, after training again and continuing to train, but with a smaller learning rate, you'll actually see a big dip in the error, in your validation error. And that seems to be relatively consistent for especially convolutional neural networks, but also other kinds of deep learning models. So yeah, super useful to change your learning rate. The smaller your data set is, the less that matters. But once you want to train over all of ImageNet or a very large corpus, this is super useful. There are a couple of other, yeah?
So do you see that because with the large learning rate, you were actually just like jumping over points of minimum?
That's one intuition, yeah. So one intuition is if you have a large learning rate in the very beginning, you just want to explore your energy landscape or your optimization landscape more broadly, but then afterwards you might start missing out on having more carefully fined local optima that are smaller and harder to find and easier to sort of jump over with general SGD. Yeah.
Does that TensorFlow have functionality to change your learning rate real time?
TensorFlow has lots of fun options for optimization. So it has momentum and so on as options. And definitely it has also great visualizations that show you sort of the errors that you have and so on. All right, now those are some options. There's an even better one for a lot of NLP problems, which is ADAGRAD, or adaptive subgradient methods for online learning and stochastic optimization. It's a great paper that's introduced by John Ducey in 2010. I think he's now a professor here in the stats department. His idea, and it's in some ways a continuation of some other folks, is to actually adaptively change your learning rate for every single one of your parameters. And this is going to be super helpful if you have certain parameters that are used much more infrequently than others. So let's say, for instance, you update your word vectors in your large optimization problem. And now you have certain words like the and a and his and he and she and so on that you see in almost every other training example. And then you have another word like zebra or aardvark, or some really rare words that you see only once. Now intuitively, what you'd want to do is when you see a word only once or twice in your whole training corpus, you want to really update it with the one thing you just learned about it. You want to make a larger update step for those word vectors. You want to have smaller update steps for word vectors you see all the time, because you don't want to have those be jumping around constantly. after a while, you just kind of realize the is a determiner. It's usually in front of other nouns, and it's not that, you don't learn that much more useful stuff about it after you've trained word vectors for like an hour. And so that's essentially an idea that is used here. And so the way they use this or implement this, and there's lots of nice theory behind it. If you're into theory, I encourage you to read this paper. Is basically you keep track of the current sum that you've had at all past training steps for a specific parameter. So you compute this G here, which is essentially for each element. So at the time step t of your iteration, you have for the ith element of your theta vector, you have some partial derivative here. And you keep track of those, and you basically sum up all of them from past time steps. And so intuitively here, if you have the, for instance, it happens in every other window, this sum will get very large, and so the learning rate for that parameter gets smaller and smaller. Now there's...
You keep track of all the gradients, you just keep track of the sum of squares?
That's exactly right. So here, so this is the sort of theoretical equation, but of course you notice you don't really need to have access to all the past ones. You can just keep track of the sum of squares. Now, there's some folks who then said, well, but after a while, you may get also stuck in a local optimum, and now you can never update that parameter again. So now there are various variants of this idea where you essentially say, well, let's not take let's maybe have this whole sum, but every other epoch, maybe after 4 epochs, we'll reset the sum. And we kind of allow 100 flowers to bloom again, and we'll explore a little bit broader again. And then we'll let it sum up again and get smaller. And then one of the better methods at delta actually will have a window, and so you do need to keep track of some of these squares, and you basically keep the sums of, or just the absolute values, depending on the method, of the last like 50 time steps or something like that, and you basically update it like that. But AdaGrad is also that's a good default. I've used it in lots of papers.
Are these built in?
Some of them are built into TensorFlow, not all of them are. Awesome. Right, so now let's assume you found the right network structure, you implemented it correctly, you know you implemented it correctly because either you used TensorFlow or you checked with finite difference gradient check. You optimize it properly, you visualized your activations, and you know it's doing the right thing, at least when you start optimizing, and you carefully visualized your training and your validation error, and your training error is getting smaller and smaller, but at some point your validation error stopped improving, stopped decreasing, and it's kind of plateauing in a still relatively high state. But your training error went down almost all the way, and you have 99% training accuracy. You basically can, whenever you see an input from your training data, you classify it correctly. That's basically the point where you say, all right, the model, and these models are very powerful, and they're able to almost memorize all your inputs. There's a good rule of thumb there too, which is if you have more parameters than training examples, then your model is much more likely to be able to just memorize all your training examples. But the more it memorizes, the less it generalizes in many cases. Not always, but often. And so when that's the case, it's time to regularize. And a lot of the breakthroughs that enabled deep learning to work better and better over time also came through better regularization methods. So the simplest one, the first step, could be to just reduce your model size. So maybe you have too many parameters, you don't need that many to get to a reasonably good performance, so you could just take out some layers or reduce the number of units at each layer. That's a relatively simple tool. The second one we already covered as well. You kind of assume you have a prior on your weights, and you have a simple L2 regularization term on them. Sometimes regularization is called weight decay also in deep learning papers. And another trick is actually early stopping. Maybe you have the right number of parameters, but if you let it train for too long, it'll overfit, and you just stop after a certain amount of time. And you can use the best validation error to find out when to stop. So one very common technique that I've used a lot and a lot of people do is you actually keep your weights for the last 50 iterations, and every one epoch, for instance, depending on how large your data set is. If your data set is smaller, you can use every 5 epochs. If you have a very large data set like ImageNet, maybe you look at every 1/3 of an epoch. Then you save all your weights and you look at your validation error. And you do that for a day or 2 or 3 days, depending on how large your training data set is. And at the end, you just pick the one model that had the best validation error. And that may be the model that you got after 2 days, and maybe the model you got after 3 or 4 days. But just picking your validation, picking that model based on the validation set is a good indicator, as long as you establish that your validation set is useful and large enough to not be super noisy. And there's some other potential constraints you can put onto your activations, like sparsity constraints, but they're not used as much anymore, so maybe we won't go into too many details. One way to prevent overfitting, or so-called feature co-adaptation, where you basically have certain features fire only when they exactly see a specific combination of inputs, is called dropout. It's a very popular technique, has a lot of nice theory that was, not used to invent it. Jeff Hinton, who invented this, has just phenomenal intuition, but afterwards a lot of people analyzed it and tried to come up with interesting theory of why it worked so well. But basically the main idea is that at training time you will just randomly delete 50% of your inputs and set those neurons to 0. It's basically hurting your model. You're taking out information from your model, because these neural networks are so good at just memorizing everything that if you don't do it, they will memorize exactly this input, these sets of pixels in exactly this constellation will give you exactly this output. Now if you start deleting some, intuitively the model can't overfit and just memorize exactly that input. It has to get used to seeing noise. So you basically delete 50% of the neurons at each layer. And then at test time, you of course never want to delete any of your data at test time. You want to use as much as you can at test time. And now the weights might be twice as large, so you can basically divide all your model weights by 2. And then they're on the right size, the right sort of general activations that come in after your linear layer. And you now have a model that is less overfit and less has features that are not fully co-adapted. So yeah, if you had only a single layer, the people have tried dropout even with simpler models like logistic regression. Even there it can help sometimes. And it's in some ways basically an interpolation between having something like naive Bayes, where you have completely independent single features, versus logistic regression, where the weights are set in the context of all the other weights. There's some of the theory explains why this works by saying, well, maybe what you're doing is you're almost training different networks, and in the end you kind of average them in your weights. So it's different kinds of model bagging techniques. But this is one of the really powerful regularizers, and a lot of people who try it in all kinds of ways for different kinds of models. For recurrent neural networks, which we'll cover later today, it doesn't work as well as for convolutional neural nets and other network types. All right, there are some other tips and tricks which we'll get to in later lectures, but these are sort of, I think, some of the most important ones that get you started and that are very useful for your projects already. There's a great paper by Yoshua Bengio on some practical recommendations for gradient-based training of deep architectures, where he talks about a lot of other techniques, especially here the main hyperparameters that we also just covered. Generally, in the end, you might end up with a lot of these hyperparameters, and it's kind of daunting. You can't really try the combination of all of them, right? The cross product, if you have, just each hyperparameter, let's assume, had only 2 options, but you have 10 of them, well, it's still 2 of the 10 many experiments you'd have to run to look at all of them. And now, in most cases, actually, they aren't just binary, like this one or that one, they're real numbers. Like how much regularization do you want to have? How many units do you want at each layer? So you have usually too many options. And a lot of people tried lots of fancy things on hyperparameter search. Surprising answer is that in many cases, just defining the range in which each of the hyperparameters should be. So let's say layer 1 has somewhere between 10 to 1,000 hidden units. And my regularization is somewhere between 0 and 10. And then just basically randomly selecting values in those ranges works surprisingly well. Better than a lot of other much more sophisticated techniques that then need their own computational cost to be computed. All right, any questions on practicalities of training neural nets? If you have any that come up and you want to look at something, you have some weird patterns, feel free to come to office hours. We can look over it. In general, it's always very useful to try to be close to both your data but also to your model. If something weird is happening and you visualize things well, you very often see what the problem is in your visualization. And it's often useful to visualize both some concrete cases and see, oh, if I plug in this text, like all my units seem to be always on, or most of them are always off. What's up with that? That's one way. And if those look good, then, but you still have some issue, you can look at the statistics too. If I do feed-forward propagation of 1,000 sentences, I can look at the statistics of how often are these neurons on or off, and what are their values.
Does TensorFlow allow you to do like neuron level?
It does, yeah. In fact, there's a beautiful visualization. Maybe I'll go over it next week, where they created a nice web interface last week that was just published. It's very cool. All right, now let's move on to language models and then recurrent neural networks. So language models are a super useful basic tool in natural language processing, and it turns out it can be improved significantly with deep learning as well. So on a very high level, all the language model does is it wants to compute a probability for a sequence of words. Fairly straightforward. So let's say I just want to know how likely is this sequence in the English language, for instance. So that might be helpful if you have a machine translation system. That machine translation system might say, well, this word could translate to these 10 other words. And this word could translate to these other 5 words. And now, just simply, you could have 10 times 5 potential translations of these 2 words without any context. But maybe, going home is much more likely of a sequence than going house, right? But both might be coming from the same German word, zu Hause or something. And so that's basically one of the many applications where language models can be useful. So what you'd usually do is you condition on some window of previous words, because it's kind of hard to compute the probabilities for all possible sequences, right? There are basically way too many, and you can't compute, you can't even keep around the counts for all possible word sequences in a language. And so what's very commonly done is you say, well, I will approximate the probability of the next word, not conditioned on all the words before, which might be like hundreds or thousands if you have a longer document, but only a specific window size again. And so the window here might be, for instance, m, so I will only look at, n here, and like noun. I will only look at the n previous words of the current word. Now, I'm not going to go into too many details, but traditionally, if you wanted to train a very powerful language model, it also works better if you have more training data. And if you took standard machine learning techniques where you basically try to keep around counts for as many possible sequences as you can for as large of n or n-grams as possible, you end up with many, many gigabytes of a large file. Right? Because you want to, in order to approximate this here, you can just keep around very simple counts, like how often do I see this word versus all the other words after this sequence of other words. And that's basically boils down to just having a gigantic table of counts of how many times, for all the different combinations. And so that's not very scalable if you want to get to large windows, and larger windows are indeed helpful if you could keep them around. And so one very powerful way that started improving language models was by using neural networks instead of these count-based methods. And so here is basically a model that is something that you now fully understand and can implement yourself. It's just a different visualization to the ones that I've shown you, and I want to expose you to these so you can see kind of that really this is all the same stuff to what we've talked about in previous lectures, but when you actually read papers in the literature, you'll just see different notations and so on. So here, this is the notation that we may have used. So you just have a softmax, and you have a couple of different layers, and X here is your window where you concatenated the word vectors for that window. And the output is still just a softmax, because all you try to do, instead of predicting a class for the center word, you now interpret the softmax to be the probability for the next word given the current window. But it still boils down to a classification problem, right? Now the classes are just all possible words, and each word is its own class. And you predict the current class just happens to be what you're training for to be the next word. And so here is one different way to describe this. We have here the so-called table lookup. That turns out to just be coming from an index. You pull the column of that index to basically get the word vector here. So they describe word vectors as just C. And then you concatenate all of these together, and they will get input to a hidden layer neural network. That's just a 10H. And then you have here a softmax, and now instead of having just 2 or 3 classes that we might have in named entity recognition, you have a lot of classes, because it's basically the size of your vocabulary as the output. And that's just the probability for the next word at time step t being exactly this word ID, given this context of the previous n words. So now with the simple window model that we've had, we could implement a simple first language model that predicts always the next word, and that we could use as a nice tool to find weird sequences in our input, or to find reasonable translations based on a set of candidate translations. We could literally have an entire lecture on just language models, so this was pretty condensed. Are there any questions? Yeah.
How many units are in the layer?
It highly depends. I think you want to have at least a couple hundred here. I think like 500 or so. Oh, and this one, these are the original equations. So instead of, I want to make sure we're consistent so you're not too confused. So in our notation, it would be this. But if you saw this paper, they would be writing it like this. But basically, it's the exact same thing. You have here your softmax, your exponents, and they just write out the layers with different capital letters for the matrices at the various hidden layers. Okay, now the problem with this, and with a lot of other language models of the traditional type where you keep the context and the counts for specific n-gram lengths, is that you're always conditioning only on the last n words. And in very few cases can n go larger than 5. You can't keep around the counts for all 5 grams. There are a lot of different 5 grams in the English language, right? So just some simple math, let's say you have a vocabulary size of 40,000 different words, and you want to now look at, just compute how often do you see all possible bigrams. Of course, they don't all appear, but that would be 40,000 to the power of 5. Many counts to keep around in the traditional models. And here we also basically only have the first previous n words. Now they're word vectors, which is much more useful. This will require much less RAM to keep around the model, but it's still kind of a fixed window. And maybe n+1, the seventh word before the current word, was the one that might give us a much better indication of which word might be next. So maybe there was a story such as there is a big series of wars in Spain, and then 2 years later the big battle off happened or something. And now, having seen Spain a couple of words before makes it much more likely to have a battle off like Madrid or some other Barcelona or some other Spanish city or French city or somewhere where Spain may have had wars. And that might always be in the context that is just before a fixed window. And this is one of the many good motivations to look into recurrent neural networks. So recurrent neural networks are super exciting because really that's where research is at right now. A lot of folks are doing research. A lot of the models that you might use on your phone when you use speech recognition on your Google phone will use recurrent neural networks. They're in a lot of different places in search engines and in other places. So let's look at the basic definition of a recurrent neural network. Again, I'll expose you to a couple of different visualizations, but for next slide or 2 slides, they're always the exact same model, just visualized differently. So in the end, the equations are usually the best way to disambiguate it. But in our original visualization of neural networks, we basically have here word vectors again at every time step. And the word vectors are given as input to a hidden vector computation here, a standard single layer neural network that basically the main reason why they're called recurrent is that we're using the same parameters, the same matrix W for computing the hidden layer activations at each time step. So to compute the time step at t-1, we'll use W, and for t, we could use W, and for t+1 we use the same W. So let's say, for instance, we try to compute a recurrent neural network language model, which is quite common. What we might do, let's say we have here an input sequence of word vectors, x1 to x capital T, for the total number of tokens that we have in our whole training corpus. Now what we will do at a single time step is to compute a first layer, which is basically a standard neural network layer with an activation that's a sigmoid. This could be a tanh2 or rectified linear, it doesn't matter, some f, and we sum up these two linear layers. Now, whenever you see this, it's important to keep in mind that you could rewrite this as just a standard layer. So when you have some f of z1 plus z2, for instance, and that might be f of w1 times x1 plus w2 times x2. Now you can see this as essentially having a w1 block here and a w2 block, where you basically took each of these matrices and you just concatenated the two matrices times the concatenation of these two vectors, x1 and x2. Is that intuitive of why those are the same? Basically, here you multiply this to get to the first element of this here. You multiply this times this plus this times this vector, and well, that is exactly what happens here. You multiply this by this plus this by this, right? And so whenever you see a plus, you can think of just having concatenated two inputs together. If this is not intuitive, you should make sure you write out the indices and see why those come together. All right, so basically here, at each time step, we just have a single layer neural network. And it's the simplest recurrent neural network definition that we have. And xt just happens to be the word vector at the tth time step. So sometimes I use these brackets to determine this, because it's not, in many cases here, this is the time step, but then the time step means that at this time step we have a specific word, and now we have to look up which word vector actually corresponds to that word index. And then to predict our probabilities over all the words, we just have our standard softmax definition. And we will interpret that output to be the probability that the next word, xt plus 1, is exactly that specific index in our vocabulary. And here are just two other definitions and visualizations of that model idea. Sometimes people write it like this, saying this W here is the same computation, or the same W here is used at every time step. Or sometimes you just visualize one time step and you assume that it's the exact same computation at every time step, or the same W hidden is used. So the superscripts here are basically indicating that this is the matrix of parameters that governs how you compute part of the hidden layer based on the previous hidden layer, and this is part of the computation that's used to compute the hidden layer from an input. Yeah.
So to clarify, a time step means a word index within a list of words, or an iteration?
That's a great question. So a time step means exactly at one token in our case, one word. Yeah. So if I have, I like to go, then, I is time step 1, like is time step 2, 2 is time step 3, go is time step 4.
This is just all purely like assuming we have the weights trained and everything. So this isn't we're not worrying about training. This is just assuming a trained model and we plug it in for this problem.
That's correct, yeah. So we assumed here we trained this, but we'll soon get to training, and training is also going to be relatively similar to all the things we've done before. So let's, basically look into some more details here of the recurrent neural network. Main idea again is just we use the same weights, the same set of weights W at every time step. And then everything else is very similar to what we defined in standard neural network notation. One interesting detail here is often how do you initialize the first time step, H. In many cases you just basically set it to 0. And it's often, again, very good to carefully define the dimensionalities of your parameters. So we define here D as D subscript H is the dimensionality of your hidden layer. And so this has to be a square matrix, and then DH has to have the same number of rows, but it can have a different number of columns because the word vectors might have a different dimensionality to your hidden input. They don't have to have the same dimensionality. And WS, in the case of training a language model, is basically number of rows is the size of your vocabulary, and then times your hidden state. Cool. So how do we train this? Well, it turns out we use the exact same cross-entropy error that we used for classification, which is basically just here the negative of, I guess, the average log probability over our data set. So again, this is just the predicted output from our softmax times the actual true word that will appear at the next time step. And we will sum this over our whole vocabulary, and then we sum at each time step. We basically compute this, and then we basically sum this over all possible time steps. And so one way to evaluate this might also just be saying, well, let's just compute exactly what this loss function is, and then the smaller this is, the better, or sorry, the larger, I guess, the larger the probabilities are that we predict for the correct words, the better. But what's usually more common is to use this in terms of perplexity, which is just 2 to the power of this term. And so in that case, lower is actually better. Now, in theory, we would have all the tools to train this, but if you actually do train it, you'll realize that it gets quite hard. And I think next week we'll have some time to dig into this and look at some mathematical derivation of why this is hard and where Jacobian matrices are coming into play. But basically, intuitively, the problem is you multiply here the same matrix at each time step during backprop. So this is the delta that we carefully, painfully derived most of in the last lecture. And to compute these error signals, delta, at each layer, you have this computation. And now if you have, for instance, the 10h, and your derivatives here might be really small, then that's problematic, right? Because you have small numbers that you multiply at each time step going backwards in time now. And if your w is very large, then you also multiply large numbers with the same large numbers at every time step. And so your deltas can basically both vanish, they become smaller and smaller, and in the end you can make use of, having seen Spain 10 words before, because the gradient that arrives at Spain is close to 0. But because of w and having the same exact w at each time step during backpropagation, you also may have exploding gradient problems. And so we'll get to exactly what this means and why this is a problem in next week's lecture. But I wanted to make sure that you can now have most of the important tips and tricks to really train something in practice. It might already be useful for your problem sets, and if you can now basically get started on implementing some of the most basic baselines for your projects, and introduce to you on a high level what a recurrent neural network is. And next week it'll get really exciting, because then you will basically go over TensorFlow. Bharath will give a lecture on TensorFlow. He's been working on it a lot in the last couple of months in his research. And then we'll look at even more powerful recurrent neural network variants, like long short-term memories or gated recurrent units. And then those are basically the tools that people are now using in all the top papers. And those are the higher level building blocks for some of the most powerful techniques that are currently out there in the literature. Cool. That's it. Everybody, welcome to Tutoring 4D. Today we'll go over TensorFlow. It's a bit of an experiment in the sense that I don't think there's ever been a great deep learning class that already covers TensorFlow, so we're now really at the cutting edge of technology. As such, there's no really other good material you can learn from, and we're doing this experiment a little bit with you. So please feel free to ask questions during this lecture. I haven't been able to code as much as I'd like to in the last couple of months, so Bharath, who's been working with TensorFlow extensively the last couple of months, that it's been out only, is going to give today's lecture. In terms of organization, today the problem set 1 is due, so hopefully you're all on time. You have at most 3 late days for this problem set. If you have any urgent questions, do come to office hours. I can make some exceptions with my office hour today too, if you're stuck, although ideally mine will be about the projects. Thanks for all the ones who have come already to Project Advice Office Hour. I'll try to also keep track now and have a list, so if you come, let's put down your name to make sure we verified that you came to Office Hour for the project. We'll release problem set 2 tomorrow. It will be largely based on TensorFlow. Once you know TensorFlow very well, it's a very easy problem set. But that's a big if. So hopefully today is useful. I think we went over this last night, over this lecture, and if you pay attention, you could almost like copy and paste things and it should always run. You should really be able to understand every line of code that we'll go over, that Bharat will go over. So do ask questions when they come up. Also, we've had around 40 people or so who filled out the class survey. Thanks to those 40. It looks like we improved the amount, so we're more like 55 to 60% of people think it's the right speed right now. If that was a sample bias, because all the people who are happy are more likely to take the survey, and you aren't happy, please do fill it out so we can adjust the speed accordingly. Because TensorFlow is non-trivial to set up and install, we'll have special sessions about TensorFlow this week, and then you can always, of course, ask in any office hour if you have any questions. We'll go especially over how to set it up in AWS, another very practically useful skill these days. You can essentially start your whole own cluster if you want and run many more experiments in parallel. That's about it. Are there any questions about the organization, problem sets, office hours? No? All right, then take it away.
All right, so I think we could probably get started just by talking about what's the state of deep learning today. So for those of you who've been following kind of the deep learning public library, there's a kind of a zoo of libraries out there. There's like Theano, Keras, cuDNN, MXNet, et cetera, et cetera, et cetera. And if you've been following attention, each major company basically has its own deep learning library, and many academic labs have their own deep learning libraries. So before we even kind of dive into TensorFlow, you need to start asking the question, which deep learning library should we use, and why should we bother using it? What are the kind of axes of deep learning libraries, and what are the strengths and weaknesses that all the different deep learning libraries bring to the table? So I think there's a few axes you can use to kind of think about deep learning libraries. The first one I'd say is, when you are specifying a new deep learning model, are you writing a config file or are you writing a program? So some of you may have experience with, say, Caffe, or maybe some of you did an internship at Google a couple of years ago, and there's the disbelief system. And in these systems, when you want to make a new deep learning model, you're not writing code, you're writing basically a JSON file. So you write down a JSON file that specifies your complicated model, and once you specify this JSON file, it auto-creates the model for you. So in some sense, this is convenient because you can think of a deep learning model as kind of an object that you specify statically. And the nice part is that if somebody else specifies a deep learning model for you, you can copy-paste the config file. You don't have to write new code. Now, the trade-off is, for anybody who's done a lot of things with JSON, you know that things get hairy quickly. For complicated models, for things like recurrent neural nets, for the very deep convolutional neural nets people use in practice, you get giant JSON type files floating around. So I think there's a story in the Caffe repo, which is one of the major deep learning packages. There's a 7,000 line configuration file for the ResNet deep network, which is one of the ImageNet challenge winners for this last year. And the reason is that network has something like 150 layers, so they basically copy the JSON config for one layer 150 times. So if you go into that, you see 150 repeats of a config file. So things get hairy with configs. So as people built experience with deep learning, it became clear that you don't want to have config file descriptions of deep learnings. You want to really have it be part of your program. You want to be able to use standard programming constructs like for loops or other programmatic constructs to construct the complicated deep networks people tend to use in practice. And I think in this problem set, you'll see a bit of that. We'll make you construct a recurrent neural net using TensorFlow, and you'll see how easy it is. It's basically 10 lines of code in a for loop when you do it programmatically. If you're going to do it with a config file, that would be a significantly more challenging exercise, and I think that was a research paper at some point doing it in Caffe. So let's assume now that we're going to stick with programmatic construction of deep learning models. The next question is, what language should we use? So if you've ever done a lot of numerical computing, you'll kind of know that numerical programs have to be written in kind of an optimized language. So for many years, this was Fortran. So you'd have kind of mountains of Fortran code sitting in the back end of all these national labs running things like nuclear simulations and the like. So today that's improved a little bit. You can actually use C++ to write high quality numerical code, and there's great libraries like Eigen that'll make this easy for you. But even so, writing C++ is not in some ways, it's like writing a config file. You have to worry about a lot of things that are not directly relevant to the learning task at hand. Things like memory management. So in practice, most people tend not to write C++ when they're making new deep learning models or even numerical models. Rather, you want to have a high-level kind of wrapper around the C++ that lets you call into the C++ efficiently, but lets you use the syntax and the memory management constructs of a high-level programming language. So there's really two contenders in the deep learning space. One is Lua, and the other is Python. So Lua is kind of a game engine wrapper. It's designed to have very quick interop from C to Lua, and the Torch library makes good use of Lua to write scripts in it and basically tie directly down into the lower level numerical code. So a lot of people really like Torch. Some people have some great stories with it, but the downside is Lua is not as mature an ecosystem as Python. So Python's really where a lot of the scientific community, the kind of programming community, the web community resides nowadays, and the convenience of having all these libraries at hand was something that we felt we couldn't give up on. So we decided, all right, so let's use a programmatic deep learning model, let's use one in Python, and what are the choices left? What languages, what deep learning packages will meet this criteria? So for those of you who know a little bit about deep learning trivia, you might have heard of the package Theano. So Theano is kind of a symbolic tensor manipulation package in Python. In many ways, it's kind of the forerunner of TensorFlow, and in some ways, it's even more advanced than TensorFlow. It's certainly a more stable package. It's been around longer. So you can ask, why aren't we using Theano? Why are we using TensorFlow? And part of it, I think it's that TensorFlow is new, it's shiny, that's one aspect. The other aspect is that TensorFlow has kind of more support for building giant models. So when you start building very large deep learning systems, one thing you might want to do is not just use, say, one GPU card to train your model, but you might want to use a whole bank of GPU cards. And if you start reading papers in this literature, you'll find things like, we trained on a bank of 16 GPUs for a week, and you can't do those types of experiments on a single GPU. So I think one place where TensorFlow really shines is the built-in support for distributed systems. So you can kind of build distributed deep learning models, and we felt that that was a skill that we wanted you to have, and that was better served by having you learn TensorFlow. But if you want to ever write models in Theano, you'll be able to use your knowledge of TensorFlow, and basically it's almost a one-to-one mapping, not quite, but you can port that knowledge over. So kind of for all these purposes, we decided, all right, let's go with TensorFlow, and actually, but we should say a couple caveats. TensorFlow is a very new library, so some of you might try Googling TensorFlow versus Theano versus X speed benchmarks. And one downside of TensorFlow currently is that it's actually a reasonable bit slower than most of the other deep learning packages on these benchmarks. So you lose something like 50% in speed on a single GPU today. But I know there's a lot of smart engineers at Google really trying to hammer away at that. So I think that part will be fixed. So assuming these things are fixed, these are kind of, just wanted to give you kind of a picture of the landscape before we dive deep into TensorFlow and start talking about it. So now that we've kind of gone over a bag of motivation, the question is, what is TensorFlow? Now, the obvious answer is, it's a deep learning library. It lets you build deep learning models. But if it's a deep learning library, why didn't we call it DeepFlow or something? Why is it TensorFlow? And the answer is, at its heart, TensorFlow and Theano are not really deep learning libraries. They're basically numerical packages that make it easy to deal with these mathematical constructs known as tensors. And the idea is it's a package that lets you define arbitrary functions on tensors and lets you take their derivatives easily. Now, that of course begs the question, what is a tensor? And unless you have kind of extensive background in numerical physics, you might not be that familiar with the concept of a tensor. So I'll start by saying the things that a tensor can be. A tensor can be a scalar, a tensor can be a vector, and a tensor can be a matrix. And it turns out that when if you fix your math just right, and I have some details on the slide, and you can look this up or you can go look in Wikipedia. A tensor is basically a multi-dimensional array of numbers. So for anybody of you who've played with things like Python, NumPy, you'll know that there's very easy ways to define, say, easy generalizations of matrices, kind of multi-dimensional arrays where you can say, if you have a 3-dimensional tensor, you'd have 3 index variables, I, j, k. So you can kind of think about it as copies of a matrix that you can index into. So kind of the reason that tensors are so interesting and useful for machine learning is basically every operation you'll ever find in any machine learning paper can be written as functions on tensors. And in fact, this is a bit of a cute exercise. Any operation basically in the numerical chemistry, numerical physics, any numerical literature that you can find can be written as functions on tensors. So a neat little thing that they've done in the TensorFlow docs, you can go look this up, is they actually have a partial differential equation solver written in TensorFlow, which is really cute. It's the sort of thing that you wouldn't expect a machine learning library to be able to do, but it's kind of neat to know that it's there. That said, it's a terrible PDE solver. You don't want to actually use it for anything, but it's nice to know that you can. It's kind of reassuring. So another kind of analogy that I'd like to kind of come back to is that a lot of people don't compare deep learning libraries to kind of standard numerical libraries, but in some ways that's really the comparison we should be making. TensorFlow, I'd argue, is actually more similar to a package like NumPy, in that both of them are basically libraries built around these n-dimensional arrays. And the idea is that these multi-dimensional array manipulations are at the heart of both packages. So if you know NumPy, I'm going to argue that it's not that hard to actually figure out TensorFlow. Now, the things that TensorFlow gives you that NumPy doesn't, the biggest, I'd say, is that you can move things on a GPU. So there's a lot of code I've written in NumPy, and I've basically been copy-pasting it into TensorFlow with a few changes, and I'm automatically getting GPU usage and getting a 10x speed up in my code, which is a really nice perk. But of course, the other big one is that NumPy doesn't really talk about derivatives. So if you define a function on a NumPy array, you're responsible for finding the derivative of that function if you need to. And basically, like we had you do in the last homework, you can do some matrix calculus and figure out those derivatives. But as an aside, there are Python packages that will automatically differentiate functions on random NumPy arrays for you. So in some ways, TensorFlow is, I'd say, a GPU version of NumPy with some extra intelligence baked in for functions. So let's kind of do a very, very quick recap of NumPy. Now, I hope all this is familiar to everybody here, otherwise you're going to have trouble with the homework that's due today. But the idea is NumPy gives us a bag of operations we can apply to various matrices. So in this case, we're doing something like we make a 2 by 2 zero matrix, 1 matrix and 0 matrix. We sum it along an axis, or we might reshape it to have another shape. So these are kind of the standard array matrix manipulation operations that NumPy allows you to do. Now, the neat thing is that you can basically do exactly the same thing in TensorFlow. So there's a lot of kind of things going on in this slide. So let me just kind of talk through what's going on. So in the last slide, we said, let's import NumPy as NP. In this slide, we say import TensorFlow as TF. The next thing we will do is we'll say, there are a few bits of cabbage here that aren't directly mapped to the NumPy, and the little arrows on the screen will tell you what these bits of cabbage are. For now, you can ignore them, but kind of the heart is we can call tf.zeros to make a 2 by 2 matrix in TensorFlow. We can call reduce sum, which is the analog of the NumPy function sum, to sum it along an axis, and we can use getShape, which is the analog of shape in NumPy, and we can use reshape, which is the analog of reshape itself. So once you kind of have this back and forth between NumPy and TensorFlow in your head, it's not at all hard to start writing TensorFlow. You just do the same things you do for NumPy, and you kind of carry it over. And to help you along this process, we put together like a small dictionary. So a lot of the operations you can do in NumPy, you can basically carry over to TensorFlow. TensorFlow, one nice thing is it has syntactic sugar. So if you do things in NumPy, like you have a matrix and you multiply it by a scalar and you add another matrix, there are these complicated things called NumPy broadcast rules that make this all work out most of the time. And TensorFlow, luckily, has these same broadcast rules baked in. So you can actually do things like, say, 5 times a TensorFlow tensor will do what you think it should, just like it'll do what you think it should in NumPy. So kind of as a bit of a confession, when I'm writing TensorFlow code, I usually write a NumPy version, then I translate each function one at a time. And for the homework, this might be something you might want to do. Try writing something like the forward pass of whatever deep network we ask you to implement in NumPy, and then just translate it to TensorFlow. If you know the function you're looking for, the TensorFlow API, people on Stack Overflow have done half the work. You can say TensorFlow version of NumPy sum, and there is, in fact, a Stack Overflow post that'll tell you exactly what this is. So luckily, the large community that's built up has already made these things somewhat digested, so you can just use Stack Overflow in Google to figure out these tricks. So now, though, we're going to start talking about the ways in which TensorFlow is not NumPy. And the first one is that TensorFlow requires explicit evaluation. What does that mean? So when you call np.zeros and you make a 2x2 array in NumPy, you can display it directly. It is basically what you think it is. When you dive down into the C, it's a block of memory you've allocated that has zeros filled out onto it, and it's basically a call to malloc or something like that. But if you look at the TensorFlow code, that is not what's going on. When we call tf.zeros and we try to print it out, we get this weird looking tensor object. So in some ways, the heart of TensorFlow is that although it looks like we're doing direct operations on various multidimensional arrays, there's actually another hidden step. So we'll return to this concept kind of again and again over the course of the rest of this lecture, but the idea is that TensorFlow is a system for defining operations on these tensors, and it forms a structure known as a computation graph. And the idea is that you define a computation graph, and it's a symbolic entity. But the computation graph doesn't have any values till you run it in some context. So the key thing is that when we call .eval, which you might remember from all the slides previously, we're implicitly running the TensorFlow computation graph in a context. And if you remember that bit about tf.interactive session, that's a convenience that TensorFlow offers for you. So it's setting up a global environment. So TensorFlow computations, you can think of it as creating these functions on these multidimensional tensors. Then you're setting up an environment for those computations to exist. Then you execute those computations in that given environment. So when we actually do up here ta.eval, we're saying use the global environment, execute the computation specified by the tensor TA in the context of this global environment. And in this case, since TA is just a zeros, it does what we think it should. It makes a zeros array and it kind of prints it out to screen. So that's kind of the critical bit between TensorFlow and NumPy. NumPy is actually doing operations on memory the minute you tell it to do anything. TensorFlow instead, you're describing operations that you'd like to have happen. Then in some sense they're compiled and you execute those operations. So there's kind of this symbolic barrier in between. You can get around it when you're playing with things, but it's very useful to keep in mind that TensorFlow is not NumPy in this one way. So we were just talking about kind of the need for executing TensorFlow in a particular context. In the TensorFlow library, the object that encapsulates this notion of an environment is called a session. So the idea is that when you have a TensorFlow computation graph, and when you've defined some function on tensors you'd like to have executed, then you say, I'm going to start up a session. Then within the course of this session, I'm going to execute this computation. So in the previous slides, we used the function .eval, tensor.eval. That's actually just syntactic sugar underneath the hood. What .eval says is find the session that's currently in scope, execute the computation I asked in that session, and return me the result. So the key bit at the heart of TensorFlow is basically session.run. And this is a function we're going to see again and again. And session.run is basically how you interface with the TensorFlow computation graph. You have this abstract computation, you get this concrete environment, the session, and you run the abstract computation in the concrete environment to get a numerical result. And this is kind of the workflow that goes on in TensorFlow. And in this case, we have a simple example of doing something like that. We set up two constants, we multiply the constants, and the key thing is that C, that is A times B, is a symbolic value until we create a session and run the computation in that session. When we run that computation, we get out 30, which is what we'd expect. But 30 does not happen until we actually evaluate it. And here I'm just, yes?
So I'm assuming that if you had used two different interactive sessions, like TF1, TF2 for A and B, and then set that equal to C, everything would just explode.
Yeah, that's getting gnarly. So interactive session is just to make life friendly for you in the shell. It's not what you should be using. But if you set up two different sessions and you had A in the first session and B in the second session, ooh, that gets nasty. I'm actually not sure what would happen. It's the sort of thing that you shouldn't be doing. So you're welcome to try. Like TensorFlow is mostly polished, but every so often you'll do something and you'll see this explosion of C++ errors onto your screen. And that's a sign you're kind of taking the library in directions it doesn't support yet. But it's a fun exercise, I'd say. Try it out. There is, in fact, one thing I should mention. If you're going to start playing with this, I'll talk a lot today about computation graphs in TensorFlow. Now, TensorFlow, in all the code that we'll present in this class, we're going to have a global computation graph. It's going to be an entity that exists in the ether. But you can actually manipulate multiple computation graphs simultaneously in TensorFlow. So you could do things like you could set up A in one graph, B in another graph, and then they wouldn't be able to talk to each other. But again, this is a bit of an aside.
Is there a way to copy a tensor object without evaluating it into another session?
That is so the graph exists independent of the session. So computation graph is an entity that exists. So the various tensors exist in the graph. They don't require the session to exist. But the particular numerical values that they take on in one session need not have any connection with the numerical values they take on in the next session. So that's kind of the connection there. So here I'm just repeating some things I already said. Interactive session is a useful tool. And another thing, when you're debugging, use IPython, use interactive session, play with tensors and print them out. It's very hard to gain intuition for these things without actually running the computations, and interactive session is your friend. The other thing, again, here's a bit of looking forward. When we say session.run C, we're actually executing what in the TensorFlow docs is called a fetch. So fetch is basically, you have this abstract computation graph, and there's two operations, kind of jumping ahead. You feed, you put data into the computation graph, and you fetch, you take data out of the graph. So you can kind of think of the abstract computation graph as creating a program that you compile. Then maybe from the command line, you feed in some input args to the program you've compiled, and then you take some on standard out. So by analogy to these shell programs, the input args are the feeds, which we'll talk about in a couple slides, and the output args are the fetches, which we'll again come back to in a couple minutes. So again, just repeating things I basically already said. So computation graphs are the central entity in TensorFlow computations. Every time you call a function in TensorFlow, like when we go back, if you remember, I said tf.constant or A times B, you're actually, what that really translates to, you're saying is, find the global graph that is currently in scope, add these operations to that graph, and hold them within memory within that graph. So one kind of, I'd say, nasty thing about TensorFlow is that it functions with respect to a global graph that exists in the background. So it's not quite functional. In NumPy, when you say A times B, there is no global memory that remembers that you said A times B. In TensorFlow, there is this global graph structure that's recording every operation you make. So if you get weird things that go on, you might just want to sometimes close your session and restart it, or like Control-C it, because there's this implicit notion of memory that's handled through the global graph. And we've been talking about this abstractly. I put a couple of pictures in following this, so hopefully that'll help you gain intuition once we get to some more complicated examples. So we've talked about some operations. We've shown some basic examples of numerical manipulations you can do in TensorFlow. And until now, most of it's been basically copy-paste from NumPy. But in some sense, TensorFlow is more than just an array manipulation library. You could say it's basically a prototypical programming language, a very simple one. And any programming language worth its salt has variables. So variables in a standard programming language are basically boxes that hold state. So TensorFlow similarly has the notion of variables. And when you're building a machine learning model, all the parameters in that model you want to hold in TensorFlow variables. So you can think of, say, a weight vector in a machine learning computation as something that you want to put in a weight box. And you're going to go back and forth to that box and put things in and take it out and update it. So really the notion of having mutable variables is critical for machine learning. And so it's critical for TensorFlow, and we have this first-class object, the variable, to really help us get to it. So here we're going to kind of walk through a very simple use case of a variable. So a variable is a box, and like a variable in a standard programming language, a variable does not have a value until you initialize it. So in C or Python, if you use a variable without declaring it, you're going to get an error. Or in Python or JavaScript, I think you can actually get away, it'll be none or something like that. Basically, that's a good way to think about it. A TensorFlow variable is basically none. It doesn't exist until you initialize it. In this case, what we're doing is we're setting up, I think, zeros. We're saying, I'm going to make a variable W, let's call it weights, and this will stand in for, say, a weight vector of the type we might use in a machine learning language program. And we're going to initialize this weight vector with a zeros matrix. So one thing that you kind of have to keep in note is that TensorFlow requires you to be explicit about the notion of initialization. So in the former examples we've seen of TensorFlow, we make various constants and we just run them in a session, and they will come out correctly. But you can't do that for variables. And the reason in TensorFlow logic is that variables don't have meaning until you initialize them. So until you explicitly initialize variables in TensorFlow, and you do that with the call to tf.initialize all variables, variables will blow up on you. And as you're getting used to this, you'll have a few horrible error messages that say something like uninitialized variables cannot meaningfully be used or something like that. But the key thing to remember, the difference between a constant tensor and a variable tensor is a constant tensor doesn't have to be initialized, whereas a variable tensor, that is a box that holds value, always has to be initialized, and you always have to call initialize all variables, or its more advanced cousins, before you start doing computations on variables. But once you initialize them, you can do basically the same sorts of things. So you can use session.run and feed it in a variable, and it'll behave just like session.run fed in with a tensor, and we actually have a simple example of that on the screen. Basically, I set everything on this slide. There's kind of a dichotomy between constant tensors and variable tensors. Constant tensors, feed in, you're good to go. Variable tensors, you need to initialize them before you can start doing things with them. Once you initialize a variable, it behaves basically like a constant tensor, but you can do funkier things. You can play around with it. And here's a nice example of the sort of things you can do with variables. So if you remember back to, I don't know, Programming 101 or whatever intro to programming course you took, one of the first things you might implement in a programming language is something like the notion of a counter. That is, we have some variable, and let's say we set it to 0, and we're going to repeat an operation some number of times. And
does anybody have any questions so far?
Are we good? Questions? Yes.
Why do we need a name for the variables?
Good question. So again, it kind of comes back to this notion of a computation graph. So remember, when we do things in TensorFlow, we're implicitly storing the computations done in the global graph. So once we store something in the graph, there's a question of how do we get back to it? Like maybe I created this graph and another program elsewhere wants to talk to that graph. So you need some way of indexing into the graph, and the way you index is by the name of the various variables or nodes that are in the graph. So it's mostly convenient as a lookup key. There's things like get variable, which we'll talk about later, which allow you to query the graph and get out a variable from this graph. So it's just a convenient way of indexing into the global computation graph. Yes?
Why is the graph used?
Why is the graph used? That's a good question. I think the reason it comes down to a graph is actually technical. We've covered the backpropagation algorithm in lecture over the last couple of weeks. And basically it turns out that although we only made you do backpropagation to compute the derivatives of these matrix multiplies and the like, it turns out that backpropagation is actually general and can be extended to graphs. So if you have, I think, a directed acyclic graph, you can, thinking back to algorithms class, you can linearize that into a chain, and going forward in the chain, you can use the backpropagation algorithm to take derivatives backwards through that graph. So in some sense, kind of from a purely purist perspective, a graph is the most general data structure on which you can take the backpropagation algorithm. So if you're doing it, you might as well do it on a graph because it's general. The other thing is it's useful in practice. Recurrent neural nets are graphs. Kind of complicated convolutional networks are graphs. There are more complicated deep learning algorithms, things like attention models, which we might say a bit about, that are even more complicated graphs. So basically, you need the full generality of graphs because there are papers and useful deep networks where you have graph structures. And without that generality, you can't implement everything you want to. Yes?
So talking more about the graphs, so you mentioned before that TensorFlow is optimized for clusters and GPUs. So does TensorFlow in the backend handle all the optimizations to do that efficiently? Graph structure?
So that's actually a very good question. You need to handle it manually. It turns out it's very challenging to actually distribute computations across multiple compute units efficiently. So what TensorFlow does under the hood, and we won't need this for the class, is that you can actually say, put different parts of the graph on different compute substrates. So you can say, I want these parts of the graph on GPU 1, I want these parts on GPU 2, et cetera, et cetera, et cetera. So there are fine-grained ways you can kind of spread the graph out yourself over various GPUs, but there's no automagical way that'll do this. Like, one dream people often have is, well, can I just define a trillion by trillion matrix and have it spread out into the ether? But no, you can never do anything like that. All operations in the graphs must fit within single GPUs. But the nice thing is you can put different parts of the graph on different compute substrates, which is why this is a very useful, kind of answering your question as well about why graphs. It's a very useful technique for handling where computation is done, in addition to specifying complex computations.
So can I have a variable name, like two variables with the same name but different name tag, or maybe just different variable but with the same name tag?
So the question is, can you have different variables with the same name tag?
Yeah, because when you define variable, you have a name, right?
So it depends. Like, we'll come back to this again, but there's a notion of scope. So you can set up namespaces in TensorFlow to have, just as in Python, you can have, say, two variables with the same name in different functions that don't see each other. You can do something similar in TensorFlow. I think that a name does actually uniquely specify a TensorFlow variable once you expand out all the scoping, but in the same scope, two things that have the same name do refer to the same object. So it does uniquely specify, but you have scoping to allow you to reuse names, so you don't need to constantly keep inventing new names. Yes?
So just to follow up on the naming question, so state and counter both sort of refer to that variable. Right.
So the question is state and counter.
We say state equals variable, name equals counter. I was wondering, like, counter refers to it, but also state refers to it. We're doing test.run of state.
So I'm not seeing a counter variable. Which variable up there?
The first one.
Oh, sorry. I see. All right, this is actually getting into a bit of, so the question is really, the variable up there is named counter in the string, but it's called state as a Python variable. How do these two things talk to each other? And this is actually getting to a good point. Python namespaces and TensorFlow namespaces are different entities. So counter is an entity in the TensorFlow computational graph, whereas state is a local variable in our Python script. These two things don't know about each other. Counter doesn't know that in Python we're talking about it as state, but given state you can reference and check counter by calling .name. State.name will give you back counter. So this is something that can trip you up. TensorFlow namespaces and TensorFlow naming don't talk to Python namespaces and Python naming, so you can think of it as pointers basically. There's something on memory in the global graph, and you have kind of pointers that you can call whatever, but that doesn't change what's in the graph unless you do it explicitly. Do we have any more questions? All right. Cool, so let's return to talking about this example. So the idea of this example, hopefully you've had a chance to look at it by now, is there's a counter and we're going to increment it. And the idea is we start by making a variable to hold the counter. When we call it counter, in Python we refer to it as the local variable state. And what we're doing is we have two operations. We have a tf.add operation and we have a tf.assign. So one thing to note is that when we make this new value that's calling the TensorFlow add operation on state and on the constant 1, we are not updating the original state. We're just making a new tensor in the graph that happens to have the value of 1 plus whatever is in the variable counter. So it's only when we call assign to explicitly overwrite what's held within the counter variable that we update it. So you can look at the Python translations on the right to give you a rough sense for what's going on. Please don't take this too literally. Like, this is at best a metaphor to help you think about what's going on. You shouldn't read too much into the equals plus 1 and all the things that are written in the comments over on the right. So most of the time you won't actually have to deal with the sign, but if you wanted to do complicated things where you're updating variables or doing some type of complicated machine learning algorithm, this is the type of thing you'd want to do. In practice, various optimizers that TensorFlow has built in take care of doing these sorts of updates for you. So you usually don't have to play with variables yourself unless you want to. So we talked a bit about fetches, and the idea was that fetches are the way to get information out of the global computation graph. And we've typically been calling session.run on one tensor. Now you can just feed in a list of tensors and get the values for all those tensors out. So nothing new here, but the main reason I want to emphasize this is if you read the TensorFlow docs, you'll see the term fetch come up repeatedly. That's all fetch means. You're calling session.run and you're feeding in a list of tensors, and you're going to get that list of tensors back from the computation. The more interesting concept, actually, before we go there, I'll show you the first picture of what a computation graph might look like. So the first thing I want to emphasize is this is not what's actually going on in TensorFlow underneath the hood. This is just a picture to help you think about what's going on. But if you look at kind of that simple example we put up on the previous slide, we have 3 constant tensors that we've defined. And the idea is that the first constant, we set it to 3, the second to 2, and the third to 5. Then we take the second and third constants, we add them, we get an intermediate value, and then we multiply it by the first value to get out mul. And the notion of a fetch is in the giant black arrows that are at the bottom of the screen. Those are the things we're pulling out of the computation graph. This computation graph has nothing going in. Everything that's in there is already specified within the text of the program. But we'll see examples of where we feed in data and then we fetch it out. But this is a simple computation graph where we're just fetching data from the computation we're asking to execute. So, any questions here? Does this notion of computation and the graph begin to make sense? Yes?
So what if at one point in the computation we fetch intermed and then maybe like 50 lines later after some other steps we decide to fetch mul? Does it efficiently like keep track of what intermed was, or does it just start from scratch?
I'm pretty sure it starts from scratch. Unless you've updated the variable state. So if you've updated variable state, it has memory. If you don't, it's functional. So this is a purely functional computation graph, no memory. For the people who've done functional programming, you'll like this. This is like, maps and reduces and all those good things. But unless you update variable state explicitly, there is no change in the memory of the system. All right? So now, of course, the next question is, we know how to fetch data from a graph. How do we put data into the graph? And there's a very simple trick you can do. You can call convert to tensor. So if you have any Python list or if you have a Python NumPy array, you can just call convert to tensor. Within within a TensorFlow computation that'll directly pull it in for you. So when you're kind of messing around with TensorFlow in the command line, I suggest you do this. Just use NumPy to make some data so you know what it is, pull it into TensorFlow and start playing with it. So this is kind of a good way to get started, good way to start playing with things. But it is a little inconvenient if you want to do it in a program, so there is a more rich built-in notion of how to feed in data. And the key concept is what's called a placeholder variable. So placeholder variable is a special type of variable, but in some ways it's a dummy variable in that you're not going to update a placeholder, or you're not going to do anything with it except use it as a receptacle for the user to put data in that'll be fed through the computation graph and computed upon. So placeholder variable is simply an input node in the computation graph. So the computation graph we saw a couple slides back, that didn't have any input nodes because we didn't have any input in there. But we'll shortly in a few slides come and see an example of computations where you do have placeholder nodes to feed in data into the network. So here's a very simple idea of how you might use a placeholder. So we're going to define two placeholders. We're going to specify their types, their floats. So the way you should think about it is input 1 and input 2 are two variables whose type you've declared is a float, and there's nothing more known about them. So when we call output to be to be input 1 times input 2, output is a purely symbolic variable because there is no numerical value associated with it. And this is where it's useful to think about the computation graph. In the computation graph, it's a simple node, perfectly well defined. But if you try to do this in NumPy, for example, it's not clear how you do that translation anymore because there's not a notion of dummy placeholder values in NumPy. So the idea is that we make a concrete instantiation in the session, and we call session.run again, but there's one new bit in this, and that's the feed dict, which is kind of over in the corner there. So the idea of a feed dictionary is that it's a mapping from placeholder variables to concrete numeric values. In this case, I think we're setting 3 and 7 and 2 to the two inputs. So we're saying input 1, I want that to be a 7. Input 2, I want it to be a 2. So you can kind of think about it as a command line program where you have dash dash input 1, 7 dash dash input 2, 2. So each time you run the program, you can use a different feed dictionary, and that's analogous to kind of calling the program with different inputs. So when you execute the computation by calling it run and use the fetch on output, you get back the value of output. So you use the feed dict to feed in value to the computation graph, use the session to execute that computation, and fetch the value of output, and you get out 14. Now this seems like an awful lot of trouble, but this is a very convenient metaphor to have, and we'll find it useful as we kind of go further into the discussion. So, yes, go on.
At what stage, so for example, if you declared them to have different shapes that were incompatible, at what stage would TensorFlow give you an error? Is it when you try to run it, or when you try and just do the multiplication?
Oh, that's a good question. I think it is when, the question is that if you have incompatible states and you multiply them, when does TensorFlow give you an error? When it's defined or when it's run? I think it's when it's run. I don't think it has compile kind of declarative guarantees when you actually do it. I might be wrong about that though, but I think it's actually when you run it, it'll start blowing up on you. And TensorFlow is finicky. It does care about these things. NumPy is kind of nicer. It'll massage things for you if it makes sense. TensorFlow, you actually have to care about these things. So we're actually running low on time a bit, so I want to get to a big example, so I'm going to hold off on taking questions for a bit and try to get through to the simple linear regression example that I think will help you with the homework. So let's save questions for the end for the next 20 minutes. So here's kind of the one improved version of the computation graph we saw previously. Before we had kind of a fetch. We took data out of the graph, but there was nothing coming in. In this case, we have a feed. So that's kind of the dictionary that's put up on top that specifies the data flowing in. So the way to kind of read this graph is that the part in the middle is a computation. You have this multiplication op. You have a feed coming in up top that pushes data into the graph. And you have a fetch that pulls it out in bottom. So very, very simple. Again, for this, it's not even worth the trouble almost of drawing it. But when you start getting to more complicated operations, it helps to have this abstraction and this way of kind of thinking about these computations when you're playing with this. So before we kind of go into a more complicated example, there's one concept which you kind of touched upon in a question earlier, and that's namespacing. If you have variables floating around in any programming language, you need some notion of scope. Otherwise, you're going to have like temp1, temp7, temp39 floating around. So if you don't have some way of controlling the scopes of various variables, you're not going to be able to build complicated programs. And in TensorFlow, the key things we use for that are variable scopes. So variable scope is basically a simple way of introducing a scoped environment into TensorFlow. And getVariable is a way of retrieving a particular variable that respects scope. So this sounds terribly abstract, so we'll walk through a couple examples to kind of see what's going on. So underneath the hood, the namespacing in TensorFlow is much like the namespacing in the file system. It's very simple. So we have here two nested scopes, foo and we have bar. And when we nest this, what you see is we're basically just adding foo slash as a prefix to the name of the variable. And here we've called it v, and it's in the foo bar environment. So we have foo slash bar slash v, and we have :0 to name that to indicate that it's the first variable named v, in that environment. So for our purposes, we're not going to worry too much about the :0. The part I think it's important for you to get is the foo slash bar slash. So you have scoped environments and you have scoped names that let you hold models. Now this won't be terribly important for simple examples, but when you start building complicated structures, complicated recurrent or convolutional networks, it does become important to start thinking about namespaces, because otherwise you can't build the complicated deep learning models. So this is just a simple programming language primitive that you should all be very familiar with, and it's a TensorFlow analog of that primitive. There is one other thing that namespaces do. So one thing in deep learning models that you often want to do is the notion of what's called weight sharing. So the idea is that you have some idea, some belief about how a model works. And you might say that in something like a recurrent neural net, there is some operation, some transformation that exists at each step in time. And that's how we get from the present to the future. And this transformation is the same at every time step. And this maybe agrees with our notion of reality. If there's some type of description of reality, there is the same underlying process happening at each step. Now, the way you represent that in a machine learning model is you do something like weight tying. You say in a recurrent neural net, the weights that we use at one time step t are the same as the weights we use at t+1. And TensorFlow has a very convenient way of dealing with this type of weight reuse, and the idea there is to use the variable scope to control this. So there's a reuse variable in these variable scopes, and when you set, by default, reuse is set to false. So when you ask for get variable, you're making new variables each time. It's creating a new variable under the hood for you whenever you set reuse to false. But when you set reuse to true, you can find variables you've already created. And in something like a recurrent neural net where you're going to reuse the same weights at each time step, this is exactly what you want to have under the hood. So here's a simple case where we have this scope foo. Then we call getVariable, we make a new variable there. Now we say reuse variables, and then we call getVariable again, and we get back the exact same variable we've called. If you try this without that get scope, it'll actually blow up on you. It'll say, wait, there's two variables named v, I don't know what to do anymore. Bam, and it'll crash. But if you set this, then you are basically using weight sharing. And this is very convenient for building complex models, and you'll need it on part of the homework. So we do have, I think, some time. Are there any questions about variable scopes and how they're used? All right, cool. So I think we've already talked a bit about what getVariable does. The key idea is that depending on what's going on in the global scope, it does two different things. The first is that notice that getVariable respects scope implicitly. If you call getVariable in scope foo, it'll look for foo/v. It won't look for bar/v or any other scope. So getVariable respects scope underneath the hood, which makes it sort of a convenience. If reuse is set to false, getVariable creates new variables for you under the hood. So it's kind of the preferred way of making new variables deep inside a TensorFlow program. But on the other hand, if you set reuse to true, then what getVariable is going to do is it's going to search for a variable that exists in the computation graph that you've just created previously, and when it doesn't find it, it'll blow up on it, it'll throw a value error. If it does find it, all is good. We just find the same variable again. And here we basically repeat an example much like the one we showed. And we can kind of come into and come out of variable scopes at different parts of the computation. So it's a very nice way of, you could say, encapsulating regions in the computation graph and saying this part of the computation graph is a conceptual whole, and I can enter and exit that part of the computation graph. So I still think this is all pretty abstract, so let's jump into, I think, a simple example, and I think this will help tie all the concepts we've talked about today together. So in many ways, the simplest prototypical machine learning algorithm is just linear regression. So you have some input variable x, and there's some output variable y, and we want to learn a mapping from x to y. And in this case, we've instantiated a little bit of sinusoidal-ish data. So we have a linear-ish increase in y as x increases, but there's some type of sinusoidal noise that's in the data. So nothing fancy, very simple one-dimensional learning model. So how do we actually use TensorFlow to build a model on this data, and how are we going to put in all the pieces of TensorFlow mechanics we've learned to actually construct something? So this slide has mostly cabbage, but there's a couple of concepts we've seen here that I'll come back to. First, we need placeholders. If we're going to define a computation in TensorFlow, we need some way of putting data into the machine. And in a machine learning algorithm, we have input training data that we want to feed into the computation graph. So you're going to start by making x and y placeholder variables that'll take in the training data and the labeled examples and use them to train the machine that we've defined. And you see a little bit in there about TensorFlow being finicky. So we do have to do some reshapes to make sure the shapes match out nicely. And I think the best way to do this is just write down what you think is reasonable. It'll blow up on you, and just make whatever small fixes it tells you to. So not that bad in practice, but it is something that hopefully they'll clean up moving forward. So now we kind of come to the actual heart of the linear regression algorithm. So we have kind of the model mathematically is we have some rule, some weights w, we have some bias b, and the rule we're learning is a linear function y equals wx plus b. And the idea is that conceptually w and b all fit within kind of the same scope. They're a linear regression module. And when we're having a deep network, you might have, say, the fully connected part variable scope. You might have the convolutional variable scope, the recurrent variable scope. In this case, it's a very simple variable scope that is just a linear regression variable scope. And we make two variables. We make weights and we make a bias. And since this is a very easy one-dimensional example, we say, okay, the shape is just 1 by 1 for w, and again, just 1 for the bias. So these are both one-dimensional variables that we put in. Now, we have the two variables. We have the placeholders x and y for the input data, which we defined in the previous slide. We have the two weights, w and b. Now, what is it that we're actually computing with? And in machine learning, the central thing is, the loss function, j. So what is the function that ties the variables in the model to the data? And here we define the loss, and the loss is simply going to be the L2 loss. We're going to say y minus wx plus b. Let's take the sum of squares over all the x and all the y, and that's going to be our loss function. Now, how do we define that in TensorFlow? Okay, we have y, a vector of labels, we have x, a vector of inputs, and we have w and b, these constants. So just do the tensor arithmetic, y minus wx plus b, and square it. And now you have a tensor of size number of samples, which is the component-wise error, and then you do a sum to get out the total loss function. And you can kind of piece together how this relates to the symbolic mathematics. The reduced sum is kind of like the sigma in the kind of the written out math, and the y minus wx plus b is basically the y minus y pred squared part. So are there any questions here? Yes?
Do you need to use the TensorFlow add function to add b?
do we need to use the TensorFlow add function to add b? No, because this is one of the nice things. TensorFlow does some limited broadcasting operation, so it'll figure out that, okay, wx is a tensor, b is a tensor, do competent y's addition of the tensor. So you don't need to use the dot add. Syntactic sugar takes care of it. Yes?
So here using tf.getVariable, could we also just do tf.variable?
Ah, I see. I think you can. When you're using a variable scope, it's good practice to use getVariable because you might want to use weights again in another part of the graph. And if you use getVariable, it'll respect the scopes and it'll handle the underlying namespacing. If you wanted to do it yourself, you probably want to say something like linear regression colon weights or something, in which gets nasty. So this is just a nice way to do it that you should do in practice. Oh, and I don't know if I repeated the question. The question is, do we need to use getVariable, or can we use dot variable directly? And the answer is you can use it directly. It's just messier. Yes.
The reusing there is the same of copy NumPy.
Sorry?
The reuse variable parameter in this get variable is the same of copy NumPy.
I'm sorry, I don't understand the question. The reuse variable is the same as copy NumPy?
Copy matrix in NumPy.
Oh, I see. Is it the same as the copy matrix in NumPy? No. So when we call numpy.copy, we're actually doing a memory copy. There's a region of memory that is in some matrix, and we're going to copy it to another region of memory. When we do reuse variable, we're saying, are we going to use the same node in the abstract computation graph, or are we going to use a new node in the abstract computation graph? So the key thing is, remember, nothing happens in memory, no computation is executed until you create a concrete session. So this is all an abstract construction, and this is just a graph that we've defined symbolically. Any questions? Yes?
So x and y have to be placeholder variables?
X and y have to be, yes, basically because you want to feed in user data to fit a model. You could make them whatever variables you wanted to, but if you want to fit a learning model, you do need placeholder variables. You do need x and y to be placeholder variables. Cool. All right. So in the previous slide, we defined this variable loss, and the loss corresponds to the function j that we use in machine learning practice. Now, of course, as you're all familiar with, the key thing we want to do is del j, del w, or del j, del b. That is, we want to be able to find the gradient of the loss with respect to the parameters that define the model in order to be able to learn. Now, how do we do this in TensorFlow? So the nice thing is that TensorFlow implements a limited form of automatic differentiation. So for most cases, we don't actually need to minimize losses ourselves. We can instead use TensorFlow's built-in suite of minimizer objects or optimizer objects. So the idea is that an optimizer is just another node in the abstract computational graph. And it's a special node, and it's one that if you pass in some scalar tensor, in this case loss, it'll figure out what it has to do to optimize that under the hood. So if you remember back to the assign variable, the assign operation in the counter example, underneath the hood, the optimizer is doing something like an assign operation. It computes the gradient of loss with respect to the various variables in the network. Then it uses assign to do an update to those variables. And in this case, we're using, I think, the atom optimizer, which is one of the family of optimizers. But for a simple example, you can think of this as just a gradient descent step. There's some theta old, you have some del theta, some update term, which you've computed, and you're saying theta new equals theta old plus some fraction lambda times the update, del theta. So it's the basic gradient descent step that we've had you implement many times. So underneath the hood, you can think of an optimizer as performing this update for us, and it helps save us some thinking. Questions?
What is atom optimizer?
Oh. So atom is just a convenient optimizer. You don't need to worry. That's in some ways, the question is, what is the atom optimizer? And it is a particular type of optimizer. There are many advanced variants of gradient descent that are more or less stable for different models. I think the reason I chose to use Atom here is I think you'll use it in the homework. And the nice part about TensorFlow is that it encapsulates a number of these optimizers for you. So you don't necessarily even need to know what Atom is in order to use it, as long as you can make that API call. That said, it's a well-written paper, so I recommend Googling it and checking it out, or asking one of us at office hours about it. But it is a type of gradient descent algorithm, which is useful in practice. All right, yes?
In terms of its partial support for automatic differentiation, how, like, do you know if it will automatically differentiate the whole sigmoid function in one go, or will it decompose it into, you know, the sum and the division? Like, how optimized is that automatic differentiation?
That's actually, the question is how optimized is automatic differentiation? And if you have something like the sigmoid, is it going to decompose it internally, or is it going to do a more optimized thing to handle it? And the answer is it really depends. So I think for something like sigmoid, I think you can implement it yourself. You can use TensorFlow.exp and various things. And in fact, no, we don't ask you to do that in this. We ask you to implement softmax in this homework with TensorFlow, and we ask you to do it using TensorFlow primitives. But for simple things is fine. If you have a very complex operation, it might become slow doing it the fully general way. So I think underneath the hood, you can actually replace some of these operations and have kind of shortcuts. But for this, you need to write new TensorFlow code in the C++ API under the hood. So you can do it, but it's more like if you're a developer working on TensorFlow. If you're a user, you should try to kind of stick with the primitives because it's just much easier. It might be slower, but it's probably good for a first prototype. That, or you can buy a bank of GPUs and just use that, and it's all okay. All right. Any more questions? So we should move on, because this is actually still pretty simple. This is just one gradient descent step that we're showing here. How do you actually learn a model? And this is where it starts to get a little gnarly. There's a lot of things going on in this slide, so I'll just say a little bit about the general idea without diving into details. When you're doing learning with gradient descent, the idea is that there's some number of steps you're doing. And in each step, you're taking a fraction of the input data. And upon that fraction of the input data, you're computing the derivative of the loss function on that input data with respect to the parameters that came in. And based on those derivatives, you're going to do an update to the variables that you've stored. And this TensorFlow code basically does exactly this for you. It's saying that there's some number of steps, 500, which we're going to take. At each step, we're going to take our input NumPy arrays. And by the way, this is one of the really nice things about programmatic design deep learning APIs is you can do things like, I'm just going to randomly sample my NumPy matrix using random choice. Whereas if you're going to do it in a proto language, you have to do horrible things like write down random files on disk where you've pre-shuffled and then written down a shuffled version on disk. Whereas here, it's just so much nicer. You use NumPy to do random subsamples for you, and you can do things on the fly. So we take a random subsample. I think our batch size here is whatever our batch size is. And then we say, all right, let's just use the optimizer that we defined in the previous step to take one gradient descent step on this mini batch. So this is kind of composing all the various operations. So this is kind of abstract. So it might be nicer to kind of look at it visually. What is actually going on? So this is a complicated diagram, so let's kind of break it into parts. So if you remember sort of the visual language that we've set up, fetches are the black fat arrows. They're the things that come out of graph. The orange things coming in up top are the feeds. It's where you put data into the graph. So the idea of this graph is that we're computing this cost function, which we put up on the screen. And we feed in some data, that is the mini batch of data that we're putting in. We pulse it through the graph, and we fetch out the optimizer. And the idea is that one fetch of data from the graph, given a feed of the mini batch, is going to execute a single step of gradient descent. So the for loop that we saw in the previous slide is basically, you could say, I kind of like to think about it as a wave almost, like you're putting in data, it's like pulsing forward through the graph, and you fetch it out. And you're repeating this like data motion 500 times in the computation. And that's what TensorFlow is. It's a system for defining computational graphs to compute functions. And in this case, the function we are computing, which might be easier to read from the math, is just this L2 loss thing. We define this function as a graph, we put in data, and we pulse it through the graph, and we pull out the loss, and we use a special optimizer to update the internal state. And we do this 500 times in a for loop. And this is kind of the heart of what is going on in TensorFlow. So I think here I'm going to pause and take questions, because this is the critical bit of what's going on in TensorFlow. So, floor open.
Can you go back to the slide?
Yes.
So why is there a underscore? You don't care about?
So the underscore, the question is, why is there an underscore? And that's just a Pythonic style. If there's a variable that for some reason you need to have returned to you, but you don't really care what the value is, you use an underscore. In this case, that's the optimizer operation. So we want to fetch the optimizer operation from the graph, but in some sense, we don't care what it returns. We just wanted to do the update to the internal state. So this is actually a way of just documenting in our program. We don't really care what's the output of the optimizer operation. We just wanted to update internal state within. Yes?
So what would be an operation? Could it just be some machine auto returning something?
So an operation in this case, the optimizers, for example, there's a gradient descent optimizer or an atom optimizer. Those are operations. So we didn't really go into what a TensorFlow operation is, but they're just, you can think of it as parts of the computation graph that do things like update internal state, but they're just parts of the computation graph like everything else. And I think, in fact, addition or multiplication is an operation. They don't even have to update. It's just some transformation of tensors that's computed internally within the graph. And the question was, what is an operation, and do we have to know much about it? No, not really. It's just a part of the graph. Yes?
Is there an easy way to tell TensorFlow to run that for loop in parallel and just update asynchronously?
That's a good question. So the question is there a way to make this for loop run in parallel and just have TensorFlow take care of that underneath the hood for us? I think the way you do this is basically, that's a good question. There is a way to do this. There is a way to set it up and do a distributed gradient descent workers. And I think I'm a little fuzzy on this, but I think you define a function and there's some type of broadcast. You say that you're going to do it on a variety of GPUs. I don't know. I haven't looked into this carefully, and it just came out in the supported API. So I'm going to punt on this, but yes.
You're doing random choice, right? Would it be better to just have your data sequentially loaded effectively? So, i.e. going over the batch if it's large enough and just taking chunks?
So the question is, why do random choice in gradient descent? Usually random choice is actually helpful for maintaining stability of a learning model. And when this becomes really useful is if you have if different parts of the data are qualitatively different from other parts of the data, and you have a large enough data set, models exhibit what's known as forgetting. So like if you start, say, with the data from 2 years ago, and you work your way up to sequentially to the data from yesterday, the distribution of data from 2 years ago might be really different from distribution today. So there's a lot of forgetting that could happen. You could forget the patterns that came in the past because you're learning the patterns in the present. But if you do kind of this jumbled shuffle, you have to account for all the data. You have to account for a random sample of the data, which means the model can't forget. So in practice, it's healthier to do a random subchoice when doing an update to the model, because that ensures you've got everything in there. Questions? Are we good? Yes.
So I think, I don't know, maybe he wasn't asking that, but what is it advantage of doing a random choice versus a random shuffle and then sequentially go through data like that?
So the question is a random choice versus a random shuffle?
Yeah.
I see. Okay. So why not just randomly shuffle the data once and not worry about it? Yes, absolutely, you can do that. There is no difference in practice. This is just convenient, and I was hacking together a Python script, so I was like, why not? If you have a large enough data set, you might not want to do this choice in real time, because that'll get you cache problems. You're right. So it is, for large data sets, it's probably smarter to do a shuffle before time and write it down.
But you do want every batch to have a different shuffle, every epoch.
Yes.
Is there any kind of practical suggestion for the batch stats, like optimal performance in a regression or neural network?
So the question is there a practical suggestion for what a batch size should be? And the answer I found is something like small powers of 2, 32, 64, 128. There is really, it's in some sense, it's a hyperparameter. It's some aspect of the model training that really depends on your hardware, on your particular data set. You just, I'd say try out a few on your validation set, see what works better. Most of the time it doesn't make a big difference. Like, yeah, batch size 1, probably don't want that. Batch size 50,000, yeah, probably don't want that. But anything in kind of the smaller regime, it's mostly all the same. You can try out a few things. It's basically a hyperparameter. Try it out empirically. There's no real good rule of thumb. All right. We do have a few more slides, so I'm going to break here if there are no more questions. Okay. So here again we have this complicated graph thing, and it fits a nice model. So you can see it learned the straight line. So machine learning works, TensorFlow is great, we're done, we're out of a job, you know. You can write tiny scripts. So basically, this is kind of a toy learning example in TensorFlow, but all the programs that you'll write for doing non-trivial learning in TensorFlow will have very much the same structure. You'll have these for loops, you'll define this computation graph, that is your model up front. You'll take in your data in placeholders. You'll have a for loop in which you take some fraction of that data, then you'll run the graph one time, that is the model, that'll update the parameters in that model, and you'll repeat until you feel you're done. And what done is depends. There's many, in practice you should be doing something like tracking error on a validation set, because this was a tiny toy example, we didn't do that, but in practice you should not be doing what I'm doing on the screen, you should be doing something healthier, and the homework does make you actually look at error on a validation set, but for now this is okay. So the one thing we really didn't talk too much about today is that how does this automatic differentiation happen under the hood? And I think we touched upon it a little bit in a question, in that it's just a backpropagation algorithm that you've already learned a bit about. And the idea is that when people were defining TensorFlow, as they define things like addition, multiplication, or exponentiation, for each operation, each primitive, they wrote down a gradient function associated with it. So each TensorFlow primitive underneath the hood has had somebody write down a paired gradient function. So if you have exponential, you have a gradient of exponential function. If you have addition, you have a gradient of addition function. And the idea is that when you build up a graph with these primitive nodes, when you're doing the forward pass, you use the function, addition, multiplication, exponentiation. When you're doing the backward pass, as in backpropagation, you use the paired gradient function. And you use that just to use the calculus chain rule and propagate information through the graph. So there's nothing that magical. In fact, it's not that hard homework exercise to just do this and write like a mini automatic differentiation. And I'm not actually the one writing this homework, so I was thinking actually about having something like that in there, but I decided not to. But it's not that bad. It's something you could do, and it's something that you shouldn't think about TensorFlow as magic. It's just doing some simple math underneath the hood, but it's nicely implemented so you don't have to worry about it. So practical suggestions. I think we've touched on many of these already. I think the key thing is that when you're getting used to TensorFlow, it helps to think about it as sort of a NumPy wrapper. Try doing things like writing functions in NumPy, convert the NumPy arrays to tensors, print things out. Things that will trip you up. TensorFlow is fastidious about things like shapes and types. So you will get things like int32 given where float 32 is expected. Simple things like that, it's not serious, just figure out what TensorFlow is asking for, what it's expecting, and it'll work out. One thing that will trip you up is that some operations that are very natural in NumPy are not directly supported in TensorFlow. So NumPy, you can do nice things like index into multidimensional array with another multidimensional array. And if you're going to implement softmax in the vectorized version in NumPy, there's a very natural way to do this. And some of you might have even used it in the last homework. That natural implementation won't actually work out in TensorFlow. There's like open GitHub issues and people complaining, so I think they'll fix it, but you'll have to be smart. So a lot of beginning with TensorFlow is about knowing how to start from the NumPy version and then distort it to work within the TensorFlow API. And we'll give you some exercises that'll make you work through this process and kind of internalize it. The other thing, again, is interactive session is your friend. Use IPython, debug things. The TensorFlow API is a little dense at times, so it helps to know what you're looking for. So try writing a version in NumPy, do a translation one at a time, use tools other people have already built to help you. Just look at it in Stack Overflow or something. So kind of doing a translation is easier than trying to write it from scratch. Another thing which we didn't touch on in this lecture at all is TensorBoard. So one of the really nice things about TensorFlow is it gives you kind of a visualization toolkit to look at models you've created and to look at the learning process as it's happening. Now, we're not going to use that much in the class. The main reason is that TensorBoard is kind of built to run on your local host. If you want to use it running on a remote server, you need to do things like SSH port forwarding, which gets a little hairy and we didn't really want to make you deal with it. It's a nice tool. If you're going to do your projects, you might look at it if you're having trouble, but you don't need to do it for anything that you'll use in this class. But we encourage you to play with it on your own time. So, kind of the most important question the last minute is, where can you use TensorFlow at Stanford? And the answer, I think, for most of you is just go on Corn. It's up on Corn now, so you should be able to log into Corn, load up the TensorFlow module, and run the computation. And for the homework, we don't need you to use a GPU. You should be able to run all the homework on the CPU Corn implementation. If you do have access to a Stanford GPU cluster, something like Sherlock or Xstream, feel free to use it. Like, it'll make life faster, but the homework is made to be runnable on a CPU implementation, and you should be fine. If you want to do things like experiment with AWS and GPUs, we'll have a special session. Xiaojing, one of the TAs, is going to host a session telling you how to get up on AWS, and we have a machine image that will make it easy for you to start running TensorFlow. So go to his session on Sunday. And as a final thing, here's just a little hint for the homework. So in the homework, you'll have to define embedding matrices, and these are here are just some functions that you might find useful. So just take a look at the slides if you're stuck on the homework. And with that, I think we're done. Are there any last questions? Yes.
Yeah, if you go back to the for loop that had the optimizer code, how do we ask the optimizer not to optimize certain variables? Like, for example, if I added regularization to my loss function and I didn't want it to optimize the lambda scalar multiple of the regularization, how would I ask it not to do that?
Oh, that's a good question. Easiest way, just remove it from the graph. I think there is a way to set a variable to be non-learned. I'm not sure about the API version, but I think you can do this. In practice, a simple way is just comment out that part of the code. But the question is, how do you ask certain parts of the computation graph not to be optimized? And I am reasonably certain there's a way to do this, but I don't know off the top of my head. Question?
So in terms of the computation, let's say I have L1 loss or ReLUs or R10H. Does TensorFlow handle the pointy bits when you do the computation?
Good question. So if you have a non-differentiable loss function like a ReLU, does TensorFlow handle it? And yes, it does. Underneath the hood, it handles it by ignoring it. It turns out that you almost never hit the pointy bits, so you can just pretend it's all hunky-dory, and it works out basically all the time. And on the pointy bits, you just pick one of the sides to kind of pick your derivative. And the convergence proofs, like, for those of you who are interested, Steve Boyd's class talks about this in convex optimization. There's like subgradient convergence theorem, so things all work out on the pointy bits. In practice, you just pretend it's not there and it's fine. All right. Cool. Well, thank you for listening, everybody.
Hey, welcome to lecture 8 of 224D. So, the problem set 1 was already due, and hopefully we're all on top of it. So thanks so much for the feedback on the class so far, that to the people who've given it. I've had 52 responses, so it's probably a good subsample. I'm happy that compared to last year, I think we had roughly 1/3 of people for whom the speed was right, 1/3 was too slow, 1/3 was too fast. We improved a little bit over that, so we're 2/3 of the folks think the speed and the lecture complexity is just right. So I'm happy to hear that. There is still 1/4 of people who think the lecture notes were a little too fast and a little too hard. So today we'll do a little bit of recap. Also, there are a couple of other pieces of feedback that were really great to see, and I'll try to incorporate them starting today already. Some folks want to see more of the intuition behind the math and models, so there will be a lot more of that today. We'll go through another toy example, which is another piece of feedback that people want to see more of. And then next week, I'll do also a recap session of all the most important concepts. Yeah, there will be a nice sort of high-level intuition, for instance, today of the problems that we may encounter when we try to train recurrent neural networks, and then some intuition and math to fix it. One student was worried about the vectors being, having different dimensionality, row versus column vectors. In theory, all the vectors in the class should be column vectors. So whenever I did mess that up, let me know. It's good, very possible that I did. But in theory, they should all be column vectors. On the problem sets, there are some people who just didn't like them but didn't give quite constructive feedback. A lot of people, I think the majority of folks liked it, which is good. That was also because last year, the first problem set was one that we did last year. The next ones are going to be new. I don't think there's been ever a class yet that used TensorFlow for the problem set, so there's very little for us to learn from the mistakes of others. So bear with us. If there are any issues, do let us know on Piazza, and we'll try to fix them. We tested them quite a bit with me and the TA teams, and went over them, but I'm sure there's still some small issues that crept in. We're trying to also add all the dimensionalities. That was another piece of feedback. Some folks got tripped up on the dimensionality of inputs and outputs. It partly is something that you should know from the math, but we can also make it easier by providing that in the comments, and we'll try to do that for this and the next problem set. And then another major piece of feedback was that people would like to see a list of proposed projects. And I actually think that's a great idea. So I asked a bunch of research groups at Stanford, mostly NLP and the deep learning groups, to see if they can come up with additional ideas. And then everybody who came to office hour and asked me, I gave some ideas, but I might make that more easier and basically compile a list and tell you. So in order for that to still have any useful impact, I'll move the proposal deadline to next week, Thursday, so today in a week, so that you have some time, and on Tuesday we can go over a list of potential projects. For those of you who haven't had their own ideas yet. Those are just going to be proposals. It's very much encouraged that you have your own ideas based on your research or your interests, and you can do whatever you want. Also, there's one question around whether the extra credit deadline for the data set and having a first baseline was for the proposal or the milestone, and it's the milestone, so not the proposal. You don't have to have already a data set and the baselines figured out. But we do encourage you to do that once you have the milestone deadline. All right, are there any other questions organizationally, or? Hopefully tonight problem set 2 will come out. We tried to run it on some of the clusters on Stanford campus, and there's some issues, so we're trying to iron those out. Yeah.
Do we all have access to all the clusters? Or?
That's the thing. I don't think everybody has access to all the clusters. So I think there's some from the different departments, but we want to make sure that it works smoothly for as many of you as possible.
And did you guys pre-install TensorFlow?
Yeah, we did. Yeah, you would, otherwise you'd spend the first month doing that. So we've been working with the infrastructure folks who've been very supportive. But then it's also non-trivial sometimes to install TensorFlow. And it's installed locally. But if you just import TensorFlow STF, it should work on most machines, but hence the slight delay. Cool. All right. So I'm trying to bring the folks, the 1/4 of people for whom it was a little too fast, up to speed today. Last lecture, I wanted to make sure we have at least an idea of recurrent neural nets, because we were thinking the problem set would come out, and we want to make sure you know sort of the high level of the model. So today, I'll take a step back and walk slowly through some of the concepts of recurrent neural networks, of language models, tie it back, give some examples from natural language processing, so that you really get a better intuition of why they're so useful. And then we can deep dive into the problems that you will encounter when you try to train them in a variety of ways. And then we can actually start extending the baseline recurrent neural networks. Once we understand them, we can go to bidirectional ones and deep recurrent neural networks and so on. So it'll be very exciting, because those are models that are very viable and useful for you to use in the rest of your life, but also in the projects. All right. There are no further questions? Cool. Then let's talk a little bit about language models. We kind of breezed through that at the end of last week's lecture. So main recap, we want to compute the probability for a sequence. And I mentioned that this will be useful, but here a couple of real examples. Let's say you tried to have a machine translation model, and the machine translation model comes from French, for instance, where sometimes adjectives are in front of nouns and sometimes they're behind nouns. And now your translation model might give you two potential candidate translations from French. And one might be the cat is small, or small the is cat. And now you want to basically know that one is a much more likely sequence than the other. So the cat is small, the probability for that foregram should be much higher than of the sequence small the is cat. Likewise, in translation, you often have certain words that can be translated into different words in the other language. So for instance, home and house might be the same, might be both possible translations for Hause or house in German. And so if you have the possible translation walking home after school versus walking house after school, then to English speakers it's very obvious that one is a much better translation than the other. But to a machine translation model that just co-occurred and counted how often do I see this word next to that word versus not, it might be less obvious. So it's useful if we have basically good probability estimates for sequences. And you can think of similar things when you have speech recognition, where you say, I want to know the price of wood. And now wood, the default and the times you most often see wood is in the sense of like, I would like to do something, that kind of wood, and they sound very similar. And so a language model might help you and tell you which of the wood is more likely given the sequence of other words in front of it. So generally, those were approximated, because it's very hard to compute the entire probability distribution given all possible sequences of the English language, for instance, or other languages. And so we'll use an obviously incorrect but necessary Markov assumption in traditional language models, where instead of predicting the next word based on the entire sequence of words before, where we would have to keep a very large table, we'll basically just look at the n words before the next word we'd like to predict. So this is an approximation, very common one, but it's obviously not a true one. The next word of a sentence, or the next word that I might utter, will always depend on a lot of other words that I've said before. And so when I was talking about computing counts, this was basically what I was saying. So here, let's say you want to get the probability for the next word after the first word, and let's say our window n is only 1. In that case, for just basically looking at unigram or bigram probabilities, we will only look at the counts of how often do we see the sequence W1, W2 divided by how often do we see W1 by itself. Now we can basically go through all possible words that we have in the English language, and we create a very large table where we look at how often do we see the words in this sequence versus how often do we just see W1. And we compute that very, very large table. Now, just that will not be a very accurate estimate, right? If I just know that that happened before, a lot of different nouns might follow. So another way we could do it is extend this to bigrams and eventually trigrams. So here we have a simple bigram model, so we condition the probability of seeing a third word based on the preceding 2 words. But now we need to collect all the counts in our entire corpus for every possible sequence of trigrams. And there are a lot of trigrams, right? So if the English language has at least 50,000 to 100,000 useful words, so that's 100,000 to the power 3 many possible numbers we now need to collect and keep around, even at test time, to compute that probability of just a single word. And in general, we want to have not just conditioning on bigrams, but ideally tri or 4 or 5 grams. And we know that the performance improves the higher n is in these n-gram counts. And eventually, we want to not just condition on the 4 grams, because maybe there is no 4 gram that you've ever seen at test time, so you might want to do so-called back-off, where you smooth your distributions based on 4 grams, trigrams, bigrams, and unigrams. But the problem is there are a lot of those n-grams, especially as n gets larger. And so there's a paper by Heffield et al. On scalable modified Kneser-Ney language models. Kneser-Ney is basically just a way to combine the probabilities of all the n-grams with n-1, n-2 to unigrams. And so the best thing they could do after a lot of very low-level optimization was to have one machine with 140 gigs of RAM, trained for 2.8 days, and built a single model with 126 billion tokens. And that's basically a huge requirement. So you could never run that kind of model on your cell phone, right? So here come neural networks, where now, in theory at least, we will hope that every state here captures all the information from the past. Of course, in practice, that isn't really the case, and we'll find ways of making that a better approximation and more true. But at least in theory, we will hope that the hidden states that we compute at every time step in a recurrent neural network will capture a lot of the history that we've seen before. And the main reason we call them recurrent neural networks is that we will actually tie the weights at each time step. So there's no bound of how many time steps we could compute these hidden states for. And the nice thing here is the RAM requirements will only scale with the number of words, times maybe 100. So instead of having to keep around the number of words to the power of 3, 4, 5, it's only 100 if we have 100-dimensional word vectors times the number of words, plus a couple of the weights here that we have to also keep around. And y will again be our output. So then we walk through a couple of different visualizations and the straight-up definition of this. So here we essentially assume for now that at every time step we have a word vector that we now can compute. And we will compute a hidden state here with a simple linear neural network, where we basically have hidden connections from the previous time step and the hidden visible connections or hidden and input connections with W superscript Hx. And then the softmax is again just a simple classifier that we now all know how to derive the derivatives of. We know how to backprop that into a neural network, and we can predict any class that we would want at each time step. So the class could be, in the case of language models, the next word, but the class could also be the sentiment of the sentence so far. And the class could also be the label of that word at that current time step. Lots of different things you could train this on. That's why it's such a powerful and general model. In the default case for RNN language models, it'll just be the next word that we're trying to predict at each time step. Awesome. All right. So again, main idea, we use the same weights W, and we'll run into trouble with this, but it makes it nice because that way we can essentially extend this model to arbitrary length sequences. And again, it's very important to define the proper dimensions. So here we will define d subscript h as the dimensionality of our hidden states. So W superscript HH will be a DH by DH matrix. WHX will be a DH by D matrix, where we define D to be the input, the dimensionality of our word vectors. And then WS, in the case of language models, will have the size of our vocabulary, many rows. So this is a very large matrix if we have a lot of words. And then we basically want to predict here the probability distribution over the vocabulary at each time step. So our y hat here is defined as just a probability, again, of the next word, but for all possible word indices. And then we can compute our the same cross-entropy loss function to predict the words instead of classes. So this used to be the sum over our classes, and now it's just the sum over the vocabulary indices. And YTJ is basically the ground truth that we have in this current mini batch or at this time step, and J is the index of the correct, that should be the correct class. And then, well, yeah, so this is the ground truth. In most cases, this will be 0. So this is YTJ, and then Y hat is the actual predicted probability for that class. And then just a lot of people, instead of taking this as the final evaluation, because here training looks very similar to testing. We want to predict the probability, we just push the probabilities to be the right, have the right distribution, largely a 0, like a 1 hot kind of probability. All probability mass should be at one time step, and then basically to get to the main number that you'll see in a lot of papers, we just take 2 to the power of the negation of this average log probability over the whole data set. So intuitively, the less perplexed you are, the better the model is. The less the model is surprised to see a specific word coming up next. And you want to basically assign most of the probability mass to the actual word that appears next. But you basically get some credit also for saying, well, probability for next word being Spain might be 0.5 instead of 0.9. That is better than 0.01, right? So even if you just give probability mass to all the nouns, that's better than not even understanding whether it should be a noun or an adjective, and then having a broader class and a distribution that is less peaked. Okay, so now the main problem with RNNs is that while in theory they should capture all the information of the previous time steps, the fact of the matter is that it's actually really hard to train them to be able to do that. And the main problem comes also from its main strength, which is that we're multiplying the same matrix at each time step during the forward propagation. So we're asking this simple linear transformation plus these non-linearities to change the state a lot based on any single word that's coming in. And we're hoping that inputs from many, many time steps ago can still change this despite applying the same transformation at each time step. And so as we're trying to take the derivatives here with respect to W at each of the time steps, we'll run into some problems. I encourage you to really go take a 2 time step, a recurrent neural network, and just derive the derivatives here for instance, the partial or the derivative with respect to w over a certain prediction at time step 2, for instance. It'll be a great exercise. It's very insightful. So let's look at the actual problems that we will get when we try to train this. And they're actually very opposed. So in some sense, it's funny that we may run into both of them with this model family. We, in fact, will have both vanishing and exploding gradient problems. So if you train them vanilla and you try to, you optimize it, you run your stochastic gradient descent algorithm, at some point you may all of a sudden get not a number. And all your derivatives blew up, all your parameters are blowing up, and you're like, oh, did I have a bug? And you don't actually have a bug. It might just be, you might still have a bug, and you should check your finite difference gradient check and see that there is no bug. But then even if you have a completely bug-free code, you may still run into not a number issues. And that's an obvious problem, and if you have it and you see it. The vanishing gradient problem is a little more subtle, and you might think it's doing what you want to do, but it really can't. And so let's analyze what happens here and gain a little bit of mathematical intuition behind the vanishing gradient problem. So at training time, you'll remember we'll get a delta function, a delta error signal that will basically add and backpropagate at every time step. So at yt, we'll propagate a delta into xt, and then we'll also propagate one into further time steps. And at yt plus 1, we'll do that again, and it will basically keep on going. So there should be errors also here into all the past time steps, in theory, all the way until time step 0, when the sequence actually started. Right. And again, it just comes from the chain rule. So let's look at a simple formulation of a recurrent neural network and see what actually happens when we apply the chain rule to a potentially very, very long sequence of time steps. So let's define our RNN here slightly differently. It's actually very, very similar. Instead of defining h as f of that linear transformation, we'll just apply f only once we compute our y hat. And for now, let's not assume that's a normalized probability just for the sake of this analysis, and just assume we have just a linear transformation that gives us unnormalized scores at each time step. And f here is again our non-linearity, such as the sigmoid or tan h. Are there any questions about this slight reformulation, where we basically just move the non-linearity from the definition of h into the definition of y? We still have f here, where we applied f also to the previous time step. And because of that, it's essentially the same thing. All right, now let's look at the total error that we have over an entire sequence, where at each time step we try to predict some output. So derivative of our error with respect to w will basically be derivative for all the single errors that we have. Again, this will just be our cross-entropy error, for instance, in the simplest case. You could also have linear regression, any kind of error you can think of. At this could be a max margin error. Doesn't really matter for this analysis. We'll have some error, and to get to the error of the entire sequence, we basically sum up the errors at each time step. So we'll have an output y, and each output y will give us one error signal. Can you raise your hand if that makes sense? So for those who haven't raised their hands, can you formulate a question? Okay, so it's essentially we have lots of little logistic regression problems at each time step, but now they're all underneath it. To get to the hidden states that we use for as input to our softmax, it happens that they're all connected and they're all in this chain. It's a long computational graph in TensorFlow language. Yeah?
At each layer, do you concatenate the hidden input of the x, or do you sum them up?
That's a good question. So the question is, at each layer, do we concatenate them or we sum them up? I wrote it down really quickly I think last week, but you can assume that if you have w times this f plus this w times this x, it's similar to when you basically put both of these matrices w next to each other and you concatenate the hidden and the x. So in some sense, it's still just a linear layer, but the inputs are coming from different places. That's a good question. All right, so now let's assume this is our h. Just have w times nonlinearity times our previous hidden state, plus a linear combination of our word vectors at that time step. Now, if we want to compute, so we have this main sum now. Now let's look at the element at each time step t. That will now depend on all previous time steps. So we'll apply the chain rule, and it's a pretty hardcore application of the chain rule, because now you have all the hidden time steps before, and the current time step depends on all of the previous ones, right? So derivative of the error at a certain time step t with respect to w will basically be the sum of all time steps from k equals 1 to the current time step t of this whole expression. A lot of derivatives and basically applying the chain rule to get to the derivative with respect to w in the end, which is inside each of the hidden states that we computed until that time step, right? So intuitive here, we use w at each of the time steps, and so to compute derivative with respect of ht plus 1 here with respect to this w, well, this w appeared here to compute ht, and ht minus 1, and ht minus 2, and ht minus 3, all the way until h1. So this is really where we have a lot of them, right? Because each of the HTs depends, or the HT depends on each of the HKs that came before it. Yeah?
So the difference compared to what we were looking at before in terms of the backpropagation, the W's at each layers actually aren't updated. This is computing all the way back to the first time step, and then update the W, which always applies again. Right?
So the question is, the W isn't updated. So the W is only updated during optimization, but you're right, at each time step during your optimization, you don't update W yet. You basically have the same W to compute all the errors at that time step, and then once you compute your gradient, then you can update W again. But it's the same W, and it's not different at each time step. And in all the neural networks that we've defined before, we've had, W1 for the first layer and a different set of W2 for the second layer, and so on. Yeah. Yeah.
When your training sentences are different length and you want to do mini batch training, is there a way to unify like the derivative?
So that's a great question. So the question is, as you have different length sequences and you try to update all your derivatives, is there some way maybe you can make that more efficient, or you can combine them? And the answer is yes. It's actually deep down in TensorFlow, you'll realize that if your mini batches, one mini batch has length like a sentence with 50 words, and then all the other elements in your mini batch have length of only 5 words, then if you send each of those to one CPU or to one core or to one machine, then all the other ones are going to be done, and then everybody else in that mini batch is waiting for that last sentence, and it actually slows you down a lot. So it's very much a computational trick, but it's very useful to have mini batches that are all where each element of that mini batch has roughly the same computational cost. And then there are actually some really hacky ways for people to try to put all of this together in efficient matrix multiplies on GPUs. And in those cases, you actually sometimes even zero pad. Even like doing 0 multiplications of matrices and inputs that are all 0, but doing it very efficiently in one block can be more efficient than not doing it and having ifs and so on. All right, now let's copy this last expression here to the next slide. And let's look at this particular output here. the way we'll derive this, and by looking at all these separate elements of the chain rule, is not as efficient as what we would do in standard backprop. In standard backpropagation, we multiply matrices in a much more efficient way, but we can analyze this here, and it'll be very useful to see and interpret what's going on here at each time step. So remember again our definition of the hidden state. Now, in order to compute the derivative of ht at the current time step where the error came in with respect to all the potential hk's that came before it in this time series, we'll also have to apply the chain rule. So here, the derivative of ht with respect to hk will be the sum of wherever that case started, so we don't have to go past that, but starting from k and having j sum from k plus 1 to t, and have the product here of all these different partials. And now, as you compute this, this is essentially going to be a derivative of a vector with respect to another vector. And that means that we have to use a Jacobian. And basically have here, in general, definition of the Jacobian, if you have a vector valued function, which is very rare. All our costs usually end up being a single number, like the whole cross entropy error. So in most cases, our function have a single output. But in this analysis, when we look at this partial here, we'll have to use the Jacobian. General definition, if you have a vector valued output function, is basically that you have a vector for each of these derivatives of f, for instance, with respect to the whole. X is basically a vector, a derivative of f with respect to each of the elements of x. But then because f itself is a vector, you basically get overall a matrix with all the partials. So basically you have the cross product. Each element of the output has a derivative with respect to each of the elements of the input. We don't really have to use Jacobians in any of the derivations. So if you're accidentally running into a Jacobian, you probably could have simplified things in your derivatives. Okay, so now let's look at this exact derivative here of hj with respect to all the j minus 1s. Again, this is our definition of h. And so to compute this Jacobian, we'll basically want to look at all the elements of the Jacobian matrix. And when we write that out, it will become relatively straightforward, but it's still a good exercise to go through it. We don't really have to dig again into all the derivatives. There's also one of the feedback I got to not go into all the sub-indices. It's a relatively straightforward application, again, of the tools that we've seen. But one way to describe that very efficiently is to actually combine all of these and write in the end this kind of equation where we have W transpose times the diagonal of f prime, where f prime here is again coming from this element where you see the other matrices inside. And so the diagonal of a vector is basically just a very efficient way to write a matrix of this form, where you take each element of that vector and you align it along the diagonal of the matrix, and all the other elements of that matrix are 0. So you basically have this matrix multiplication here. And we're missing the superscripts. Does anybody have an idea which superscript we're missing? So we're multiplying by f prime of the previous hidden state. Okay, well, in our previous definition, we had WHH and WHX, but here we cleverly dropped that superscript. So it's really just this thing, because the derivatives at each time step, they just end at that word vector, right? So we don't need to carefully look at those. And the hidden to hidden are only in this part. There's no hidden to hidden connection here with the input. So this is the exact solution of this set of derivatives. All right, now it's a good exercise to go through. I think if you write down all the different elements, you'll see how you can put it together in the end, and just this is really just a notational convenience to put it together. Yeah, very good exercise to do at home. Now let's look at basically the norms of this Jacobian. So we defined, again, the final solution here was basically this equals this. Now let's look at each of these elements. Basically here we can define the upper bound of these norms as basically the norms multiplied by itself, with each other, I mean. And now we can just define the norm of W transpose to be beta W, and the norm of this diagonal, simple diagonal matrix, as beta H. And those are basically just by definition the upper norms, the upper bounds of those norms. Now the gradient in total is this product of all these Jacobian matrices, right? And each of these is associated with a step in the forward computation until the current time step t. So basically, once we put we try to upper bound the norm of all of these Jacobians multiplied with each other, we can basically get to this final output here, which is our beta W times beta H to the power of t minus k. Right, all the possible matrices, and basically applying this simple upper bound. And now the problem is that these betas could be either very small, in which case we multiply Jacobians and we multiply all of these numbers with smaller and smaller numbers, or they can be larger than 1, and then as soon as they're larger than 1, we multiply a number that is larger than 1 with itself many, many times. And so t can be 1,000, right, or 5,000. So even if one of the betas or this product here is only 2, it's to the power of 1,000 if we have 1,000 different time steps. And that's exactly why we get the vanishing or exploding gradient problem. So we basically applied the chain rule on a high level, and we looked at some simple upper bounds in terms of the norms of some of the elements of those chains in the chain rule, or elements of the derivative computation, and that's how we gain some intuition of where the vanishing and exploding gradient problems are coming from. Yeah.
So when you say the sequence length would be on the order of thousands, like are you applying this to an entire body of text?
That's right. So the question is, how do we get to 1,000 for time step t? And the answer is yes, we can apply this to a very long document, a whole book if we want. We can also compute character recurrent neural network models, where we have each time step is basically taking as input a single character only, and then computes a hidden state. And then you can get very quickly to very high time steps or very long time sequences.
Another question. So I see the problem with exploding gradients, that the locality assumption would be violated. But for the vanishing gradient problem, you would still get a strong signal from the early parts of the sequence.
That's right. That's right. So that's actually a perfect segue to the next slide. Why is the vanishing gradient problem actually a real problem? So again, the error at the time step will ideally actually tell us tell the next previous time step from many, many time steps away to change during backpropagation. So let me give you an intuition. So ideally, when we try to predict this word here, we will be able to modify some signal, like to change based on what the next word is. So let me give you an example here for language modeling. So similar things actually true for question answering and lots of other really hard problems in NLP. Let's say I have the sentence, Jane walked into the room, John walked in too, it was late in the day, Jane said hi too. What does your internal language model say is the next word? John, exactly. So you're able to take all the previous time steps from many time steps ago, and we can make this arbitrarily harder, right? We can say there's a battle in Spain, and now these two clans used to fight each other for many centuries and blah blah blah, and then they met again in the city of, right? And now you can put much higher probability onto all the cities of Spain. in your internal language models. If I asked you, like, give me the best probability estimate for the next city, you'd say Madrid or something. But if you forgot that it was about Spain and just had a lot of other family history, you would forget that and you couldn't predict that. So some people actually make a somewhat, well, it's kind of a fun argument of saying language modeling could solve all of NLP. Like, you can say, here's a bunch of input, I asked you a question, and at the end of the question mark, you need to predict the next couple of words, which are the answer. And you might also say, well, question answering kind of captures all possible NLP problems. What's the translation of a sentence? What are the part of speech sequences of the sentence? And so on. So in some sense, language modeling, if we really were able to predict everything perfectly, would solve almost all the NLP problems. Now, in practice, it doesn't really. But here we see the problem of why we might want Jane and John here to modify over 1, 2, 3, 4, 5, 6, and so on time steps to try to help us predict the next word. Now, the problem is when we actually backpropagate that the next word here is John, and now we multiply the Jacobian and it's smaller than 1, at some point it will, in many cases, empirically, you can get to at most 7 time steps back. And after 7 time steps, the error does not modify anything in our parameter space anymore. Basically, the gradients in almost all cases have vanished. Until then, they're so tiny, they don't change the internal states anymore during backpropagation on the W. And so basically that means the model cannot tell itself that really what mattered back here, you should give some change to your internal state to better predict the next word. And if you had general, simpler, non-recurrent models where you just have an input and you have a lot of deep model, a lot of very deep sequence, you can also get the vanishing gradient problem. It's not as common, but it still will happen. And we'll actually go through a little IPython notebook now. And that's, of course, very problematic. If you have some input, you have a very deep network, and then you try to predict some output, but now the output, actually, as you try to predict an error and you send your error signals down and they don't arrive at the input, well then the models will stay random, right? If that happens right away. And so let's look at a very simple and clean kind of toy neural network implementation and then compare 2 different unit types. We mentioned the rectified linear units already. And look at a very, very simple, it's not really vanishing yet, the gradient there, because it's only a 2-layer neural network, but it'll give you some good intuition, I think. So this is modified from an example from Andre's class in 231N, where we basically, let me zoom in a little bit more, just set up our simple matplot. Actually, just take the one that we trained already. All right. So we just set up our network, some simple plotting function, then we will randomly initialize here a very simple classification problem where we have the blue class, the yellow class, and the red class. And we make it so that it's not a simple linear problem that any simple linear regression or logistic regression could solve. And then we'll define our sigmoid function, the gradient. So this is essentially our f and f prime. And we define the rectified linear activation function too. Here again over the elements. This is always element-wise if it's a vector. Now let's define a simple 3-layer neural net. We have some inputs x, have some labels y that we want to predict. We'll have our step size, the alpha learning rate. We have a regularizer, standard L2 regularization. We'll define here getting all our, from the model, getting all our parameters out of that model. So we have our hidden states, the bias, and our W matrices for each of the linear layers. Now we do simple forward propagation. Let's take the standard case that we looked at a lot more, which is the sigmoid. We have basically sigmoid off, and then simple matrix product times our input x, plus our bias terms, and then element-wise non-linearity applied to it. We'll do that again. element-wise nonlinearity, hidden layer, it's in NumPy with the dot plus the bias term, and then here the final output of our scores. So W3 here is the softmax, or the softmax weights, and we exponentiate them, normalize them to get our probabilities. Now we'll compute our log loss, basically the average cross entropy loss, just like we did in lots of other examples, and like you will do in problem set 2 also when it comes out tonight. We'll compute the loss coming from our predictions. Y here is also, again, the classes that we try to predict. Then we have part of the regularization that adds. Now just we have basically the regularization just had a regularizer times W each of the Wij's squared. So the derivative is fairly straightforward. It's half times that. But for just computing the loss, that's just the default L2 regularization. Overall loss is from the data plus the regularization. All right, then we can print this as we optimize this. So this will be, at multiple steps. So now we'll go backprop. We did forward at each time step. We computed our hidden states. The hidden states, again, were just hidden layer 2, and the scores, and then the probabilities. So now we go back through the network in our backpropagation, and we've derived all of these very carefully. You derived in the first problem set the delta messages that will come in for taking derivatives of the softmax. So that will be the delta error signal that's coming from the scores. And then the derivatives, we also learned, are always the activations that are coming in times the delta that is coming from the top of that layer. So that's the derivative of W3. And then derivative with respect to just the bias terms, or as it often is the case, just the deltas. We derived that too early in the class. Now let's look at the simple one, sigmoid, because we kind of see more of the equations that we derived carefully. And this is a really nice toy example. It's also on the website. You can carefully go through it. We have exactly the equations that we looked at before, which is W transposed times delta. And then we have times the element-wise nonlinearities. That was the main final equation that we had derived. And we see it here nicely on one line in the code. And then again, the hidden layer times the delta message that comes in with the outer product to get the derivative of the matrix W2. And again, the bias terms, and then same thing again with the final W1 to get all the derivatives. All right, now we'll just add everything from the regularization, update our weights with the gradients, step size, and so on. And then we can also evaluate at each iteration what our training set accuracy is. Again, by just doing forward prop through network, getting our classes, and then looking at how often we get the predicted class to be actually the true class Y. Are there any questions about the code? I'll walk through it semi-quickly. So the question is, do we only have an input at the first layer? So let's look at the forward propagation. So here's forward prop. We basically start to compute the first hidden layer based on the input data x that we get times W1. So the input to the hidden layer 2 is the output of the hidden layer 1.
Yeah, so we
don't have a library for like the recurrent network?
That's exactly right. Yeah. So the question is, how is this different to the recurrent neural net? You're right. So this is a total toy example. This is not a recurrent neural net. It's just a 2-layer neural net, and it's just the standard definition of a neural net. And what we'll see is basically a very toy version of the vanishing gradient problems, which is we'll just observe that the gradients that will arrive at the lower layers are already much smaller than those that arrived at the top layers. Yeah, great question. Yeah, that's good clarification. So yeah, this is not a recurrent neural net. Just a very simple toy example of a standard neural net. Thanks. All right, so now we can train this 3-layer neural net. We initialize all our parameters to small random numbers. Iterate a couple times, train it with 2 different types of nonlinearities, rectified linear and sigmoid. Let's focus more on the sigmoid. And then we can basically look at the sum of the magnitudes of those gradients over time. And the main simple observation we're trying to make here is that the sum of the magnitudes of the gradients that come into the first layer are already much smaller than those that came into the second layer. And this is not even recurrent neural net, right? This is just a simple 2-layer neural net. And we already see that they're almost half the size. And they're already relatively small. So now imagine they get halved each time, and you have 1,000 time steps, right? They're basically 0. They're getting close to 0 very quickly. And that's the main thing here. And it's slightly, it's not as bad for rectified linear. And in fact, the rectified linear are just linear once you're not at the 0 stage. So you won't have this problem as much. It won't go down as much. But then if you can think about it, if you take the same matrix W and you have some parts of which are linear, and you keep multiplying the same W with linear things, then you get the exploding, even not even exploding gradient, but exploding hidden states, right? Because at forward propagation, you multiply the same thing, and for all the things that are positive, you blow it up. So rectified linear are not like the simple, straightforward solution that you might think they are. Though they can help, and we'll get to that a bit later. And so just to look at the outputs here, you can kind of nicely see this is the output with the sigmoid. It actually wasn't able to perfectly fit this example right here. And this is the output with rectified linear units. You can see some of the lines here a little straighter because it's a linear element for each of the hidden states. And it very nicely fits this function. So this is a great intuition and a very nice, super simple kind of toy example for implementing straightforward neural net from scratch in NumPy. It's on the website in the syllabus page. All right. Are there any questions about the example? All right. Now, of course, we do actually use recurrent neural nets. So how do we deal with these problems? Well, vanishing gradient problems are much harder to fix, and it's something that we will only learn about next week. Basically, we can't use the same vanilla recurrent neural net definition that we just saw. We'll have to use long short-term memory recurrent neural networks that are much more complex, but also now that we have the basic Lego blocks, just interesting combinations of those Lego blocks. For the exploding gradient problem, that is something you really have to solve because you can't train them at all if this isn't the case. And maybe one last word on the vanishing gradient problems too. If you think that all you need to know to make a certain predictions are the last 7 time steps or so, then the vanishing gradient problem isn't that problematic, right? It's only the problem if you really want to push the accuracy higher and you think that your problem requires you to understand the entire sequence of the words that came before. All right, now let's look at the exploding gradient problem. Basically, this is a super simple trick. It was first introduced with no mathematical sort of reasoning other than it works. By Tomasz Mikolov, and the trick is, well, whenever your gradients get too large, you just set them to a maximum amount. Problem solved. Now, of course, when you run your gradient check through that and your gradient check hits that and you just clip it, your gradient check will fail. It's not the actually correct derivative, right? It just happens to work incredibly well in practice. So we just have a maximum threshold, and if the norm of our gradients gets above that threshold, we set it back to that threshold. Super, super simple, but makes a huge difference. Then a couple of years after Tomasz Mikolov introduced that, Joshua Benjo and his group tried to actually understand what's going on there and gain some intuition. And I really like this paper. It's from just 3 years ago. And again, these recurrent neural networks are super old models, right? They've been around for many decades. But when people say, oh, there's nothing new, it's just kind of taking old neural nets and there's nothing exciting in deep learning, then there is actually a lot of exciting stuff here, right? People are understanding these models a lot better. They come up with lots of tricks to actually be able to train them, and that's one of the many reasons for having this resurgence in deep learning. And it's not just sort of the old connectionist networks. There are lots of interesting new ideas, and this is one of them. So let's look at the super simplest possible recurrent neural network that we could come up with, which is only has a single hidden state. So instead of having h be a vector, it's just a single number, a scalar. And we still have the value of b, our bias term. And we basically try to have a very, very simple prediction problem. And now we can visualize how big the error is depending on where the weight is for that simple prediction problem. And here is basically what this really great visualization shows us, which is they're very high curvature walls when you optimize the objective function. So usually when you take convex optimization, for instance, you always assume you have a very nice bowl and you kind of try to get to the global optimum. And you see this is basically impossible here. And it's a very not well behaved kind of objective function and optimization landscape that we're trying to optimize. Now, when you're here, you have this relatively smooth curvature, and you basically just take small steps for each gradient descent step that you do. And you'll notice here is basically once you hit this point here, this high curvature wall, the standard gradient descent will push you way back very far from this to try to avoid this. But now you're basically way off again from further away from where you started, and you're much worse off because now, who knows what's over here. Now the idea of clipping the gradient and rescaling it is essentially just say, don't go crazy, don't go very, very far away based on what you've just observed. So very, very simple intuition. Yeah.
What if you're actually up in the upper left corner and you see that you fall down a lot and you prevent yourself from falling down? This method.
Yeah, I mean, we don't know the entirety of that landscape, but just empirically, that doesn't seem to be the case. There's, you sort of see it here slightly that, it might just keep going up. All right, now there's another trick for dealing with vanishing gradient problems, and it works for some cases, but it's not the final answer that everybody will use. But there are two important tricks. The really important one is we can actually initialize our W's, both the WHH that goes from hidden to hidden, as well as the WHX that goes from input to hidden, with the simple identity matrix. So just that, it seems so trivial, but it took people several years. I came up with this idea in another type of neural networks, actually more general. We'll get to it in 2 or 3 weeks, called recursive neural networks. And then Kwok Lee, a good friend of mine, is working at Google now, came up, this was 2 weeks ago in a year, sorry, should have updated that. Basically last year with a similar idea. Initially, intuitively, what that means is that whenever you bring in a word vector, as you start your optimization, all that you will do is you kind of average them all in. right? And then you let the model start doing something smarter than averaging. Intuitively, when in this IPython notebook, what you'll observe is that in most cases, what most people will do as they initialize their W matrices, it'll just be random numbers, completely random. So as you take an input in and you project it through one layer neural network, it'll basically be a completely random transformation of that input. Now, what this idea is basically saying is, well, let's not make it completely random. Let's actually just by default average the word vectors as we start to try to compute what a good hidden state is. And then he also actually uses the rectified linear units, and he uses it for sequences that aren't super crazy long. Now, actually, this example here, for instance, is kind of a artificial data set where they try to compute the class of digits. So you have basically digits from 0 to 9, and you have little pictures, let's say 64 or 32 by 32 pictures of that, and instead of running a convolutional neural network, which we all know is the best model, they take a recurrent neural network and then take the input at every pixel as the input at that time step. And they run a recurrent neural network over all the pixels. So you have a relatively fixed, it's at most 32 by 32 many hidden states. And if you have very small initialization here, or just have this identity matrix, it's not going to blow up. You're not going to have like gigantically long sequences. So you can get away with the rectified linear unit here. And they show that the combination of these two ideas will get much higher test accuracy, and you can train the recurrent neural network to higher accuracies. Now, on a more realistic problem of recurrent neural networks, and really how they started to gain a lot of popularity, is in language modeling. And so again, Knester-Ney is kind of the de facto standard for language modeling before neural networks came out, and for many people who are skeptical of deep learning, it still is, that basically is a clever way to combine the counts and the probabilities from a 5-gram model and 4-gram model and 3-gram model and 2-gram, unigram, and bigram models. And so here we look at perplexity, which is exactly based on the definition that we gave before, 2 to the negative the average log likelihood there, and our average log probabilities. And what we see here is that basically for a standard corpus like the Penn tree bank, the model is less perplexed if it's a recurrent neural network than it is with this Knester-Ney baseline. Now, all those numbers have since gotten even further improved, but this was one of the first times where people thought, wow, neural networks can actually be really useful. And again here, the RAM requirements of the neural networks are already a lot better than that of these gigantic count-based models. Now, this one is a little confusing. There's backpropagation through time. It's actually they should be the same thing. There's basically a very simple trick which wasn't that obvious to the authors at the time, but really as you do your forward propagation, you only have to do one backpropagation to update all your weights. Basically, you sum up all the delta error signals that you get at each time step as you go backwards through the network only once. And originally the authors of that paper thought that you have to do that at each time step. So at time step 10, you go and you backpropagate your errors all the way to time step 0. Then you go to time step 11 and you propagate all your errors to time step 0, and you go to 12 and you go to, Instead, what you have to do is you start at the end of your sequence, and you sum up all your deltas, and you keep going backwards until time step 0, only in a single pass. Now, one trick that was evaluated and analyzed is to also have so-called class-based or hierarchical predictions. It's not super hierarchical, but so the first step in that idea. And the main idea here is to actually have classes, and each class only has a subset of the words. So at training time, you only need to update the class probabilities, of which there are between 30 to a couple of thousand instead of hundreds of thousands, and then the probabilities inside that class. And so we'll basically compute the probability of the next word given the history. History is now our just hidden state h in this factorization. We'll first compute the class given the history, and then we compute the probability of that word given that class. So that makes things a lot more efficient. So the minutes here per epoch are basically much smaller if you have fewer classes, and then as you have more and more classes, it gets slower and slower again. Likewise at test time, but basically your perplexity also suffers and the model works slightly less well. But it's a really clever idea, right? Because again, your softmax has 100,000 words in it. So you always, just to predict the next word, you have to have a matrix multiplication that's very costly of 100,000 times the size of your hidden state. Here, you just have times the size of your hidden state times the number of classes that you have, and then the number of words in that class only. So it's much more efficient. Are there any questions about this? Yeah.
How do they mix the RNN and the KN?
How do they mix? So there are a bunch of different ways. The simplest one is you can just average the two probabilities from both classes. And then you basically, if one thought it had higher probability mass, it'll improve the output and the perplexity a lot. All right, now those were the simplest problem, and really very few of you need to evaluate language models again. It's kind of been one of the most sort of done tasks in NLP. And so there's some higher level, and it's also usually only in sort of intermediately useful task. It's not useful by itself in many cases. And in fact, nowadays, the holy grail for a lot of the projects and a lot of the applications that we'll do is so-called end-to-end training, where you just care about the final thing and you don't have any other objective functions in there. You just train the one thing that you care about, you have a very large data set for it, and you train everything, the whole model, jointly, including the word vectors. Propagate into everything, take derivatives with respect to every single parameter that you have in the model. You don't need to train one thing. So let's look at sequence modeling. For some other tasks that are a little more exciting, such as named entity recognition, which by itself is actually useful. There are companies that actually pay you, or you pay them like a cent for every document where you find your named entity tags. There are other fun tasks that we can basically do now with this model family, where we want to predict any kind of label we can think of for a specific word. It could also be entity level sentiment and context. There are thousands of companies that say, if you're a company and you want to understand what people are saying about your product on Twitter, we'll go out and find all the mentions of your company, we'll disambiguate whether it's Ford, the car manufacturer, or Ford, the actor, and then we'll find only those that are the car manufacturer, and then we look at entity level sentiment. And another one that's kind of fun and a little less often seen is identifying opinionated expressions in general. So this is a fun paper by Ozan Irjoy and Claire Cardi from just 2 years ago on basically opinion mining with such recurrent neural networks. So now you can see you're actually literally close to the cutting edge of what real research is doing in the last couple of years. So here they basically want to classify each word as either a DSE, a direct subjective expression, or an ESE, expressive subjective expression. And I'll just give you a real example here. Let's say, for instance, the committee, as usual, has refused to make any statements. So now, as usual is an expressive subjective expression. It basically indicates a sentiment without explicitly saying it. It's not this is bad, but it's like as usual, and then you kind of get that they're trying to indicate here that they're a little annoyed. And so we're going to use very common notation. You may actually see that notation if you work on sequence labeling problems in your projects too, which is the so-called BIO notation, the beginning and inside of any kind of tag that you may have that has multiple words being in the same expression, and O is basically it's not any of the labels that we have. So BIO, pretty common notation scheme. again, yeah, tags either just beginning of the entity or the continuation of that entity. So as usual is 2 words, it's 1 ESE, and so we'll have basically give the first word a BESE and the second word an IESE. All right, now the simplest thing we can do is just apply that exact same recurrent neural network again. And now I've gotten the feedback from some folks that it's better to have the exact same notation for everyone, but I also want to prepare you, if you try to read the related materials, you'll see that every single paper often uses its own notation, and they're all kind of the same, but I want you to be able to be familiar with those, and really you'll see very quickly through just using different letters and different notation. But here, basically, we have again x, our word vectors, so that's exactly the same. Now W here is not hidden to hidden, but it's just observed input to hidden, because x is our word vector. Y is now our output label. Similar again as to softmax, but instead of calling it the softmax function, I see written out as softmax, he calls it G. And now H is again our memory, computed from the past memory and the current word. So this is exactly the same recurrent neural network that we saw in the first couple of slides of this lecture, just slightly different notation. And we'll see in a second why it might help to have this notation instead of superscripts. Because we'll introduce now bidirectional recurrent neural networks. So let's say we wanted to predict as usual, and we want to predict usual by itself. Now if we've seen just as in the side from the left, then maybe we're less certain whether this has this exact label, but if we see the comma in front of it, maybe that will help us to make that distinction. So in general, to classify a single word in a context, it's very helpful to look at not just the left context, but also the right context. And that's the very simple intuition behind why we might want to use bidirectional recurrent neural networks. The main difference, there's really no difference. One goes from the left to the right, and one goes from the right to the left. You can basically take your sequence, reverse it, and then run another recurrent neural network with a different set of weights. Simple idea, very powerful. Again, because we can use information from the words both preceding and following the current word that we're trying to classify. So now he uses this arrow to the right for the simple recurrent neural network that goes from left to right, and this arrow goes from right to left for the recurrent neural network that goes from right to left. And now imagine we had the superscripts of HH, it would get kind of ugly. So that's why he dropped the superscripts and we just use different variable names. Yeah.
So at test time, does he average out the hidden states, or does he just run the two networks and average the predictions?
That's a great question. So the question is, what does he do at test time to actually predict Y? And the answer is in the slide. Can anybody see it right away? Let's try to analyze the notation very carefully. I guess this is not really a notation we described very well before. What do you guess this would be? That's right, concatenation. So the idea that he will use is he will actually concatenate the hidden states from forward and, well, now I can't say backward because that would be, it's not actual backpropagation, it's just a recurrent neural network that goes from right to left. He will basically concatenate these two vectors and gives that as an input to the softmax. Your suggestion of maybe averaging is actually not that far off. It would be a very reasonable hyperparameter to try in your model either averaging or concatenation.
So does that mean that when he trains the weights and he's backpropping through Y, he's actually backpropping through that concatenation? And
that's right.
U is the U another weight matrix?
U is the softmax weights.
Oh, okay.
So the softmax weights now don't get, they basically have number of columns, not just D, but 2D, where D is the hidden dimensionality of the hidden states.
You're not applying an affine transform to the hidden layer anymore?
No. I mean, you applied the standard recurrent neural network coming from the left, standard recurrent from the right. They all have their non-linearities. And then you just have your softmax weights, but those are basically number of rows is the number of classes that you have. So he here has basically 2 classes for each of the 2 types of things he wants to find plus O. So there are 5 potential classes that you might want to predict. Yeah?
So I still don't understand the fundamental reason for having a bidirectional RNN. Is it something like that, even though we want the state in the RNN to capture everything that has been seen, it truly does not do that, so that's why we need to have bidirectional?
So the question is, why use bidirectional recurrent neural nets? Is it because we can't really keep track of everything that's to the left? The answer is, even if we could keep very good track of everything that's to the left, it will help in many cases to predict a label for the current word by also taking into consideration everything that's to the right. But the recurrent neural net, maybe we don't have enough time to do the switcheroo, but basically at each time step here, you get it? All right. So basically the forward prop here will only be modified by these 2. Sorry, the left to right RNN will only be modified by these 2, but now maybe the words that come right after modify and give us a lot of really obvious signal. So let's say, simple example, you have an adjective that could also be an adverb. He is, okay, can't come up with a good example, but some adjectives can be adverbs too. And now you see, just afterwards, you see a noun, and then you say, oh, like bad. Like he's, well, you could say badly. Anyway, you get the idea. So if you see a noun right afterwards, then it's obviously an adjective. If you see a verb right afterwards, it's an adverb. And so that is a simple way where you don't even need to know all the context from the right, but just the last couple of words to the right, and this model will help you. All right, so H here represents, basically in some sense, summarizes all the past and future around that single token. Now, what if we wanted to make it even more powerful, and we actually want to have a deep transformation that every word vector goes through and every hidden state goes through? And this is the final culmination of models of today's class, which is a deep bidirectional recurrent neural network. And now you understand why TensorFlow is so amazing, right? This is just another computational graph with a bunch of nodes, and you just define it with this equation, and now you don't have to manually go in and derive all your derivatives. Imagine how horrible that would be. It would take us probably like 2 lectures just to go through all the indices. So intuitively, it's very simple, right? We have now at each time step 3 hidden layers before we predict the output at that time step. And now each of these will basically have also recurrent connections at that hidden state. Yeah?
So for the input X, are we giving it the raw words codified as like one class, or are we giving it word embedding?
Those are still word embeddings, so they also came from a complex model.
So why would you need to give it word embeddings? Because it seems like...
You're totally right. You don't have to.
Yeah.
You could, in theory, assume that those are one-hot vectors, and then the first layer kind of brings in the word vector, because if it is one-hot vectors, the columns of those would essentially be the word vectors. You're right. So this is like a monster of a model. Turns out to work slightly better. Now, really quickly, how do we evaluate this? This is actually kind of important. I'd like to go through it a little more slowly. But you basically have manually labeled all these different, at every word you have the crown truth label, and you just look at how often you get it right. The problem is that most words don't have any of the main important 4 labels, the ESE and DSE. They're just O. They're not a subjective expression at all. And so if you just looked at accuracy, if only 5% of all your words are either a direct a DSE or an ESE, then your accuracy is 95%, and you think, oh, this is so great, I'm done. So whenever you have such a skewed distribution, it's extremely important to actually evaluate with F1. So F1, very simple measure. Basically, we look at the precision, it's the total true positives, and we divide the true positives with the true positives and the false positives, and we look at recall true positives divided by true positives plus false negatives, and then we have here our precision recall. We multiply those two and basically get here this mean F1 of precision and recall numbers. And that will essentially balance out, and you can't just say, well, everything is in the O class, I get 95 accuracy, right? That might have high precision, but then very low recall, because you're losing all the ones that aren't that, and you basically average those two out. Now, we can look at number of layers and what helps and for different problems, and basically we'll observe, regardless of whether you have 24,000 parameters or 200,000 parameters, that after 3 layers of depth at each time step, you don't really gain anything in F1. All right, so let's quickly recap. Recurrent neural networks, one of the best models, model families of all of deep natural language processing, likely one that you'll want to use and compare with in your projects. With TensorFlow, you'll be able, in problem set 2, you'll be able to very quickly implement that. Training them can be hard. TensorFlow will automate some of it. You really want to carefully look at your vanishing and exploding gradient problems, especially if you think that the important signal for any prediction you're trying to make at a time step is many time steps away. You're going to want to use more important and powerful RNN extensions like LSTMs and GRUs, which we'll cover next week, and then you're all set for some really cool projects. Thank you. Hey.
I'm running this NLP with a MapReduce.
Cool.
And I'm getting some error, exceeding the GC error.
All right. Hello, everybody. Sorry for last lecture's fire alarm. Stopped us right in the most exciting bit on LSTM, so we'll try to catch up today. I hope we'll still be able to finish on time. LSTMs are super important, so we want to make sure we give them some time and gain some intuitions and that you ask some questions. We also had a video issue. Unfortunately, with the craziness, we kind of lost the audio of Tuesday's lecture and the video. So for those of you who are now only through video, the Stanford students can log into STPD. And for YouTube, we'll try to find another solution. But worst case, it'll just have to be last year's lecture and then check the slides for a diff. Are there any questions around organization for the class today? I hope you're all TensorFlowing away now. All right, awesome. So today we'll finish LSTMs and then we go into recursive neural network, a whole different kind of model family, though we'll see there are lots of connections also to recurrent neural nets that we've already covered. So this is where we ended on Tuesday, just when the fire alarm started. So we defined our LSTM, which is essentially another way to try to combat both vanishing and exploding gradient problems, but also keeping around longer term context and information from many previous time steps ago. And we again here have just a couple of standard neural network layers, 3 of them, the input, forget, and output gates with a sigmoid to be between 0 and 1, and a new memory cell, C tilde. And then we will compute the final memory cell, C, by basically multiplying the, again, this is the Hadamard product, just element-wise product. F is a vector, CT minus 1 is a vector. We multiply here, so if the forget gate is all 0, then we will ignore the CT minus 1, the cell from the previous time step. And if here we have now an independent input gate, so the input gate will define how much we're going to use from the intermediate memory cell. And then the final hidden state again has the option also to essentially take into consideration this input again element-wise, or ignore parts of that input to make a final prediction. So usually we could have, for instance, a softmax classifier on this HT, but maybe we want to keep things around from previous time step, but we want to make them irrelevant for the actual classification of the current time step. So it's yet another tunable parameter that the model itself can tune and determine whether it's important or not. Yeah.
When do you choose between NH or sigmoid?
So here, the sigmoid is kind of the right choice because we want to either ignore inputs or smoothly go to really caring about them. So in this case, you almost always use the sigmoid. And here, theoretically, you could use ReLUs or other activation functions, in theory also sigmoid. Some of it is a bit of a black art. It just happens to optimize better with 10H. But also, if you have here ReLUs, then let's say your ReLU brings in a really, really large number, and now you actually have an input gate that wants to kind of ignore this input and put it at 0.01. But now because your ReLU is so large, your input doesn't have enough power anymore over actually modulating how much that input matters. And so it, in some sense, makes more sense here to keep around somewhat bounded activations. Does that make sense? Cool. All right, any other questions around the definition and equations? Yeah.
Can you give a little bit more information about how the input gate, which is the I, and the input modulation, or the block gate, which is C, how that T, like how they're actually interacting with each other?
How do I and C tilde interact with one another? I guess in general, the input gate basically can just modulate how much the current time step matters. And in some ways you could say, well, why have HT minus 1 here at all, for instance? But then you would hope that whatever this modified, I can still kind of overrule. So in some ways, because C tilde is in this formulation bounded between -1 and 1, it's still at the whims of the input gate to really be taken into consideration or not. But for instance, interesting enough, the input gate here is only between 0 and 1, right? So if this is negative, and unless I is almost all the way to 0, it will stay negative, for instance. So, but there's no, I don't know what else to say about how much they interact. I mean, you basically just have this simple product between numbers, and some are between 0 and 1, and others are between -1 and 1. But intuitively, it makes sense to basically allow the input to ignore all of what came at this time step here through C tilde. So basically now, this kind of model could, for instance, very easily keep a counter, a very simple counter of trying to, in your memory cells, keep around a lot of information. And also note here, yeah, so you apply the 10H after the CT. So just to get to the final hidden state. Cool. So now I think all the illustrations of LSTM units are a bit overwhelming and in many cases not super useful. At least not, I didn't find like they give me better intuition than the equations. But people are different, and so of all of them, some I think, yeah, but it depends on what you want to do. Basically here you define your simple multiplications, and you have nicely here overlaid where you have what kinds of non-linearities and sigmoids and so on. So this is one such illustration. I find this one a little more useful, and this one, I guess, it abstracts away a lot. So you kind of see, all right, intuitively your memory cell input comes, you have the input gate that will modulate how much that memory cell input matters. Your forget gate can determine how much of the recurrence do you ignore from the past and how much do you want to forget from the past, and then your output gate can kind of determine what you actually use for classification at that time step. So those are just different illustrations, people trying different ways to make it a little more intuitive. I think it's one of the nice things and clear differentiators for the GRU is that we really do have that ability to say, at this time step, while I have some information that I think will matter later, I will not expose that to our softmax classifier, right? So that is one of the things that are more powerful. LSTMs, while very old, are currently very on vogue, and you've noticed this if you came to Project Advice Office Hour already. I suggest using LSTMs for a lot of tasks as a good first baseline. They're very powerful, just like the recurrent neural networks. You can start abstracting away and you just say, well, generally I have some input xt and some input ht-1, and then I will do a lot of stuff in here. So this will just be my LSTM unit. And now you can stack them just like you could stack the recurrent neural networks. You can have deep LSTMs at each time step. You can, and then unfold them also over time. And of course now each element, each LSTM unit itself has multiple deep layers or multiple layers inside of it also. Now, because you have all these weights, of course, you do need a lot of data. So you have to be very careful. You know, if you have thousands, your input dimensions will basically determine how many parameters you have. And now you have sort of 8x times, you know, input or hidden dimension squared many parameters. So if you have a 1,000-dimensional hidden state, 1,000-dimensional inputs, you all of a sudden have many millions of parameters in this model. And so ideally, you'll have at least a couple of millions of training data points to train this kind of model. Yeah?
Could you explain which one of those gates actually contributes to vanishing gradients?
So the vanishing gradient problem here. So you have CT, so the question is which gate matters most here. And in general, the vanishing gradient problem can be fought if you can take derivatives and you don't multiply numbers that are smaller, much smaller than 1 with the inputs from the previous time step. So in this case here, we have clearly CT-1, for instance, and if f this forget gate, which is really kind of 1 minus the forget gate. Some people define it differently. You'll see a lot of slightly modified versions of this. Some people write 1 minus ft and so on. But the main idea, there are a lot of different LSTM variants too. I pick one here. A lot of people tried a lot of different variants of adding, you know, additional Hadamard products here and there and inside here, and there's so-called peephole connections that will allow you to have access and so on. So there are a lot of different ones. In fact, there's a great paper by Jürgen Schmidt-Huber called LSTMs as Search Space Odyssey, where he takes a bunch of standard benchmark data sets and compares like 20, 30 different LSTM variants on all these different ones, has lots of really great plots. It's actually a good paper to read if you want to also in your project kind of carefully compare a bunch of different models. But basically here is if f is close to 1, then you multiply here a number by 1 in order to get push your delta error signal through to the previous time step, and so that will basically make the gradient vanish much less than if f was close to 0. All right, so last year, and I mentioned this before, when I said, you know, deep learning is on the rise, even for machine translation, it was just in the second place in a WMT, which is a huge machine translation competition. It's a workshop on machine translation. It's international competition. Lots of top groups in translation compete in this workshop and have public data sets for training and development and then testing. And last year, the systems that were based on deep learning were still not the very best systems. And I had oracled that this will change. And indeed, the competition results, all right, not from yesterday, but from Monday. So I was hoping to get to this slide on Tuesday. So basically from this week, it's a little hard to read, but when you look at the top systems, you will see neural MT, and what that means in most cases is you'll have some kind of gigantic GRU or LSTM variant in the model. And now all the top entries here are basically neural machine translation models. And in general, if you get asked, when will deep learning work better? Well, if you have near infinite data, deep learning will eventually solve the problem one way or another. better than most other traditional machine learning techniques. And machine translation is one of those areas where you have a lot of training data. Like you talk many gigabytes of training data. And it's a nice place also to apply monolingual data, of which of course you have like terabytes. You can download all of the internet as much as you can, collect in monolingual data, and you can improve machine translation models through that. And at the very bottom here, you have various phrase-based systems that kind of keep around the counts and do a bunch of clever feature engineering. And even those eventually started incorporating neural network models, but weren't able, if you still have mostly the phrase-based systems where you take the counts and you do all the alignment and stuff that I described, they're just not competitive anymore with the top neural systems. Now, there's some fun things that fall out of deep LSTMs also when you basically just look at what are the hidden states of the translation. And in general here, I'm cheating a little bit, so this is not necessarily just a single LSTM. This is going to be a more powerful deep LSTM. So let me just showcase really quickly what I mean here. So in general, we have our input vectors xt here and xt plus 1. And we plug those into some recurrent neural nets, and those were xt plus 2. This is our standard recurrent neural network. Now, we introduced deep ones, where now you can have connections and at each time step actually have deeper layers. Now, what you'll often see is that people will just say, well, this whole block actually is an LSTM layer. And so internally, it has its own little layers, but people don't even draw those anymore. It's becoming more and more of a complex Lego block. People just accept that Lego block consists of 5 other Lego blocks that we all defined very carefully in the early classes, single layer neural nets put together with some Hadamard products, and that will be an LSTM layer. So when you have these neural machine translation models, you have 1,000 dimensions for each of the hidden layers. So you have millions of parameters, and then you have times 8 for all the different blocks and matrices inside each of the parts of the LSTM, and then you have multiple of these times 1, 2, or 3, or even 4, where we have different layers of LSTM blocks. So these are pretty crazy beasts to train with huge number of parameters. Does this make sense? I know my handwriting is terrible. Basically, you can abstract away the more complex Lego block here, and then have kind of the LSTM building blocks where you have a bunch of separate layers and they all get put together. But in the end, they usually have an input x, some ht minus 1, or sorry, I guess this is ht. And this block will have some output ht plus 1. And that ht plus 1 will be the input to this next higher order LSTM block. Yeah?
So there are 2 outputs for each Lego block?
Are there 2 outputs for what?
So there are 2 outputs for each block. So one goes right and one goes left.
That's a great question. Are there 2 outputs per block? So each LSTM, if we can switch back to the slides, each LSTM has an HT, but now that HT is taken as an input both to the next time step as well as to the higher order LSTM at that time step. So basically, if you're looking at a higher order LSTM, you'll replace XT with HT from the lower layer. So you could introduce like superscripts, for instance. So you have, for the first LSTM block, you have H superscript 1 at time step t, and then you have H superscript 2 at time step t that takes as input the output of that layer. Cool, so now we can look at the vectors from the last time step of the last hidden layer, and we trained that with a machine translation model, a very deep LSTM, that actually goes back to a lot of the very simple stuff that we described when we just had the RNNs, but instead of having a simple single linear layer, you have an LSTM block, and now you'll basically observe that some very interesting semantic patterns are falling out of this. So we can take this 1,000-dimensional vector now and apply PCA to it, and then look at a couple of sentences and the encoder that you get from them. And really cool stuff happens here. So for instance, Mary admires John, and Mary is in love with John, and Mary respects John, for instance. They're all close to one another. Or she was given a card by me in the garden versus in the garden I gave her a card, are also close to one another. So what you see here is that despite the word order being quite different, the different memory blocks and cells of the memory actually kept around the relevant information in a way that is somewhat invariant to the order of the words. So this is super exciting results. So really, machine translation is a great way to train models to just learn great representations for the language that you care, that you actually care about. It's almost as if it gives you a grounding in a way to understand, well, if I had these two sentences and one translator translated into this language and another translator in another book with a slightly different word, maybe didn't give her a card, but a car or something, it learns that these are all very similar from the translation. So translation is a great supervision for learning good representations. And like I said, you could combine these in various kinds of ways. You can add new kinds of feedbacks and so on. And this is not, I'm not going to ever ask you to derive this and to really follow all the details, but I want to show you that now that you have these Lego blocks, it's a crazy exciting time right now, because everybody combines the Lego blocks in new kinds of ways, and you can have these input and forget gates, and you can modify them between different layers. And right now they're still very quickly, you can come up with new models and see if in real experiments on real data sets they actually improve outputs, and you can get some cool papers out. All right, so now we've basically covered recurrent neural networks. They just go from left to right, have a good time step. They're super exciting, a lot of ongoing work these days. The GRUs, or gated recurrent units, are much better than standard recurrent neural networks, and the LSTMs are often even better, but not always. So you really have to carefully compare the two. And again, this was sort of very advanced stuff. I'm not going to ask you to take a deep LSTM and derive all the gradients. It'll just be so many sub-indices. It's unpleasant. But really want you to gain intuition of how you can now creatively play around with these basic Lego blocks that we introduced, and you can combine them in new and creative ways. And you want to gain some intuition. Oh, my gradient vanishes because I multiply numbers here. Oh, if I add this gate, then maybe this won't happen as easily, right? So these kinds of high-level intuitions are what you should take out of the past lecture, but also what I'll talk about now, which is recursive neural networks. They're much simpler, so you should be able to follow it a little better, but we also don't have to go into all the details anymore. But if you still have questions, please do ask now and in office hours. Cool. All right. Any questions around recurrent neural nets? LSTMs, GRUs?
Why do you say that LSTMs might be better and juries out? Like, what are some of the benchmarks that lead people to question?
Great question. So when is it better? It really depends on the paper, and there are a bunch of papers that compare them on machine translation, on summarization, on question answering, and so on. And it's not obvious that in all of these papers, one model always wins over the other. And there's no nice sort of theoretical justification of why one would always work better than the other, and there isn't in practice a clearer answer yet either.
So it's not a question of one of them causes the gradient to go up, and they do just fine in that respect. It's more application specific.
That's correct. So it's not like one has a huge theoretical problem and always, has exploding gradient problems and the other one doesn't. They're both very powerful, very good models, and models that you ideally will run in a lot of your projects to compare. Yeah?
So how are these techniques for other languages than English?
So the question is how...
More cognitive, like inflectional languages.
Sorry?
Inflectional languages.
So the question is, how would these models work in languages other than English, and maybe some with crazier morphology and very long words? So to give you an idea of what this means, basically German, for instance, has some very, very long words, and the words themselves capture a lot of information. So you might have a Dampfschifffahrtskapitän, which is like a captain of a boat that is powered by steam, right? And so in English you'd have multiple words describing that, and in German you can put that all together. So now if you start with just word vectors, you're going to be in trouble because there's so much information there, because you can kind of creatively combine nouns into so-called compound nouns in German. You get a lot of rare words too that you might never see, and then it's harder to translate them. The same is actually true even for English when it comes to translating special nouns and company names and things like that. And so there are a couple of simple fixes, and in fact several of the papers here use this, which is one thing you can use is morphessor. So this is actually a way to split words with based on some very simple metrics into their morphemes, into the smaller parts, suffix, stems, prefixes, and compound nouns separating out the nouns. And then it looks to the model very similar, and it's much easier to just take the standard LSTM. You can also go all the way hardcore to characters. There are actually some papers that recently came out, and you just translate from one character sequence to another character sequence. It's quite phenomenal, but that also works very well. You have to fiddle around a lot with the crazy learning dynamics, because now the sentences aren't at most 20, 30 words, but they're 20, 30 times 5 or 10 or so for the word lengths. But yeah, you can go with these kinds of models all the way down to characters, and then the language doesn't matter. It used to also be for Chinese sort of the inverse problem, which is multiple separate characters might actually be put together as one word, and so maybe you would want to run first a way to do Chinese word segmentation, and then you translate the model. But these neural machine translation models and all the neural sort of sequence models, they can just take the characters and they figure out how to put words together. They're very powerful. Yeah.
Is there like a resource, like a paper on visualizing features from deep within LSTMs? Because I know there's been lots of work on visualizing the deep features from CNNs.
Right. So is there a good paper on visualizing RNNs? There is. There's one actually from this group, the NLP group at Stanford, Dan Jurafsky, and one of his PhD students.
Do you remember the name of it? Or?
I think it's visualizing recurrent neural networks or something. I can look it up after class. Do you have the title?
Justin Johnson. I know he worked on visualizing something. I don't know if it was with that group.
No, it's a different author. Cool. All right. So now let's talk about recursive neural networks. So generally, when we built our word vector spaces for single words, we found that they basically capture syntactic and semantic information, right? Parts of speech, like nouns, all cluster in one part of the space, and then as you zoom into the noun cluster, you see different semantic features and semantically related and similar nouns clustering together. So the vector of Germany would be closer to the vector of France than it would be to the vector of Monday, for instance. Now, of course, words never appear in isolation, and the question is, well, how do we represent longer phrases, like the country of my birth or the place where I was born? How should we represent the meaning of these longer phrases? Not just like all the context of everything we've read so far, but that phrase in isolation. And the simple answer can be, well, we also just want to map them into that same vector space that we had the words in. And ideally, they will now also capture syntactic and semantic information. So noun phrases that have prepositional phrases inside of them, like the country of my birth. Of my birth is the prepositional phrase. The country of my birth is an overall noun phrase, which recursively has another noun phrase inside its prepositional attachment here. So ideally, those will also capture similar syntactic and semantic information. And so we've looked a lot at single word vector spaces in this class, and there are lots of other methods that we haven't gone into, traditional methods like Brown clustering. And certainly those kinds of vectors are useful as features to be plugged into any kind of machine learning model, neural network or not neural network. And then we also have in information retrieval and other fields document vectors. So the simplest one is just a bag of words vector, where every word that exists in a document gets a 1 every time I see that word in the document. And you have just a size of a vocabulary kind of document vector. Now, of course, the bag of words kind of representation will ignore word order and is not as ideal. You have to say, though, that if all you're trying to classify is the general topic of a document, you might not need to understand the whole sequence of all the words, right? If you just want to say, is this about sports or politics, you don't need to understand carefully how each word comes after one another. All you need to do is identify, well, does it mention Obama, does it mention the White House, and so on, or does it mention, touchdown and things like that. So for very simple information retrieval or document exploration and classification problems, you might not have to go all the way to a complex neural network model. Now, where it gets really interesting is when we try to describe phrases and sentences in a way that captures the word order as well as the complex semantics that we might see, such as negation or something, and you have maybe just a short tweet or a single sentence that you really want to carefully understand well. So that leads us to the question, how should we map phrases into a vector space? And one answer that will lead us to recursive neural networks is to use the principle of compositionality, which is a really interesting, very powerful principle. And in our case, it will state that the meaning vector of a sentence is determined by 1, the meaning of its words, and we already have nice word vectors for those. And again, these are just visualized in 2D. We know already they're usually 50 or higher dimensional. And 2 are the rules that are used to combine them. So in recurrent neural networks, we just said, well, we'll always take one word at a time, and we compute a context vector that just captures everything from the left that we read up until that time point. But maybe we want to have representations for all the syntactically plausible phrases by themselves. So maybe we want a representation for my birth, because I could replace the country of my birth with like the country of my choice or something like that. And so maybe we want to be able to understand how we could replace this one in the rest of the phrase. And so the country is a proper noun phrase by itself. Of my birth in grammatical analysis is a prepositional phrase. And so we might want to change the order in which we're combining words to always try to keep around a syntactically plausible or grammatically plausible phrase. And then ideally that representation will still end up close in meaning to the phrases that are similar. So the country of my birth should ideally be similar to the place where I was born. And so the models in this section will actually allow us to jointly learn these parse trees, these grammatical analyses, as well as the compositional vector representations that represent ideally syntax and semantic information. So in sentence parsing, what would we want? Well, this is a very sort of fundamental task. A lot of folks in NLP have worked on parsing for many decades. And so just to give you a little bit of an idea, again, we could have multiple lectures just on parsing. In fact, you can have entire semesters on different theories, linguistic theories, underlying parsing algorithms that the parsing algorithms try to capture. So I took a year and a half of just syntax theories when I was an undergrad. I loved it at the time. It was super interesting because it's basically trying to capture all the complexities of language, and it really makes you appreciate how complex language is. And then depending on how far you go, you even go into places where normal speakers of the language don't even know anymore what you're talking about. But you're talking about their language and you're just understanding it very, very deeply. So for linguistics, this is a super interesting area. Now, we'll get to that later. It's a question whether we need it for artificially intelligent algorithms to fulfill certain tasks and get certain accuracies. But if our interest is the actual study of language itself, it's a very interesting formalism. All right, so if we try to do parsing and syntactic analysis here, the parser should understand that the cat is a proper noun phrase. You just added a so-called determiner here, like the. You combine it with a noun, you get a noun phrase. Similar with the mat. On the mat is a prepositional phrase, and in syntactic theory now, we could create another grammatically correct structure by replacing this PP or prepositional phrase with any other kind of prepositional phrase. Now, to sit on the mat or sat on the mat is a verb phrase, and overall this is a sentence. So this is the standard parsing task that gives us this discrete tree structure, essentially a grammatical analysis of which words go together to form syntactically plausible phrases. And now what we want is, of course, not just this discrete structure, but also vectors at each node in this tree. And this tree, again, it can be very different for every different sentence, right? Different sentences will have different trees. And so maybe it makes sense to step back and ask us first, do we really need to learn the structure? So we could, for instance, go and just say the country of my birth. Instead of finding the tree structure first, we could just go from left to right, and maybe we'll end up with some vector too. And depending on what the training data is, maybe it will be able to capture everything that we want. Of course, the tricky bit here, as you'll see, is that this structure will not give you a vector for just my birth at any given moment in time, right? It will only give you this vector here, which captures the country of my birth, but not my birth by itself. And so, you can get very quickly into very long conversations and discussions about the true nature of cognition and the brain and language by itself and so on. And you can certainly argue that they're cognitively debatable. Do we really form internally in our brain little tree structures? One thing that's clear is that recursion is very helpful in describing natural language. Right? If we want to say, is this a syntactically, grammatically plausible phrase or not, then it helps us to know that this is a noun phrase or verb phrase, and I can replace this verb phrase with another verb phrase, and it's still a good English sentence. So again, for describing language, this is certainly very helpful. And it can also be helpful to try to identify and sort of clearly specify certain disambiguations. So this one is a super interesting problem, so-called the PP attachment problem, or the prepositional phrase disambiguation. Different words for it, but basically the big question here is how to interpret the following sentence. He eats spaghetti with a spoon versus he eats spaghetti with meat. Right? Intuitively, for us it's very obvious. Well, if I eat spaghetti with meat, then the with meat PP, the prepositional phrase of with meat, modifies what kind of spaghetti I'm eating. But he eats spaghetti with a spoon. Now, with a spoon is also a prepositional attachment phrase, but it actually modifies how I eat the spaghetti. And so if you want to describe that in a proper formalist way, this is a very powerful method to do so. Basically, you have these trees, and now you say this PP attaches to this noun phrase, whereas this PP attaches to the verb phrase. And so for a lot of linguists and a lot of even NLP systems, for a long time, we assumed we first have to understand the syntactic structure, and then we can get to the semantic structure and actually understand what the meaning is really about. Again, cognitively debatable, but certainly helpful for different tasks. Are there any questions around this? I know we haven't really introduced all these tree structures, and these are personal pronouns, and they're different types of classes for verbs, so don't worry if you don't fully appreciate and understand those tree structures. But intuitively, they basically just capture the grammatical structure, and they're one-way grammatical formalism. Cool. All right. So now the question is this recursion helpful? It can be in a couple of different scenarios. So for instance, if you try to refer to specific phrases, not just specific moments in time in your time series. So you might say John and Jane went to a big festival, they enjoyed the trip and the music there. Now you might want to say, who's they? And you want to refer to just John and Jane. Or you might say, what's the trip? And if you want to refer to it only in the sentence, it's just went to a big festival. And you can go to this festival without John and Jane. So you might not want to include them in your current context, which again a recurrent neural network would do. And you can even say, what does there mean? And then that's the big festival. But there's only the big festival or a big festival. It's not the entire sentence from left to right. And you might want to have actual representations, independent representations of these phrases, depending on what systems you like to build. Now, the labeling might also sometimes be a little less clear if you only have a label from left to right or only one for a single word. So you might, for instance, say, I like the bright screen, but not the buggy slow keyboard of the phone. It was a pain to type with, or it was nice to look at. So now you want to refer to it. Maybe this it should refer to the bright screen, and this it should refer to the buggy slow keyboard, and not just to keyboard by itself. So this is an interesting task of so-called coreference resolution, or when it's a specific anaphora here, like it, basically a pronoun that you want to refer it here to the buggy slow keyboard. And in some cases, you might also just say you run experiments, and you want to just say, well, I don't care really which model you like better. You should just run an experiment, and you can compare different models. And sometimes, for instance, for sentiment analysis, up until we put out our dynamic memory network paper, the best model in terms of just pure accuracy on the Stanford Sentiment Tree Bank, which is a very commonly used benchmark data set for sentiment, the best performance used to be models based on models that use these grammatical tree structures. And now they were overtaken again, and who knows, maybe a next kind of modification of tree structured LSTMs or something will improve it again. So it's basically still up to debate. In some ways, if you're a linguist, you will love recursive applications because they really help you carefully describe language in a very good formal way. If you just want to get good accuracy, maybe you won't need it. So let's assume for some of our tasks they're useful and we really do want to use them. Now let's see how we would actually compute these tree structures and the representations for specific phrases in a grammatically plausible way. We'll use recursive neural networks for this task, and the basic definition of these is as follows. You basically just have, again, two inputs. Originally they will just be words, and later on they'll be phrase vectors, and you'll have two outputs. The semantic representation of the two nodes that we merge, and maybe on top of that, again, is a standard score. So none of this will be too big of a surprise. This is, again, our standard neural network, single neural network layer. Here we actually put the W into one matrix. So again, this could be seen as two blocks. One block that you multiply with C1 plus another block that you multiply with C2. This is what I described in the previous lecture. And we basically just have a single linear layer here to compute the parent. And then we have our standard score, linear score, to just say, well, these two should really go together. So if this score is high, we want to combine these two words for sure. Are there any questions around the formulation? So maybe we can do a quick check if we're all on the same page. So let's say our W here, we can split into two matrices. So this is C1 and C2, and this is our matrix multiplication. Right? So this is just part of our F of W plus B. Now, how could we rewrite this? And again, this is just this whole thing here is one W. How could we rewrite this if we wanted to separate out W1, W2? and have the formulation we have here, C2, and here C1.
W1, C1?
That's right. Plus?
W.
That's right. Right. So again, just straight up linear algebra. We'll often use this formulation. Looks a little nicer for recursive ones. All right. All right, so now let's, can we switch back to the slides? So now the main reason we call them here recursive is that we use the same W parameters at all the nodes of the tree. And now you will very often hear the confusion between recurrent and recursive neural nets. Recurrent ones, the way they're currently defined, will be just chains that go from left to right. At each time step, you add one word. And so in that sense, recurrent ones are actually special cases of recursive ones, because chains are special types of trees in graph theory. And so in some ways, you can basically just assume that a lot of the stuff will follow, and sometimes the recursive one falls back and is like the special case of a recursive tree structure is just a left to right structure. I see a little bit of confusion, so let me just show you what I mean. So we could have, for instance, a tree structure that just keeps combining things from left to right, right? And now, if you assumed you had modulo sort of a hidden a start state. So now this is basically very similar to saying, well, I first combine this here. You should have of course arrows. Now this is very similar to saying, well, I just basically go here, right? So just basically fold these down, and then you see that this is just a special type of tree. Main difference here is how we deal with the starting point being an input as well. All right. Cool. All right. So now let's say we had a trained model that gave us good scores for when we actually think two words should go together, and or high scores, and low scores when they don't. So now the simplest way, and the only way we're really going to look at it in this class, is with a greedy tree search. We'll basically here have this neural network, the same W weights, and we'll apply this for every possible combination of two words. And we would just say, all right, now the cat is a very obvious noun phrase. Cat sat doesn't seem like a plausible phrase. Neither sat on or on the, but the mat, again, obvious noun phrase, so gets a high score. And now what we could do is say, well, let's just make some discrete decisions and say, let's combine the two words with the highest score, and then take the output of that model and apply it to that same exact neural network again. And again, the weights here are all shared, same W at every node. And then we can again compute a candidate here and say, all right, the cat sat. How likely is now the combination of these two words represented as a single vector again with the verb sat? And now here, the largest, the cat sat is actually not an unreasonable phrase, so you might think, all right, that's still a reasonably high score, but the mat was a very obvious noun phrase, so we'll combine those two words again, and then again compute a candidate representation for what comes afterwards, for all possible combinations if we make these greedy kind of decisions. So now on the mat is essentially a very nice prepositional phrase, so it gets again the highest score, and we basically built up this tree structure like that. All right, now we can define the score of the entire tree as just the sum of all the scores of all the decisions that we made to arrive at this tree. And so here x will actually be our input sentence, and y is the tree structure. And so you have a bunch of nodes in that tree, and each node had this kind of score, and we're just summing them up. Now this one is where it gets a little interesting. This is similar to our max margin that we had before, where we had 1 minus the, or max of 0, comma, 1 minus the score of the good window plus the score of the bad window. But it's a little more complex because we have now various different gradations of difference and gradations of goodness, or essentially the loss here in penalization term. So let's walk through this slowly. I don't think you'll have to really derive this or use this yourself, though we will have in problem set 3 recursive neural networks, but you won't have to train this to actually find the tree structures. In most cases, we will assume the tree structure will be given to us. So this is a max margin training framework to try to find a recursive neural network that gives us the right grammatical analysis, the right tree structure for a sentence. Xi is, we have basically here summing over all the sentences and training trees in our corpus, our training corpus. So we have a bunch of different sentences, and each sentence has a ground truth tree yi. So this is our training corpus, a bunch of xi's, yi's, and yi is some formulation of this tree. And now what we want to do is we want to maximize the score, and the score again of the whole tree is just the sum of the scores at each of the nodes, of all the nodes. And we want to maximize the score for our current sentence xi and its correct tree yi. And now, what is this monster here? So basically, what we're going to do is we're going to try to find the maximum of all possible trees a of xi. So a of xi is just a large set of all possible trees that you might create from that sentence. And basically, each of these will be some distance delta away from the actual correct tree. And you can count that by basically how many of the words, how many of the right decisions that you make to get to this tree. And then once we found that tree, we want to actually lower its scores, because unless it's the exact same tree as yi, so if the maximum currently scoring tree of all our randomly initialized parameters, unless it's actually the exact same tree, we want to penalize all its scores, because we messed up. The algorithm messed up in finding the right tree structure still, in terms of the scores here. And so once the highest scoring tree, y, is actually the same tree as yi, well then these two will cancel out, and delta here will actually be 0, because the difference between yi and yi is 0. So you made all the same decisions, and then you're basically done with trying to optimize that tree. Now, of course, a of x, this set is exponential. It is a very, very large number of trees. You have millions of possible trees, even for sentences of just, length 40 or so. And so really what we're going to do here usually is a smarter search, often a beam search with a chart that tries to find the best tree. So far, the structure here that I described was just a greedy version. It's the simplest way. But maybe you make a mistake internally here and you want to be able to recover, so you might want to keep around multiple possible choices that you may have made. And so that will be basically one way to do this is in a beam search. No, don't worry if you're not familiar with that that much. You're not going to have to implement beam searches or charts. Any high-level questions around that equation, though? So basically, if you make just one incorrect choice here between y and yi, then delta will be 1. But if you have a completely wrong tree where you made a bunch of wrong decisions, then your delta will be much larger, and then you're also going to try to penalize all these incorrect decisions even more. And so once you actually have y be the correct tree that is exactly yi, then it will also be correct up to a margin to the next highest scoring tree that isn't correct. And it will be nicely pushed away all the incorrect decisions. All right, so now how do we train this? Well, really it'll be mostly backpropagation as we've already derived it. We'll see these two equations if we implement this from scratch in NumPy again. But there are three major differences that sort of conceptually you might stumble over. So the first one is that we'll actually sum up all the derivatives of W from all the different nodes, somewhat similar to what we've done in the recurrent neural networks. You might see the splitting of the derivatives at each node based on that difference of notation. And you basically can add different error messages from all the parent nodes that you're getting and the node itself. And so a lot of this is actually quite similar to what you've seen with recurrent neural nets, where we had the error signal at each node and we basically sum them up going from right to left. Here you just happen to go in this tree structure. So let's just quickly gain some intuition for why you can actually assume that there are different W's at each node. So let's say we had the simplest kind of model here. This is actually a recurrent one, and if you just now derived derivative of this function, so f again, just non-linearity, we could assume W here for now is just a scalar, and we have this very simple function. You take derivatives and you just apply the chain rule in its simplest form. You're going to get to this equation. If you take separate derivatives of each occurrence here and you assume, well, maybe this is W2 and this is W1, and then you actually sum them up and you apply the simple chain rule to that, you end up with this. And now if you basically drop the indices, you realize, oh, they're actually the same. That's just like very simple. Just to gain some intuition. Because I use this equation here a lot, I just want to make it clear that generally as you get an error message from your parent and you send it to the children, you'll end up at some point with a delta error signal here that basically is part coming or going to the left child and part to the right child. So this is usually a notation that you will see. And now at each node, and I'll show you some like code. It almost looks like pseudocode, but it's actually real code. Intuitively here, you might have a score. You do have a score at every node of the tree, as well as from the parents. And so basically what that means is in forward propagation, you compute these scores, but then you continue using the parent in the next computation higher up. And so the total error messages that will arrive at each node that is internal to the tree will be one where you have your score sending you a delta message and your parent sending you a delta message or an error signal. And you'll basically sum them up. And it's, again, it's a good exercise to gain some intuition of why mathematically you end up just summing them up. So we got asked for some nice code. So here's some very simple recursive neural network code. We'll assume here we have rectified linear units in our tree structure. So our hidden node here is going to be just computation of W times horizontal, in this case, stack of the left node and the right node plus our bias term. So there's straight up simple neural net, and our nonlinearity followed by from this simple inner product, matrix vector product, is just our rectified linear unit. Now instead of linear score, we can also use a softmax at every node and actually classify every single node in this tree. So let's use the simple softmax here. This is a trick that I think it will be good to derive of why you can do this mathematically, but you also always want to basically subtract the maximum. It'll give you the same output, but because we're going to exponentiate this, it'll help you numerically to stay much more stable. So the real question here, I kind of went over it quickly, is why is it the same if you take out a linear value from all your elements before you apply the softmax. And proving to yourself that that is the same is a good exercise. So then here we just have our softmax, basically sum up probabilities at that node in the tree to be 1. And again here we just assumed we know what each node is basically its own little class, and just proper object-oriented programming, each node has a left child and a right child. And that's one simple way in object-oriented programming to get to define a tree structure. And now I mentioned these two equations and again how important they are, and we'll see them here again directly in the code, modulo maybe some transposes depending on what we use as the vectors. But so the softmax gradient that you already derived will give us a delta at that node. You basically have your y minus your y hat minus y. Then this is basically the delta coming from here. So you have your softmax weights times transposed to have the final error message that comes into this node. And then here you have your f prime. So I'm skipping about over this one. Basically, if you, but I shouldn't, if you have, if you're at the top node of the tree, then you might not have a parent, right? If you're at the root of the tree. But once you do have your internal child, you will basically get the delta from your current softmax at that node plus the error that was coming in from your parent. And now we will have our f prime of z, this one right here. And in the case of the rectified linear unit, that is just a simple 1 or 0, whether you're in the linear regime of your rectified linear unit or you're in the 0 regime. Now this one is an interesting special case. If that final node is actually a word vector, then you will basically add here in your lookup table or your word vectors, maybe your large word vector matrix, you add that delta error message into the word vector. So again, those are part of your training. And this is also true for all your recurrent neural networks. And now this one is where all the juicy bit is and all the interesting stuff. So here, our derivative of w, well, it's the outer product, just like we have here, the outer product between delta and the activations. So the activations in this case are just the concatenations of your left and your right children. So basically, you see exactly this equation here in the code here, and you basically sum up at each node, you add more to the derivatives of your w. Deltas derivatives with respect to b are just the delta messages as we've seen in one of the early lectures. And now we're basically going to split up and send the error signal down. So here you will see the w transposed, this w times delta. And this part here we will only do once we actually arrive at those nodes. So that will come later here. And there you go. And that basically now you can run and recursively apply the backpropagation function with the new delta, the error message that now gets sent to the left child and one that gets sent to the right child. So this last part here is exactly the splitting up of these delta messages. So intuitively here you have again one of these computational flow graphs. You go up the tree to compute all your activations, and then you go back down the tree in the reverse order. Are there any questions around backpropagation through structure? All right. So, as before, do you have one?
So I'm a little unclear. If you go back to the code, how do you control the structure of the tree?
How do you control the structure of the tree? So, basically, you assume for now that you just defined an object-oriented setting here where you have nodes, and each node is a standard sort of object-oriented programming type object. and it has defined a child, a link to its child on the left or its child on the right.
I guess my question is, how do you know the structure?
Oh, great question. So how do you know the tree structure? So this backpropagation through structure always assumes you have a tree. So either you, and in most cases, and in the case of your problem set 3, you will be given a parsed tree. Well, we take the, in our case, Stanford parser, actually happens to also be one of the best parsers in the world, and the Stanford parser will give us what the tree structure is for every sentence. And then we actually, for sentiment analysis, took those tree structures and labeled all the nodes and all the phrases in the tree to really understand, oh, now you add negation, now it should change in its sentiment. So it's a very nice and intuitive kind of data set and labeling process. And so in your problem sets, you will just assume the tree structure is given. Now, if you actually try to find the tree structure, you would use this kind of model where you trained it and then you will use a simple search procedure. Who here has taken 221, the standard AI class? Okay, so like roughly 1/3 or so of you. So you'll have looked at a lot of different like sort of traditional AI search methods like A-star search and so on. So these kinds of beam searches and other kinds of searches are kind of a traditional part of AI. So yeah, you'll use those kinds of search methods to find what the right tree is. The simplest one is this kind of greedy structure where you just say, well, what's currently the best method, currently the best choice, and then I'll just put the tree together this way.
Well, I mean, I guess beam search doesn't, but like A-star needs a heuristic that is consistent and all of that jazz, right? So that it actually converges. Beam search is not guaranteed to converge.
You cannot do nice dynamic programming with these recursive neural networks, largely because you actually have these continuous vectors and you can't make the kinds of independence assumptions that you could do if you had discrete choices like, oh, this is just a noun phrase. But really, and that noun phrase is locally the best one, and because it's locally the best one, it will be globally the best one. You cannot make these assumptions. You might have the highest score for these 3 words, but then because of the continuous vector representations, the highest score for the subtree might not mean that that's also going to be the best one for the overall tree. So all you can do is beam search. And again, don't worry if this went over your head a little bit. Ideally, you've taken 221, but you don't need this for the projects or the programming assignments. Cool. So now we'll basically, again, have forward prop, back prop through structure in this case. We'll get our gradients. We already talked about AdaGrad. It's a very nice method to basically have a different learning rate based on the past gradients squared of all the previous time steps. That will update our different vectors and matrices. And because you have actually technically here a non-continuous objective function, you use a subgradient. Again, we're not going to go into too many details in this class about that. Now, you can actually get reasonably good results if you just take a single W matrix at every node of the tree. But it's also kind of crazy to assume, just like with recurrent neural networks, that one single W matrix could capture all the complexities of all the different combinations for adjectives and noun phrases and verbs and prepositions and so on. And it's a little much to ask such a simple function, right? Concatenating 2 vectors, multiplying them with a single matrix W, having these simple linear transformations and adding a bias term to capture all the complexity of language. And so one of the extensions of recursive neural networks is to syntactically untie the weights and actually use different W's depending on what kinds of phrases and words you're actually combining. And so on a very intuitive level, the standard recursive neural network will use the same W at every node. But because we actually often use a parser that tells us not just what the tree structure is, but also what kinds of phrases we have. So this might be a noun phrase, and this might be a verb phrase, or an adjective phrase, and so on. We can actually use different W's depending on what category. So capital letters here are categories, and the small letters are the vectors. And so we can actually combine these 2 vectors differently because one is in category B and the second one is in category C. And again, yeah, we're sort of now arrived in slightly more advanced territory, but intuitively we're using the same kinds of building blocks that we've used before. Yeah.
So if we're treating recursive neural network as, or recurrent neural network as a special type of recursive neural network, does that, because in traditional RNN we only have one set of weights, and I always wanted to ask this question, why don't we use different weights for different time steps? So wouldn't this be kind of like an example of using like different weights for different time steps?
Yeah, so the question is this an example of, or I guess not quite an example, but this is an interesting analogy to using different weights at different time steps in a recurrent neural network. And I think you're absolutely right. I'm going to say that there's probably going to be a paper this or next year that will try that, because now, this is again, side note, don't worry if you don't follow what I'm saying right now, but batch normalization, for instance, you start to collect training data that is different at each time step. So I think a logical next step is to go back and say, well, why don't we have a different W1, W2, W3 for the beginning of recurrent neural networks? The problem is, of course, what if you hit a test sequence that is longer than a training sequence, and then you might just say, well, I have W1 to N, and N plus 1 has all shared the same W. Again, you kind of fall back to a recurrent neural network. I think it's an interesting research question. Somebody should definitely try it. It would be a great project too. Cool. All right. Now, one of the problems when we try to find the tree structure is actually that having a matrix product, a matrix vector product, at each potential combination of phrases is actually very complex. And so what we end up often doing is to take a very simple model that's just based on counts. It's called a PCFG, probabilistic context-free grammar. Again, don't worry if you not follow this. And that will give us a bunch of candidates, like 200 or so. And then we'll use the more powerful recursive neural network that understands the semantics and has complex vector representations to just basically prune out all the unlikely candidates and give us one that makes most sense based on this simple sort of pre-processing step. Now, these are also models that have all been kind of evaluated and invented in their most basic forms in the early 90s. So Pollack in 1990 invented recursive auto-associative memories. So these are essentially autoencoders that are recursive. They try to recover at each time step what came into that time step. Turns out to, in my own experiments, not always be the most useful objective function to try to capture meaning very well, but it's a good regularization to not try to overfit to your supervised objective at each node. And then, of course, whenever you do something in deep learning, Jeff Hinton will have had some idea similar to what you're doing also in the early 90s. So yeah, lots of folks have tried this, and there are some cases where recursion makes even more sense. So if you would have, for instance, programming languages too, and you try to understand, well, this part now modifies that exact region in that specific window. If you have, for instance, for loops or something, you want to now have a for loop and a sort of abstract syntax tree. In programming languages, it also makes a lot of sense. Or different logical operators where you might say, I want to negate something, but I want to negate it exactly until right here. And you have parentheses, and whenever you have complex sort of Lisp type programs, for instance, it makes sense to think of them as trees. And like I mentioned, parsing by itself is also a very large field in NLP. A lot of very smart people have worked on parsing. And for a while, these recursive neural networks were quite accurate, and we actually shipped them in the Stanford parser. They're a little faster than some of the traditional methods, but were more accurate. But a lot of back and forth actually happened in the last couple of years, and I think currently a neural network is again the top model to understand these tree structures. I think more importantly, we can analyze what's actually being learned in these recursive neural networks, and we find some nice notions that linguists had invented, and now these RNNs, or because RNN is now somewhat ambiguous, I'm going to call these sometimes RVNNs for recursive neural networks versus recurrent neural networks. Again, one is a special type of the other, so it doesn't matter too much, but All right, side note end. Basically here, this syntactically untied recursive neural network basically had these different W matrices for the different vectors, right? And again, coming back to this idea that you multiply the two, you can see here the two blocks of W that multiply with a determiner and the other one that multiplies with the noun. So if I say the cat or a cat, what this basically learned is that it doesn't really matter that much. It's going to be a noun phrase regardless. And in terms of the meaning, you care much more about the noun than you care about the determiner. Is it this cat, that cat, a cat, the cat, and so on? None of that matters. The cat is really what matters. And this is exactly what this model learned. The weights here that are multiplied with the noun are actually much larger than those weights that are multiplied with the determiner. And intuitively, in linguistic theories, people have a notion of so-called head words, the word that matters more in the combination of a phrase. And so there are lots of interesting linguistic theories of people who really understand and analyze language. And it's kind of cool that the model itself learned similar patterns. So for instance, in verb phrase and noun phrases, often when you combine a verb phrase and a noun phrase, it ends up being a verb phrase. And so the verb here matters, again, more than the noun phrase. We can also look at semantic similarities and syntactic similarities by looking at nearest neighbors. So we embed a bunch of sentences, and this is a much smaller data set than what we saw for machine translation, but some similar patterns are falling out when you use recursive neural networks. So here we take a bunch of sentences, a couple thousand, and we basically project them all through a recursive neural network into a vector space, and then we look at nearest neighbors in that 50 or 100 dimensional space. And when we look at the nearest neighbors, these are the sentences that fall out for here three picked examples. So all the figures are adjusted for seasonal variations. The closest neighbors to that are all the numbers are adjusted for seasonal fluctuations. So basically just replaced figures and numbers and variations and fluctuations, two synonyms in this word vector space. And all the figures are adjusted to remove usual seasonal patterns is the next closest one, which is kind of interesting because now it basically adjusts this whole verb phrase to remove usual seasonal patterns versus adjusting for seasonal fluctuations. Sorry, I guess adjusted and adjusted are the same here, and here you're adjusting, removing usual seasonal patterns, and here you adjust just for seasonal fluctuations. So now here you have a couple of organizations, and you basically see that it captures, again, the syntax, similar to our word vectors, where we captured, first this is a noun, but then let's zoom into the noun, you have similar semantic information too. So Night Ritter wouldn't comment on the offer is close to Harsco declined to say what country placed the order, which is, and the next closest nearest neighbor in our high dimensional embedding space is Coastal wouldn't disclose the terms. So you can kind of see, some organization, some kind of negation can be wouldn't or decline, so different ways, and then commenting, saying, disclosing something of some financial nature. And here are other ones like sales grew or rose or surged and so on from some amount to some other amount. And very interestingly also we can look at exactly this disambiguation case and see if our word vectors and distributed representations for the phrases help us to do this disambiguation. This is not really a proper experiment because it's a tiny training set and a tiny test set, but we can see if this happens at all if we add these sentences to our training set. So here we have training sentences, he eats spaghetti with a fork, or she eats spaghetti with pork. And then the test sentences are he eats spaghetti with a spoon and he eats spaghetti with meat. So ideally, because the distributed vector representations for pork and meat are similar, and likewise spoon and fork are similar, a neural network model can kind of make that cognitive leap and say, well, this should be similar to this one and not the other way around, whereas a model that would just traditionally use traditional machine learning and take counts of words that are completely independent, they're just one-hot vectors for some kind of counting, wouldn't do very well. And that's what we did observe here. So the compositional vector grammar, which has a recursive neural network inside, did correctly put the with meat prepositional phrase close to or attached to the noun phrase. All right, now I mentioned that we can have the softmax layers too. I showed you the code for the softmax. So we can take each node in a tree, apply a softmax classifier to it, and classify also what that node should be in terms of its class. And what was really fun to see in 2011, this was the first paper of my thesis in 2011, was that instead of taking word vectors, we can also take vectors that represent little regions of images, so-called superpixels. And then we applied the same principle of compositionality and said, well, the meaning of a whole region of an image might also come from smaller regions of the image and how they're combined. And so we used this idea and basically learned how to combine different areas of images and got some really nice results also, where it's the exact same model that we used for parsing sentences, but now we parsed images, little regions of images. You have a W vector here, and you basically combine them with these scores. And for some time, it was actually a really, really accurate model for basically classifying and segmenting whole scenes. So these recursive neural networks, just like convolutional neural networks, can be very generalizable between different modalities. And that's one of the reasons why I care more about the methods and less about the application. And you can have projects in a variety of different fields, because the power of these models is really that they're applicable to everything. All right, so next week we'll talk about some more variants of recursive neural networks, and then we'll get to convolutional ones and some other ones. Thank you.